Today in the tech world, we're not just building products anymore, we're training systems. Earlier, companies used to launch apps. Now they're building models that can create apps on their own. A system that can write code, generate videos, design creatives, all from a single prompt. This is already happening. Every industry, whether it's healthcare, finance, marketing, or software development, AI is quietly becoming a part of everything. And the people who understand it, they're not just using tools anymore, they're building them. So here's a simple question: where do you stand in this shift? Are you someone who is just using prompts or someone who is understanding the architecture behind it? Because today, just using AI isn't enough. The real advantage comes when you understand how these systems actually work. If you think generative AI is just ChatGPT, then you're seeing a very small part. And if you're a beginner, this is the best place to begin. Because in this course, we're starting from zero. We'll break things down step by step: how AI actually evolved, how we moved from basic machine learning to deep learning, how neural networks became more powerful, and how we reached a point where models can understand language, images, and even creativity. In simple terms, we'll move from what AI does to how AI actually does it. So, without wasting any time, let's get started.
Now, let's go with the another deeper understanding on what exactly has to be done over here so that we all will be on the same page. Okay. So, see, whenever you learn about generative AI, okay, so there's a time, okay, once upon a time when I was learning generative AI. So the thing was, there's a lot of complications. Okay, there's a lot of things, but we didn't had a specific source where we have to look onto. So earlier, when there was a research, okay, one on the generative AI part, what we used to do, we used to look on that research, okay, what exactly those particular mathematicians, statisticians, data scientists, what they are doing and what exactly they are cultivating from there. Now, today, as I look on to today's part, what I understand is now you guys have a specific structure to understand what exactly generative AI is, what the history of generative AI is, how it began, how the nature and everything has been done, and what exactly are the different parts to it. Okay. Now coming to the part, guys, right? So now let me give you an idea on how this generative AI track goes on actually. So firstly, you begin with LSTM. LSTM is like this stepping stone, guys, everybody, that will help you to go ahead and move forward to the generative AI part. Now, once a person is aware about how exactly LSTM works and what is, the thing around the LSTM, then the next thing that you guys will be learning will be encoder and decoders. The next stepping stone onto the part of the journey of transform, journey of generative AI. Then once a person is aware about this particular segment also, then the person can move towards transformers, everybody. The major stepping stone in the part of generative AI. This is the three particular stones of your Gen AI part. So basically, transformer is nothing. It is encoder and decoder only. There is some X factor that is included over here, so that with encoder and decoder you add a X factor that will actually help you to make a transformer. But that we'll discuss in the later part of the class. So this is your journey towards the part of generative AI on the core behalf, everybody. Okay. Now, once you will be aware about what transformer is and how exactly transformer works and operates, then you'll have some particular different segments coming into play. So you'll firstly learn about large language models. Okay. You will learn about what are pre-trained models, what are fine-tuned models. Okay. Then around this part in the fine-tuned and pre-trained, you will learn about Hugging Face. Okay. And you will learn about the pipelines. Okay. And then in that series of fine tune, I'm not very aware if your fine tune is there or not. So if you are going to learn with the fine tuning part, so the things will be a little bit on the other hand of the side. So here you will learn about performance efficient fine tuning, supervised fine tuning. You will learn about data sets. Okay. And there are some other techniques also that I think I'll suggest you later on if in case you guys want to learn. Okay. Now, once this LLM part is done, everybody, okay, once this LLM part is completely bringed out, then using the LLM will be utilizing some particular aspects. Like you will learn about RAG over here, RAG, retrieval augmented generation, retrieval augmented generation. And inside this particular part, when we're learning about it, inside this particular part, we'll get a knowledge on what exactly LangChain is. Okay. And inside LangChain, there are multiple different things that we'll be discussing about over the period of time. So We'll discuss about vector databases at the very first place. We'll discuss about documents. We'll discuss about splitters. We will discuss about runnables. We will discuss over here about parsers. Okay, and other particular different segments. Okay. So before beginning to the part of generative AI and before beginning to the part of what exactly encoder, decoder, and everything is, what we'll do is we'll brush up. Okay. I'll go ahead, I'll brush up on the part of LSTM a little bit so that you guys can go ahead and you guys can have a clear bit of understanding. So guys, let's let me take you a little bit back to the days when you guys were learning about RNNs. Okay, what exactly is RNNs? It's recurrent neural networks, right? Perfect. Now, what exactly recurrent neural network used to do, guys? Everybody. So let just to put it in very easy format. Let's say if this is your neural unit, this is your input part, okay, and this over here is your output part, right? And there used to be a feedback loop over here, if I'm not wrong, right? Let me write this over here also. Feedback loop, correct? Everybody. So basically, what you used to do, you used to take an input, used to give an output, but with a feedback loop, right? A self-feedback loop. Now, there's a problem with RNNs that was specifically due to business part. The problem was actually two. First was short-term memory. Okay, RNNs, they didn't had a very long memory. Okay, so if you, in case you want to do a task that was over a long period of time, you wouldn't be able to do it, right? The second one was the gradient problem. Now, what exactly was the gradient problem over here? So it was not only the vanishing gradient that was a problem over here, it was also the exploding gradient. Okay. Now, since it is a refresher, so I'll keep it in very easy format. What exactly your vanishing gradient and what exactly is your exploding gradient is. Okay. So vanishing gradient and exploding gradient. Perfect. Let's understand these terminologies in a quick format. Okay. What exactly vanishing gradient is and what exactly this exploding gradient part is. So I believe guys, you might have came across this particular, graph, a kind of graph like this that we generally often term as the gradient graph. I believe most of the people have already looked into when you guys were learning about gradient descent and all that. Right. Now there are two pictures to it. Okay. Now for an example, what happens in vanishing gradient and what happens in exploding gradient? Let's have a quick revision on that. Okay. So when I talk about the vanishing gradient, right? So basically vanishing means your gradients over the period of time, they got vanished. They got invisible. We were not able to track them up. Right. So how does it happen? This is your formula. Wx plus b. Everybody. Right? Learning rate. सही है? Wx through which you train your feed forward neural network. Weights plus inputs multiplied by bias. Sorry, plus bias multiplied by learning rate. Now what happens is due to this feedback loop, this particular thing gets multiplied over the period of time. So say that if a person is working with a learning rate of 0.02, so over the period of time, if you multiply this term multiple times, the smaller unit will get much smaller. For example, let's say if for the first iteration this is 0.02, then for the next iteration again you will multiply the learning rate, resultant factor 0.004. सही है? Now again over the period of time, if you go ahead and if you multiply this term again once, you will get much smaller metrics, right? So say that if you multiply it again by 0.02, then what will happen? You'll get a much lower term, that is 0.00008, a much smaller term. One more zero, let's add. Now if you plot the same thing on this, this gradient graph, everybody. So this is just an analogy, okay? It's not the exact explanation, I would say. This is just an analogy so that everyone will be aware about this part, okay? So please have a check over here. Now suppose that your gradient was over here at 0.02 sitting. Okay. Understand that this is an analogy, it's not the actual mathematics that you see. Now over the period of time, when the gradients deplete, your movement through the graph, okay, when your particular gradients they drop to a particular optimal level, it becomes so slow that even after a lakh iterations, if you drop the machine, okay, even for a 1 lakh iteration, if you're running the machine, there still won't be any effect on the gradients over here because you're still moving at a very, very, very slow learning rate. And isn't this what exactly is vanishing gradient problem, guys, everybody? In a very easy format. I'm not talking in the mathematical terms, in the most easiest format possible. the gradients over the period of time, they actually are so slow that you don't see any changes in your network, correct? And the opposite happens in the part of your exploding gradient problem. What happens over here is that the gradient, if your learning rate is too high, then your gradients, they bounce off like this, correct? They won't be able to converge. That is the problem that was with the RNN. Now, in order to mitigate this issue in the part of your, in the part of the RNN, we had to come up with a new network, a network that shouldn't have this problem, that shouldn't have specifically the problem of the gradients. That is where we came to know a new terminology. Okay, I believe you guys might have came across this terminology, gated mechanism. So basically, instead of passing the inputs in the network one by one, we'll have gates that will help us to go ahead and help us to pass the inputs, and that is where the concept of LSTM came into play. Okay, so I believe that you guys will echo on the same part that LSTM is actually made up of three major gates, everybody, right? So just dividing this over here so that we can have a quick understanding on the same. So the very first gate that we have in the part of LSTM over here, this is called as a forget gate, everybody, right? That helps to forget the information that is not relevant. Then the second gate that we are having over here, this is called as the input gate, right? That help us to input the information, the new information basically. And the last particular piece or the last particular gate that we have in this particular entire layer is called as the output gate, that helps to regulate the output throughout this particular mechanism, right? And obviously they have their internal working also, but since I told you this is just an overview, so I'm just trying to draw the same. So this is over here your forget gate, everybody. This is your forget gate over here. This over here is your input gate, and this over here is your output gate. Okay, and obviously they have their own combinations of sigmoid function, sigmoid tan h, and tan h sigmoid, so they have their own combination with the cell state working throughout the period. So you have your cell state, you have your hidden state over the period of time, right? And this entire thing is called as a memory cell, right? So just to give you a diagram representation, this is your memory cell, this over here is your cell state, this over here is your hidden state t minus 1, right? Hidden over here and cell state over here. Perfect. Is it the same diagram that you see in the LSTM, everybody? And obviously if you'll go in a too deep understanding of the same, so over here there's there's a sigmoid function that works, then over here there's a sigmoid function with a tan h working over here, and then you go deep down the road, again there's a sigmoid, and then again there's a tan, right? Perfect, guys, everybody. Now what exactly LSTM used to solve the problem? What exactly was the problem statement that LSTM was solving for us, everybody? So let's tweak this question a little bit. What was the advantage of LSTM over the part of RNN? So basically, guys, the very first issue that we got to solve from over here was the memory problem. Now in RNN, we only had a short-term memory, but here we had two memories specifically dedicated for long-term and short-term uses. So over here, if you have a look, so this particular cell state is the one which is dealing with the long-term context or long-term dependencies, whereas all the short-term dependencies were handled in this particular hidden state, or all you can say it's like a RAM and ROM structure. Okay, so if I put an analogy over here, guys, can I say that this is the RAM, everybody, wherein all the task is happening, everything is happening in the the hidden state, and whatsoever is very relevant, you go ahead and you save in your hard drive, right? So isn't this like the same kind of structure, everyone, wherein all the processes being done in the hidden state, and any particular major update or any particular major information that we can use in the long term is updated and saved in the long term memory or your cell state, everybody? Perfect. Second problem that we solved over here was the vanishing gradient problem. So here, this was mitigated because of this gated mechanism part. Okay. Now, since this particular LSTM has three particular layers, that is input, forget, and output, these gates control the flow of information, deciding what has to be kept, what has to be forgotten, and what has to be updated. Okay. So in this way, we were preventing the loss of information over the period of time, and due to this design, it allowed the gradients to flow more effectively during the propagation. Okay, so that was the major advantage that we had over the part of RNN, everybody. Okay, so LSTM is more of a RNN plus memory control architecture. Okay, everybody. So when I say LSTM, so you can remember it because since LSTM is also a variant to RNN, so it's a RNN but with much better memory control mechanism. So you'll have a much better control over the memory, saying that's a long term or short term sequence. Perfect. Now LSTM also had some issues, everybody. So it's not like LSTM didn't had some issues. Now the problem was with the data, that the kind of data that we are using. Let's have a check on that, and let's start with the first topic of our day, everybody. Types of data that we are dealing with, everybody. So generally whenever we use LSTM, it is mostly to generate a sequence to sequence output. Is my understanding correct, everybody? Oh, please. A sequence to a sequence. Like let's say if you're passing an English statement and you want to convert into French, that is what is the job of LSTMs, right? Now here comes the understanding of two particular things: static sequence length, and second is the dynamic, or somewhere you'll be you'll see it written as variable sequence length. Now this is the understanding that we need to have. Now when I talk about LSTM, okay, so LSTM is a machine that works sequentially, right? So if I talk about the part of LSTM, it works sequentially. Now if you are working with a very long sequence, okay, if you are working with a very long structure of sequence, then what will the problem in LSTM will be? That one input, let's say if you're having one input over here, that will be processed to one out. Eventually it will be a very time taking process for the part of LSTM, right? But as a user, you see Chat GPT today, right? So when you talk about Chat GPT, you provide a sequence length. Like let's say you search about, okay, what is software engineering? You get a whole paragraph on the same, right? That means that nowadays we are not looking for something that is static. We are not looking for one-to-one conversation, right? We are looking for one-to-many or many-to-one conversation. That means the length of the sequence can vary over the period of time. You can put one particular word, you can put 100 particular word. It depends, and the output that you can expect can also be different, right? Let's say a person can enter two particular words and he can expect a 200 word of paragraph, and maybe you can just put 200 words and you can expect one particular output, like as a sentiment in case, right, as a output. So that was the main problem that we were having, and that is called as variable length sequence. Now to clarify this part, everybody, we had a new terminology coming into play, that was sequence to sequence models. Okay, sequence to sequence models. Now what is the sequence to sequence model terminology? So it is not a different kind of architecture that you have learned. Okay, it is not something different that we are going to learn. To clarify, a sequence to sequence model uses LSTM as its component, but it represents a more advanced architecture designed specifically for sequence transformations. You know, tasks like text summarization, machine translation, conversation is generally done through sequence to sequence models. Now, what is different as compared to the LSTM? So here we can have a variable length input and we can have a variable length output. That is the main advantage over here in this particular case. So you can have a variable length input and you can have a variable length output. That makes it very much suitable for the part of going ahead and working with multiple sequences. Moreover, specifically talking about this, guys, so in LSTM, we also have one major problem, everybody. Okay. When we talk about LSTM, so if you are working with, let's say, 1,000 words, maybe LSTM can perform very well because there is one single architecture that is working, one LSTM cell to be very precise. But let's say if you are working with a sequence, because ultimately we are going to work around the part of large language models. Okay, the models that heavily rely on very enormous part of data. Now, when I talk about very enormous part of data, that means that we are not talking about something in hundreds or thousands. We are talking in terms of billions, everybody. We are talking in terms of trillion gigabyte of data, everybody. Now, just to give you a very quick fact representation over here, I believe you guys might have heard about GPT 3.5, right, or GPT 4. You know the size of textual data that was used over there? The total size, I'm just talking about the textual data, everybody. I'm not talking about any other part of the data. It is just a textual data. The total size of the textual data that was used in GPT 3.5 was around about 2 or 3, sorry, 40 to 50 TB. That is terabytes, not GBs, it is terabytes, everybody. Okay, I'm not very sure about the official figures of GPT-4, to be very honest, But this is the figure for GPT 3.5, and that is the actual size of the data only in the textual format. So now you tell me guys, if you just install or if you're just working with one particular LSTM cell, do you think that will be enough for us to handle that much big data? No. I think the very first problem that we are going to face over there is that the part of context itself. Your particular one LSTM cell won't be able to handle different contexts. So multiple contexts will be a problem over there. Is my understanding correct? Because obviously, if you're having a diversity of data, since you're talking about a 50 terabytes of data set, so that means you'll have a very diverse data set and you'll have to focus on multiple different contexts. So do you think will it be possible for the part of LSTM to go ahead and focus on multiple contexts being a single architecture? I guess my answer remains no over here, right? That is where guys this particular architecture also comes into play, sequence to sequence. Here what we do is we have multiple LSTMs working together. Okay, that we're going to discuss a new architecture. So using this multiple set of LSTMs, we will be able to go ahead and we'll be able to have a flexible part in which we can go ahead and we can focus on multiple different contexts at one particular given moment of time. Now, let's have a focus on what exactly the sequence to sequence data is, everybody. So I welcome you all in the first particular part of your entire thing, that is encoder decoder architecture. Or generally you'll also see people calling this as sequence to sequence modeling. Okay, so let's try to understand this, what exactly this encoder decoder is and how exactly this architecture works, what exactly are the integral details about it, and how exactly this whole thing works at the end of the day. Okay, so let's take a very brief understanding on encoder and decoder, and then we'll move towards the technical side of it. So the very first question that comes on everybody's mind is, what is this encoder and decoder actually? Because hence you have mentioned earlier also that this is a part of LSTM, will be using multiple LSTMs at one time. So what exactly this particular architecture is? So everyone, this is a two-part architecture. Okay, one is used to transform one sequence into a particular format, and the second takes that format and converts it into whatsoever kind of output you want. Let me give you an idea. So say that you are having a input. Okay, there's an input that you're handling right now. Okay, what do? You pass this input to the encoder, everybody. And now what is the job of the encoder is? Are you guys aware about embeddings, data embeddings, word embeddings, right? So what does this encoder does? It converts the data, it compresses data and converts it into something that we call it as context vector, everyone. This over here is the major part of information. And now what happens next second is where this decoder takes this context vector and generates a particular output for you whatsoever you have trained this machine for. And this is how the architecture of the encoder and decoder looks onto a very high level. Now what exactly are the specific jobs of it? So let's try to understand this firstly. So the first one, encoder. Now the job of the encoder specifically is to understand the input. Now, when I talk about encoder, guys, so what encoder does, it processes the information, it processes the input that you are going to go ahead. It compresses that information into a single vector, or you can say the context vector in our case. Now, this is usually done with a stack of LSTMs that are working inside. It processes one input at a time. Now, but the change over here is that instead of going ahead and instead of working with a single particular LSTM, we do have a stack of LSTM that keeps on working inside like this, everybody. Okay, so this is one particular LSTM that we are having over here. What it does, it has multiple same kind of LSTMs working over here like this. See, okay. So now in this way, guys, if you have one particular LSTM, I think you will have a problem, right? Because obviously one LSTM will be very slow. Now let's say if I have given multiple LSTMs stacked together to you to go ahead and work for a particular problem or a particular problem statement, don't you think now your work can be actually super fast, everyone? Correct? And let me now tell you how exactly this whole thing works and what exactly is the understanding on this whole part of encoder. So everyone, the main reason why the encoder actually converts this entire thing into a into a context vector is because we need to give the entire data a fixed size representation. Now see, When you talk about a textual data, so a textual data can be in numerous different sizes, right? You can have sizes varying from, let's say from one word to let's say thousands of words, right, everybody? So let's try to get a problem statement and let's try to understand this problem firstly. So say that you want to translate from English to French, right, everybody? So there's an English statement and you want to give it into translation into French, right? Now the input that you will be getting over here will have a variable length, right? Input can have two words, input can have three words, and automatically the output will also have a variant length. That means we can have a many to many sequence over here. This is the problem statement that we're dealing with. Now guys, the issue is we can't directly feed these words into a decoder, right? We need to summarize it somehow, because obviously decoder is a machine, right? It won't understand this particular written word. Like let's say if I write I am Dev, right? Neither the encoder nor the decoder will be able to understand this raw text directly. Will these particular words will be understood? No, it won't be, right? So what needs to be done over here is we need to summarize it. We need to break it down. We need to convert it into some particular format that the machine can understand. And that is where, guys, the encoder comes into play. Now, what does the encoder will do? Let's say for an example, if this is my particular statement, now what decoder will do, decoder reads the input statement or reads the input data one by one. So what it does it firstly chunks this entire thing into something called as tokens, everybody. So encoder starts reading these input tokens one by one, and at the end, what it does its hidden states, or you can say the hidden states of the LSTM, they form a context vector. Now what this context vector is exactly, let's have a talk about it. Okay, context vector. So a context vector is basically a compressed summary of the entire information. Okay, now why exactly a compressed summary, everybody? Okay, what is the need of this context summary? What is the need of going ahead and having a kind of a compressed representation? See guys, the first need of the particular compressed representation is the fixed size. Okay, so whenever we are talking in terms of sequence to sequence model, a encoder and decoder, they have to communicate. Okay, and the encoder, what does it? Because obviously you are having variable input length, right, everyone? So let me take you back to the classes of your ML, everybody, when you guys were learning about machine learning, everybody. Now say that everyone, if a machine or if a ML algorithm that you have trained, it has been trained on 9 feature columns, everyone. For an example, okay? So your training data consists of 9 feature columns, right? Now comes your testing data, everybody. When you using this, you are going to test this model. You have given 11 features. Now tell me, will this particular algorithm work? Why it won't work? Any particular understanding on that? Because there's a mismatch in the shape. We trained our machine on 9 features and now we are expecting the machine to go ahead and work with 11 features. And that is where the encoders comes into play. Now think of this in this way, guys. If I put an encoder over here that can actually convert this 11 features into specifically in a dedicated size of what exactly the machine is expecting, can I go ahead and can I put this into a more compressed representation? Basically from 11 we'll be compressing it to 9, right? And then once we'll pass it to the machine will be able to work on it, correct? So isn't this a compression of information over here? This is the exactly same thing that we are doing in the encoder part. So what we do is, since all the inputs that we are getting, it will be in different shapes, different length. So what encoder does, it tries to compress them into one specific fixed length so that the whole information can be given to the decoder, and thus decoder doesn't have the problem working with different length of sequences. I hope I was able to make the point clear over here, right? So using this particular part, you will have a memory efficiency, and encode itself means that you are going to represent the words in the form of grammaticals, orders and relationship, all in the numerical format. So instead of representing in in the format of given array, what you will do, you'll represent the entire thing into an embedding, so that you won't be only going ahead and representing the meaning. Instead you will be also representing the grammars, you'll be representing in the order, you will be representing the relationship between those two given particular words. We have an example, guys. Just a quick example, everybody. The cat sat on the mat. For example, this is the sequence that we are having. Okay. Now the cat sat on the mat. We have a particular given statement over here, and now what we are going to do is we need to go ahead and we need to convert it into the particular part of compressed representation. Okay. Now tell me guys, everyone, when I talk about embeddings, you have multiple techniques over there. You have, you have techniques that can convert it into a particular vector, like bag of words, word to vec. But if I talk about models like LSTM and all, they work with the context. They work with the understanding on deeply with the context. What word is related to what, right? So like for an example over here, if you see, the word cat over here is a subject, right? Whereas if I talk about the word sat, this is a verb, right? So we have different relations over here. So what the encoder will do, encoder will compress this full idea, taking in consideration that this is actually a verb, this is actually, a noun, this is a subject over here, into a particular statement, everybody. And this statement will be represented numerically, everybody. So if you talk about a basic, the basic earlier ideas of, bag of words and all, so they can't understand these kind of relationship, everybody. Okay. But an encoder can learn this. The structures can be captured over here. The grammars can be captured. The subject verb agreement can be captured over here. Okay. Chalo, let's have a work on how exactly the compression happens. So let's have a check on how exactly a sequence is encoded into a context vector, everybody. Okay. So let's say for an example, I'm using one single statement over here that I am learning AI. Perfect. This is the example statement over here. Now, what exactly we are going to do first is we are going to convert each and every word into a particular word vectors. Okay. So this is the particular written statement over here, everybody. Okay. Now the first particular problem statement over here is that we need to go ahead and we need to convert them into embeddings. Why so? Because the machine won't be able to go ahead and won't be able to understand the raw textual format. Alright. Now talking about embeddings, everybody. So there we have two kinds of embedding, guys, everyone. One embedding is called as static embedding, everybody, and one is called as dynamic embedding. Okay, see, let me clarify this part, then we'll move forward. So tokens is not embedding, guys. Tokens is basically when you segment a particular statement into small pieces of words, everybody. That is what tokens is. So these particulars are your tokens. Okay, and when you convert these tokens into a numerical representation, say a vector, when you convert those particular tokens into a numerical representation, that is what is embedding is. Okay. Now talking about what kind of embeddings we are having. So in market, we are having two kind of embeddings. We have a static embeddings and we have dynamic embeddings. Okay. So we have static embeddings and we have dynamic embeddings. Okay. Now coming around the part of static embeddings first, because that is what you have learned so far. So see that guys, I am giving you an understanding over here that I am Dev and I am a researcher. A very simple statement. Okay, just to give you clarity. Now, if I want to encode this statement into a numerical format over here, I can use one hot encoding very simply. Or else I have other techniques like bag of words. Now, using these particular techniques, I will be able to convert this entire sequence into a particular, a particular vector. Now you'll be able to go ahead and you'll be able to convert this entire thing into a vector, maybe a vector of 0 and 1s, right? Now tell me guys, your 0 and 1 vector, will it be able to go ahead and will it be able to capture the nature, the relationship and everything? No, right? It is just giving you idea, okay, Dave, the word is there. Okay, you are having the word, right? Now let me give you another understanding over here. Say that I am having a statement that says I am going to Bank of India. Say for example, okay? And the next is I am walking on the bank of river. Now there are two statements over here, everybody. Okay. The bank word that I have mentioned over here in this first particular word and this first second particular word, are these both having the same meaning? No, it is not, right? If we are talking about the first particular word, that is the Bank of India, it is specifically stating a financial institution, a bank that can give you money or can take the money, right? But if I'm going to go ahead and if I'm going to talk about the second particular word, that is the Bank of River, it's a natural body. Okay, it's a natural, it's a nature surrounding. A bank of the river where a person can go ahead and have a walk. right? So now that is where, guys, the need of dynamic embeddings comes into play. What you need over here is such embedding system that can go ahead and that can adapt to the words depending upon the context, depending upon the relationship, depending upon the nature of the word. Contextual embeddings. So that is where, guys, the concept of dynamic embeddings comes into play. Let me put it in this particular part. Okay. So this is where the concept of dynamic embeddings comes into play. The embeddings based upon dynamics, okay, the context, the nature, the relationship, the subject verb agreement, everyone. And in this case, you'll be using that particular model that are having higher dimensionality. Like in case you talk about the BERT models, okay, BERT, okay, or you talk about these kind of models that are actually very good. You talk about the embedding, the large embedding models like text embedding models, okay, the Google embedding models. So that is where the concept of this embedding model part will come into play, everybody. Now, the few differences over here, let's talk about it. So here we'll have a fixed fixed vector length, or you can say there'll be one fixed vector actually that will handle entire thing. So each word will have a fixed vector. So your vectors won't keep on changing. They won't be dynamic. Okay. So you need to go ahead and you need to have a very fixed vector. Here your words vector can change. Okay. So each word vector depends upon the context, everybody. Now there's a huge, I see there's a huge discussion that is going on over here that so BERT model is bag of words, or where do we place the word to vec? Let me put it over here. So the models like bag of words, glove, fast text, even your word to vec, they all come under the static part, everybody. Okay, they all go ahead and they all works under the static part. They are not actually a dynamic embedding model actually, because what they are going to do, everyone, listen to this very importantly. Okay, what word to vec does, they assign one vector per word regardless of context. So we are not taking context in consideration over there. If you read the documentation of word to vec specifically, the context is not taken in consideration over there. Okay, so let's say in this case, the Bank of India and the Bank of River, they both will have the same particular context. But if I talk about a dynamic embedding, specifically here, those models will come into play like BERT. You will have GPTs, you will have transformers coming into play over here. So these models, what they will do, they will have a changing particular, changing vectors will be there. There will be changeable vectors based upon the words. Like for over here, let's say for Bank of India, you will have X vector. So for Bank of River, you will have Y vector because there is a difference in the meaning. Okay, everybody. So just for analogy, you can understand is like each vector over here, everyone, in this particular static embedding part, each word is like a photo. Once a photo is clicked, you won't be able to change it, right? But over here, guys, in the dynamic embedding part, each word is like a movie clip. Okay, you see in movie, there's a different particular scenes going on, right? So this is like a movie clip, a movie scene basically. It keeps on changing depending upon the context, everyone. Okay? But there's one cons also. Okay, so with pros, there's cons also. Okay, static embeddings are computationally very efficient. Okay, so you have very less computation consumption over here. Dynamic embeddings are very big models. Okay, they are not lightweight models. They are very big, very heavy models that needs a lot of computation to run. Okay, but also they have their pros. You will have much deeper understanding of language. You will much have a deeper understanding on the context, on the grammar part, right? That is the main advantage and the disadvantage over here. Now coming back to our last topic that we're going ahead with. Okay, so we were talking about how we can encode. So let's have a check over here. So now once we have this word, I think I was working on the word, what was the word? I'm learning AI, right? I'm learning AI. Now this is the word that we are having. So whatever output we get from embedding, that is context vector. So for each and every word here, you will have a embedding created. Okay. Say that for an example, you will have a embedding E1 over here, E2 over here, E3 over here, and E4 over here for these particular words. Okay. So what we have done, we firstly tokenized everything and then we have converted them into a embedding, right? In every particular word, they are having their own embedding. What is embedding? It is basically a vector that captures the deeper understanding of words, right? Now we have the embeddings created for these particular words, right? Now what we are going to do, one by one, we are going to pass these particular, words through our encoder. Or you can say through the stack of LSTM that we are having over here. So just for your quick understanding, everybody, these all are your LSTMs itself. Okay, nothing else. These are your LSTM that are stacked over here. Okay. Okay, just for your understanding, these are all your LSTM cells. Now what we are going to do, we can go ahead and we will be able to pass these all words one at a time going ahead in this architecture. And through this particular part, while this information will pass, we'll be also updating the hidden state as per the, the concept of LSTM, guys. Yes or no? Once you process a word, you update your hidden state, right? Just talking in the terms of LSTM. I'm not going ahead and not talking about anything else. Okay. Now, how the machine knows it's the correct context? Coming to that part, okay? So basically, when we talk about this part of encoder, so the architecture goes like this. So this is your input, everybody. Okay. Above this input, what you do is you have an embedding model, everyone, right? So obviously, once you will pass the input, your data will be gone into an embedding model that will actually go ahead and actually find an understanding of the words. So basically, over here, you are working with the contextual understanding. See, this is the contextual understanding you get over here. So you'll have vectors that will have a contextual understanding. Then what you do is the question should be over here. They how the machine would understand which vector has to be taken first and which vector has to be processed second, right? And that is where, guys, the second particular part comes into play. That is your positional encodings, everybody. Okay. So what positional encoding does with this contextual understanding or with this context vector, what they do, they add a order. Okay, what is that order? So let's say with this vector, we'll add a position. This is a position 1, stating that this particular embedding has to be processed at the first place. Then with this, we have to process this embedding at the second place, and then this is the processing at the third place, and then this is the processing at the fourth place. And through this, the machine knows which particular vector has to be processed the first go, which particular has to be processed the second go, based upon the length and based upon the sequence of the particular statement, everybody. Okay. And then inside the LSTM, what happens is based upon the previous word, their meaning and how they are related, the hidden states are updated. Like for an example, let's say if I give you an idea, so this is your initial state, everybody. Okay, this is your initial state. Let's say this is 0 right now. Okay, there is no information over here, right? Now this is your input number 1, everybody. What is your input number 1? I. Okay. Now at the first hidden state, what you will do, your LSTM takes the previous input, guys. Everybody, yes or no? Your LSTM that is there, it works with the previous input that is 0, right? And will take the embedding of this word number 1. Just trying to put a very layman equation over here so that everyone can understand. At the H1, that is the hidden state 1, your LSTM takes the previous hidden state and the current encoding so that it can work ahead with that. And now how exactly it has decided that which particular vector has to be taken in consideration, guys? Because with this particular word coming into play, we have two things. We have embedding and we have positional encoding, stating that this has the priority 1. That means this will come first. This is the place 1. Now once this operation has been done, comes your second input, I2, that is your word am. Now what is in the previous hidden layer, guys? Everybody, what is in the previous state? This is your previous hidden state over here, guys, right? Now what we'll do, now in the second particular hidden state, now your LSTM will go ahead and will take the last updated hidden state, that is your H1 over here, this one. So this will be forwarded over here, and now we'll be work with the embedding number 2, everybody, right? And so far what will happen, again the processing will happen and the H2 will get updated. Okay, and then comes the I3, that is your input number 3, that is learning. Okay, and here comes the hidden state 3. LSTM will go ahead, take the last updated hidden state and the embedding of the current part and will update it, and so forth. You will reach to the last stage also. Okay, that is your AI wala part. Okay, you will reach to H4. Your LSTM will reach out to the last hidden state, that is H3. We'll take the embedding of the word number 4 and we'll start working on it, right? Now the final hidden state over here, that is your H4, this is your context vector, everybody. Now why I'm calling this as context vector? Why not the upper 3? Why the only last one? because now it contains all the context from the previous list. So basically, what we are trying to say over here is that this particular last layer, specifically if I'm talking about this particular H4, this H4 is our context vector, guys. It captures everything the model remembers about the entire sequence in a fixed size vector representation. So this last hidden state from the encoder LSTM is your context vector. So let me write it over here, everybody, for a clear understanding. The context vector, okay, the context vector over here is your H4, everybody. Okay, now this particular vector will be passed to the decoder to generate the output, everybody. Now see, just to give you an analogy, okay, for everyone to understand how this thing might have gone, let me give you a clear bit of idea over here is what, okay, this might be a question that might be coming into someone's mind. What is the encoded in this version? When I say this is the encoded vector, so what is encoded in this version of a statement? What does encoded part means to? Okay, so when I talk about the encoded part, so encoded means who is doing this thing? Questions, everybody. Who is doing what? Right? This is the first question. Second is what is being done? Okay. Let me frame some question. Let me ask the answer to you. Third question is what is being learned? Okay. And what is the tense over here in this statement, guys? Okay. And what is the order and the syntax? This is all the information that you will have in that encoded way, encoded representation. Okay. Who is doing what, everybody? In this particular given statement, I am learning AI. Who is doing what? Which particular word represents who? I represents who, correct? What is being done over here? So I guess we are learning something, right? And what is being learned, everybody? AI, right? And what kind of tense it is representing to? Am, right? Am is the word that represents the tense over here. That is, we can say present tense basically. Okay. And what is the order or the syntax, right? So that can be taken from the states, how the states are representing the same, like H1, H2, H3, H4, correct? This is what exactly is there in the encoded vector, everybody. What is being learned, how it is being learned, and everything. There's the analogy to make you understand the same, everybody. Okay. Now, what happened internally, I guess since you all are aware about LSTM, so I will just reiterate what happened inside. So the LSTM has weights, right? Every particular neural network architecture has some weights, right? So what happens is once you pass a word, so the LSTM, the weights that the LSTM is having, they start learning that how much the current word that is having information, what information has to be thrown away and what information has to be forgotten, and how much information has to be processed in the next layer. Like for an example, if I give you a visual representation of the same, so it's basically like if you are having a word, I am learning AI, for an example. Okay. So once you have been through this embedding layer, everybody, once your data has been through this hidden layer, so you got some embeddings from over here, E1, E2, E3, and E4. And these embeddings were thus forward to the part of LSTM. Okay. And the LSTM has reproduced its own part of layers like H1, H2, H3, and H4. And this last part is what exactly is your context vector, everybody. This is what happened internally over here. Okay. So the fixed size over here means, guys, everybody, the context vector will have the same number of features no matter if your sentence is very long or very short. Okay. Even if, let's say, for example, let me give you an idea. What is this fixed size context vector is, everybody. So when I say about the fixed size, okay, so that means that let's say if I am having this part, I love AI, and let's say I'm having a next statement, I really love learning AI. So now you see, guys, there are two particular statement having two particular different size, right? So even if the second statement is much longer than the first one, still the size of both the particular words in the terms of vectors will remain the same. In the terms of embedding, it will remain the same. Now next question will be that why we are using this fixed size then? Because the decoder, that will generate the output will expect a fixed size input vector. If a particular model is being trained, it will always be trained on a specific size of vector. You can't have a variable length of features going in. So the size of the embedding vector is something you decide when you're designing or when you're training the model. So it's not universal. See, there's some common practice that we go ahead and will do. Okay, let me put this in a very easy way. So the most common dimension, the most common size of the vector is 768. Okay. Now the question that can come over here is why? Because the majority of the large language model that you see in today's date, they are trained upon these particular, this particular size of vectors. You talk about the BERT models, these all are based upon this size of embeddings. Okay. So if you're going to go ahead and if you're going to work with these kind of models, you need to have 768, 768 dimension of embedding. Okay. So according to common practice, the particular embedding size differs from 50 to 1024 dimension. Dimension mean features. Okay. So if you talk about word to vector, the size of the vectors over here is either 100 or either 300. Okay, ranging between this. You talk about the glove models, so they have basically embedding from 100, 50, 200, 300. These are the embeddings part. You talk about the PERT based model specifically, they have 768 strict. Okay. And obviously, the larger models, the more large your models will go ahead, the more larger embeddings you will need. Because if you will have a shorter embedding, so you won't be able to capture the entire context of the model. You won't be able to capture the exact meaning of the model. So the much bigger your model goes, the much bigger, bigger embeddings you will need. So it depends upon multiple factors, like what is the size of your vocabulary is. Like the more bigger vocab is, the more bigger vector will be. What is the complexity is, how much memory or how much computation you're having, that is a very large factor. Also, what is the size of your training data is. Okay, so that is where the size of embeddings also differ. Okay, and there are also some kind of trade-off that we do, like if you go ahead and if you want to have less memory uses, so definitely you need to go ahead and you need to have bigger particular vectors, right? So you pick the embedding size as a parameter basically. Okay, and it is tuned based upon experimental parts. Okay, so if I talk about I love AI, that is having three particular words. So final state will be obviously H3. And for the word I really love learning AI. Okay, so for this the final vector will be H5. So now the question is, how can H3 and H5 be a same fixed size vector if they correspond to different timestamps? So the number of hidden states there, they depend upon the input length. I believe you all are aware about it. So each hidden state vector has the same size. Okay, like for an example, let's say if you have fixed the size till 5112, for an example, this is the size of your vector. So that means you will have vectors till H512. Okay, that means 512 will be your last vector. So the final hidden state is taken as the context vector for summarizing the whole input. So in this case, dear, what will happen? For I love AI, you got the particular last state as H3. Okay, for a vector size of 512. This is your vector size. So your final state here is H3 for this size of vector. And for this statement, your final vector was H5 again for this size of vector. So both the ones are having the same particular size regardless where they have ended. Okay. So which timestamp it is ending on, that doesn't matter. Okay, because ultimately the entire size of vector is 512 only. Okay. So 512, when I'm talking about, it usually refers to the dimensions, the size each vector will represent for a single token. I'm not talking about the entire word. It is a dimension that will be related to a single token. Fine. So the number of tokens can be larger or smaller in this dimension. Okay, fine. Are you getting it? So it's not about one word, it's about one particular token. Okay. And if you're having more than 5112 token, okay, if your sequence goes more than 5112, okay, still each token will be represented by a vector, and each token will have one vector representing 512 features in it. Okay. So I'm going to show you the code actually, okay, that we are going to work on. So the examples remain the same, wherein we will be having a particular statement, the same one, the Bank of River and Bank of India. And here I'll try to make you understand that how exactly if you use an embedding model, let's say like BERT and all, how when you can get different embeddings on different particular given words, everybody. Okay, so that is what we are going to understand right now. Okay, so this over here, guys, is a particular code for the part of your vectors, everybody. Okay, so here what we have done is we are using a BERT model. Okay, so this is BERT based uncased, everyone. BERT based uncased means that is BERT vanilla model, and it has been trained upon lowercase letters. Okay, that is what uncased means to everybody. Now please have a check, everybody, over here. Okay, now see this over here, guys. What I have done, I have used this BERT based model, and you can see this is my first statement, this is my second statement, and then I'm tokenizing these two statements, everybody. Please have a check. Okay, so we have tokenized it, and we are getting this in the tensor format. Okay, and then what we are doing, we are getting the embeddings of these particular models, sorry, these particular statements from the particular model. So we are using a BERT model, and we are creating a embedding of it, so vector format. And then basically what we are doing, we are trying to get the tokenized word, and we are trying to map them with the particular embeddings. Now you see this, guys, what I have done is I'm trying to get the contextual embedding of the word bank for the index number 1, that is the word number 1, and the index number 2, that is the word number 2. And you can see I'm using the last hidden state over here. Now we have just convert that into a numpy array so that you will be able to see for a better comparison, and you can convert it. So see, this is the particular tokenized sentence, guys, everybody. See this, everyone. This is tokenized sentence 1, and this is tokenized sentence 2. Okay, everybody. Okay. Now if you see inside, these two remain same. Bank of River and Bank of India. Correct? Now, what I have done, I have implemented the cosine similarity matrix over here. Okay? Cosine similarity I have mentioned, and we are trying to compare the similarity between these two vectors. Okay, everybody. Are these two similar or not? So now if you see, there's only 50% similarity in between these two particular words. That means between the Bank of India and Bank of River, there's only 50% similarity. Okay. It's not 100% similar. That means the vector of these two particular given words are only 15% similar, not at all similar. Okay, this is for the embedding of BERT, everyone. Okay. Now let's have a diagrammatic understanding. I think I've already drawn a diagram of encoder earlier also. Let me put a more better diagram over here for everyone to understand how does an encoder looks like. So this is the encoder diagram. Okay. There's a reason why I'm putting the diagram later on, not in the earlier part. There's a reason behind it. See. Now this is a diagram of an encoder, how it looks. So firstly, you obviously have a input layer over here. Okay. Because now if I'll create diagram, you will be able to stimulate everything over here. See. Now what happens, your encoder is having two particular, your encoder at the input level, it will have two particular things. So here you will have embedding on the first go. Okay. Plus you will have a positional encoding at the second go. Okay. That means at one moment of time, you will be firstly converting the words into their embeddings. Okay, that means you will be carrying out the relationship part. You will be trying to understand the relationships and all. And the second particular part is positional encoding, wherein you will go ahead and wherein you will add the positions to those particular embeddings, everybody. Okay, that is the part wherein the input works, everybody. The first part actually. This was the first part. The first layer in the part of encoder, guys, everybody. Okay. Now the second part will come as the feed forward neural network, everyone. Okay. That means over here what will happen? We'll have a feed forward neural network that will, pass this whole thing into the particular next particular part of it. So here is your feed forward network. That will actually go ahead and will help you to do it. This is the part of your encoder, everybody, very simply. Okay, we are not adding any other information over here, any other bits of information over here. This is a simple encoder diagram that I have presented before you, that you have learned so far, everybody. Okay, now there are obviously some parameters that we use over here. I think I've already discussed that. So you'll have your embedding model size. Okay, so embedding size. Okay, then obviously how many tokens and all that also you'll have. So this is the architecture of the same, everybody. Okay, now detailed components, I'm going to write it right now. So the first is going to be your input embeddings. Okay, this is the first component, everybody. So obviously each word will be mapped to a vector. Okay, so we'll be going ahead and we'll be mapping each word to a vector, obviously of a n dimension depending upon the model. So let's say if you are working a BERT model, so generally you will have a dimension of 768. So for BERT the dimensions are fixed, it is 768 only. Okay, then once you have a embedding available, then you'll go with positional encoding, everybody. Okay, what exactly is positional encoding, guys? So since the architecture, since this encoder doesn't have an idea on which particular vector has to be used when, so what we use positional encoding for giving the order, used for ordering the vectors, used for ordering the vectors. Which vector has to be processed first, which vector has to be processed second, that is what exactly is the job of your positional encoding is, everybody. Okay, and now in between this this two layers, there's one more layer that actually sits, everybody. Let me show it to you that. Okay, see over here, before we proceed to the final layer, there is a normalization layer. Okay, there is a normalization layer that is there. Okay, and connected to it there is a neural network layer, feed forward neural layer. Okay, and then there is also one more normalization layer that is added over here. Okay, now what is this add and normalization layer? So this is basically wherein we go ahead and where we try to normalize things. Okay, because obviously if you want normalize, so maybe there will be some particular vectors with having high value, low value, so that kind of thing. Then using the feed forward neural network layer, what we do is we go ahead and we actually use a ReLU or whatever kind of activation layer you want to use. You use a activation layer in order to go ahead, in order to supply this whole thing to all the particular layers and to make the flow of the data going through the entire architecture, everybody. And that is how the encoder works over here, guys, everyone. So this is your diagram, and above we had the understanding of the encoder plus the embedding part. Okay, everybody. So what exactly this thing is? Okay, what exactly this RNN over here are? So basically, guys, there are two very different encoder types actually. Okay, see everyone. The one you guys are learning right now, this is RNN LSTM wala encoder, and the one that we are going to learn, there's one thing called as transformer encoders. Okay, now what happens over here is, here the architecture is recurrent. That means you go ahead and you take one token at a time. Okay, here basically what happens, we have a feed forward layer, because ultimately what we are going to do, we are going to learn about attention mechanism, okay, that works behind the scenes. So we will go on and we'll learn about it. So what happens in this part is, what happens in RNN and LSTM encoder, each token is processed once and the encoder remembers the past tokens using the hidden state, the example that you have seen here above, this one. Okay, so there is no concept of feed forward layer, feed layer over there, because ultimately whatsoever you guys are learning, it is being learned through the hidden states over here, right? Now, but when we talk about the part of the transformer based system, therein I am going to introduce you one particular mechanism, that is attention mechanism. That is where this feed forward term will come into play. Okay, with the terms of your vanilla part of your LSTM RNN, this won't be there in the picture. If you remember earlier, the picture that we were having, it was very simple like this. Let me draw it. So after this embedding part, you directly had the last part of output, correct? But once we'll go around the part of attention mechanism, this is the new architecture that we'll have with the current modern transformers. That is why I've introduced the earlier encoder with the first diagram, in which we were having direct output, and the one that I've introduced right now is with this one. Okay. So the feed forward only exists in transformer based encoder, not in your RNN and all that based. Okay, in RNN wala part, you go ahead and you can directly take the last input from the hidden states. Okay, whichever hidden state you are referring to. Okay, this is the architecture. Now then, guys, let's go back to the first diagram of the encoder decoder that we have seen over here. Now we have a context vector with us. Okay. Sorry, my bad. I guess this won't be visible to you. So let me write it, context vector. Okay. Now guys, this is the architecture to the part of decoder in the technical terms. This is how the encoder looks like. Okay. And what will happen over here when we'll go to decoder? Let's have a check on that part. See, decoder now. Before going to decoder, everybody, let me take an idea. Now guys, before going to decoder, what we are having in our hand, the context vector. Okay. Now our job is to go ahead, our job is to decode the context vector using a particular decoder. Now anyone, can you think about what exactly the decoder might comprise of? Because if I talk about encoder, we had a lot of stacks of LSTM working over there. Any thoughts on what might be in decoder? Let me give you an idea, everybody. When I talk about the decoder part, so the very first understanding is yes, it will take the part of your, the context vector and will start decoding it. But what exactly it will be? See, when I talk about decoder, guys, decoder is also having similar kind of architecture as of encoder. So there is no difference over here. This one just addition. Let me tell you what. So here also we'll be having LSTM cells. Yes, we'll be having LSTM cells. Perfect, because that will help us to go ahead and that will help us to process and translate each and every word to a dedicated task. Yes, that is correct. But moreover, you'll be having one more thing over here. What is? Once your input data goes into this decoder, guys, once your context vector is provided to this decoder, what happens? See, decoder has two special tokens, guys, everybody. One is called as start of the statement, or you can also call it as begin, or it is called as a start. There are a lot of terminology that can be used for it. So basically SOS, begin, start, or whatsoever, these basically state that the decoder is going to start, or we are going to start with the generation. Okay. And at this end, we have a special token called as EOS, stating end of a statement or end. Okay. Or basically it is also called as, stop. So these tokens actually tells you that, okay, decoder will stop decoding or it will start doing generation over here. So decoding stopped over here. That is what is the meaning of these particular two tokens, and it will be generally in the very starting LSTM. Okay. So whenever your input comes, the very first input that will go will be start SOS, and the first input will be given from over here. Okay. So once we have the compressed representation, then how exactly this whole thing will come into play? See, we now have a compressed representation. Let's say context vector we got was h5. Okay, this is our context vector, that is h5, hidden state 5. Okay, now what we are going to do, everybody? Let's take a small example over here. Let's try to understand how exactly a decoder might work. Sorry. So see this, guys. So our example word was I love AI. Okay. So for this, everyone, let's say that I want to translate this entire thing, everybody, into Hindi. Okay, there's a translation task that we are doing. I want to translate this into Hindi. So what will the Hindi translation to it? मैं, right, for example like this, or I love learning AI, for example. तो मुझे AI पढ़ना पसंद है, kind of like that translation. Okay, so if we are having that kind of understanding, so what we are going to do, we are going to design a LSTM based sequence to sequence model, everybody. That is what our job is, everybody over here. Okay, so here in what decoder will do, now our hidden state that we are taking in consideration is h5, for example. Okay, so let's say in this case it will be h3, and if we are taking the word I love learning AI for a better understanding, so this will be h4. Correct, everybody? The last decoder state. Correct. So in this case, guys, what will happen? Let me write over here. Decoder hidden state over here is h4. I'm taking this statement. So h4 is the hidden state over here, and the decoder cell state that will start with, okay, that will be also c4. Long term memory, short term memory, right? h4, and this is your c4. Long term and short term memory. Correct, guys, everybody? Decoder hidden and decoder cell state, c4 and h4. Is it correct? Based upon your LSTM wala part. Cell state was the upper line, hidden state is the lower line. So this is basically a short-term memory, or your RAM part wherein all the temporary thing happens, correct? And this is your cell state for your long-term dependencies, correct? So the same thing I have written over here. This is your state number 4 for cell state, and this is your state number 4 for hidden state, correct? Now the first input to decoder is going to be SOS. That is the start of the statement. We always start decoding with a SOS token. Okay, so this is a special token, guys. Okay, this is a special token that is called as SOS, or start of sentence. So this SOS is embedding, and this is passed to the LSTM along with your H3 and C3. Okay, now guys, tell me, if I'm going to pass, so this is your LSTM, the first LSTM layer basically. So what I'm going to do is I'm going to pass this SOS along with your H3 and along with your C3. And this is the output terminal. Okay. Now tell me, guys, obviously from here you'll be passing the, this output to the next layer also. But over here, can I expect the first conversion as ma? So let me give you an idea what we have done over here, everyone. So we have passed the SOS, the start of the statement. We have passed our hidden state, that is our context vector over here, and we have passed our long-term memory. Based upon this knowledge, the decoder, assuming that everything goes fine, so assuming that we are getting the first output as ma. Is my understanding correct? Here I'm assuming that everything is going fine. The machine is able to understand the context very well. The context vector is properly provided and everything is going good. So this is the first output that I should expect in the translation task, everyone. Correct? Hai? Now, once we have produced the first particular value, then comes the generation of next token. Now, what we are going to do over here is we will be using this predicted value, okay, this first predicted value as the input to the next decoder layer. That means for this next particular decoder, this will act as an input, everybody. Okay, and then what we will do is obviously your hidden state will move forward, okay, because earlier we were working with h4, let's say, or h3. So the new hidden state will be h3 or h4 plus 1, so n plus 1 whatsoever it is. So considering the previous hidden state was h4, so the new hidden state that you're working will be h5, right? So what will be the equation over here for the next token? What will the equation over here for the next token? The input over here is ma, okay? We pass this ma to this LSTM, okay? Plus, can we pass the new hidden state that we have created over here? This is your h5, and this will predict AI, like whatsoever AI is in Hindi. Okay, I'm not very sure how do we write it. Let me write it with my understanding. So I guess it is AI. Okay, this is what is in the Hindi. So now you will again go to the next particular understanding, next token, right? For next token, guys, the new hidden state will be H6. Yes or no? Correct. So this output, that is your AI plus LSTM plus your H6, that will give your next particular output, and so on. It will start producing your sequences, everybody, and this sequence will go on till you hit the EOS or the end of the statement part, everybody. Okay, this is how the decoder will keep on producing this particular entire state. Okay, to make it more clear, guys, I'm going to write a pseudo code over here for your pseudo pseudo understanding. See, everybody, so you all also be on the same page so that we can echo out. Okay, so let us start with the initial state from the decoder. Okay, what is the initial state from decoder, guys, that we have received? So let's say this is my hidden state variable and this is my cell state variable. Okay, in order to keep the things more transparent, what I'm going to do is I'm going to write some particular variable names over here. So like, let's say this is our hidden from encoder last. Okay, this is my hidden state from the encoder last state. Okay, and this cell state is the encoder last cell state. So the name of the variable is also accordingly. H encoder last, that means encoder's last hidden state, and C encoder last, that means the encoder's last cell state. And then we have a input token over here, the special input token, that was basically your SOS, start of the statement. Now guys, what we are going to do over here, we are going to iterate, right, over all the all the length we are having, all the length of the context vector. So for x in a range of maximum length, like whatsoever is the maximum length is, okay, we will take a embedding, okay, what embedding of the input token basically, okay. We will go ahead and we'll calculate the output and the hidden and the cell state, right, using LSTM. We'll use the embedded data from over here, this will come, and we use the last hidden state, correct, and the cell state, obviously combining both the short-term information and the long-term information, and then we'll make a prediction, right, because obviously this particular thing will produce the output, so this is your prediction, right. And then using this prediction we'll implement the the softmax function, something like that, to go ahead and to utilize this whole thing out, right. So this is how the decoder will work. Okay, so to make them very much clear, let me go ahead and let me put it in an analogy format. Okay, let's say for an example, you are a person who has been given a job to translate a English into a French language, into any other language. Okay, but the only problem over here is you can only listen to English statement once. Okay, and then you have to write a translation. That means you can't go ahead and you can't complete it, listen everything and you can do a translation. You have to read a statement, you have to write, you have to read and write. So this is like it goes. Okay, So you have to listen to an English statement once, and then you have to write a translation. So basically, the job of encoder is of the listener and the note maker. So what the encoder is doing? Encoder is listening to all these English statements one at a time, and as it, as it hears a word, it takes note and it actually summarizes the main point. And the summarization of this whole thing is your context vector. And now this decoder is basically your translator and your speaker. Okay. So decoder basically receives this, this entire summarization, that is your context vector. Okay. And then what it does, it actually goes ahead, it actually tries to translate. Okay. It tries to go ahead and actually tries to speak this all translation one at a time. So for each word, you go ahead and you refer to your context vector. Okay. What exactly was the meaning? And then you translate it. Okay. That is how this whole thing is going ahead and working on. Okay, guys. So now let's see how exactly this translation. Okay, I think translation is working word by word. So basically, the translation isn't usually word by word. So see how exactly it works. It depends upon the grammar, it depends upon the word order, it depends upon the vocabulary. So the key idea is that decoder is generating word step by step, not exactly one word, word by word. It's actually step by step, H1, H2, H3, H4, H5, so on, based upon your context vector, based upon your hidden state and the cell state. Okay, because see dear, your context vector over here is having the entire understanding. Okay, this is the whole sentence meaning, okay, captured in one particular vector, right? Now this has been done by encoder. Okay, so the decoder doesn't have to guess a word to a direct match. Okay, instead it has to use the summary to generate the word. Correct. Now, what does the decoder does? It produces one word at a time, and each word conditions upon different things, like the context vector and like the previous word that has been generated. Okay. So say that the previous word generated was I was, and you are basically waiting for a word to be generated. Okay. So this X word that has to be generated, the generation depends upon this word, the context vector. Okay, and based upon these two, this word will be guessed or this word will be generated. Okay, so now how exactly context is utilized in decoding? So dear, the context vector is basically, the last hidden state. Okay, basically the last hidden state, or you can say also the last cell state from the encoder after you process the entire thing. So this vector is basically passed as the initial hidden state of the decoder, right? Say that, guys, the encoder's last hidden state, if I talk about, was, let's say, H8. Okay, for an example, everybody. That means this H8 is going to be the first hidden state for decoder, everybody. Let me know, please. Correct? Now, so instead of starting from scratch, what decoder is doing, decoder starts with a state that already knows the input statement. Now, instead, what we are doing, we are not starting from the very start. We are starting from a state where almost everything in the input is known to us, right? And now what you do is, now decoder takes this SOS token, the special token, along with your, the starting hidden state, and then it try to predict the statement. Okay, and at each decoding step, it takes the previous word embeddings. Okay, because if you will take the previous word embeddings, you will be able to get the understanding. Okay, what was the word was, what was the relationship was, right? And then based upon that, and based upon the last hidden state, you can go ahead and understand, okay, which will be the word that will best fit according to the last embedding and last hidden state. So as the decoding proceeds, the decoder hidden states, they also evolve as encoder, carrying forward the context of what has been generated earlier. Okay. See, it works like this, everybody. Encoder, we got your particular whatsoever context vector was. So we got this context vector. Okay. And this context vector is basically the hidden state of your encoder and the cell state of your encoder. Okay, the last ones. Now, when we talk about decoder over here, guys, everybody, so we firstly initialize the decoder's hidden state. Let me write over here. You initialize the decoder hidden state, which is basically the final states of encoder itself, nothing else. See, right, everyone? Perfect. Now, what you do is the first input token is your SOS, the start of the statement. And combining these two, you get the first output. Okay, Now, once you have the first output, obviously your hidden state will get updated. So this one, let's say for the first decoder hidden state, you will move to the decoder hidden state 2. Okay. And now in decoder hidden state 2, what you are going to do, you are going to take this particular decoder hidden state 2 with the previous output, okay, embeddings, in order to go ahead and in order to formulate the next particular generation. And obviously after the generation, again you will go ahead and again you will update your particular hidden state, and this is how the context will be going and will be used further down the road. Okay. So there's a key difference between the RNN based model and the BERT, because BERT is a transformer based model, and we have not started a transformer based architecture yet. Because when we talk about RNN and LSTM based, the part here, so here even we are missing on one particular thing. Okay, that is basically here we don't have the attention mechanism part. Okay, BERT is mainly designed for understanding tasks. Okay, so what does it? It processes all the input sequence at once, okay, in parallel during the encoding. That is where the things happen. Okay. Sure. So now let me give you an idea on the last part of this particular whole module. So this last part is on about the part of how exactly we'll be having a diagram, like the last diagram on the part of encoder decoder architecture. Since we have completely got the idea on all the things clear about that, what exactly and how exactly encoder decoder works and the other show parts. So see guys how exactly this whole thing works, and what exactly is this whole part is. So if I talk about your encoder looks something like this. Okay, you have your inputs. So how the connection and everything works, let me put down over here also. So this is your input, and obviously your inputs then goes to the embedding model, okay, that actually embeds the things, okay, and obviously has a positioning and all that. And then this embedding goes into your LSTM. Okay, and LSTM, obviously you will have a connection of LSTM. So you have LSTM1, LSTM2, LSTM3, LSTM4, and so forth. You will have LSTMNs that will obviously produce n number of HN and CN, that is the hidden state and the cell states. Okay, and whichsoever is the last out of all of this will be your context vector. Okay, so this will be your context vector. Say that for example in this case, this I am taking as H8 and C8. These are your last particular vectors. Okay, and this is the end of the sequence of a encoder, everybody. Now from here we'll pick up the pace for the part of decoder, guys. Okay, now in decoder the things starts from SOS. Okay, the start of the statement. Okay, what we do, we take the start of the statement, okay, and we take the embeddings, everybody. And in this embedding part, what we do, we combine this SOS in the first decoder LSTM. See, this is decoder DLSTM1. What we do is we take the LSTM cell H8 and C8. So basically we are taking H8 and C8, okay, and we combine them to find the first particular part. So from here we get the context. Okay, from here we'll get the context, and then this LSTM can go ahead and can predict something. So from here we'll get the first prediction. So your DLSTM1 will produce a output. Okay, and now this particular predicted token and your cell state for this one will be updated. So now it will be DLSTM2 basically that will be working. So now the DLSTM2, what it will do is it will take this particular output and the last particular updated hidden states. Okay, so continuing forward, you'll have H9, DLSTM1, H9, and C9. And then the next particular generations will happen, everybody. Okay, and this will continue till we reach to EOS. So in decoder, things are very easy, guys. Okay, in decoder, things are very easy. Okay, so after this particular part is done, you will have one particular output that will be come into play. That is your output number 2. Okay, once you will have this output number 2 coming into play, then again you will initialize the next particular part, that is your LSTM3. Now this LSTM3 will take your output this, okay, and obviously you will be updating the H10, right, because H9 and H, as C9 has been used, so now you'll have H10 and C10 coming into play, and it'll work for the next particular generation. Okay, so basically when we talk about the part of decoder here, I told you we start with SOS, right? So this tells the decoder that okay, begin the generation, right? and the prediction of first one is done using the distribution. Okay, so you have the context vector, right? So using the probability distribution over the vocabulary and the softmax function, we actually generate the first token. Okay, so say that all the words whatsoever you have predicted, so you implement a softmax function over here so that we can get a probability. Okay, because before that we are not having any words, so we are solely dependent upon context vector to go ahead and find out, okay, depending upon the embedding and the positional vector, what could be the first word will be. Okay, to just to clarify this all part over here, guys, I'm going to show you a bit of code, guys. Okay, please have a check onto that. Okay, please have a check over here. This code will be really helpful for you. Now you see over here, guys, everyone, what I have done, I have trained a particular machine on the part of encoder decoder for English to French translation, everyone. Now see how exactly things has gone through, okay, and how exactly work has been done. So we have two sample data sets, guys, everybody. Okay, just to clarify everyone's doubt. Now this is the English treatment of on the part of NLP. So I love NLP and how are you? And these are the French translations to the same, everyone. Okay, so this is very small, thing that we have made, and we have made a tokenizer, everyone, over here. Okay, we have made a tokenizer, and this tokenizer you can get from Keras. From Keras, you can actually import tokenizer directly from their processing module. So this over here, we are tokenizing the English statements, everybody. Okay, and this over here we are tokenizing the French statements. Okay, and I hope all of you have got the idea why English statement has been taken once and why French statement has been taken once, because until unless your decoder won't have any idea about what you're going to translate, how it will translate. Correct, that is a very general common sense. Now we are padding the sequences, okay, in order to make sure that everything is in the same sequence, and this is the dimension that I'm taking for the embedding model. Okay, so we are taking an embedding of 256 dimensions. That means all the particular tokens will have a vector of 256 dimension, not the statements, the tokens, guys. Again, I'm repeating, all the particular tokens will have the embedding of 256 dimension. This is our encoder input. So I'm defining an input layer wherein I'm passing the length of my sequence. Okay, the length of the English sequences over here. Here we are initializing an embedding layer. So you see this, guys, over here, this is our embedding layer. So maximum number of instance. Okay, fine. See, guys, everybody over here, the latent dimension over here that you are mentioning again and again, this is the encoded dimension. So embedding dimensions, dear. Vector size, Dharmendra. 256 is the size of embeddings. Okay. 266 dimensional vector. Okay. Let me write over here. 256 dimensional embedding vector, dear. Okay. Okay. Now what we are going to do, we are embedding it, and here we are having the LSTM, because obviously if we are having this embedding of the same dimension, so itself I have taken the encoder also of the same particular dimension. So our LSTM is having 256 units. Okay, and then basically I'm processing this entire thing in this particular code. So we are using the encoder LSTM to go ahead and to process our output, our hidden state and our cell state using the embeddings. Have a check, guys. These are embeddings. These are our LSTM layers, and what we have to do, we have to pass these embeddings inside this LSTM layer. Is this understanding correct? You will pass this embeddings inside this encoder layer. So basically this one will be passed over here inside this, correct? And then through this LSTM part, we'll be able to return two things, our hidden state and our cell state, correct? So these are your encoder states that I have defined over here. So we have got our hidden state over here. Okay, this is your hidden wala part and this is your cell state wala part. Okay. Now, once we have this all thing present, okay, now we come to our decoder. Now, guys, decoder is of which language, everybody? Because the encoder was supposed to be in English, correct? So decoder is in which language, everybody? French, right, everyone? Yes or no? That means the training of decoder has to be done on French. So the same process we will repeat over here for the decoder also. See, have a check over here, guys. We have passed the French language part over here. We have done the embedding for the same. We have decoder LSTM over here. We are getting the decoder LSTM with the decoder embeddings. You can see this over here. Okay, and have a check, guys, over here what we have passed as the main part. What is the initial state in the decoder, guys, everybody? What we are taking in the initial step of decoder? Have a check. Encoder states. What is the initial state in decoder? Cell states. We just defined earlier. See everybody over here. What is the encoder states, everybody? The last encoder states are the initial state for the decoder. Remember that part? So see, this is our encoder state over here. And the same thing we have passed over here as the initial state. See, are you able to see this? Right. And at the last, obviously, decoder will not produce a word directly for you. It will produce a vector for you. So you need to put a softmax function to find the probability, okay, out of all the prediction, which one is having the highest probability. That will be your correct prediction. So this is your output for the same. Say softmax function has been used. Everybody over here. And this is the output. Okay. Now this is the components of it. So this is your encoder part, this is your decoder part. But this combines doesn't gives you a a sequence to sequence model. We need to make a sequence to sequence model over here. So how can be done? So see this guys, everybody over here. So what I have done, I have made a sequence to sequence model over here. Check this out guys. We have a model in which we are taking the encoder inputs, right? We are taking the decoder inputs, okay? And what we are expecting as the output is the decoder output. Is this understanding correct? These are your input parts and this is your output part. And then we are compiling the model, okay, with our loss function and our optimizers. And then I have trained the model. You see how on which particular data the model has been trained, everyone. The model has been trained upon English sequences for the encoder, French sequences for the decoder, decoder target data, the batch size and the epoch. I guess you are already aware about these parameters. So this is my target data over here. Okay. This is my French sequence and English sequence on which we are training the model. Okay. And here basically guys, I'm trying to infer this model. That means whatsoever model we have built so far, I'm trying to infer it. That means I'm trying to test it out over here. So you see this is our encoder model with encoder inputs and encoder states. Okay. Everything has been taken from above. So we already have our encoder inputs. Okay. Okay. So this is your target part. And now this is what we want the model to feed in, and this is our expectation is. And this inference part is basically guys, inference is that part particular of a large language model wherein you have trained the model, now you want to use it. That is where the inference comes into play. So inferring the trained model. So here we are having the encoder model in which encoder inputs and the encoder states we have already defined earlier. So in case if you are not clear, so encoder states is over here guys, everybody. And the encoder inputs are over here. You can see this. Okay. So here we are having an encoder model. And then what we are doing, we are defining the decoder state for hidden, decoder state for cell state and decoder input state. So we are keeping the size, shape same everywhere so that we don't have that shape error issue. And then for the input part, you can see what will be a decoder states input guys, everybody. These two, right? The decoder hidden state input and decoder cell state input that I have mentioned over here. Okay. And again, what we will do over here, once this whole part is done, again softmax and all that, because we already have trained the model over here. So most of the parts has been taken from over here itself. So you can see your embedding part is over here. Again, embedding size, latent dimensions, and how the model will be trained. So we are using the decoder LSTM that we have trained over here in order to go ahead and train this model. So again, you can say decoder embeddings. So embeddings we are using initial states. That means the earlier states of decoder. So we'll getting it from over here. And so far we will go ahead and we will decode this entire thing. Now this is a translation function that is basically everything what we have done so far. It's actually done over here. Now you see the SOS wala part, everybody. See, wherever we will find the EOS, we'll break this whole thing up. Check this out. I told you about SOS and EOS. So SOS will be automatically considered in the tokenizer. It will automatically add that. The EOS, once we'll identify the EOS, we'll go ahead and we'll break the entire generation over here. So now you guys have a check how exactly this happens. If I run this part, everybody, see this is running through right now. It will take some time. Okay, it will take like 2 to 3 minutes to go ahead and to run this. Okay, it's connecting right now. So see, we are training the model over here, and training is super far because we are having very less part. Okay, see, this is a translation, guys, everybody. Okay, and if you want to see the input statement, this is my input over here. See, translate statement, I love NLP, and this is the translation of the same. So this is the code understanding of this particular part, everybody. Okay.
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.
I want to first of all take you guys through an understanding on LSTMs or long short-term memory models, a concept in deep learning, an architecture called recurrent neural network, a simple aspect of what RNNs and LSTMs are. You have a cell block, you have another cell block, you have another cell block, wherein you pass the data of a previous hidden state, your current input, your previous hidden state, your current input, your previous hidden state, and your current input. I'm sure all of you have heard of this concept in theory, but did you know when we practically implement a recurrent neural network, this is not how we program it. In the program, when I said RNN and cell 64 or cell 32, what do you mean by that? Let's say I say RNN 32. Does this mean there are 32 RNN cells back to back? When you program 32 units of RNN, is that what you mean by 32 cells of RNN blocked layer by layer by layer? Is this what? If I say that I have an RNN of size 32, cell number 1, cell number 2, cell number 3, cell number 32. Is this how the neural network is going to look like? The answer is no. Guys, practically speaking, I think you need to understand some foundational basics. Let me talk about it, right? Let's say you want to take a recurrent neural network. You already know a recurrent neural network works in a very simple way. You have a previous hidden state, you have a current input, right? You have a previous input, a previous hidden state, a current input, another cell of previous hidden state, current input, previous hidden state, current input, previous hidden state and current input. This is how your RNNs will look like, okay? Of course, you guys know that RNNs have an advantage and a disadvantage. Advantage, long-term memory can be retained. Disadvantage, vanishing gradient and exploding gradient. But all this is theory. I am talking about the practical implementation. Listen to me carefully. Suppose if I have a review of the customer. I love the restaurant. I hate the restaurant. The restaurant is amazing. The restaurant is terrible. And you have a label, positive, negative, positive, negative. If this is the data set, point number 1, what kind of machine learning implementation are you going to be doing in this? Can I say this will be a classification task? Will the classification be classifying the reviews into positive and negative? Agree? So somehow I will be using classification model to make my classification occur. Positive is 1, neutral is 0. Point number 1, we are going to be implementing something called sentiment analysis. As a data scientist, the first thing you're going to identify in this particular class is to get the understanding that this is a classification problem. Now, my people, all the reviews column like I love the restaurant, I do not like the restaurant, all of these reviews, what do we do with these sentences? Please remember guys, be it your large language model, be it your small language model, multimodal model, deep learning model, any kind of natural language processing related model, every single column of your review, you are going to convert everything into something called as a vocabulary. Practically speaking, you do not directly jump it into word vectors or embedding. You can't do that. Practically, it doesn't work like that. What do? You first convert your entire review section into a vocab. What do you mean by vocab? In your programs, I'm sure you must have used a variable called max underscore features. Suppose if you have 1,000 reviews of all the customers like I love restaurant, I hate restaurant, XYZ, XYZ, XYZ. Tell me this. Every single word, for example, love. If love is repeating itself 937 times, so can I say that the frequency of the word love is the highest? The occurrence of that word is the highest. So love is going to be created as a dictionary, and love with the frequency will be the first word that will come up in the vocabulary. Now the second word is the word the, and the repeats 867 times. Understood? So the will be repeating second. Then you have the word day 627 times. Then love will be 432 times. So did you understand that whenever you are given a text, my first task number 1 is to convert the reviews vocab or the reviews data into a vocabulary where everything is sorted according to the frequency of their occurrence? That my first task is to convert any textual data into a frequency of words, right? My people, what happens is every single time you convert it into a vocab, there is also one other thing you do. You maintain their ID. We call this as a word ID. So for example, can I say love is available at ID number 1? The is available at index number 2. Day is available at index number 3 and love is available at index number 4. Let's take a simple assumption. So let's say if you have a sentence called I love food. So what will be step number 1? Can I say I love food is converted into word indices? Say for example 45, 123 and 89. Because I is available at index number 45. Love is available at index number 123 and food is available at index number 89. Will I say this is the first step in doing any natural language processing task? Right after your texts are converted into word indices, okay, can use WordNet for ID? Yes, that is also possible. Either WordNet, or if you want to escape all that together, you can just use something called glove. So tell me this. I love food is converted into indices. What will happen in step number 2 is every indices is then converted into an embedding dimension of something. Say for example 45 will be 0.2, 0.8, 0.1, 0.9 and 0.3. This is nothing but the embedding for the word I. Everybody, this is where lot of you will be confused in the future, but I want to help you clarify this. Can you see that there is something called the dimension of the embedding? You said you had a word called I love food. I's index is 45, love is 123 and food is 89. Did I convert the index I into an embedding? Can you control the dimension of the embedding? Can you control the dimension? Suppose the dimension of the embedding is a 128 dimension vector. What does it mean? It means that the word I will be represented as a vector of the size 128. That the word I, a simple word I, can be converted into a word vector of the dimension 128. Love will be converted into a dimension of size 128. Food will be converted into the size of dimension 128. Now, one of the biggest misinformation in natural language processing is larger the dimension size, better is the understanding. The larger the embedding size you take, the better will be the representation of that particular embedding in the representation of this text. The reason why I say this is because you took the word 45 or index 45, you converted this into a dimension of say 100. You took the sequence 123, converted that to a dimension 100. You took the sequence 89, converted that into a dimension 100. So now you have word vectors or embedding vectors which are created for each individual indices. Please remember, your embeddings created are dense representations. Your embedding values are gonna be filled with numbers. They are not gonna be filled with zeros or actually basically zeros. Understood what I'm trying to say? Dense means every single number in that particular embedding will have some number to represent its knowledge. For example, if I show you two embeddings, 1, 0, 0, 0.98 versus 0.9, 0.6, 0.2 and 0.1. Between these two arrays, which one have more empty values? Or the values not empty specifically, but they give you no information. Can I say this is a zero index and this is a zero value here? Basically, only two numbers are representing the information of the word I, and the rest are completely empty or sort of zero. They are giving no information. So which one among these both are more denser representation? The first one or the second one? The second one is a more dense representation. Dense means it's explaining the word I in multiple different aspects. So what do you do, guys? You converted your I love food into word indices, and word indices are converted into embeddings, correct? My people, your word indices or your embedding, the 0.2, the 0.8, the 0.1, the 0.9 and the 0.3 are then added with something called as hidden state values. So can I say I have three hidden states? Right? I have some initial or some hidden state. So these are also gonna be assigned or kind of validated and given to me. I hope you know that in every recurrent neural network, a previous hidden state is passed to you. You pass your current input, and then the basis of that, you decide to either get an output y of t or the next hidden state y of 1. If this is h of 0, this is h of 1, right? You know this? I will take my previous hidden state, take my current input, depending on the problem statement, I will pass it on. If you guys are causing or using recurrent neural network to do classification, then will my recurrent neural network look like this? Only the output will have one single output. Rest, every single output of every block is not accepted, or we stop it. We don't want it, because we have to do something called many to one mapping. I hope you know this. We are taking a longer set of word and we are just converting that word into one single output, positive or negative. In a classification problem, we do something called many to one mapping. We do not take the input or output from every single output cell block, only from the one block outside, the last one, right? Okay. The question that, sir, if I write down the concept called RNN of 32, does it mean that I am taking 32 RNN blocks and I am taking it like this? The answer is no. RNN 32 means the cell is only one. You have only one RNN cell, but the hidden state representation are going to be of the dimension or the size 32. RNN 32 does not mean there are 32 RNN cells. In your recurrent neural network or LSTM block, when you see this thing called LSTM 32 or RNN 32, please don't confuse yourself with saying that there are 32 cell blocks. No, cell block is only one, but the amount of hidden vector representation in your hidden state will be of the dimension 32, because larger the dimension size, the better understanding of the vector or the model is what you're going to get. So basically you're trying to make this model training happen in such a way that the entire knowledge of the model is represented by this hidden vector dimension of size 32. That is why when you say the word I love food, right? Your I love food is going to be converted into word embeddings, and those word embeddings are going to go inside your RNN or LSTM cell. For example, if you say one LSTM cell, if I write down this sequence called LSTM of 64 unit, I hope you know this 64 and any number here is called as unit, right? These 64 units represents nothing but the size of the hidden state. This 64 here represents nothing but the size of the hidden state. Sir, what do you mean by the size of the hidden state? Tell me one thing. Will you have the word I? Like I love food, you will say I. So can I say I will be represented by some kind of an embedding, like say embedding of the dimension 100. Can I say embeddings of the size 100 could be the size of the word I? We downgrade the word embedding to represent the word I in a hidden state by the size 64. Your hidden state for the word representation I will be only of the size 64. This is what it means by the sentence LSTM 64. As a data scientist, if somebody asks you this question in your interview, hey, then I want to increase one RNN cell, then another RNN cell, then another RNN cell. Is this possible? The answer is yes, guys, this is possible. But the answer should be, why should you do this? Do this for a specific reason. First of all, these are called as stacked neural networks. Okay? Is a type of neural network architecture called stacked recurrent neural networks or stacked LSTM cells. Can you see they are stacked together on top of each other? First stack of RNN, second stack of RNN, third stack of RNN. Can you see? Or an LSTM layer or an LSTM cell or an LSTM cell. So sir, can we take multiple RNNs or multiple LSTMs? The answer is yes, you can do that. But is it because you want to increase the accuracy? No. You do not stack RNNs because you want to increase your accuracy. You stack RNNs or you stack LSTMs because, yes, for two main reasons. To understand the semantic relation and a long-term dependencies even better. RNNs and LSTMs in theory will say that we will remember long range dependencies really well, but in practical life they don't do it. So what people do is either they stack the RNN or LSTMs or they take bidirectional LSTMs. Meaning one sentence will go like this: I love food, and in the other cell you will say food love I. So am I passing both the front and the back portion of the text so that my understanding becomes better? So first of all, from now on, any program that we are going to build, are you guys going to have an understanding that text converted into vocabulary? Vocabulary is converted into some kind of embedding space, and that embedding space is then reduced or shortened by whatever cell structure or cell unit that you take, and this is the reason why we get the output. Your understanding for the cell structure of RNNs and your cell structure for LSTMs is clear. If this is clear, we take like a small hands-on part so that we are able to visualize the data, see how the RNN and LSTM is able to process the data, and judge or make a output possibility or some kind of a prediction. Just a quick hands-on. First of all, everybody, simply I'm going to import NumPy as NP. I'm going to import pandas as PD. Yes, these two are very important libraries. Suppose all of you, including you and me, we are sitting in the class, okay? Let's take an example. And we want to build an application to make, some kind of a prediction. You know what? I think I'll take this data set. I'm going to import Kaggle Hub, okay? And let me also import OS. Import OS, okay. I want to load a data set, okay? The name of this data set is actually Amazon Fine Food data set, okay? Amazon Fine Food Reviews. I'm assuming that is what the name is, okay? Fine Food Reviews data set, okay? Reviews data set. If I load the data and show you how it looks like, so let me just show it to you. So let's say path is equal to Kaggle Hub. So let's say Kaggle Hub dot dataset downloads, right? Yeah, download, okay. And I think the name of this is Amazon Fine Food Review. Amazon Fine Food Reviews dataset. Let me just check it. So snap Amazon Fine Food Reviews. Okay. What we are going to do is we are going to just load the data into CSV underscore file is equal to os.path dot join. Let me take my path, which is going to be one that I have defined, comma, review's.csv. Let me pass it on to us as reviews.csv, and we will ask the data frame to read it. So pd.read CSV, and inside this I will pass in the CSV file, right? So CSV file we are going to load, and I think it should just download it. So let me write down this step as step number 1. This is going to be step number 1, load the data. Okay, df.head of 3. Do you see the data set right in front of you? We have a product ID. We have a user ID. We have a profile name, something called helpfulness numerator, helpfulness denominator, score, time, summary, and text. Off the bat, when I look at this data, I only need 2 columns from the data. One is the score and the other is the text. Basically, df of, if I just take the value called score, okay, df of score, right? If I just print it, okay, I see that scores dot value counts, what does it look like? 5-star ratings. Okay, got it, cool, no issues. Basically, guys, if you observe this data set very carefully, what do you see in this data set? You are given df.head of 2. What are you given? You are given the text. See, for example, I have bought several of the Vitality can something, but for this particular review, how much star was given in the review? 5-star. Product arrived labeled as jumbo salted peanut but did not get the product well. What is the review of this? 5. So tell me, your classification or your classifier will have how many categories to classify? 1 star, 2 star, 3 star, 4 star and 5 star. Can I say there will be 5 stars between which we have to classify that my review is how many stars? Is it a 2-star review, 3-star review, 4-star review, 5-star review, correct? We will be able to classify them between stars of reviews. So did you understand that will be the goal in the entire project that we are going to be doing? We are going to be taking our data and we are going to be reviewing it and making sure that we are able to classify them according to the proper stars. In order to get started with our entire process, should you not do a slight EDA or a little bit of, what do I say, a little bit of investigation in our data set? What does the data set look like? What kind of problems does it have? How can we solve those problems? Not a callable function. How many reviews do you have in the data set? 5,68,454 reviews. Can I say that this data set size is comparatively larger? Like a very large data? You have 5 lakh reviews of people which I will be able to understand and make my analysis proper, right? So we have 5 lakh data set, okay? What other columns do you see in the data? So df.columns, right? Dot to list, right? Let's say dot to list, right? And run this. How many columns do we have? ID, product ID, user ID, profile name, helpfulness numerator, helpfulness denominator, score, time, summary, and text. Don't you think we only need 2 things? Text and score? Everything else is just appearing irrelevant to me if I want to learn the concept of RNN and LSTMs, correct? If I want to understand very basic idea, like for example, how many total reviews do we have? If I print, okay, I'm going to start the EDA from here, okay? If I want to know total reviews, how many total reviews do I have? So I'm going to print F double quotes of total reviews, REVIEWS. What will be the total reviews? Can I say length of DF? 5,68,454 reviews, right? If I also print df.info, what will this give me? What is the df.info going to give me? Text is in what data type? It's an object data type. Score is an integer data type. Text is of object data type and your score is of integer data type, right? We were able to print the info of the data set. Right after we print the info of the data set, can I also check df dot is null dot sum? What does this do? How many null values exist in the data? How many null? 27 null in the summary and 26 null in the profile name. Do I even need to drop the null? Because isn't my text and my score that is important for me? Nothing else. Right? To me, score is important. And what is important? Score is important. And what is important? Text is important. I do not need to drop anything. The score has no empty values, text has no empty value. Can I say that df of clean data is equal to df of, can I say text, comma, score? I am taking both my text and score. Just a separate data frame with just these values. Just for simplicity reasons, I'm still going to write drop NA. So if I print df of clean, what will this give me? df of clean data. What will it give me? Will it give me the text and score? This is what I wanted in my data set. If I want to process this in the future, I have both the text and the score. So have I separated them out? Taken these out together. Now, before we print this out, after removing the text, what is the overall data? What is the length of the data? So for example, if I write it like this, F double quote of after cleaning data, okay, after cleaning data or processing data, what is the overall data set size do we have? Length of clean df, okay? So clean underscore or df underscore clean, right? So df underscore clean will be how much? Is the review 5,68,454? Right? We know for a fact that we are actually working on 5 lakh plus reviews that we are going to be building our algorithm on. I am only doing basic stuff, nothing complicated. Right? So far, this is what the data set is what I am provided with. There are 5 ratings available in the program, correct? 1 star, 2 star, 3 star, 4 star and 5 star. Agree? Tell me, don't I want to print distributions of the rating? For example, can I print it like this? I want to know what is the rating distribution. This is the most simplistic thing I can do. So tell me score underscore counts equals to, okay, df underscore clean of score dot value counts dot sort index. What is this going to give me? If I do this particular thing, score counts is equal to df clean of score dot value counts dot sort index. What does this do? Is this going to give me an output like this? Listen, score counts will be something like this. Which count has what value? Score 1 has how many count? Score 2 has how many count? And I will sort it out based on the lowest to the largest. So basically I have the count also. I am getting a simple distribution of my data and I am able to print it. So can I say I can have percentages print? My people, listen to me very carefully. Print score counts. Okay. Score counts. Can I do this? Print F double quote of percentages. Okay. Everything will make sense. Score comma count in score count. I think, wait, I will be able to access it like this, right? Score counts dot items. Please tell me this is going to give me a zip index, right? So if I say list of score counts and unpack it, yeah, it will give me a list index. So items, I'll be able to loop through this. Okay. Percentage should be equal to count divided by length of df underscore clean, the total number multiply by 100. Okay. So I will be able to print for the given score for 5 stars. Okay. For wait, control X, come over here. For 5-star review star, my percentage will be percentage. Okay. And because this will be so let me do it like this much percentage. The numbers 52,268 was not making much sense to me. I did not understand the distribution like I'm supposed to understand. You know, like 3,63,000, 80,000, 42,000. So did I convert the entire distribution into percentage? Is this making sense? That 1-star review is only 9% of the overall distribution, 14%, 7%, 5%, and 9%. Do you see there is any problem in this data set? I see a big problem in the data set. Do I see imbalance in the data? Is this data going to be something called imbalance? So tell me one thing. Does RNN or LSTM handle imbalance data? The answer is no. No. They will perform the worst if you pass imbalanced data. Just because deep learning algorithms do feature engineering and all this stuff by themselves, that doesn't mean that imbalanced data is gladly handled by deep learning models. That doesn't work like that. But so far, are you clear, my people? I am able to calculate my rating distribution, convert it into convert it back into, say, for example, a certain categorization. How is it imbalanced? My entire distribution, only 9% have 1-star. Isn't that imbalanced? However, 5-star are 63%, right? Bhaiya, 63% of the people who have given me reviews are 5-star, only 9% 1-star. So if I want to understand genuinely what 1-star review looks like, will I be like, I don't know, you have to take or you have to do, anything else? So how to solve this? See, the problem is SMOT, okay, SMOT isn't, how do I say this in a nice way without sounding bad? SMOT isn't practical, okay? If you ask me, have you implemented SMOT in your production code? Never. Not once in 12 plus years of my life have I ever used your SMOT into handling imbalance of the data. Okay. There is a reason behind it. Okay. There are multiple different techniques to handle this. Okay. Sometimes you don't need SMOT to make it happen. Sometimes a simple, undersampling can make it much more easier. People usually prefer more penalty heavy or cost sensitive algorithms over SMOT. People don't like it. Personally speaking, undersampling or over, how do I say this? Okay, so imbalance is a little tricky problem, guys. So here is the problem, okay? If you ask me which algorithm will be able to handle imbalance well, see, I can't answer this directly because it depends on the goal of the problem. How much imbalance exists? If you have one photo of a dog, 9,999 photo of a cat, do you think any imbalance algorithm will be able to help you? If you want to predict what is a dog, what is a cat, you only have one photo of a dog and 9,999 photo of a cat. Tell me, even data augmentation, is data augmentation going to help you? Sir, kuch nahi hoga. Nothing is going to happen. In reality, if your data is terrible, there is nothing you can do. Data augmentation also will not help you. What will you do in the data augmentation? Photo, rotate the photo, randomly zoom the photo, randomly zoom out the photo. This is the max data augmentation you can do. Correct? The cat will be cat. In data augmentation also of a dog, you will have a random rotation, random zoom, random panning. What else can you do? You will have to add the data. If this is the extreme condition, do you think any algorithm is going to help you? No, right? Okay. So remember, either you have undersampling techniques, oversampling techniques. We also have something called SMOTEC. Okay. So actually it's written like this: SMOT, synthetic minority oversampling technique, plus we have something called TOMAC. Okay. This is considerably better than SMOT. Better than SMOT, SMOT TOMAC works, but it cannot be applied to any random value, any random data. You also have something called penalizing class factor. It's called PCF. Okay. You can also use a PCF. Smotomac, oversampling, undersampling. These four are somewhat practical in nature, but again, it's no one-shop solution for everything. Okay, so listen to me. Let's understand which one can we do and how can we do it. Currently, we are facing the problem of what we call as a imbalance of the data. We have imbalance in the data and we will fix it later. Okay, how we will fix it, we don't know. We will fix it. It is always good to see 1-star review, how do they look like? 2-star review, how do they look like? 3-star review, how do they look like? So can I say, my people, what I'm doing in the example is having a sample review. Okay, sample review analysis. Can I do this? I'm doing something called sample review analysis for score in 1, 2, 1, 2, 3, 4, 5. Can I say this? For score in 1, 2, 3, 4, 5, sample underscore review is equal to df of clean. Okay, I want to take score. Okay, okay, so if this is my main criteria, so wait, df of clean score is equal to for each individual value of score, I want to extract the preceding text and ilog at index 0, basically that particular review. So can I say print of, okay, f double quotes of, print of f double quotes of, I can say that the sample review, okay, the sample review, if the review is very, very large, like the sentence is very, very large, only print the first 200 characters. Okay. Product arrived label as this, like I am able to understand the, wait, or you know what, if it makes your understanding better, so I will say print of f double quotes of I can say that my score, right, sorry, my score is this much star review. Okay, this much star review. Okay, product arrived labeled as jumbo salted peanuts. The peanuts were actually small size unsalted. Not sure if this was an error or if the vendor intended to represent the product as jumbo. Do you see, he said nothing negative, but the review is 1 star. See, there is no negative, hatred, nothing of that sort. Even though that was said, a little sarcasm, and the star review is 1 star review, correct? Let's look at the 2-star review. If you're looking for the secret ingredient in Robitussin, I believe I have found it. I got this in addition to the root beer extract I ordered, which is good. The cherry soda flavor. Okay. I have bought several of the Vitality canned dog food products and have found them to be good quality. The product looks more like a stew. Okay. So this gives you 2 ideas. What idea did you get from this data? Anybody? Sentences are grammatically correct, right? Can I say the sentences are grammatically formulated correct? There is proper ... There is a proper full stop. There is a proper representation of the double quote jumbo. Now remember, this could happen in some reviews and this could not happen in some reviews. But at least on the sample that I see, I can see that this is just one of the example where the samples have been grammatically formulated well. In some cases, it will be good. In some cases, it will be bad. Since we are sampling whatever sample we have, this is what we have understood. What is point number 2? What is the second analysis that you can do? No negative words, specifically no words that represent hatred or any other words. So negative and positive related sequences are not available in the sample. Since this is only one sample, this is our analysis. We have not seen the entire data. It could be a possibility, but only based on the sample, this is what we were able to find out. There is no specific mention of any negative or positive word. It could exist. We don't know. But based on the sample we saw, this is what we know. But tell me one thing, this is only one sample that we saw. We have not seen multiple samples, correct? So do you think we need to do some kind of a data visualization? Do you think we need to do some kind of data visualization to get a better idea? I want to calculate this, okay? df of text underscore length, length, okay, is equal to df underscore clean or df underscore clean of df underscore clean of, can I say text, okay, text of dot string dot length. What is this sequence dot string dot length going to give me if I calculate this? And if I calculate df of clean, and if I calculate word count, word count, word count will be equal to df of clean of the column text dot string dot str dot split. Okay, I want to split it, and dot str dot length. Okay, so if I run this piece of code in DataViz, okay, and I am going to take, oh, this is going to take a little bit of time because there are 5 lakh, sort of reviews that we are going to be doing. But df underscore clean, I split the word into individual value method, and I'm taking the word count and I'm taking the length of the words. Is that easy to understand? Not a very complicated process. We in matplotlib, we have something called sizing the canvas. So what do I do? Import matlib.pyplot as plt. Is this correct? This is going to help me. Now, how do you size the canvas in matplotlib? plt.figure. Inside the figure, can I not take a variable called figure size is equal to 15,5, for example? Can I do this? This is what we call as sizing the canvas. Agree? Now tell me this. I want to plot 3 distribution plots that I have in my brain. My brain is thinking of giving you 3 different plots. One of the plot that I want to plot for you would be something like this. Plot dot subplots, okay, of 1, 3, 1. What this means? So basically, let me write down. Plot number 1, rating distribution, okay, distribution. Score counts, the one that I have already calculated, dot plot, okay, kind is equal to bar. I'm going to plot a bar chart. Let me say color should be equal to sky blue, okay, and let's make it not very light or dark. Let's keep the alpha as 0.8. Plot dot title, 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 and I will call this title as rating distribution, okay, and let's take a larger font size, okay. So font size, what was the name of it? I forgot. Plot dot title, font size. Is it font underscore size, or I think it was font size, but just making sure, just got it right. Yeah, so this would be font size is equal to 16. Okay, that's how we are supposed to take it, right? Okay, so font size is equal to, I'm not going to take 16. I think I will take it to 14, not more than that. Okay, okay, that's fine. Plot dot x label will be passed as, let's say, rating in stars, right? I'm going to be giving the rating in stars. And plot dot y label would be, I will have number of reviews, okay. And do I need to also show, wait, let's have a look at it first. Yeah, this does not look good. So let me take 8 with 5. Let's actually take this more than 7, right? Yeah, let me actually reduce it even further. Let me take it 5 by 5. Let me see if this kind of looks good. And let me take this, let me actually make this slightly larger. Okay. And let me make this also slightly larger. So let me take it as 18,6. Yeah, this will make more sense. So I have a larger distribution here. Okay. but I am not able to see the size of the dimension. So let me annotate. So can I say for I index comma value in enumerate, okay, inside this I will take score counts dot values for every single value. Plot dot text, I want to annotate it for index comma value. Let's make the value go up beyond the 100 points, okay, where my f value would be nothing but the value itself. And for that particular value, let's take it as a center. Yeah, let's take it in center. And this is more than enough, I'm assuming, right? No, let me make it go 1000. Okay. Ignore the program. Just look at this graph here. Clearly, if you ask me, is there a distribution sort of difference between the texts? Let's make it bold. Okay. 1-star review, 2-star review. Oh, this is not rotated well also, right? So can I say plot.xtext, okay, TICKS text, rotation is equal to 0. Does this work? Awesome, cool, okay. I am plotting the rating distribution of the data which I got in the percentage, but as long as it is not visualized, I don't get it. Clearly, what can you see in this particular example? Of course, 5-star rating beats every other review. Even if I combine one star, 2-star, 3-star, 4-star, will I be able to match my 5-star review? Even if I decide to club 1, 2, 3, 4, 5, will I be able to match up to the expectation? No. Anybody confused with the code here in the plot.subplot? Did I write anything new in the program that you already do not know? What is annotation of the data? What is X label? What is Y label? What is X ticks? What is title? Can I complete plot number 2? My people, I am going to call this plot as text length distribution. This plot will be helpful for you in the future. So please know what I am doing and how am I doing. So can I say plot dot subplot of 1 comma 3 comma 3, right? I have taken 3 comma 2, 1 comma 3 comma 1, 1 comma 3 comma 2. Okay. So plot dot hist, right? Am I plotting something called histogram? Inside the histogram, df of clean off, what am I plotting? Text length, comma, bins equal to, let's say 50 for now. Let's see how it goes. Alpha is equal to 0.7 and color is equal to, let's give it light green, right? And let's also give it some kind of an edge color. Edge color is equal to what matches with green. So my edge color is going to be red. Okay. I am also going to have a plot dot title, title title, and I am going to say that this graph is what we call as text length distribution, length distribution. Okay. And let's make our title also bold. So font weight, WEIGHT, font weight is equal to bold. Okay. Since we have seen it is not very bold. Okay. Okay. Plot.x label. Plot.x label, I will pass that as a number of characters, right? And plot.y label, I will take the character length, character frequency as one of the y label. So I have a frequency on the y label, right? If I center it, I need to have a vertical axis line. So what is it called? Axis vertical line. Yeah. AXV line. Vertical line, I will take the df clean value. Okay. I will take the text length as it is. That is going to be passed in the data. But this time I will take the mean of that particular thing. I will take the color is red. Okay. The color will be red. And to make sure I distinguish the mean, I will take the line style will be equal to a hyphen and a dash, or maybe take a double dash. Okay. And because I want to have this label, so I will Do I give you a label which is directly mean, or can I do it like this? Okay, let me say that mean, which is centered at df.clean, okay, is nothing but your text length. So I will take text length, text underscore length. So can I say text length? Where is text length? Let me copy text length, paste it here. Okay, text length dot mean. uh okay, right? Plot.axv has no, okay, y label. Plot.y label, x label, oh, spelling, right? X label, y label. Okay, my mean is centered, but my mean has no legend. So wait, my data has no legend, right? For the label that I'm trying to pass. Mean is going to be 4.366666. Okay. If I zoom out of this particular thing and look at this graph, what do you understand? When you look at this graph, I'm going to zoom into it a little bit. What does this graph represent? The length of the reviews. On an average, how many characters review is found in the entire 5 lakh review? How many words and how many this? So can you see here the number of, okay, let me do plot.tight layout, plot.tight underscore layout. Okay, run this. Okay, good. Now there is no overlap of the frequency. Tell me this, does this not give you a genuine idea about the distribution of your text, the length of the text, the number of characters and the frequency? Do you not see, because my data set is so imbalanced, my mean is being pushed towards the left? Because many 5-star reviews or the reviews that have a higher density, lot of people have written a lot of content. Can you see? The bar here represents the frequency of the word and this here represents the character. A lot of people in the reviews dataset have written a lot of reviews. On an average, what is the average character found in the data? 436 characters on an average is the mean centered. So does this give you the idea about the distribution of the text? Meaning you will be given a lot of sentences or a lot of characters for 1 star, 2 star, 3 star, 4 star, 5 star. People love to talk and they have indeed given a lot of content for the reviews. So did we take the text length distribution? Have we taken the text length distribution? 436 being the mean. Apart from text length distribution, can I also take something called as a word count distribution? Because whatever the text length is not able to provide me, the word count will tell me. So for example, if I take plot.subplot of 1 comma 2 or 1 comma 3 comma 3, my people, can I do this? Observe carefully. Plot.histogram, okay, plot.hist of df of clean of which word count? Because I've already taken word count, comma, bins is equal to 50, okay, the bins value worked. Let me take the same exact alpha, color and edge color, okay, because I don't want to change it. Let me come over here. Plot.title, plot.y label, plot.x label. I'm going to copy everything as it is and I'm going to paste it here. I'm going to call it not text length but word length. Okay. Word count distribution. Okay. Font weight is bold. Number of characters ke badle number of words. And this is also going to be frequency. We can also pass in just like how we pass the vertical line here. I'm going to copy this and I'm going to pass it here. Here, instead of text length, we need to convert this into word count. Okay, word underscore count. Color is going to be red. Line style is this. Label is going to be text length. के बदले we will pass it as a word count dot mean, right? So I'm going to copy this. I'm going to paste the word count dot mean. And I'm going to have a plot.tight layout control X, control plot.out layout outside, and I'm going to run this. Okay. What did this happen? Oh, I'm going to run this. Wait. Run it. Okay. What do you see in the word count distribution? I think I did not plot the legend, no? Plot.legend. Do you see that the text length and the word count are same? Here the word count distribution is also centered at a word on an average of 80 words but an average character of 436. Did this give you guys an idea? When I plotted the DF of clean with word count, what did you have? Did you have the data where you had the text length and the word count? I have already calculated the word count, already calculated the text length. So the distribution makes sense. That on an average 80 words, on an average 436 characters. Got the idea? We've been able to achieve some finer level of understanding on what my data looks like, what am I supposed to do with that data. We've changed the data quite, we've manipulated the data into giving us a certain kind of response. So if I look at my DF of clean data, which is my data frame right here, right, dot head of 2, the data looks something like this, right? 2, the data looks something like this. I have a text data, I have the score, I have the text length, and I have the word count. Okay. Now to make the problem slightly simpler to deal with, what I recommend we do is we convert our problem statement into a binary classification problem. Now, sir, what do you mean by binary classification problem? What do I mean is any review which is a 1-star or a 2-star review, I want to call this as a negative review. Any review which is a third review is we are going to call that as a neutral review. Okay. And any review which is a 4 stars to 5-star review, I want to call this as a positive review. I do not want anything to do with my neutral review because this gives me no information. I want to keep it directly to negative and positive because what I want to do is I want to know what exactly causes my review to go negative, what exactly causes my review to go positive. So to simplify the problem, what are we going to do? We are going to take a 5-class problem, which is a multi-class problem, right, into a single binary class. 1 to 2-star will be negative, 4 to 5-star will be positive. I don't want the 3-star. So tell me this. Sir, if I want to convert this into a binary classification problem, can I take a separate table? Can I say DF of binary is equal to DF of clean? I take the clean data set, which is the clean data frame, and I say score, right? Because this is what I want to choose. In pandas, we have to take it outside the name of the table. So DF of clean. So data frame of the score, which is not equal to 3 dot copy. What does this mean? What am I doing here? I have taken a variable called df of binary. I said for that data frame, for that table, I want to take all scores which are 3 and copy. What does it mean? Am I taking all the neutral reviews and kind of creating the binary labels later? So if I print the df of binary for all of you, just for your understanding, will it look something like this? As long as you are not 3, it will only have 1, 2, 4 and 5, correct? No use of 3, only 1, 2, 4 and 5, correct? Everything apart from 3. All 1, 2, 4, 5, right? This is a basic pandas function. So df of binary, okay, df of binary of, if I say something called sentiment, am I creating a new column where I'm saying that df of binary, I want to take my score. If it is greater than or equal to 4, I'm going to convert that into as type int. What does this mean when I write this program? Control X, run this, run this. Now, I've also run this, okay. df of binary dot head of 2. What does this mean? Just to be sure, I'm just going to take my score and check for the value counts. Just to be double sure so that I know I do not make a mistake. Okay, good. So this implementation ran. Let's make this happen. df of binary sentiment is equal to df binary of score is greater than, oh, how dumb can I be? Why did this happen? Because it ran on the entire process, right? Of course, this will make sense. It ran on the entire process. So now if I say df of binary dot head, yeah. What did I do? Anything which is 4 and greater than 4, did it become a binary sentiment called 1? Anything which is not 4 or anything apart from 4, did it become a binary sentiment 0? I ran greater than or equal to 4 on the score itself. That doesn't work because I'm checking for each individual indexes, which makes no sense. If I run this, what will it give me? Binary label for each individual number, correct? So tell me, if this is the data that I have, what will the distribution looks like? Okay, the distribution of my data, how will it look like? Will it look like this? Print F double quotes of negative reviews, which are 1-2 star reviews, will be how much? Can I say sum? I want to take all df of binary. Inside the df of binary, I want to take all sentiments. Okay, let me copy this. Let me paste it here. For all values of sentiment, actually, let me take it out like this. Bracket, sum. If I write sum, open the bracket, close the bracket. Take the whole thing as it is. df of binary, just put it inside this. Of sentiment. Can I say equal to 0? Is this something that I can say? Equal to 0? And for better visibility, let me take a comma outside here. If I copy the whole thing for negative distribution and paste it here in the bottom, and let's call it positive. Positive review, which is a 4 to 5 star review. df of binary of sentiment is equal to 1. Can I say this is what I can say? This is negative star review and this is a positive star review. What do we see? Do we see any 1-2 star review is 82,037 and positive star review is 4,43,777? Do we have 2 reviews? 1 to 2 star and 4 to 5 star. Are they binary class? As proven, I have converted them into binary classes. I don't need to worry about them. Now tell me one thing. If you want to check imbalance in the data, okay? If you want to check imbalance in data, can I say negative underscore, okay? Negative underscore, say class frame, okay? Class or auto PCT or PCT is equal to negative PCT is equal to sum of df of binary. Okay, let me copy the whole thing. Sentiment equals to 0. Let me copy the whole thing. Sum of df of sentiment equals to 0 divided by length of df of binary. What is this going to give me, everyone? Multiply by 100. And if I copy the whole thing, paste it here and call this positive PCT. Positive PCT. This is going to be 1. Length of binary, df of binary is going to be this. What is this going to give me? Is this going to give me the overall imbalance in percentage? So if I print negative PCT as it is, okay, F double quote of, let me call it negative colon bracket negative PCT, copy and paste, copy the whole thing, paste it in the bottom, write down positive, Control Z, let me call this negative as positive, right? So positive is gonna be negative PCT ke badle positive PCT, right? We are gonna remove this part. What does this give you an idea about? Rather than looking at the numbers and calculating it by yourself, am I able to look at the percentage imbalance in my data, which is always preferred, right? If it is always given in percentage, it gives me a better idea. So can I say that if my positive percentage is greater than 70%, if my imbalance is more than positive percent, can I print the answer like this? Can I print, for your understanding, that data set is highly imbalanced or data set is imbalanced? It is highly skewed. It is highly skewed towards what distribution? Towards positive reviews. See, this would be the answer. Highly skewed towards positive reviews. Does that make sense? So were we able to get an understanding that, sir, of course it looks like it is a positive review. So in the next step, do I need to handle the imbalance? Now comes the strategy for me to handle imbalance. Now, have you heard of a package in sklearn? So from sklearns.utils, I'm going to import something called resample. Okay, I'm going to run this and very quickly let me just check. Replace n samples, random strategy, stratify equals to none. I can pass the stratification. Okay, cool, no problem. Okay. We are going to fix this particular balance problem with a little bit of resampling. Okay. Before I teach you something called resampling, have you heard of a concept called sampling with replacement and sampling without replacement? Sampling without replacement. Do you know what this means? You cannot pick the same item 2 times or twice. You cannot take the same item twice. Example, what if my array looks like this? 1, 2, 3, 4. Can I say this is my population? My larger value, not the population of statistics population, but from the one I will derive from. And my sample size n is equal to 3. So is 1, 2, 3 a valid sample? Is 1, 2, 3 valid sample? Brilliant. 2, 4, 5 a valid sample? Yes, this is sampling without replacement. But can I take 1, 1, 3? No, because 1 is repeated twice. No. What about 2, 4, 2? What about now? Can I take this? No, because 2 repeats itself. In that case, what will be sampling with replacement? So 1, 2, 3, 4. Can I take 1, 2, 3? Is this a valid sample? Valid sample. 1, 1, 3. Is it a valid sample? Valid sample. Can I say negative underscore reviews, REVIEWS is equal to reviews is equal to df of binary of df of binary? I'm going to take the same particular thing. Every sentiment in my data, every single sentiment in my data, which is of a binary class 0, I'm going to copy this and I'm going to paste another thing here and I'm going to call this as a positive review. Okay, reviews, and the sentiment will be 1. My people, what am I doing? Am I separating my negatives from my positives? I'm separating the table with all the negative reviews separately. I'm separating the positives table separately. Why will I do that? Because my positives have a larger sample and my negatives have a smaller sample. Can I not resample them and generate positive equal and negative equal? Can I not do this? It will help me to take some from the positive table, some from the negative table, make sure that they are equal. Yes? So did I separate out my tables of negatives and positives? Sir, of course I did that. Print. Listen to me carefully, okay? Original imbalance in my data is how much? Print. F double quote of what is the negative imbalance that you have in the data? Can I say negative imbalance looks like this? Negative imbalance looks something like this. Now guys, tell me if this logic makes sense to you, okay? Negative reviews, colon, bracket, okay? Not here, outside. Outside the colon, we are going to take it. Colon and bracket. Inside this, if I take another bracket and put another colon here and say length of negative reviews divided by length of df of binary. What is this going to give me? If I run this answer here, is it going to give me the same answer but both of them together? 82,037 is 15% of the overall data. Correct or not? See here, I took the number separately and here I have taken the percentage separately. Yes or no? 15% and 84%. I'm combining them together for your reference. Same thing can be applied for what? For my positive review. For my negative, I will remove the negative, call this positive, and I'm going to call this length of negative reviews, call this as positive reviews, and I'm going to say for my positive reviews, I'm going to take my positive reviews, right? All my positive reviews, and I am going to pass it as length of df of binary. Do I get both my negative number and the percentage, which I will use in the later stages? So sir, how do we do it? We are going to be implementing a strategy called undersampling. What are we going to do? We are going to undersample a majority class into what? Into matching the minority class. We are going to undersample the majority class. The undersampling will be applied to the majority class such that, so that I match to my minority class. Does this make sense? Me undersampling the majority class to match to my minority class. Does this logic make sense? Okay. So can I say number of minority? Okay. What is my number of minority class? Can I say that the length of negative class or a negative review is nothing but that is the number of my minority? Right? Okay. Positive. Okay. Positive underscore down sample or down sampled data can be used something called resample of my sklearn package. Will I pass something called positive reviews? Point number 1. I will put replace equals to false. What do you mean by replace equals to false, everybody? What does it mean that I am saying replace equals to false? Sample without replacement. Make sense? Number of samples that I want for my class will be nothing but number of minority. I want this to match because I want to match my down sample to match the minority class. That's why the number of samples is equal to number of minority. And to make sure your answers and my answers are matching together, can I say random state is equal to 21? Cool. Okay. What did I do, everyone, here? Did I downsample my positive class such that the positive downsample class will match my minority class? All I have done is a very simple resampling technique. After I have done positive resampling, can I say BALANCED, balanced? So data frame underscore balanced is equal to pd.concat. What am I going to do, my people? Concat what? Negative reviews with what? Positive downsampled. Positive, actually, let's not take this p small, let's take this p small. Positive downsampled. So df of balanced is equal to pd.concat negative reviews and positive downsampled. But I will not take my data as it is. I am also going to shuffle my data. So df of balanced is equal to df of balanced dot sample. I am going to write down something called frac equals to 1 and random state equals to the same thing that you have given me, 21. Dot, okay, dot reset index. Inside this, drop equals to true. So tell me, before balancing or my original balancing is this, correct? This is my original balance, no? After imbalance, can I print the original imbalance and after imbalance or after balance? Can I do this or not? So tell me, in the original balance or after balance, let me say after balance, AFTER, after balance, let me also print this. Total samples, TOTAL, total samples will be how much? Length of DF balanced. Here, instead of negative reviews, what will I do? Will I take this df of balanced df of balanced, I will remove this negative review part. Okay. I'm actually, you know what? Let's not take it like this. Let's take it like this. Let me remove this. In the total sample part, let me take it like this. Negative PCT. Okay. Let me copy this as it is and let me paste it here. Okay. Okay. Let me remove this. We don't want negative stars. I just want negative and I just want positive. Okay. So sum of df of balanced, let me copy this and put it here. df of balanced, sentiment is equal to 0. Let me take df of balanced, copy the whole thing. Sentiment is equal to 1. Okay. And for this particular value, now I'm going to calculate the number. Can I take sum of df of balanced? Actually, let me close this. Since this is a part of the double quote, I think I will come outside the bracket. Negative sum of this. Let me take a bracket here. Sum of df of balanced. df of balanced. Inside the df of balanced, I want to specifically choose sentiment. Sentiment will be equal to 0. Divide the whole thing by length of df of let's say balanced, and the entire balanced will be multiplied with 100. Okay, so what will I do? I'm gonna take this particular example here, copy the whole thing. Let me do it like this. Copy the whole thing and paste it here in the bottom. df of sentiment is equal to 1, balanced is equal to 0. Is my negative samples and positive samples, they match? Are the positive samples and the negative samples, when I ran them, now they match? Right? Now, tell me one thing. Now that we have balanced the data, okay, what are we going to do? Are we going to make our data slightly different into training and testing? Because now comes my actual part of implementation of the algorithm. I will be splitting my data into training data, testing data, running the RNN model and the LSTM model. So tell me, my people, when we took the original data, did it not take us time to do balancing, understanding, reviewing, exploratory data analysis of sorts? We have done some very simple EDA and it took a lot of time. Remember, in your real life, this is also going to be the case, right? I handle a team in my company for credit fraud analysis. Okay. I deal with financial data. Majority of me and my team's time goes in exploratory data analysis and feature engineering. Understood what I'm trying to say? No matter which company, job, startup, whatever you're going to join in the future, majority of your time will either go into feature understanding or EDA. This is the truth. Making a model is not hard. Running a machine learning model or a deep learning model is not hard. It's a simple piece of code. Did you find running the code easy or learning easy? Which one is a little bit more complicated? When should you apply LSTM versus how the LSTM code is? Which one is easy? It's in which condition should you apply LSTM? So understand, it's the practice that takes time, not the implementation. So now what are we going to do? We are going to take a sample. So tell me, sample underscore size. Guys, I am going to take a smaller sample from 82,000. You know why? The problem is, can you see in Google Colab, we only have 3 options: CPU, T4 GPU, and V28 TPU. This is called tensor processing unit and this is called graphical processing unit. Okay. The problem with the free version of GPU and TPU is the RAM isn't very high. So when we train the model, it will take a lot of time for the training to happen. So can I take a smaller sample size? Minimum of 50,000, comma, length of DF of binary. What is this going to give me if I write this piece of code? If I do not have a smaller sample size, use up to 50K. So DF of sample is equal to SAMPLE, sample is equal to DF of binary dot sample. What am I going to pass? N equals to sample size, comma, Random state is equal to, I'm going to maintain the random state equals to 21. Is it possible for me to do it? Yes. But tell me one thing. Have I taken DF balanced or have I taken DF binary? Which one did I take? Isn't DF dot binary something like this? Dot head of 2. Isn't DF binary is this versus DF of sampled is this or balanced is this? Dot head of 2. Which one should I essentially be taking? Balanced one or binary one? The balanced one. So can I say DF of balanced? That is going to be my DF of sample. Can I say sample underscore negative is equal to sum of DF of sample, okay, of sentiment, comma, sentiment is equal to 0. And if I copy the whole thing here and paste it in the bottom and say sample positive, okay, PO sample control Z underscore positive is going to be DF of is equals to 1. Print. Can I do it like this, my people? Negative sample or sample negative is this much. Sample negative and copy the whole thing and paste it in the bottom. So sample positive will be how much? Paste and paste. Run this. Have I taken random values, anything within 15K? Agree, disagree? Have I taken the values of sample size up to 50,000 at a random state 21? It gave me 25 and 24. Believe me, it will be balanced. It will not be a problem. So did we do it? Have I taken a small distribution? Maybe 50, 49, 51, 49 percentage. Okay. Don't be somebody who wants to directly jump into implementation of RNN. You haven't done anything called text processing. We have not done any text processing. So tell me one thing. Can we do this? Can we clean our text data? What do you mean by clean our text data? Convert everything, every single sentence into lowercase. This is the first step that I can do. And this is something you will be doing a lot in your career whenever you're going to be doing any kind of text processing. So first of all, will I convert my text into a lowercase? Remove any special character. Like sometimes people like to add emoji also. So tell me, if I say smiling emoji, okay, smile emoji, okay, do you know what is the UTF-8 encoding of smile emoji? U plus 1F60A, okay. If I write down in the text like this, will you be able to understand what this is? Does a human intervention require or is it required no to understand what this is? So any special character like a hash, at the rate, exclamation, all this nonsense needs to be removed from the data. I only want string. Keep only letters and spaces, correct? Only letters, words and spaces will be allowed, and any extra white space is available or is if any extra white space is even in the data. For example, I love space ice cream, okay, space and then space ice cream. So tell me one thing, do we have a 2 white space character here, extra white space, 1 white space here? I am only going to do this much. If you want to do more than this, you can do it. I am only going to do basic. So can I say I'm going to have something called clean text data where I'm going to be passing the text? I will have a function. What is the first thing I want to do with the text? Text.lower. Yes or no? Am I going to be doing something called text.lower? Very good. Okay. This is going to be my first text. What will be the next text? Have you heard of a website called Regex.com? This is the example text. If I do this, listen to me carefully. A to Z and A to Z. Have I chosen every character which is a small letter A to Z, capital letter A to Z? Yes? Am I only choosing only and only letters and letters? There will be no plus W. I don't want it to be anything greedy. Okay. Let me make it as small s. Sorry. Can you see the full stop and some spaces and these are highlighted? Do you know what this is? This is what we call as a regular expression. You know, if you only want to choose letters, can I just choose, go to regex.com, validate if my regex is correct, come back to this particular thing and mention re.sub, substitute, what will I do? R of bracket hat A to Z, all the small characters, all the capital characters I want to choose. Can I say I will only be choosing this particular character for all the text values? Yes or no? So am I removing all special characters here? Remove all special characters. Can you see here? All special characters like full stop and are highlighted because these are the ones that will be removed. And every other character or line is added. Do you get the logic? I am choosing only to take single space with the hash s, only capital A to small z, capital A to small z, right? So I have basically removed all special characters, numbers, and keeping only letters and spaces, okay, and spaces, spaces, okay, spaces. Look, for example, if I have a character like this, okay, listen to me carefully. If I have a sentence like this, I love dash 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 ice cream so at the rate much I love it dearly. Okay, I love it dearly. When I apply this, okay, this space or run character, if I run this, what is it giving me? Is it removing everything that is just an extra special character that I don't want? So see, right in front of you, we got highlighted. See, dot. Even the dot got highlighted. At the rate will be highlighted. At the rate will be highlighted. Exclamation will be highlighted. Anything which is not a letter got highlighted, right? Sir, I also want to remove all the white spaces from my character, right? Sir, what if someone emphasizes like this? So much. See, for that, the regex will be different. So much does not highlight or is not highlighted or will not be caught because you need to implement something called substring sub pattern matching. Because so is also a character, much is also a character, that will not go away. Understood? For that, you need to do stemming, lemmatization. Understood what I'm trying to say? There are better variants to handle that. So much and all of that, you can do it in a much different way. Understood? Okay. Text is equal to dot join. Okay. Dot join. How many characters or what on the basis of what do I want to join? Text dot split with no space. And can I say return text? All the special characters removed, all the words converted into lower, all specific things converted into extra one single white space. Can I say this is the function? Processing. Am I going to be doing something called text pre-processing here? Plus, 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 plus. So that from now on, from here onwards, we are going to be doing text pre-processing. My people, how do we apply a function on an entire column in pandas? df of balanced of, what am I passing here? In this particular example, df of balanced, what am I going to be passing? What will I be passing? Will I be creating another variable called clean text? df of balanced, and what am I doing on the balanced data set? On the text of the balanced data set, am I going to apply the clean text? Oh, not res, re, right? Have I imported re by the way? Oh, I did not import re, no? Import re. Let's run this. Let's come over here. And where did we go? We have come over to the text preprocessing part and run this. Text preprocessing done. If I print my df of balance dot head of 2, do you guys see? I have the answer, my clean text. See, our family now uses this place. Everything is converted into all special, all small, and everything is removed. Correct? When you work on any deep learning based model, be it your RNN model, your LSTM model, specifically your CNNs model, or any variant of CNN model, okay? Any kind of deep learning based model, there is a certain process you need to follow. If you understand that process really, really well, building any generative AI application becomes very, very easy. What I mean by that is, if the foundations with respect to RNN, your LSTMs, your other variants of RNN like by RNNs, stacked RNNs, by LSTMs, GRUs, by GRUs, right? If those foundations are absolutely clear, building any transformer based model, both pre-trained or fine-tuned, becomes very, very easy. The question is very simple. Sir, between word2vec, between globalized vectors, embeddings which is built by Keras and TF-IDF, which one to use and which library is better, right? Which library do I use? Which text embedding method do I use? First of all, TF-IDF is not an embedding technique, okay? Word2vec, between glove and between the local embedding which is created by Keras, which one is better? First of all, none of these are good enough for a larger data set. Okay. If you want a very context rich embedding, meaning whatever sentence you give or whatever sentence you have, I want to get a very deeper semantic relationship of the text, the contextual representation of the text, very, very deeper. In that case, always prefer using pre-trained models like BERT. There are multiple different variants of BERT, right? We have something called distal BERT. You have both cased and uncased version. Then sir, why do we use word2vec? Why do we use glove? Why do we use its internal embedding? The reason is, see guys, back in 2011, 2012, when Thomas Mikolov, the creator of word2vec, created word2vec, he wanted to showcase the capability in natural language processing that any sentence, any word, including some characters, can be converted into vectors. Meaning, this three-dimensional or n-dimensional space where a word can also be represented as a vector. Like for example, the vector for this particular word apple, for a vector for a specific word called banana, right? So first of all, I want you to understand that both word2vec and glove, okay, are built not for production, right? If you ask me, sir, can I use them in production? Preferably nobody uses them in production. Any kind of research work you have, any kind of demo work you have, both word2vec and glove will do a good job. They are good at converting a specific text into a highly rich or a high dimensional vector. But do they convert this necessarily into a dense vector? Well, that is not guaranteed, right? Sir, why do we use embedding built by Keras? Please understand one thing, guys. Keras has an internal embedding model. The reason why we have it internal to Keras is because whenever you try to write any recurrent neural network, RNNs, your stacked RNNs, you want one layer data to pass it on to another layer data, right? So the embedding layer of Keras comparatively is better than your word2vec or glove or your TF-IDF. And I don't need to tell you about TF-IDF more, that TF-IDF works, but it does not necessarily work for every single sentence. If I ask you this question, right? Man eat hot dog eat man. Do you think the meaning behind both the sentences is different? If you take man eats hot dog eats man, is the context and the meaning behind these two words different? When I say a man eats a hot dog, okay, are we aware that there is a man here who is eating a specific kind of food called hot dog? If I rotate the sentence slightly and say hot dog eats man, are you telling me a dog which is very, very hot is eating a man? And hot in what sense? Is he hot in a normal slang, that is a good looking dog? Or hot whether the temperature of the dog is higher? Now tell me one thing, your bag of word, your continuous bag of words, your TF-IDF, do they do justice with words or sentences that repeat itself once again, even though you're trying your level best in your terms frequency, your inverse document frequency, right? You're trying your best to capture the context. Will you be able to change the context or map a very high level of context? No. TF-IDF was used in classical machine learning to get as more data or information out of the text. Unfortunately, it breaks. There are some edge cases where it doesn't work very effectively, specifically in longer text, because all it does is a frequency calculation of text. Understood what I'm trying to say? So please understand one thing. Sir, between word2vec, between glove, between embedding, between TF-IDF, which one would I preferably use? Word2vec and globe are more research-oriented vectorization techniques. You're not going to be using them in production at all. At all. You're not going to find a longer sentence or a longer chunk of a text and use this in production. You don't do that. What about embedding? You can. It's a good thing, but also not great. You don't have a context-rich embedding. Embedding generated by Keras is a dense vector representation, not very, very rich, because it is not a pre-trained embedding. So, sir, which model do I think I can use in production, which I would love it? Always prefer using Roberta. Okay, you have another variant called Dino, right? You have USE, Universal Sentence Encoder, or any kind of BERT enabler like BERT based uncased, BERT based cased, distal BERT, any kind of variants like these. Yes, they will generate a very deep, very semantically high context, or semantically rich dense vectors. So prefer none. If I would ask you, prefer none. Sir, which embedding is usually used in production? Like I gave you the idea. For a large data set, preferably use these. These one will give you a much better representation. Now, there is one more model, which I'm not sure if you guys have heard of it, but I love it. It's beautiful and it works amazing. Have you heard of a concept or a model called TF5 FLAN? Okay. There is a model built by Google called T5 XXL and T5 FLAN. Okay. If we ever get the time, I want to show you the capacity and the capability of a T5 model, how it works and how you can use it for multiple different types of combinations, right? Guys, when I'm going to be teaching you transformers, first of all, remember that there are two kind of models specifically in transformers. You have something called encoder and decoder. You have encoder only models, decoder only models, and encoder decoder combined models. So first of all, you guys need to understand that in transformers, wait, I have a small question. I think you guys also did something called encoder decoder model also. Is my understanding correct? You guys have some idea, but some of you were telling me, sir, we are not clear with the encoder decoder model. Is the understanding correct? Like, I think in the last class, majority of you were saying, sir, we have done something called encoder decoder models, but we don't understand them clearly. Understood. Now listen to me carefully. I taught you how to complete pre-processing until something called as text pre-processing, correct? Everybody remembers what we were doing? We were doing an RNN LSTM variant calculation. We are trying to run a model, but what have we done in the past? In the past, we have made one single mistake. I don't want you guys to repeat that mistake. And the mistake is when we have the data, we pre-process the data and directly start applying RNN and LSTM models. Guys, when you talk about being production ready, you don't make this mistake, right? We'll be explaining you the encoder decoder model once I make sure your foundational understanding on the RNNs and the LSTMs are absolutely sorted. My intention is not just to teach you just the RNN and LSTM part. I also want to teach you some of the best practices you implement. Combination of both the model building plus best practices building. Once you have your foundations absolutely clear in this, I'm going to take you through an encoder decoder model. Then we are going to go through the transformer model. So let me explain what is it that my plan is with you guys, right? Let me explain it to you. See guys, if you want to start generative AI, see, Using any large language model, installing it locally and using it is not very hard. You don't need an Intellipaat trainer or somebody like me to teach you how to install it locally. YouTube will teach you how to do that very easily. In 5 minutes, you should be able to install your own local models, right? Any kind of a giga file, if you install, you can make it. The point is not that. The point is to understand how the large language model actually is able to do a next sentence prediction, next word prediction. How does the entire model, how does the philosophy behind large language model works? How do multimodal models that can input text, video, audio, any kind of data, and they can still work? The intention is to understand the foundations very, very clearly. What I mean by that is, are your foundations in machine learning clear? Good. Are your foundations in deep learning clear? Good. Are your foundations in reinforcement learning clear? Good. Then you have to even start approaching large language models. Because if you don't understand these techniques really, really well, directly jumping into large language model is going to 10th standard without giving first standard to 9th standard. Of course, you will fail. The point being this, when you guys have studied the most baseline philosophy, which is LSTMs and RNNs, do we just directly implement LSTM? No, you never do that. Do we not measure or do something called hyperparameter tuning in RNN and LSTMs? Trying to identify the best specific parameters on where my RNN can run the most effective. Once I do that, do I also save my model? Do I save my model in some kind of a file which I can load it separately? So understanding and implementing this becomes important because in the future, any deep learning model you implement, any kind of model you implement becomes absolutely important, right? Reinforcement learning not included in the curriculum. In your so in your large language models, okay, your GPT, your Claude, your any other open model, they have been trained using something called reinforcement learning on human feedback, RLHF. Okay. I'm going to give you an idea. What do you mean by PPO, DPO? That is a part of reinforcement learning. Understood? Okay. PPO and DPO, and there are multiple different types of methods using which your large language models were trained. Understood what I'm trying to say? So not necessarily you need to learn something called Q star, Q learn, anything like that. Just some basics of reinforcement learning would be more than enough. Understood? I am going to go in the sequence, one step at a time. While doing it, we are also going to learn something called sequence to sequence. We are going to learn encoder decoder model. We are going to learn transformer model. We are playing with pre-trained transformer models. Then we are going to jump into generative AI. Understood? Cool. This is how the sequence will look like, guys. Okay. Now listen to me. For all my data, I was able to perform something called text pre-processing. Agree, disagree? I was able to perform a text pre-processing and my text pre-processing is done. That's very, very good. Now tell me, to build any kind of recurrent neural network or a long short-term memory model, I need to implement something called max features. Do you guys understand what's max feature? Max features is basically building your large vocabulary, right? Vocabulary, meaning whatever data you want to train, every single sentence will have a sentence like I love cars, C-A-R-S. I will also be here. Love will also be in the corpus and cars will also be in the corpus. Each individual word, how many words do I want to take at maximum in my vocabulary? How many words have I given everyone? Can we take 10,000? Can I say that to build my model, the number of words I want to include in my vocabulary? Think of this maximum features as your vocab. Okay. We call this as a vocabulary, sort of like the data. Now, every single sentence that you take to do analysis, do you require the entire sentence for analysis? No. What we do is, if the sentence is very, very long, we cut the sentence at a specific length. We are also going to define at what length we are going to cut the sentence, and this sentence will help us do the prediction. So what do? I'm going to take that the maximum length I'm going to include in my sentence would be up to 100. What does this mean? The maximum length or the maximum sequence length I'm going to include in my analysis. So what do we do, everyone? Do we start doing some kind of a tokenization? Yes or no? because this is also an important step. We call this as a tokenization principle. Agree, disagree? So what are we going to do? Yes, these are number of words per review. These are number of words per review. Understood? These are number of words per review. Good, very nice. So what do I do, my people? I want to print that. What am I doing here? I am doing tokenization. So can I say it like this? Maximum vocabulary size, okay, maximum vocabulary size, SIZE, is going to be the max feature part. Just for your understanding, I'm going to print the whole thing, right? Let me copy this. Maximum features, words, 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 okay, WORDS, words. I'm also going to copy this. I'm going to paste this in between, and I'm going to say maximum sequence length, right? SEQLEN, maximum sequence length would be the maximum length here, and that many words I'm going to prefer. So if you can see here, maximum vocabulary size will be 1000 words and maximum sequence length will be 100 words. This is how I'm going to do it. Now I need to prepare my data, okay? I need to make sure that I work. So maximum features is equal to top 1000. See, yes, so call it like the most highly frequently repeating words, which are going to be the highest repeating words, which are going to be top 10,000 repeating words, highly frequent words. Understood? Now tell me, what was the last thing that we did on the data? Did we print a data called DF balanced on which we implemented? So can I say DF balanced? I need to copy the same thing. DF balanced of what do I take? Do I take clean text dot values? And if I take the y value, take a small y, again take DF balanced, which is the same particular thing. And in this particular thing, if I take sentiment, okay, sentiment, and here if I do dot values, what will the values of x and y tell me? Word like the, of, are, they are a part of vocab. See, what happens is, highly frequent words like a, and, the, of, and, they also are a part of vocabulary. But usually what happens is, if you use any kind of models like Keras, TensorFlow or PyTorch, and you try and implementing and building a vocabulary, right? These words are usually what we call as a stop word, right? So for example, what mode of words do you think are stop words? If you have a sentence, I love eating ice cream. Have you seen that when I do stop word removal, I am able to remove a specific kind of word from my entire vocabulary, like a, and, the, XYZ, 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 right? So the point is, usually we retain the stop word removal in Keras, and Keras is very smart about it, right? It doesn't just let any random word repeat itself again and again, right? So it's not like the top 10,000 words are only going to have a, and, the, of, in, only a specific kind of words. These are called supporting sentences. So actually supporting words that retain. Rest will be removed. Like a, right? Like suppose a, in, all these representations will not exist. But of, right? Of will be an important representation. So only some will represent, not all. Understood? Not all, some will be represented in the data. We can choose how much and what representation we need to give. We can always choose that. But not all will be represented equally. If I show you, I'm going to show you an example of that also. So tell me, what will this X and Y give me? Is it going to give me all the features of the data? And this is going to give me all the labels, all the zeros and ones in my data? Yes or no? Agree, disagree for this particular value? Now, sir, I want to run my tokenizer values. Sir, I want to tokenize my data. How do you tokenize the data, my people? Can we go to our import statement? Sir, how do you do tokenization here? For tokenization to work, do I need to import some kind of a tokenizer? Have you heard of any kind of tokenizer that we have? Yes. From TensorFlow, okay? In TensorFlow, you have a submodule, okay? In that module, we have something called Keras as the submodule. In TensorFlow.keras.preprocessing, okay, we have a submodule called text. And from that, you're going to be importing something called tokenizer. Can you see here? I'm importing something called tokenizer here. A simple tokenizer called TensorFlow.keras.preprocessing.text. I'm importing something called tokenizer. So what am I going to do in this particular sentence? I am going to use this tokenizer to actually tokenize my sentences. I can actually use the instance of the tokenizer directly. So how do I do it? Can I write it like this? Tokenizer, okay? Tokenizer is equal to, can I call it tokenizer? And inside the tokenizer, the number of words that I want to keep are going to be the maximum features in my data. And OOV underscore token is equal to, you're going to write it like this. You're going to take two arrows and you're going to write something called OOV. Okay. Do you know what is the meaning of OOV? It's called out of vocabulary. Tell me, when you're working with any kind of data, isn't it possible that there is a word called, say, gensim that was never seen by the data? This is an out of vocabulary word. When I did my training and when I did my testing, right, I never saw the word gensim. But if it appears in your analysis or if it appears in your production, will you be able to handle that data, my people, if you don't know the meaning? No, right? Understand what I'm trying to say? What do you mean by out of vocabulary? When a model hasn't seen a data, a word, that word that was not trained can be called as an out of vocabulary word. Out of vocabulary token means, please don't give me error when you encounter a word, you're gonna find out of vocabulary word. Please don't give me error. Replace the word with OOV token so that I don't get any mistakes or errors. Understood? What do? Tokenizer dot fit on text. Okay, my people. There is a method that we call as a fit on text. So tokenizer would have something called fit underscore on underscore text. And inside this, I'm going to pass my training data as it is, right? As mentioned in the documentation, right? So in the specific part, I have taken everything called number of words. Number of words would be the vocabulary size. Any kind of filter that you want to take, I don't want to take it. So that's why I have taken something called fit on text, right? So what this does is this is going to make sure that my data or my specific words are going to be tokenized, right? Now what I need to do is, there is another kind of topic or sentence managing technique called padding. So tell me, sir, if I want to implement padding, what do I do? So what I'm going to do now, I'm going to write down the import statement here only so that I can later on import it separately. So see guys, if I want to do any kind of padding, I'm sure when you guys must have studied your convolutional neural networks and your recurrent neural networks, you must have studied a concept of padding, right? So if you want to pad a sequence or if you want to pad your data, your specific sentence or the line that you have been receiving, what you can do is you can also pad them using the concept of TensorFlow. So what am I going to do? From TensorFlow, okay, from TensorFlow, you have a submodule called Keras. You're going to repeat the same submodule called Keras again and again. Inside this, you also have the same preprocessing module, and inside this, you have another submodule called sequence. And here, you're going to import something called pad sequences, right? So you have pad sequences. So sir, how will I approach padding? What is it that I'm going to be doing in the padding? I am going to take each individual sentence and I am going to pad it on the basis of the sentence length that I have taken, right? So what do? Once my data is converted into tokens, I'm going to take that my input data x underscore padded is going to be equal to pad underscore sequences, which is what I've taken. I'm going to pass my x data, which is going to be, so here see, I have taken the tokenizer, I've taken this on a fit on text, right? What I need to do is, I forgot to do one more concept, and which is converting the text into sequences. So to do that, just take x underscore, let's call it sequences. Sequences is equal to, let's also do, wait, so let me do it like this, right? Rather than running it like this, we did fit on text. Let's actually do something called fit on sequences also. So let's take tokenizer dot, what was the method name? Fit on sequences. Let me copy this. Let me do fit on, Control Z, give me 1 minute. Let me do fit on sequences also. Let me paste it here. Dot fit on sequences. And inside this part, I'm going to pass in the data X. So now I have the tokenized data. I have the fit on sequences for each individual array value for X sequences, right? This will convert every text into sequence. Then the padded will be pad sequences of, let's say, X sequences. Let me not pass X directly because it will not know which to reference. X sequences, the max length, max, I think length is going to be equal to the maximum length I have taken, right? This is fine. And after that, I think we also have something called padding is equal to post is what I'm going to be doing. And I'm going to have it all truncated, because truncated value is going to also follow something called post. Truncate or truncating, if I'm not wrong, right? Truncating is equal to also post. Okay. So let me explain what I'm doing here. See guys, when you do directly something called tokenization, there are certain processes you need to follow. For example, right? If I want to show you an example, right? If I say print F double quote of the actual vocabulary that you guys have actually passed in the data, the actual size of the vocabulary will be length of tokenizer, okay, dot word index. So if I print each individual word underscore index, I'm going to pass this, and let me take it for all, right? For these many words, please give me the answer. Wait, df balanced of sentiment dot values. Oh, there is no full stop here, right? Max vocabulary size is this, and running the indexation, give me 1 minute. Sequences must be iterable. So give me 1 second. Pad sequences will be X sequences, maximum length is this. Truncating, give me 1 second. Sequences must be iterable. Have I not made them iterable? Are they not looping through it? Give me 1 minute. So tokenizer is fed on text, right? Tokenizer values are fed on text, which is going to be passing the value here. X sequences will be tokenizer is converted. Oh, I think I understand. Is it going to be something called text to sequences, right? So do we have text to sequences? Okay, wait, let me give me 1 second. So tokenizer dot text to sequences. Yeah, this is the name of the method. Give me 1 minute. So if I come over here, not fit on sequences, this is text on sequences. If I pass in from text to sequences, if I have the value of X, give me 1 minute. Let me loop through it. The actual vocabulary. Oh, I think I did something called fit on sequences, not text to sequences. This should work now. Give me a second. Let it go to tokenizer.text to sequences. So basically we have to pad sequence later, and this will cut it off to 50. Yeah. So actual vocabulary size is 1,13,343. So against this, if I want to measure my final sequence, right? SEQUENCE, final sequence shape. Let me check what that be. The final sequence shape would be, I think, somewhere between X padded sequence with the shape of the data, right? So that would make it how much? Final sequence shape is 1,64,074 cross 100. Okay, understood. So basically everything is in a sequence of 100, and everything is going to give me a value for 1,64. This is, I think, what we had in a original data, right? DF balanced. If I come over here, if I come over to DF balanced, what was the df balance dot info, or let me just print my shape. It was 1,64,74. Understood. So let me explain this piece of code from here to here, right? From this specific sequence to this specific sequence, right? Also, why don't I do one thing? Let me also actually print it in the same specific value, okay? Show look at the final data. Give me 1 second. Look at the final data. So how will we look at the final data? It would look something like this, right? So if I say print f of original, text would be something like this. I have the actual data X. For 0, I only want to show you the top 100 words. And if I take the same exact value where I show you the sequence of the data, so it will be X sequences, right? I will also take the same value here and only maybe the top, wait. So I think you need to also show it like this. Otherwise there will be an error here also, because I want to show you only the top 100 values. The same specific thing will apply here, where I'm going to show you only for the top 20 sequences, right? The first 20 numbers of sorts. And if I print here, and if I also show you the padded sequence or padded shape, let me show you the shape here also. So in the padded shape, if I pass in X underscore padded, I'm going to show you for that specific value that I have printed. Let me also print the shape of it. Give me 1 second, let it run. What is my runtime? My runtime is a CPU, which is fine for now. So our text, our family now uses this in place of butter or the file, fine, so good, padded sequences 100. Okay. So first of all, let me copy this piece of code, right? Let me copy it from here to here. Give me 1 second and paste it. Okay. Let me expand this and let me also take my output. Okay. Let me also take my output and paste it somewhere in the bottom. Okay. For any text processing that you're going to do from now onwards, okay, I want you to remember a couple of processes that are going to remain consistent throughout your code whenever you want to implement them from now on. Okay. See, two things. We have a tokenization concept, right? In your NLTK, in your other libraries, we are specifically choosing to use something called TensorFlow. So how are we doing it, sir? Right? Let's talk about this. See here, I have taken a sequence, or I have taken a portion or a module built by TensorFlow called tokenizer. Can you see here? This is a variable. Actually, this is the name, or this is the import that we have done. Can you see here? Tokenizer is equal to this, right? This tokenizer object that I have taken will take what? It will create or limit the vocabulary to how much? Will only 10,000 vocabulary size. Agree, disagree? Right? Any word that does not exist in the data and that comes in your real-time data will be replaced by the token called OOV. So my model will run, but it will not give me error. Cool? Until here? Now, my people, there is a method called fit on texts. Okay? Fit on text does multiple different things. Number one, what it does is, how many frequency of words do you have? For example, if you have a word called apple, repeats how many times? Mango repeats how many times? Some other word. How many times? Whatever words you have in your value, how many times does it repeat? It creates word frequency for all the values of x. So can you see here? I have taken every single text data called clean text data, and in all the data, I'm counting all the frequencies. Agree, disagree? Once you take the frequency, you need to create something called word to index mapping. For example, the word apple will have an index 1, the word banana will have an index 2. So can you see here, based on the highest frequency, I am also creating its index in order. The most frequent word will be assigned the index 1. The second most frequent word will be assigned the index 2. The third more index frequent word will be assigned the index 3. Understood? Once the frequency is calculated, I take a table with all the top frequency values and I map them in the sequence. Remember one thing, please be aware, your out of vocabulary token in PyTorch is given index 0, in TensorFlow is given index 1. Understood what I'm trying to say? By default, any out of vocabulary token is by default given 1 in TensorFlow, but in PyTorch, in some variants like TensorFlow, like PyTorch Lite, TF Lite, they give it index of 0. So what does fit on text does? Word to index mapping. That is the only job of fit to index wala part. Okay, got it? After we do this, we use something called text to sequence. Now, my people, what text to sequence is going to do is, if I want to map my word corresponding to an index number quickly, I want to get it as fast as possible, and I want to return a list of all those values. If you can see here, our, is it returning 180? Family, is it returning 380? Now 93. Users 1000. This 9 in 11. Places 613. Off 8. Butter. You got the idea? I want this mapping of original data to the sequence map. So what do? Do I take all the values of sequences where I have the word and the index sequences mapped properly so that I can pass it? Understanding what I'm trying to say? If I want to map it back, if the process is supposed to go forward, I also want a way to get backward. Your text to sequences is going to convert each word into a corresponding index value. So if you pass a word, I'm going to get an array of all the indexes. Any sentence you pass, I will be able to get its index back to me. So the will be 2, cat will be x, apple will be 3, dog will be 5, example like that. Every single time you're going to run natural language processing, you will do this. Listen to me very carefully. Fit to text. Fit to text. Okay. Did you not implement fit to text pad sequences and text to sequences while implementing an RNN, while doing tokenizing. For example, Shampa loves to learn data science. Let me copy, let me put another word. Muni also loves artificial, or maybe say Muni also loves to learn about AI. Okay, AI. Tell me, after I map these words, I do fit on text, for example, will I have a word frequency like this of word frequencies of sorts? Like say, for example, I will have fit underscore on underscore text. So can I say Shampa has a word index of, I don't know, 3, right? Or Shampa has a word index of, let's say, 9, example, right? I have loves has a word index of 3 or 5. I have another word index of, say, I don't know, 2. So how many 2s are repeating? So let me just call 2 as 2. So now you have a word frequency table that looks like this. Okay, for all the data. Shampa loves to do this, Muni loves to do this, loves is repeating twice, so let me also say 2. 2 is also repeating 2, so let me just call it 2, right? We also say data science, so say science. You have a word frequency mapping like this. You are going to get something called word to fit or word to index mapping, right? So word to index mapping like this. You are going to have, first of all, the out of vocabulary word. This is going to be more important. So out of vocabulary here will be mapped to 1. You're going to have the, you're going to have loves, you're going to have all these values are going to be mapped to their preceding index. So are you able to see that when you do fit on text, when you map their frequencies, you map the frequency and you run something called fit on text, and you have something called word to index mapping. Understood what I'm trying to say? When you map them together, this specific sentences, when you map up to all the maximum features, you're going to have a word frequency where fit to text is going to give you like this word to index mapping. Once the word to index mapping is done, what do you need to do? You need to convert each individual mapping like our into a sequence of values, right? So can you see here? I am not getting any words, I am only getting sequence. Can you see here? Text to sequence. It is doing exactly what the English word is trying to say. It's converting your text, which is this particular text value, into sequence. So 118, 380, 93, 1000. Understood, everybody? Your entire data will be first converted into frequency of the top repeating words. Those top repeating words will be then converted into sequences. This is exactly what I'm trying to do. Understood? These words are your index values, correct? 118, 380, 93, 1000. What does it mean? What do you mean by these? These are the values on which you're going to be mapping the word indexes back. Understood? Index 0, index 1, index 8, index 100, index 2. You will be able to convert everything back into the sentence if you want to, because you now have a vocabulary of all the words and all the indexes. If you have all these words, you're going to be able to convert the words into your indexes very, very easily. Yes, indexes are supposed to be unique. Indexes don't repeat themselves. If you have both to and repeating, it moves on to the next index consecutively. So if you have a sentence that repeat twice again, this will be given 2, other will be given 3. It doesn't repeat itself, because at the end of the day, index matters, not the frequency. Understood? The intention is to print the indexes, not their word frequencies. Frequencies will be used in order to print the sequences, nothing apart from that. Understood? So if I have all the sequences mapped, what do I do? Once my tokenization part is done, what do I do? In my actual data, right? What do I do? I need to split my data into training and testing. Sir, can we print word indexes and frequencies? Why can't you do that? Try that out, Dharmendra, once again. So sequences or sequence in array or indexes, right? These indexes are, or the sequences are indexes value for each individual word. That's what they are. Because if you don't do this, you will not be able to create any vocabulary, and that vocabulary will not be used for training in the future. Then what are you trying to do? You want to train your data on a specific vocabulary, otherwise it makes no sense. Understood? Tell me, how do I split the data? If I want to train my model, how do I split the data? From sklearn dot What do we use? Do we use something called model selection and we import something called train test split? Yes or no? I'm going to be using the train test split to split the data. These indexes are decided on the base of appearance. Okay, let's go back to basics once again. In any natural language processing task, including generative AI, okay, including generative AI, have you heard of the concept called 5 million parameter model, 8 billion parameter model, 25 billion parameter model? I'm sure you must have heard of sentences like, Mistral 8 billion, right? Distill Mistral 3 billion, right? I'm sure you must have heard of these parameter model. देखो, these parameters are nothing but your large vocabulary sizes. Meaning, what it means is, for each individual word, do you break the word into tokens, my dear? Token number 1, token number 2, token number 3, and token number 4. Basically, they are split into words. Yeah. Each individual word I want to map to my index. That is what that becomes my vocabulary. This will remain same in natural language processing, whether you do generative AI, any other task, this will remain same. My intention for tokenization was to convert my word into index. Is everybody clear that without this step, there is no natural language processing? No natural language processing at all. Understood? That is what I was able to achieve in this particular example, only for the top 100 or padded sequence for, the 100, the length of the words in the sentence. So if you can see here, the actual original text, okay, print original text, okay, is going to be completely different from this data, right? So if I show you the actual original text, right, the actual original text, I'm going to remove this x of 0. The original sentence would be even more longer, right? Like for example, if I want to print a specific value from x, right, it would be further wrong. So if you can see here, our family uses this place of butter and other oils for cooking. It tastes so good. It was a very nice little sweet taste. It also, the sentence is longer. I am only showing the top 100 words because I am usually going to cut it at here only. I'm going to cut the sentence. I'm not going to take the whole sentence. For those sentences, for those words, I have each individual word split and I have each individual word mapping. If you want, you can print the entire vocabulary, but that would be a waste of the memory and time. Okay. See, if I take the length of x here, if I run this, if I take length of this, what do you think it's going to give me? Did I miss a bracket somewhere? Give me 1 second. Let me just call it length of x of outside of this. Oh, why did I do it here? Let me just take another value here. Length of x of, let me just run it for you guys. Length of control Z x of this. If I run this, do I get the value 100? Get what I'm trying to say? So when I'm printing the word here, it specifically 100 words would be an even larger array, right? So if I take the word like our, family, now, uses, this does not look like a length of 100 array, no? You're getting what I'm trying to say? This would be character based, no? It's only mapping with respect to our, with respect to indexes, right? Now, when I do train test split, do I pass my data like this? X train, comma, X test, comma, Y train, comma, Y test is equal to, do I pass in something called train test split right here? You guys tell me, what will be my training data here? What was the last value that we did here? Was my last feature something called X padded? This is the last feature that I have passed in my data. So can I pass in something called X underscore padded, right? That's very good. Apart from X underscore padded, I also want to pass my actual training data, which is Y, which is my reference. What is my Y? If you open up Y, is this the sentiment? Is it the sentiment that I have passed in? So my X and my Y is done. Now tell me, according to your understanding, what test size do you think works well? I think 20% is fine, good enough, right? 20% is good enough, right? Now, because I have done some kind of data balancing, can I use something called stratify is equal to your actual data value Y? Basically, for my class balance of 0, 1, it will maintain the class balance overall by stratifying the sample. Understanding what I'm trying to say? I have taken my train test split data it will make sure that the balanced value for both 0 and 1 is going to be passed. Understood? Sir, how do I handle please? How do I maintain please? How do I mention so? How do I do that? First of all, you don't have to let these pass inside your model. Number one, do you know that you have brilliant module called regex in Python, right? So in regex, if you have a value like so, can I map it back to so? If I have please, can I map it back to please? So tell me, even though you want this to be a part of your data, should you let this be a part of the data? Never make that mistake. If you do that, the model has one more token or one more token to reference and to calculate. Don't do that. What you need to do, my dear, is see, let me ask you one thing. Hey Bidu, is this a Hindi sentence appearing in English? My bro, is this a sentence in English repeating in English, correct? Now tell me one thing. You have a sentence called A Bhidu. How do a computer know A Bhidu is supposed to have some meaning, right? You have Gen Z people talking about this, right? No cap, right? No cap apparently means I'm not lying, right? So tell me one thing. When you have sentences that don't have any relationship to cap or no, but it means don't lie, don't you first of all need some kind of a target sequence, some kind of a sequence that tells you what it means? Number one. To deal with this, number one, you should remember, if you have enough representation of A Bhidu, there is no problem at all. But A can be written like A, it can be written like A, it can be written A. See, sentences like these need to be handled as much as possible using regex. In the data itself, do cleaning in such a way that A Bhidu and any kind of A Bhidu representation is standard across all the sentences. Understood? So that whenever a user passes a sentence A Bhidu, regex can handle that very, very well for you. Okay, don't let it pass it to your data. That's not a very good practice, because your data, your actual implementation will have a lot of errors. Understood? So anything like so, please, and all of that, handle it with regex. If you don't handle it with regex, so will have a different index, so will have a different index, SOO will have a different index, SOOO will have a different index. How many indexes will you create for the word? Understood what I'm trying to say? So handling this will become incredibly complicated. You don't want to do that. You don't want to get into that rabbit hole. So don't do that. Just handle it as much as possible in the original value. Understood so far, everyone? But how regex deal with this type of data? You can write a code in regex where multiple different repeating words can be handled very, very carefully. I recommend you look at a module in Python called RE. Import regex RE, or in your internet on the Google, go to something called regex.com, or there is something called regex 101. Understood? Whatever sentences you write here, you will be able to map it back. Like my name is Parth or Rudra Sharma, example SHARMA. If I want to pick up everything from A to Z, from capital A to capital Z, is everything highlighted apart from spaces? If I say I also want spaces, everything is highlighted. I want it very, very greedy. So I'm going to say W star or /W. See, the point what I'm trying to make is, if you want to map everything, you can try putting a word here. So for example, the word is so, right? If I remove everything, if I say the word so, right? SO, is everything picked up? If I don't want capital letter, I know I have lowered it. Am I picking up anything? If I say capital A to capital Z, right? Is anything picked up? No, because everything is a smaller version. So this is one of the best ways you can practice your regex skills. There is a website called regex101.com. Learn regex, you can handle and build patterns for regex. For this, you need to understand all types of regex values, okay? You need to understand what is a greedy search, what is a non-greedy search, what is space-based mapping. There is a crazy amount of things you need to do. So now, if I print for your reference, all the training set in my data, right? So what is it? Training set in my data. What is the training set in my data? Can I pass in something called x underscore train, right? X underscore train dot shape of, let's take only one specific sequence, right? Let's also take testing data. Let me copy this. Let me take testing data or testing set x test dot shape of 0, and this will, let's call this as these many samples. Let's also paste these many samples here, right? And let's also print what is the shape of the feature. So xtrain dot shape, right? I'm going to pass in the index 1, and I'm also going to say that this is my sequence length, right? My sequence underscore length. And if I run this and x test, sorry, not text. Tell me, what answer did you get, everyone? Training set is how many samples and testing set is how many samples, and the shape of the feature is 100. How we wanted it to be, right? How do we know that the balance of the data is maintained or not, right? How do we maintain that? So train underscore positive values, okay, is equal to, and test underscore say positive values, just for positive tests I'm doing, right, is going to be what? Can I take sum of y train values? And if I come over here and write down the sum of say y test value, what are you going to get as an answer here? If I print your so example, how do I show you as a percentage? So if I show you like this, right, print of training, what was the name of this table? We had a df balance, right? So we had a score text. So what is the number here for train positive? So we, if I print train positive, if I print it, that would be 65630. So if I want to take the sequence, that is 65,630 divided by, multiplied by 100, overall length by 100, right? So if I show you like this, so training of my positive value would be, so if I pass in the sequence length like this, so the train positive value, which I'm going to be taking for a specific instance, I'm going to take a bracket here, another take a bracket, and take all the train positive values, 65,630 divided by the total length. So 65,000 divided by length of whatever is my y train value, and if I multiply this with 100, right, this would give me the overall percentage. So if I take this for training positive and testing positive, so let me call this as a test positive. So this will be test positive. So train positive will again become test positive by y train of length of this. So what will this be? Random. Oh, there is a bracket here, right? And this. Okay. Do you see the percentage difference here? The training and the testing that we have done here. If I want to balance it out, stratify equals to y. Even though I have applied stratify equals to this, my balance is as much as possible depending on the train and test. If I want to implement my basic RNN, please tell me, since you have already implemented this in the past, what do I need for RNN implementation? If I want to implement my RNN, what is it that I need? Do I need to call RNN module, which I haven't done yet? There is no import of RNN related code. So how do we do it? From TensorFlow, what do we call? From TensorFlow, this is going to be one of the package. I am of course going to be using a submodule called Keras. Agree, disagree? I'm going to be using a submodule called Keras. Inside the TensorFlow.keras.layers, what will I import? First of all, you can import something called embedding, because this is what I'm going to be using, correct? I can also import what? I can also import a very simple version of RNN called simple RNN, correct? I can also import something called LSTM. I can import something called dropout, correct? Now that I want to use multiple different types of, RNN or LSTM implementation, what can I do? I am also going to show you how to implement something called optimizer. So from TensorFlow, okay, remember you also have optimizers in the Keras package called .optimizers. Which optimization am I going to import? Usually I prefer Adam, depending on the problem, that is more than enough, right? I also want to show you how to do something called callbacks. So from TensorFlow, okay, so from TensorFlow, I'm also going to show you a method called .keras.callbacks. Have you implemented callbacks, everyone? Have you ever used something called as early stopping, or have you done something called model checkpoint calculation? Right. So tell me, every time you run the model, don't you want to save the model to the best of the capacity? Whichever is my best capacity, I want my model to be saved in that specific sequence. So if I run this, I have taken embedding, simple RNN, LSTM and dropout, Adam, early stopping and model checkpoint, correct? To create a basic RNN, can I say create underscore RNN underscore model? I'm creating a simple model called RNN. To create my model, I'm sure now everybody knows that any single model that you create has to be taken as a sequential model, because this basically means that I am going to combine everything. Everything has to be combined together. Now, in order, I did not take the variant here. In order for me to take everything together, what is it that I need to do? Is there a method called sequential, right? So come over here from TensorFlow. I did not import sequential. So to TensorFlow, give me 1 second. From TensorFlow dot Keras dot model import, let's call sequential. Run this. Let's call sequential. Let me also call it again sequential. What do you do in the sequential part, everyone? Can I first take as my first layer is the embedding layer? So I'm going to be calling something called embedding here. Why do I call the embedding layer? Because I want to convert. What do I want to convert? I want to convert each of my word into what? Or my word indices, I want to convert them to what? I want them to convert to a dense vector representation. Make sense? Each individual word indices, I want it to be converting into a very high dense vector. So can I say input dimension is equal to maximum features? What do I do by this? The output dimension, let's take it at 128, and the input length, right? The input underscore length is going to be approximately the max length that I have taken. What does this mean, everyone? This embedding is equal to input dim is equal to maximum features, output dim is equal to 128. What is the dense vector representation that I want to get? What will be the dense vector representation that I'm trying to get? Is it going to have an output dimension of 128 size? The size of the dimension or the dimension itself is going to be 128. After I make the vector of that dimension, what do? Do I pass in something called simple RNN? And inside the simple RNN, how many units of simple RNN roles that I want? Can I say 64? Return sequences, always make sure if you pass in return sequences, do not have or get any return sequences. Make it false. You don't need that. Understood? Each index has 128 value. Each indices value is going to be mapped back to a word, and that word will have a size of 128 dim. Understood? If you take a word called ice cream, how will you represent ice cream? Now tell me this. You have also heard of a concept called dropout regularization, right? So what am I going to do? I'm going to give it a dropout of 0.5. Once this is done, y units equals to 64. I have just written according to me whatever units I could find. You can change the units to your values also. You don't have to follow units as 64. I'm sure you guys know that you can take units like 8, 16, 32, 64, 128. I hope you know, right? In the multiples of 2 is what you do. You've been taught to do that, right? Okay. So after dropout, I want my answer to be a classification problem. So at the end of the day, do I have to take a dense representation, right? A dense layer. Now tell me one thing. At the end of the day, sir, I want it to be implemented and I have not taken any dense representation here. So let me just take dense. Let me call dense here. Can I make it size 32? And activation will be equal to what, everybody? The activation that I want to pass. So let me call it activation will be equal to, tell me, can I pass in sigmoid or can I pass in ReLU? Because this is my first layer. Can I pass in ReLU? After the first layer, my dense representation could be else, because my output needs to be 1. So activation will be equal to sigmoid here. Can I do this? Can I do this here? Because this is my actual output layer. This is my other dense representation layer. So this is like my other hidden layer. Understood, everybody? Okay. When you take your input image, you apply convolution, max pooling, convolution, max pooling, convolution, max pooling. At the end, do you not flatten the entire image? Do you flatten the entire image? The number of values that you flatten is the number of input you have to take in the input ANN. No? Your artificial neural network, your multi-layer perceptron should match with the input sequence of this. So suppose if you have a sentence of 7 into 7, your pixel size is 7 cross 7, right? What is 7 sevens are? 49. So do you have to take a 49 sequence word, because this is how you want to take it as an input? Now, if your input is sorted, can you not take a hidden layer of size any, like 16? then a hidden layer of size 1. So your data 47 will be crunched into a size 16, will be finally crunched into a size 1. I'm sure you must have studied this in your multi-layer perceptron, your artificial neural networks are taught like this, right? So am I taking the same representation 32 where I am taking the input size of 32, passing it down to a size 1 and then getting the answer? It doesn't need to be 128. It will work. For example, it doesn't necessarily need to be 128. Let me explain. What does dropout do? For my output dimension 128, I am passing in a simple RNN. What does this? Okay. So let's get our basics of neural network correct. All of you are telling me, sir, we need 128. Why do we need 128? What is the reason behind it? Why should you only make 128? Because the model dimension is 128, so should we take 128? Let's understand this. In my code, what is the RNN's structure look like? What does it look like, my structure of the RNN? What does it do? Do I have an RNN where my structure is very, very simple? But what does the structure of the code do, or what does it do for you? What is it that it is good at? Tell me, in the structure of my RNN that I have taken, do I have the first layer as the embedding layer? The embedding layer is going to create a vector of 128 dimension, correct? It's going to create a vector of 128 dimension. Once that is done, do I have a RNN with 64 hidden units? That's the size of the RNN, not the types of RNN or 64 RNN cells. I told you this is not what we do. Do I have an RNN of the memory of size 64? My RNN will have a layer, it will have a internal memory of the size 64 values, correct or not? Your model training will maintain training within this 64 value, correct? After this, what do? I have passed in something called 50% of the neurons will be converted to 0 or will be dropped. Agree, disagree? Now tell me, if I want to connect my RNN with my dense representation, does it have to follow 128? They have no relationship with each other. Understood? You take 1260 also here, does not matter. My dense representation could be how I want the data to fall on. Understood? You're understanding? Because if you think 128 divided by 2, it is still 64. But am I not passing 32 here directly? This relationship of the vector dimension and this dense representation have no relationship with each other directly. Understood what I'm trying to say? This part is a fully connected layer of the input value where 32 neurons are being passed. They have no relationship with this output dim 128. They have a relationship with this unit. Understood? Unit 64. 64 का 2 क्या होता है? What is 64 divided by 2? Is it 32? Have I mapped it to 32? Understood what I'm trying to say? You're not worried about the output dim, you're worried about the layers you're passing with each other. Did you get the context, everybody? You're not going to focus on the output dim. It's going to handle itself anyways. So suppose if I want to run this model, so suppose let's say this is my model, I want to run this model. Can I say RNN underscore model is equal to, how do I run the model? Can I call the function name itself called create RNN model? Now everyone, once I call the model, don't I compile the model? RNN model dot compile. And in the compile part, what do I pass? Do I pass in the optimizer? So optimizer, okay, optimizer is going to be equal to, do I pass something called Adam? Adam is going to be one of the optimizers that I'm going to be using. We have Radom, AdamX, we have multiple different types. What is the loss? Are we doing a classification problem, regression problem, or anything else? What kind of losses do we have when it comes to classification? Can I say binary cross entropy? You guys know this, right? When you use softmax, it becomes a different kind of cross entropy. It's categorical cross entropy, binary cross entropy. You have a different kind of loss functions available. And what will be the metrics that I want to measure throughout the code? I am predominantly focused on accuracy. So I'm going to maintain the accuracy part of it. Understood? If I run this piece of code, okay, dense is not defined. Let me run dense once again and let me run this once again. RNN model.compile. My model is compiled. How do I make sure that my model is compiled? If you want to check your model is compiled, can we print RNN underscore model.summary? I can check the entire model's representation. Agree, disagree? Can you see here? You have a size of embedding 2. You have a simple RNN. you have a dropout layer, a dense layer of size 32 and a dense layer of size 1. Can I say this is my entire summarization of the model? An embedding layer, a simple RNN layer, a dropout layer, a dense layer and another dense layer. Agree, disagree? Did I write a simple basic RNN, a simple RNN? Okay. If I want to train my RNN, RNN underscore history, okay, is going to be what? RNN model dot fit. Now, what am I going to fit my model on? Am I going to fit my model on X train data? I'm also going to pass in something called Y train data. What will be the batch size given the size of the data, everyone? So batch, BATCH underscore SIZE is equal to, since the data set size is larger, preferably also use a larger batch size. So can I say a batch size of maybe 128 is good? Understand what I'm trying to say? Since my data set size is larger, let me take a larger batch size. How many epochs do I want to run? I am only going to keep the epochs to 5. And the validation split I want to run, okay, is going to be at 20%, right? So my validation split will be, let's also retain it at 20%. And let's print the verbose equals to 1. Let's see how the result gets printed in a nice way. Formatting, what kind of progress do we get? So let me run this. Okay. Give it like a second. Let it just run. Any error? Okay, it ran the plot. It ran everything. DF balanced, it ran deep. Okay, cleaning is done. Tokenization is going to take some time. Then we are going to run the value. So let's see if the tokenization is done. Actual text, sequence, padded shape, done. Split the data. Taken this model type run. Now epochs are going to get started. Okay, good. See, considerably, can you see this is faster? Like the run time is faster comparatively to other. I mean, trust me when I speak this, GPUs have a big impact in our life. It's gonna make it very, very good. So that's why I ask people, preferably do not buy laptops which are MacBooks, right? If you are a data scientist or if you want to do a lot of implementation, buy Alienware laptops. They come with at least 1050 Ti, 1050, 1080 Ti, you know, like you can modify it to run 1080 Ti. At least you will be able to run your own models very, very easily. I know it's not enough, but at least you have the gear to make it happen, right? So I think that's a great news. Okay, so my people, I have run my model for 5 epochs. What will be the final accuracy of the model? How do I print my model? So first of all, tell me this. If I want to print my final model accuracy, right? Or how is my model performing? Of course, it's going to be performing not that great because my epochs is 5. But suppose if you want to print it, right? So final, say final underscore train underscore accuracy of my model. Now remember my people, what happens is in the RNN history, you have multiple different values like accuracy also, loss also, validation accuracy also, and validation loss also. So if you want to only specifically get the value, you have to use a method called dot history. And inside history, you want to only print accuracy. So what do? So just copy the word accuracy here, print the accuracy here, and see accuracy is not going to be returned directly. Return the negative first index of it. Now, if you get this value, this will give you the final train accuracy. Same exact thing. If I just write down print F double quotes of my final trained accuracy here, if I copy this and if I paste it here, will be approximately 54%. Of course, I should not be surprised in this. Why should I be surprised? Because how many epochs did I run? Only 5. For a larger data set size, my epoch is very, very less. I did not get enough time to get the representation well. Can you see my loss was decreasing consistently? It started at 6.9, became 6.915, became 6.8 and ended at 6.7. So my loss was decreasing, correct? Overall, my loss had started decreasing and I had known that, okay, it's becoming better, right? So tell me, everyone, did you run a simple RNN neural network on the same data? No questions, no confusions. We haven't done any optimization yet. We haven't done any efficiency load testing yet. We haven't done that yet, right? Accuracy is increasing, loss is decreasing. Good. Let's matplotlib dot pyplot as PLT. The best way you can ever analyze your neural network, okay, according to me, is doing this. Plot.figure, let's actually size the canvas, okay, plot.figure. Inside this, figure size should be equal to, let's take a very small 8 by 6 image, right? Let's plot it out. Let's see overall how was my model performing, right? So inside this, let me take, when we have the model by the name of RNN history. That's good. So let me just take this. Let me call it here dot history. If I want to plot loss, see, loss is mentioned right here. Copy this, paste it here. Okay. Give it a label by yourself. Say that it is a training loss. Okay. Over a period of time. Let's also make a plot dot plot. The same exact history. I'm going to take the same thing. But this time, instead of taking loss, I'm also going to take something called as a validation loss. I'm going to copy this. I'm going to come over here. I'm going to paste this particular thing here. Let's call this as a validation loss, right? Validation loss. Let's also plot dot. Let's also give a title of sorts. I don't know. Let's give it model loss over epoch. Okay. How many epochs did my model run, and overall how much the loss was guaranteed. Plot dot x label is going to give me, let's say, epoch over the x, and plot dot y label is going to give me the loss overall, right? Can you see here? Oh, let me just put legend also for you. Plot dot legend, right? Can you see here? Overall, the loss is supposed to decrease, right? And including my validation loss and training loss, my loss has consistently decreased, right? Like over a period of time, considering the strength of the model, my model has decreased overall the loss, right? If I increase my epoch size to a little bit more, then of course this graph is going to become even more smooth, right? Even more better. If I don't want to do this, if I want to plot some kind of a accuracy plot, so overall, what was my accuracy? So if I copy this, if I plot my accuracy, right? Let me copy my accuracy. Let me plot it here, right? Let me paste my validation accuracy. Let me plot it here. This is going to give me the validation accuracy. This is training accuracy. This is validation accuracy. This is accuracy over epoch. Okay. And this is my epoch and this is my accuracy, right? If I run this, see, overall, my accuracy has taken, my validation accuracy has taken a little dip, went back up, but my training accuracy has gone up consistently. So it went up like this, then it shot up a little bit. So see, this is just another way of visualizing, identifying, okay, whether my model is doing good. It will become even more clear when you know for a fact that you are able to make your model run for a larger epoch. If you make your model run for an even larger epoch, it's gonna do good. But my question to everybody is, should you run 150 epoch or 50 epoch or 100 epoch in the beginning only in the deep learning code? For example, I am just trying out my RNN code. Is it a good thing to run a very large epoch in the beginning of the program? Never make that mistake. Do not make that mistake. Not gradually, not in any sort of way. You are not supposed to run your beginning code or your dry run in the biggest or the largest of the epoch cycle. You know why? Because do we yet have to calculate the best hyperparameters for my model? I don't know which model works the best. So I wanted to make sure I try and run my RNN and see how it performs. I kind of have an idea that the epochs or my accuracy is increasing over a period of over a period of epochs, and loss is decreasing over a period of epoch. First, we have only implemented RNN, but what about LSTM cells? Have we implemented an LSTM? Yes. No, not right now, because we have not done comparative analysis yet. So once the RNN is done, can I take the same exact code, my people? The one that I have written here, create RNN model, can I copy the whole thing and paste it here, right? This is a simple RNN model that I want to run. Can I say create simple LSTM model? Let me take it like this, LSTM model. Now tell me, sir, in the LSTM model, what do I do? Same exact thing. You will pass a model with a sequential value. You will first convert your embeddings into a dense vector representation. But at the time of simple RNN, what do I need to import? Do I need to import LSTM? Because I have already called LSTM here. Please observe, have I taken an LSTM cell here? I have. What did I do? I have just replaced the LSTM. How many units? 64. Am I going to return any sequences? None. I don't want any best value. I want the last value. Dropout will be equal to 0.5. dense layer is 32, dense is 1, activation is sigmoid, model is done. Can I say this is done? Instead of calling this RNN model, can I call this LSTM model, right? Can I call this LSTM model? And I can just return create LSTM model. Correct? Agree? Disagree? Just taken an LSTM model, same exact thing. LSTM model dot compile. Will I have the same exact thing? Adam, binary cross entropy, matrix equals to accuracy, and LSTM model dot summary. So instead of this RNN, LSTM model dot summary. Can I say I now have an LSTM model, everyone? I did not do so much effort. I just had this particular thing run. To run the same LSTM model, all I have to do I have to take the same exact thing? I'm going to copy this. I'm going to paste it here also. The LSTM history is equal to LSTM model dot fit. Can I say I am taking the same exact value, X train, Y train, batch size 128, epoch 5, validation 20, and this? If I run this, what will happen? My model is gonna run. So I am gonna copy both the code here, okay? Control all, control copy over here, and I'm going to paste it here. The only difference is you have to take LSTM history here, LSTM history here, again LSTM history here, and again LSTM history here. Let's make the plot very, very small. Let's take it 4 by 4. Let's not have it a larger one. Okay, model epoch versus loss. Let it run for a while. Let's see how it is doing. I can see that the loss increased, then the loss decreased very big. Peak time the loss decreased. Again, the loss is decreasing very high. Suddenly the loss just dipped very, very hard. Let's see how it goes, right? Let's run this. Let's see how the implementation works. Okay. Did you see that loss was decreasing constantly and over a period of time it became a little stagnant, right? Can you see here my model accuracy also increased, but after increasing suddenly it became kind of peaked at a certain value, it became a little stagnant. So see, LSTM comparatively for 5 epochs seems to work good, but we don't know this, correct? We do not have an idea that okay, LSTM performs better or RNN performs better, or which one is going to do good. So tell me one thing, is it not good to perform some kind of a hyperparameter search or hyperparameter tuning by ourselves so that we are able to see for which hyperparameters my model performs good? Agree, disagree? Understanding my people? See, my RNN gave a certain kind of result, my LSTM gave a certain kind of result, right? In my RNN, what answer did I get in terms of accuracy here? If I print my accuracy here, where did I print it? Somewhere in the bottom, right? Where did it go? Did I not print it? Yeah. So can you see here? It's approximately 0.5458. Let's print it for LSTM also, just for understanding, right? So let me come over here and let me print for this also. Oh no, this will rerun the model once again. Don't want that. Let's go to code. Let's print it here. Let's say LSTM history and final training accuracy is going to be LSTM training accuracy. Is it showing me 93%? Right? Looks too, looks too good to be true, right? Only for 5 epochs. Looks too good to be true, right? For only 5 epochs, I'm getting a considerably better accuracy for 93. I'm not sure. But we don't know until we perform hyperparameter tuning. Now tell me everybody, to perform hyperparameter tuning, tell me this. Let's take a param grid. I hope all of you know to perform hyperparameter tuning, you need to take a grid. Grid is the value or are the values you want to test for. So tell me everyone, what is the model type we want to test? Everybody, do I only have 2 model, one RNN and other LSTM? This is what I want to perform. I want to check for both RNN and LSTM. Make sense? What is the embedding dimension I want to try, right? Everyone, what are the different embedding dimensions I can try? Can I say let's try 64 and let's try 128, right? Let's not try more. Let's try these many. How many units do I want to test for? Can I say 32? Let's take 64 and let's also take 128. Okay, these are the units I want to try. What else can we try? Let's try dropout regularization, right? Dropout underscore rate. What rate do you want to try? Say 30% random, and 50% random stop. Let's also try learning rate. Okay, for a different type of optimizers like Adam, let's try a different type of learning rate. 0.001, let's try 0.01. Yeah, this should be more than enough. So tell me, am I going to try my model? Which model gives me the best peak accuracy for all these types of param that I have mentioned here? Agree, disagree? So tell me, in the search space that I'm going to do, we have something called random search and we have something called grid search. Correct or not? I'm sure you guys have heard of something called random search CV, grid search CV. Which one will you prefer if you want to not spend too much time in your search space mapping? Which one, according to you, is considerably better? See, personally speaking, I think the best type is going to be something called as your random search, not grid search. Considerably, if you take grid search and random search, do you know the difference between them both? Grid search will tie every single permutation and combination to get the answer. Random search will give you the same result or similar better results, but in a lesser time. Understanding what I'm trying to say? The time it takes for you to search with that model is not going to take a lot of time. So preferably, people prefer using something called as random search. Okay. But I'm going to show you a different kind of search mechanism. Listen to me carefully. You need to give me your attention. Listen to me. For param, comma, values in param grid. What am I doing here? Actually, we need to take both the values. No, this is a dictionary. So items. What am I doing here? For each individual value, how many combinations I have tried, I'm going to keep it at 1. Okay. For values in param grid dot values. What will this give me, everybody? For values in param grid dot values, what am I going to do here? Total combinations multiply equal to length of values. What will this do? What I'm doing here in this piece of code is something different, and you will understand what exactly that different thing is. But tell me, for now, what am I doing? I'm taking a piece of code and I'm trying to implement something really critical. Okay. What is this? For now, I have taken each individual value, which is model type, embedding dimension, unit, dropout rate, and learning rate. Agree, disagree? So tell me all the total possible combinations that could be printed. Can I say all possible combinations could be printed in this particular value? Every possible combination that I can have, which is going to be model of RNN with 64, RNN with 32, 64 with 50, every possible combination I have. I am calculating all possible combinations from here. Agree, disagree? Yes or no? So tell me, how many values do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 values. If I multiply, say, total possible values here and total combinations, let's print total combinations. How many total combinations will be generated if I run this piece of code? 48. How many? 48 possible combinations could be generated from the param grid. Agree, disagree? 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 2 multiplied by 2. Understood what I'm trying to say? Basically, what we are doing here, no, is 2 multiplied by 2 multiplied by 3 multiplied by 2, right? Multiplied by 2. Understanding what I'm trying to say? Did everyone get it? The total combinations that we are going to try and run, we are going to make sure that we run this. Okay. Once the total combinations are printed, I'm actually going to write down a logic which is going to implement it in a very custom manner. For example, come over here, define create underscore model with params. I am going to create my neural networks, run my neural networks, but they are going to run with a specific type of params. So for now, the model type that I want to run is an LSTM model. Okay. For now, I want to run a param type model called LSTM. What is the embedding dim? Right? Embedding dimension that I want to pass. My embedding dimension is going to be say 128, right? Let's say I want the units of the model to be 64. Am I passing the model of my own preference, which is the model that I want to give, that I want to run for all specific combination? But haven't I already tried this? I have already tried this model of a specific combination and I am able to run the model very, very specifically, right? I have already done where I have given a model a specific combination and those combinations were run and my model gave me the answer. But if I want to run, my model will completely random search. So do you think I can run some kind of a linear combination of random search? So if I remove this, and pass in something called random search, RANDOMSEARCH, random search. In this random search, how many trials of search do you want to give? So can I say the random trials I want to try is 8? What will n number of trials tell you? It will tell you that I am only going to search for 8 random best combinations. And out of those best trials, whichever is the best, I'm going to print that. Agree, disagree? I'm going to run 8 random trials among the overall combination of 48. That is how much? 48 by 8 at a ratio of 6. Understanding what I'm trying to say? Understanding? At a ratio of 6, I'm only going to run a random search trial of 8. So tell me, can I take a variable called results is equal to an empty array? All the results will be appended on this list called results. Okay. I'm also going to take a seed value of 42. Okay. So tell me everyone, to run every single model, will I take a for loop for I in range of how many iterations do I need to run? Do I need to run n trials operations? Agree? Params is equal to, okay, if I take this param grid as it is, can you see here the param grid that I have taken here? I'm going to copy this particular thing here. I'm going to write this particular thing here as it is, right? Param grid or params is equal to model is equal to this, type is equal to this, and let me also give a little bit of indentation here so that it's a little bit neater. Give me 1 minute. Yeah. Is this going to be all my params, everyone? Model type is going to be RNN, LSTM, and all of that stuff. Rather than typing it like this, all my params, I can actually also do one other things. I can also directly call, since param grid is implemented, can I call it like this? Can I say my model type, actually let's take a dictionary, let's call it like this. Model type, let me copy this. Let me write down a double quote model type. Let me remove this. How do we call it, right? Do we call param grid, PARAM, param grid of what do I want? I want model type, right? So let me copy the model type here. Let me paste it up here. And let me say I want to call model type. And out of this param grid, I want a random choice. So np.random.choice, right? I want np.random.choice. I want to pass it from model type. I want to choose anything randomly between RNN and LSTM. And this will be passed as a string value for the model type param. So model type is going to give me, model type is going to give me model type. So this is going to give me a random thing between model type. Okay, let me copy this and let me paste it in the bottom. Control Z. Out of model type, I also have something called embedding dim, right? So let me copy this. The name of this will be the same. Mapping of embedding will be np.random.choice, and I will do it for embedding dim the same way. And Control Z, I copy the whole thing. And apart from embedding dim, I will also take something called my units. So I will take units, I will pop up units here, and I will take up units and paste it here. It will not be string for embedding dim. Embedding dim will be an integer type, correct? Embedding dimension is an integer type. This also will be an integer type. And apart from units, what is the dropout rate? Dropout rate also will be a integer type. So let me copy this. Let me paste it here. Actually, you know what? Dropout rate is a float type, right? Because I think I have taken 0.30, right? So let's give it float. So apart from units, let's also take dropout rate. Let me copy dropout rate. Let me paste dropout rate here. Let me also paste dropout rate here. And the final thing that we need to take apart from dropout rate is going to be in the end going to be the learning rate. So I'm going to take learning rate. I'm going to copy this, map it to learning rate. So let me take it from here and let me take a learning rate here. So This is going to be string type, integer type, integer type. I'm going to take the last two value as a float type, correct? Okay, this makes sense. I'm going to take the param grid of that value unit. I'm going to take a random choice of it and convert it into its proper data type. So it's proper format. So it's going to be string, integer, integer, and float values. Good. Now, my people, what is it that we want to run? We are going to run the models, but for how many trials? Okay. How do we ensure the same combination is not picked twice? If you want to make this particular combination distinct for the n number of trials, what you can do is in the np.random.choice, you can use a distinct categorization. So rather than taking them as a dictionary that I'm taking, right? You take it as a data frame. In the data frame, only add a data frame when there are distinct elements available. If you don't want distinct elements available, or if you want to make sure that the random choices or the value of random choices that you're giving here are only and only distinct, either you take a dictionary, make sure all the random values are not picked twice, either take it as a data frame, run a distinct variable there, or make sure that you take it as a dictionary and make sure that the distinction is not run there. See, tell me one thing, in the code that I'm running here, what is the most important factor in the entire code? I am making sure that I am running a specific value, a specific combination of things, and to make sure that they don't run, we are going to make sure that we are trying for every possible value. For every possible value that I run, I'm going to make sure that I do not get any errors. So what am I going to do? For every possible combination, I want to print every individual value that I have tried. I want to make sure every individual trial that I have run, I want to make sure it runs. So in order for me to run that trial, what do I need to do? I need to mention that how many trials have I run. So for example, if I write it like this, the trial that I have run so far, let's start it at index +1. I don't want it to start it at 0. And let's call it the n number of trials that I have run it for, right? So if I say try, right? What do you want me to try? Try model is equal to, okay? Model is equal to. Now, in case if I want to run this model, right? I do not have a default model like RNN and LSTM. Can you see here? Here, I have taken called create LSTM model and I have taken something called create RNN models. But have I passed in the parameters like the way I'm supposed to pass? Or is it I have passed the data within the model itself? Agree, disagree? I have passed in the model with empty values inside it, correct or not? I have not given it anything called units inside as an argument here, units, the learning rate or anything of that sorts. I have not done it. So tell me, do I need some kind of a helper function here? That's why I deleted the previous version. Can you see here? I want to try something. I need to create a helper function because without this, the helper function is not going to run. So now does it make sense to do helper function? Understanding, my people? The helper function needs to be created. Agree, disagree? Sometimes when you're doing deep learning, it doesn't necessarily make sense in the beginning to create a helper function, but when you realized, oh, I think I made a mistake because I haven't created any kind of a model that will let me pass the value. So let's say, can I take a function like this? Define, right? Define, create, okay, create underscore model underscore with param. Do you remember I took this function but then I deleted it because we don't need it. We did not know the necessity of it. We did not know the requirement of it. So will it make sense now that model type which needs to follow the same particular reason, okay, like model type, embedding, ding, units, dropout rate, learning rate. So what do? Can we take a model underscore type is equal to, let's take by default RNN, okay? The embedding dim that I want to pass, is say by default 128, right? The units I want to pass inside the model is going to be say 64, example. The dropout rate is going to be, let's say, a default of 0.5, and the learning rate that I want to pass inside the model is going to be the learning, okay, so this does not, okay, the learning rate is going to give me 0.001, example. In this model, am I passing everything, let's say by, I don't know, default? Am I passing models with some default values? I've already taken model type is RNN, recurring embedding dim is 128 and all of this stuff. Now, what I'm going to do is, Am I going to run the model? Model is equal to sequential. Observe here, my people. Model is equal to sequential, and inside the sequential, I'm going to pass something called embedding model. But inside the embedding model, will I pass directly something called max features? Embedding dim, I don't need to take it the way I've had taken it in the past because I'm going to pass them directly. And the input length, right? The input underscore length is going to be equal to your max length, correct or not? This is going to be my embedding layer. Agree? So tell me, how many different types of model am I running if my model type is equal to RNN? What will happen? Or let's say if my model type is equal to LSTM, what are you going to run? Are you going to say model dot add? Do you know we have a method called model dot add in TensorFlow? And inside this, I am going to take LSTM, and inside the LSTM, I'm going to pass the units that have been passed to me, and the return sequences will be false as it is. So the return sequences, I'm going to pass it as false. Point number one. Otherwise, else, if my model is what? If it is not LSTM, what will be the model? If my model is not LSTM, then what is the model? Is it going to be an RNN model? So can I call a simple RNN here? In the simple RNN, I am also going to pass the units as it is. Agree, disagree? Return sequences, I'm also going to say something called false. Agree, disagree? Everybody, tell me, did I, after the embedding layer, added the relevant model, either LSTM or either RNN in the else condition? Agree? After LSTM and RNN, which one do you need to add? Can I say model.add in my layer? What do I need to add? Do I need to add dropout? Everybody? Do I need to add something called dropout? Inside the dropout, what dropout rate have you passed? Can I say some default dropout rate I will be passing, right? Model.add, after the dropout rate part, what do I need to use? I need to use a dense model with the size 32 and say activation is equal to ReLU, okay? Activation will be equal to ReLU. See, in the dense representation here, I am taking a size 32 because this will remain stable, correct or not, according to the architecture that we have passed. If I do again model.add, say model, model model.add, what am I adding in the model? Am I also going to add something called dense? Inside the dense, what can I do? One, activation is equal to sigmoid. Agree, disagree, everyone? Once the model is done, what do you need to do? Model.compile. In the model.compile, what do you pass? Can I say optimizer is equal to, what kind of optimizer am I passing? Optimizer, okay, is equal to, am I passing something called Adam? See here, I have already imported Adam here. What Adam learning rate do you want to pass? Learning rate will be equal to learning rate, because are we passing learning rate dynamically here? We are not keeping a static learning rate of 0.01. It will depend on what the model's learning rate is. What will be the loss? The loss will be consistent. What will be the loss, everybody? Binary cross entropy, because we don't mess with the loss. So can I say loss and metrics will be same? Because no matter if it is RNN or LSTM, the loss and the metrics will remain same. Make sense? After this particular thing is done, do we return model? Everyone. So let me take this code out, the random search. Give me 1 second. Let me take the entire code out, control exit, okay, control exit, and look at this piece of code. Is this piece of code making sense, everyone? This is going to give me the hyperparameter search for any values I want in the future. There will be no problem. Understood? Any values that I want to pass in the model type, in the embedding dim, in the units, in the dropout rate, in the learning rate, it will be able to help me. If you don't want to give it in any value, you can also pass none. Understanding what I'm trying to say? You can also pass it units equal to 64. You can pass it however you want. Understood what I'm trying to say? You don't necessarily have to give it some specific value for it to run. Now tell me, in this piece of code, I already have something called create model with param. I'm going to copy this. This is my helper function and I'm going to write it here. But tell me, what will you pass inside the param part? In the param part, am I going to pass keyword argument called params? Can you see here in Python, we have a keyword argument called params. All the params, I am automatically passing it inside the function called create model with param. It will automatically take my model type randomly, whatever I have assigned, embedding them at randomly, whatever assigned, units, dropout and learning rate randomly, whatever I have assigned. Understood? The model is going to try doing that and tell me What will be the history of the model? The history of the model will be what? Model.fit. Inside the model.fit, am I going to pass in something called xtrain? Am I going to pass something called ytrain? Agree, disagree? Am I going to pass in a batch size of, you can also parameterize batch size, by the way, but I'm going to keep it stagnant because the code will take a longer time to run. So let's say batch size is 128. Epochs is equal to, since we only want to try it out, can I give it 10? Yeah, it will take some time, but I'm okay. Okay. Validation underscore split is equal to 0.2, 0.2, and let's not take any verbose or anything. I think let's take a verbose equals to 1 actually. I am trying, this is my model, okay? My validation accuracy will be maximum of, in the history that I'm running, I want the history to return the maximum validation accuracy. So val underscore ACC, right? So validation underscore accuracy. So I'm going to copy this. I'm going to come over here and I'm going to paste the maximum amount of validation accuracy that I want. Once I get the best accuracy available, I will take my results list value and append it with what? Whichever maximum I have so far found. How many trials did I run? So the trial that I ran is going to be the index plus 1 because it runs like that. The params will be equal to the params that I have run. P-A-R-A-M-S, params. And not this, P-A-R-A-M-S, params. And the validation accuracy, okay, or validation ACCU-RACY accuracy that I have received is the validation accuracy that I got in the model. And what else do you want to save? I think we can also save the model details, model. So this will give me the answer. And so wait, result trial is I plus 1, the params, the validation accuracy, so that I can print it later. I think this is fine. So in the try part, right, I have taken, let me actually control X this, right, try, pass, accept, and then I'm also gonna do it a pass. Okay. Tell me if you're gonna give me any indentation errors. No, you're not gonna give me indentation, except done. So except, I think we can run exception as any kind of error E, and I'm going to print the error as it is. I think error ERROR, error in the trial run. The exception that I got was something called for that particular trial. So for the index plus 1th trial, the error was E, right? The exception was E. And I would still let the code continue with the logic as it is, right? If the code runs as per expectation, I ran the model and I'm able to run the model. So wait, if my model runs for a specific number of time, okay, and I am able to map it. So wait, the dimensions map. So wait, so let me take try and accept, and let me move it to a proper indentation of if, right? So let's say define for I in range of a specific kind of trial. We have a value of pass here. Let me just pass it down here. And am I at the indentation of pass? Okay, I'm at the indentation of the pass. So when I ran the model here, the try and the accept are at the proper indentation. Let me print at E and let me print continue as it is, right? So try runs the model. Let me also make sure that the model is in the right indentation. History is in the indentation, val, results, and accept. So once the model runs, I'm going to make sure that this model runs. Verbose is equal to 1. Validation accuracy is done. And I am making sure that my model returns at a specific index. So once this thing is done, we come over here, we go back, Control Z, to one indentation right, and we return the results. So if I return the results, this will give me the results as it is. If I run it, okay, params are fine, print trials are fine. So I'm gonna try the model for this validation accuracy, for this result, acceptation are done, fine. This is fine. So if I run, so let's say search underscore results is equal to, if I wanna try random search for 8 trials. What is the warning? I think I can let go of the warnings, right? Let me import warnings. Wait, give me 1 second. Let's just ignore warnings for now. Import warnings, right? And I think warnings dot filter warnings. Warnings dot filter warnings. I want to ignore all kind of warnings, right? It will run at its own sweet time. So give me 1 second. How many trials are we going to run? Okay. So this is going to take a little time, my people. Just a second. It's going to take a little bit of time because 8 trials for all combinations plus 10 epochs. It's going to take a little bit of time. But I hope you guys got the logic that the idea of creating a helper function comes kind of realizing that, oh, I'm going to be passing the param values directly. So I kind of need sort of like a helper function later. So I will create a helper function. So did you understand that what am I doing here? We are doing 8 random searches, sort of like random trials for each individual permutation and combination, randomized in nature. Okay, no permutation of sorts, just randomized in nature, but I'm picking up all. Understanding what I'm trying to say? You guys got the logic, no? Like how it works, right? And now what it's going to do is, first trial it is running for the 10 epochs. It's going to save all the best results for that validation accuracy, whichever I have received, no? That validation accuracy will be saved in this value called result. Not just the validation accuracy, we are going to save all that value of the trial in the results list part, and then we are going to print it towards the end. So see, this is trial number 2. Can you see here? We have only implemented one trial. We have just moved to trial number 2. This should take a little bit time for all the trials to run. I should have actually printed the end and the start time also. So wait. Let me also import time, right? So how long does it take between trials? So let us actually try from all the trials, right? So start is equal to time dot time, okay? And once the accept thing is done, let me also do at the try end is equal to time dot time. So time elapsed, I can also return time is equal to overall time is equal to print f double quotes of time elapsed, okay, is going to be ed, take a bracket, end minus start seconds, okay, end minus start seconds. So something like this, I can map for both the try and accept, but let the trial run for a second. So wait, is it still at epoch true? Okay, it's still at trial 2. Let it take some time, but at least we'll get an idea for 10 epochs, how does it perform? Because if I take a 3 epoch or a 5 epoch, it might not give me the answer that I'm expecting. Understanding? It will become like a toy program. It's of no use. It's not giving me any important information of sorts that I wanted. So let's just see how it does. We are already at third trial. I'm assuming it's taking a portion of ourselves, right? Tell me everybody, did we not run every single trial here in sequence? I am trying every single trial in sequence. Could I have made this parallel? Could I have done parallelization here where I get the values of all the 8 trials and all 8 trials run parallel? Yes, you can do this using a library called Ray. Have you heard of it? Ray is another library that can help you perform multiprocessing and multi-threading to some extent well. The problem in Python is we have something called GIL lock. Have you heard of this? If not, it's okay. If not, then I'm not going to get into it, but it's all right. I mean, just remember that Python doesn't actually do multi-threading the way it is supposed to. It's faking it. It's trying to lie to you on your face that I'm doing multiprocessing, but it doesn't actually perform multiprocessing. Okay, so to navigate that, we have a library called Ray that helps us to a certain extent. Okay, at what value are we? We are at a trial number 8. Okay. So basically I ran the result. Each trial is running for 10 epochs. So you can see here what type of model was chosen randomly. It was chosen an RNN with an embedding dim 128, units 32, dropout rate 0.3 and learning rate 0.01. I have tried multiple different random trials, and if you can see here, I have trial number 3 right here, right? If I scroll further down, I have trial number 4. I'm also sort of printing the validation accuracy because I want to be later on be sure about which one do I choose, right? Like which model out of all the random models that I have created, which one do I choose for my performance. So we have trial and the validation accuracy. So for trial number 4, this one will be the validation accuracy. For trial number 5, this one will be the validation accuracy, and so on and so forth. And I was able to basically run all the 8 trials. If you can see here, the last trial that I have run is the 8th trial. And here in the 8th trial, I was able to get all the results, all the random results for all the models and all the hyperparameters to be given to me. But see, what I want to do is I want to make sure I find out the best parameter, right? So my intentions are, I don't want to go through all the parameters by myself. I want to find the best parameter myself, right? I want to find the best parameter, right, by myself. Now, why do you need to do this? Is because there is one advice that is given to data scientists, but not frequently. And that is, whenever you build any model, okay, you do not build the model in terms of accuracy. You should always build the model in terms of scalability, right? Example, I'll give you a simple example. A very famous computer scientist very recently tweeted about this fact that in his interviews, he asks students or his panel, his candidates about, if I have to run a machine learning model on a 25 million data set, right? Would you choose logistic regression as a classification model? Would you choose XGBoost as a classification model, or would you choose categorical boost or cat boost as a classification model, right? So he tweeted this question about how in interviews he likes to ask people about, if you have a very large data set, right? And if I want to run nothing complicated but simple machine learning models like logistic regression, XGBoost or cat boost, which one will you prefer, right? And he showed an entire analysis that logistic regression would work out very well in the favor in terms of scalability, right? Because XGBoost may be very well accurate, categorical boost or cat boost may be accurate, but the amount of processing and the memory they take is going to consume a little bit on an extensive side. So he gave a very good example of when would be the right choice to use logistic regression for an example, XGBoost for an example, and categorical boost for an example. Using the same scenario and analysis, right? If I have not done 8 trials, but let's say I have a lot of GPU space and I ended up doing something called 100 trials, it does not make sense for me to go through the entire analysis by myself and check it. Which one is the issue, which one is going to be the best particular model? No, I want to be able to print that model myself. So I already have the variable by the name search results. So what am I going to do? I'm going to check whether search results are completely full or not empty or non-empty, right? The best result that I will have is going to find out the maximum value of search results. Okay, within search results, what I'm going to do, I'm going to take my key as a lambda function. I'm very sure all of you know what a lambda function is. In Python, so far you must have understood that what lambda functions are, right? These are anonymous functions. You don't necessarily need to declare them the way other things are declared. You just write it down and it works, right? Now, what I want to do is, on the basis of validation accuracy, whichever returns the highest or the maximum validation accuracy, I want to return them, right? For all the trials that I have run, I just want to make sure that I return for a validation accuracy, whichever model has performed the best. But we can do better, right? We can perform even better search results, okay? For now, we want to print all the results. So I have already calculated something called best results. This is going to take up the value called validation accuracy from my entire array, and it will print the best result in terms of accuracy. But I don't just want accuracy, I also want the parameters to be printed, okay? Or maybe I want a proper formatted version of it. So how do I do that? I'm going to say print, just for your understanding, I'm going to say random, okay? Random search results, okay? What I'm going to do here is, for result, okay, for result in search results, I'm going to take the entire search results answer. The trials that I have run will be nothing but for all individual value of result, I'm going to print my trial values. Make sense? Not a very complicated problem. Accuracy would be equal to result of course, I want to print accuracy. So I'm going to print my validation accuracy for all individual loops. So I'm going to print my validation accuracy here. What is the model type that you were using to run those specific trials? So inside the result block, if you observe carefully, you actually have to go inside the array which you have declared in the top called params. You have already declared an array, a dictionary called params. What I'm going to do here is, for those dictionaries, what I'm going to do for a specific type of params that I'm printing, so PARAMS params, I want to print the model type. So what do? We go over here and whatever key we have given for model type, we will copy exactly that key. So we will copy this, we will come over to the bottom and I'm going to print the model type. So what does these line or these 3 lines of code are going to do? For every single iteration or random search I have run in my search results variable, it is going to give me the value of the trial. It's going to give me the value of the accuracy. It's also going to give me the model type. Once these are done, I want to print them as nicely as possible, as neatly as possible for me to do my analysis in the future. So I will say print f of, you of course will use format strings. You're going to say trial. Which trial did you implement? So it was trial number 1. So let's say trial, whichever trial it was, trial number 1, trial number 2, whatever it is. I'm going to take my model type, which is going to be the model type. And for simplicity reasons, I'm going to make it upper, right? To print in capital letters what the model was, which model version or type have I run, and for that model type, what has been my accuracy like? And accuracy will be printed like this, ACC. So now that I have made sure that I am printing every single version of the trial that my model has run for, my model type, and at the same time the accuracy for that given specific model. Let's see why it is giving yellow. Okay, wait, give me a second. Trial IL, right? This is the version. Yeah. Okay, so TRIAL, it should be this, right? IAL, trial. This is the right spelling of it. Okay. Once the values are looped, I am specifically running through a specific configuration for me to test it out. I'm going to come out of the indentation in the for loop and I'm going to print for all versions of the values that I've just extracted. I'm going to print my trial. So which trial has given me the right answer? So I'm going to take the best result, this particular best result, and for that best result, the trial that I have run. Let me just very quickly check that the variant I have written is going to be trial, right? So wait, give me a second. I usually, yeah, so I have given it like this. TRAIL, right? So I have given it like this. I'm just going to maintain it like that. Okay, I'm just going to maintain it like this. I'm going to maintain the same thing like this. We can fix it from the variable side. Okay. So we have the best possible trial for the model. Okay, that's good. What are the parameters that I'm going to print for the model? So the parameters would be the RNN that I have run. So let me take like this. What was the last model that I ran? Best results I have taken at PARAMS, right? Give me 1 second. Let me just copy this. And I'm going to pass in like this. I'm going to say the best result would be with respect to the params I'm holding. So this is fine. This was for my finer RNN that I ran. Okay, fine. And print would be validation accuracy. So I'm going to print validation accuracy and I'm going to have the same accuracy as best results. And for the best results, I'm going to have the val accuracy, which is going to be the same thing. Let me copy it here and let me paste it here, right? What this does is it's going to give you the difference between or the results for all possible trials that I have run, all possible parameters that I have run, and all possible validation accuracy that I have run. So if I run this specific model, see, trial 1, I was running RNN, accuracy is 0.790. Trial 2 was LSTM, the accuracy was 0.91. Trial 3 was an RNN and the accuracy was 0.54. Trial 4 was an RNN, again it was 0.66, 0.89, 0.90, 0.91 and 0.56. Among all these models, which trial worked out in my favor? Like I have received or gotten a better response? Would it be a trial 1 of 0.91 model, sorry, trial 2 of a 0.9180 model? If you can see here, the parameter here is going to be trial 2. So let me just run it like this /n. So this would be a better result. Okay. So here you can see trial 2. And of course, if you observe carefully, RNNs throughout have not performed that well, right? Even with some of the random hyperparameters. Of course, I know I have not optimized it for all the right reasons, but for certain reasons, the RNN's performance hasn't been that great over a period of time, correct? Right or not? So I haven't gotten that great of results with RNN, but of course, LSTMs did a good job. If you understand one other thing, you know what? RNNs did not do a good job because they were a single unit RNN. So basically 64 units of RNNs and they were singly stacked. If I would take stacked RNNs, they would have performed better than your simple RNNs. And if I would have taken by LSTM models, they would have performed better than the LSTM models. But our intention is not to check the variants of LSTMs or RNN. Our goal or intention is to first understand basic principles. So what did we do so far, everyone? For the random results that we ran on all the trials, am I making sure that all values are printed? For all specific trials that I have run, I want to make sure that I print all specific values and make sure that these values are used and shown to the user that look, the model type that you ran was an LSTM model, the embedding dim was 64. Of course, the unit size was 32, dropout was 0.3 and learning rate is 0.01. So, of course, one other key factor I forgot to mention everybody was one other thing. My people, to make your randomized version work even better, I recommend you use the param grid a little bit more extensive. What I say by extensive is, see here, I have only mentioned couple of values like 0.01 and 0.001 and 0.1 and 0.30 and 0.50, right? Once you got the answer that the most optimized version of it is 0.30, right? If you can see here, 0.30, you can even try somewhat between 0.3 and 0.4. See if any value is kind of popping up in between, maybe 0.35 if you want to even further optimize. But remember one thing, my people, optimization doesn't mean you go crazy for optimization. If the improvement in the model is not even 1% and you had to do a lot of pre-processing, do you think the effort of you to increase the model's performance by 1% should be included? Like for example, the effort you want to put for the model to raise itself to 1% accuracy, do you think it's a great choice? Or would you prefer doing it like, say you are a data scientist, right? You had to go through a lot of optimization, lot of grid search, lot of different calculations in order for your model to go from 89% to 90%. Would you do the hard work of doing this? What do you guys think? Would you do that? What would be considered significant? Depends on the use case. Okay, let's say finance data. Super serious, complicated 1% use case. Tell me, what would you do? Would you take a chance for a 1% increment in the case? Like, would it be worthwhile your effort? Right? Okay. Tell me one thing. A 1% gain, okay, a 1% model accuracies gain, depending on the size of the data, could it mean that hundreds or probably 1,000 people are now being classified correctly? that a 1% gain could possibly mean that maybe 1,000 people are now being classified correctly, right? See, you have to take this decision depending on your business problem or your business goal, okay? Not every single business is looking for accuracy. Remember this. I'm telling you this right now. Not every business is aimed at looking for accuracy. Understood? So depends on your business problem. If your superiors or your seniors think a 1% gain is significant to their business, do it. I cannot tell you that it is either significant or not significant, because there is no proper definition to this particular thing. Like, should you call it significant? Okay, fine. Chalo, let's do that. Let's do that. Okay, chalo, theek hai. So what we are going to do is, once we have analyzed that this is my best possible model, what do? We directly going to go and again check for search results. Now, what am I doing here, my people, is I am going to train my final best model. Okay, whatever is my final best model, I'm going to make sure that I'm going to do that final training very, very well. Okay, so in case if I want to do that, I already have the model available for me, right? I already have the model that was given to me by my random trials, which I have already printed. Now, in order for me to run that specific model, what I'm going to do is I'm going to train that model with the configuration, and I'm also going to add something called model checkpointing. Okay. So see guys, what happens is every single time you work on Jupyter Notebook or you work on Google Colab, you have to rerun your cell every single time. What I want to do is I want to keep something called callbacks and checkpoints. What callbacks and checkpoints will do is basically think of it like this, right? I want to show you and teach you two concepts. One is called early stopping, okay? And the second concept is called model checkpoint, okay? What does early stopping do? Early stopping is basically if my model is fully trained or tuned, okay, let's think of it like this, right? Let's say I have told my model to run for 500 epochs, okay? And in 500 epochs, my model has learned everything perfectly in 200. Will I not waste time in the extra 300 epochs? My model will keep going on and on and on and on and waste my time, right? So what I do is, if my model performance is not increasing over a period of time, or loss is not decreasing over a period of time, like for example, loss comes down like this, like this, like this, like this, like this, but after this it has become very, very steady. So tell me, my people, from here to here, is my loss decreasing significantly? Yeah, is it like fully significantly decreasing? No. So what we do is we use a concept called early stopping. Remember, whenever you're going to be working in production, you will have to use early stopping. Okay, so whenever you're going to be working with production level code, right, when you train your model, remember, you don't upload your deep learning code online on the server. It's the model you save, you upload. Okay, just remember that. So what do? We use early stopping so that if my model has reached a certain saturation, I stop the model and save the model. This is what we call as early stopping. So I'm going to show you early stopping. Next thing is called model checkpoint. My people, think of it like this, right? Have you ever worked on a Microsoft Excel file where if you have written 5-6 more cells, you will save it, you will press Control plus S, Control plus S, Control plus S many times? Control save, Control save, Control save, fearing that your effort or your data may not be lost. If you keep editing the Excel file, say after a days, after days, after days, do you do something called Control plus save? In my neural network, if I have run the model, don't you think after a specific iteration, I need to save the model so that I don't have to rerun the model from the beginning? You're getting what I'm trying to say, right? Model checkpoints are basically a way of saving your efforts in the model version. Or when you're running the model, you make sure that whatever you have run so far are not, how do I say this, are not going to waste. You're basically saving them. So two concepts we are going to be implementing. Okay, one is going to be called as early stopping, and the other is going to be model checkpoints load. Okay, so how do we do that? First thing, we check for whether search results exist or not, right? So for in our example, search results do exist. This is a true condition. We already have calculated that the best params, okay, best underscore PARAMS is equal to nothing but the best result And in the result, I want to click my params or write down my params. This is going to give me the best params. Now, just for your understanding, you can even print this saying that, hey, the best parameters that you have loaded from the models are these for your visual representation. Now, what do we do next? We jump to creating, okay, the model of our choice. So best underscore model is equal to, you run something called create model, okay, create a model with params, right? If you can see here, I have named the function at the top called create model with param here. So if you can see here, create models with param, I'm going to call that specific function once again. But what I'm going to do is inside this function, I'm going to pass all the best parameter arguments, which is going to be this one. Now, how do you pass that is as a keyword argument. So what will I do? I'm going to pass it like a best params. So here, my best underscore params that has been extracted, I'm going to pass it to the best particular model here. And my model is going to run with exactly those values. Okay. Now, once you do that, right after you create the model, my people, remember this is how step by step you should be taking your approach. So step number 1 should be creating the model. Right after you create the model, let's do step number 2. Right after creation of the model, you need to set up your callback mechanisms. Okay. Sir, what are callbacks? I'm going to write it down like this. Callbacks equals to, now in case if you want to implement something called model callbacks, you actually have to import the callbacks. Your callbacks are not readily available for you to just run whenever you want to run them. Okay. Remember, if you want to run callbacks in TensorFlow, we have a way of calling them. So what you need to do is from TensorFlow, this is going to be like my base package. Okay. From TensorFlow, I'm going to have a submodule called Keras, which I have used. We have a variant or a submodule called callbacks. Inside the callbacks, I'm going to import two things. One is going to be called as early stopping, and the other is going to be called as a model checkpoint. Okay. So these are the two things that I'm going to be making sure I'm going to import. So let me copy this, Control X, come over here, write a piece of code, implement this, and now go back to the top. And in the callbacks part, what I'm going to do, my people, is I'm going to expand this because I'm going to be writing a lot of things in between. So the first thing I'm going to write here is going to be called as a model checkpoint. Okay. In the model checkpoint, what do you want to save the model as? Okay, now my people, this is a point which you have to be very, very careful about. Okay. There are various ways to save a model. One of the ways is something called as a pickle file. The second way is called HDF5 files. And the third version is called .keras file. Okay. Now my people, remember one thing. These are the three ways you can save the file. The extension of .pickle file is .pkl. Extension of .hd5 is .h5 and .keras is .keras itself. What it means is, whatever is your model, okay, I am going to save my model as my underscore model dot pkl. Haven't you ever saved your data as a dot pdf file, dot excel file, dot csv file, dot txt file, which can be read by a human being? You can save the machine learning models, your deep learning models, in a format called .pickle, .h5 and .keras. Now, what do you mean by these concepts? My people, these are binary files. What do you mean by binary files? Your zeros and ones, your binary files. Tell me this. In your deep learning model, okay, if you have taken a deep learning model like this, a simple perceptron like this, and when you run the machine learning model or a deep learning model like this, when you call learning, what is the learning in this particular model? Can I say weights and the biases are the ones that I can call as the learned value, right? Your weights and the biases are the ones that cause your model to perform in a certain way, the behavior. So remember, in your pickle files and in your HDF5, in your Keras files, you are going to be serializing your weights values, your hidden state values, and every other metadata that is available. So what do I do? What do you want to name this? You can name this as best underscore Amazon, right? Underscore sentiment dot h5, right? This is how you're going to be saving your model. But now you are saving this model with a specific name. What is the extension that I have used here? I have used an extension called .h5. Okay. Now what I'm going to do here is I am also going to write one more variable or one more argument actually inside this called monitor. Okay. What am I going to monitor for this model checkpoint or the callback to work is I am going to check my consistent validation accuracy. What I'm going to do is my validation accuracy becoming stagnant at a certain level or not? Okay. So I am not going to add anything like patience here. I'm just going to add something called monitor is equal to my validation accuracy. I am also going to use something called save underscore best underscore only. Okay. Save best only. Okay. ONLY is equal to, I'm going to pass something called true. Now see guys, what is save best only meaning? Whenever you run your deep learning model or any deep learning model, be it your CNNs, your RNNs or anything, every single time a portion of the metadata is saved automatically, whether you use TensorFlow, PyTorch, Keras, whatever you use, it saves all the logs of that file. Save best only requires you to save the most recent updated version in the model. Whichever value or logic or log was available for that model, we take that version and we pass it to the model. So we take that and we save the best only version. It can also happen that the recent version and the previous version has the best model at the second time. So it will revisit the last 7-8 logs. Whichever is the best, it will pick that up and it will save your model as that. Okay. What we are also going to do is we are going to take a version called mode and we are going to pass in a parameter called max. And in a second, I will explain what that is. And verbose will be equal to 1. So see what I did here is I have taken a specific callback method where I'm passing something called model checkpoint. My model checkpoint is only and only going to save the model at these arguments if the model checkpoints or the behavior of the model follows these arguments well. If you want to use something called early stopping, which is stop my model if there is no improvement, then you have to call early stopping separately. Understood? You cannot call model checkpoint and model checkpoint will also take up the responsibility of that. That's not true. So in early stopping, you pass the same exact thing. Now tell me one thing, guys. In your model checkpoint, you are checking for validation accuracy. That makes sense. But if you want to stop your model, usually what do you want to monitor? If you want to monitor whether my model is improving or not, do I not check for something called loss? If my loss is not consistently decreasing further, that means my accuracy is not going to grow, meaning my model is not learning anything. So can I say some kind of a validation loss? Understanding what I'm trying to say? Consistently measure whether my loss is decreasing or not. How many values of loss do you want to check, my people? Suppose my loss was 0.619, 0.6188, 0.6123, 0.6011. Tell me one thing. Would I call this loss to be incrementally or the loss decreasing consistently throughout, like significant loss decrement? No, right? So tell me, if I want my model to stop here, can I check for 3 size or 3 windows? If up to 3 windows, the model does not decrease in its loss, I will stop my model. Can I do this? Can this become my stopping condition, everyone? That I will stop at this particular value. I will check for the 3 losses consecutively if they decrease or not. If they decrease, good. If they are not decreasing for 3 consecutive values, I'm going to stop the model. We call that parameter as patience. Okay. So what do we do in patience is we will put patience equals to 3. What will this mean? Consecutively, if my model is not giving me any better answer, I'm just gonna make sure the value is gonna be returned or my model is gonna stop. Because you're implementing callbacks, like early stopping, you need to not save best only, you need to restore the model. So what do? We have something called restore. If I remember it correctly, is it restore best weight or weights? Give me one second. Let me just check the wait. Give me one second. Is it restore best weights? I'm assuming, right? Callbacks is callback, sequential, this is fine. Where is the restore? Wait, give me 1 minute. Early stopping, restore best weights. Let me just check it once quickly. Restore best weights. Yeah, so this is S, right? Let me come over here. Let me paste restore best weights will be equal to true. Sometimes I get confused in the syntaxes because the syntaxes I don't remember. Sometimes it is best weight, best weights. It has weird syntaxes. I know it seems like weights makes more sense because we are doing a lot of training, but you haven't worked on PyTorch yet. So once you do that, you will start crying. So you will know why I am facing problems like that. Anyways, so what did I do so far? Is I checked whether my search result part is empty or not. Once that happens, I'm going to check for my best param values. I'm going to extract something called best param. I'm going to pass it to the create model with params. I'm going to run something called my best model. But before running the best model, I'm going to implement a callback mechanism and an early stopping mechanism. Okay. Now, my people, please understand, you do not have the same model checkpoint and early stopping mechanisms for every single neural network. Please remember, do check that for a certain type of neural networks, early stoppings are not usually the same, they are different. Specifically for any kind of restricted Boltzmann machine, if you are implementing any kind of a unified or unidirected graph neural networks by any chance, if you're implementing, they will be slightly different in their syntaxes. So just be careful about that, okay? Now, I'm going to run something called as my final history of the model, okay? So I'm going to say final history is equal to the best model, which is this particular model, dot fit. Now tell me, in the fit part, do I pass something called x train? So x underscore train is going to be passed, right? I am also going to be passing something called y underscore train. I am also going to pass the batch size SIZE is equal to, let's only give it 128 because we've kept it consistently throughout. I'm not sure if I want to keep the epochs to 10. So I'm only going to keep the epochs to 3 because I want it to run faster. I don't want to take it more time. And validation underscore split will be equal to, let's give it the same 0.20. And the callbacks that I want to implement, C8 is equal to, I want to write down the same callbacks I have written here, right? So I'm going to take the callbacks here. I'm going to copy them and I'm going to paste them here. So the callbacks mechanism that I want to implement is going to remain the same it is. So if I run this particular model, what is it going to do? It is going to run my final model, and every single version which is available in the best history is going to run. But there is one small thing I want you all to do and not miss it. See here, when you ran the entire model, okay, you are also going to save the tokenizer of the model. Now, like for example, why do we need to save the tokenizer? Because every single time you run the model, I want to save this model and use the tokenizer also as some kind of a pickle file or an HDFE file and load it. I don't want to load my tokenizer again from the TensorFlow package. Making sure that reusability is at the highest, what will I do? I am going to write down with open. What will I name the file? Amazon underscore, what did we name? Best Amazon sentiment, right? So best underscore Amazon underscore sentiment, right? Sentiment dot pkl. If you write something in a pickle file and you know it is a binary file, you're going to write something called WB. WB's full form is write binary as something called F. Now what I do is I haven't imported another package called pickle. Remember, if you want to save something in a pickle file, you actually have to import pickle. So what will I do here? With this particular part, I'm also going to import something called pickle, right? Import pickle, pickle, right? That's correct. So what will I do here is I'm going to come over here. I'm going to call something called pickle dot dump. I'm going to save all that data. What will be the name of the file? It's going to be the tokenizer that I have used early for a file size F. What this does is for every single model that I have run, it's going to save all my best model with the callback. It's also going to save the tokenizer. If this does not work in the else condition, so if you can see here, I have taken an if condition here. Else, if there is any other problem in my model, I'm going to just print out something called error. Okay, ERROR, error. I'm going to run this. So if you can see here, my epochs have started running. I'm running the first epoch. My accuracy will not be that great because I'm only running for 3 epochs. So epoch number 1, right? Epoch number 2. If you can see here, Keras saving.save model, you can actually ignore this. This warnings don't make much sense. So epoch number 3, let's just hope this runs. Okay. Let us run this and let's open up the file type. Okay, this is run. If you open up your Google Colab file type, do you see 2 things have been saved so far? Your best Amazon sentiment model has been saved in a file called bestamazonsentiment.h5, and your tokenizer is saved as bestamazonsentiment.pkl. Understood, guys? So you have taken your tokenizer as per the problem that we have, and we've also taken the model in the H5 variant as it is. Now, once the model is saved, tell me a small kind of important update for all of you. When you run your entire deep learning model, do you think you upload your model to your server, or do you save the deep learning model to your server? Which version do you upload it to your server? Like, how are customers able to enjoy the deep learning or the machine learning based systems you build? Every single file or the script that I wrote for deep learning model up till I saved the model, are you ever going to use it for production? Or is it only for your analysis and model building? Everybody, did you understand one very important factor, that model building is not what you're going to be implementing on the server, right? You're not going to be giving your code away to somebody who runs it on a server, right? You are going to be giving the code to either a data engineer or a DevOps engineer to run the pipeline, save the model, and that model eventually will be loaded. So where have we saved the model, everyone? Did we save the model as the best Amazon sentiment.h5? This is the name of my model. So tell me, if I want to load this model, okay, I don't want to use any of my model that has run in the server or on this particular Jupyter notebook file. I want to load the saved model that I have taken, load the saved model and run accordingly. Okay, run as per the model that I have loaded. So what do I do? Loaded underscore model is equal to, now here you have a method called load model. Okay, because I have not imported anything called load model, what I'm going to do here, I'm going to go over to the top, or maybe I'm just going to import it here directly. See, load model is a part of the package called as sequential. So I'm sure I have taken it in the top, but I'm going to just take it again. Okay, from TensorFlow, TensorFlow.Keras, okay, from TensorFlow.Keras. In this load file, I think we have something called .models. Yeah, this is correct. Import something called as load model. So I'm going to call something called load model here. And inside the load model part, what was the name of your file that you have saved? I'm going to copy this. I'm going to come over here and I'm just going to take copy path. You don't need the path, actually. You just need the name of the file. You can remove this content and slash and slash and slash. You don't need to necessarily mention it like that. It can directly accept it. This is the name of the model that I have taken. Okay. Now you need to read that file. You have only loaded it so far. You haven't read that file. So with open, I can open any package, any part with the with part. So with open, what will I load? I am also going to load my tokenizer, which is the tokenizer. Let me copy this tokenizer here. Let me also paste the tokenizer. Give me 1 second. Let me open that up. What I'm going to do here is, specifically for the pickle file, I'm going to write something called RB. RB means read binary. I'm going to take the binary version of it and I'm going to load it. Okay. So making sure I read whatever binary file has been loaded, I'm going to read this. And you have to be very careful with the WB, RB, B, W. There are many variants of it. Okay. So you need to be very, very sure how you do it. I'm going to take this as a file called F. and I'm going to say loaded underscore tokenizer is equal to pickle.load. I'm going to load something called as the F file. So what I've done here, my people, is I have done two things. I have loaded the model. I have also loaded the tokenizer. Okay. The tokenizer. I have loaded two things. For me to be sure that my model has been loaded properly or not, I can also give some kind of a message in the beginning for the user that the model has been loaded. Okay. Compile the loaded model, but the compiled matrix have yet to be built. It's okay. We don't have to worry about it, right? What did we do? We have loaded the model. We made sure that the models ran. But here is the thing. Once you have run the model and you have saved the model, now you have loaded the model. I want to make some predictions on a given text or some kind of a text I want to do, and I want to make sure that my model works perfectly or not, right? If you want to do that, then the steps of doing that are slightly different. They are not the same, but they will be slightly different because here, I'm sure in machine learning, you must have learned of different methods like predicted probability, and predict method, right? So for example, if I say y underscore pred underscore probability, okay? If you want to print out every single model's probability, can I load the model called loaded model dot predict? Now, if you know this from machine learning, you can pass in all your X test data, and once you load this, it will give me all the predicted probability for all the values of X test, right? But my ypred, as you guys know, is a categorical variable, which is a binary class, right? So if my ypred, okay, probability is greater than 0.5, am I deciding a threshold for this particular precision? Anything greater than 0.5, then give me some answer. If it is less than 0.5, give me some answer, right? If my values of my ypred is going to have a probability greater than 0.5, I'm going to convert this into an as type, okay, of int. What does this do? And also, if I do something called dot flatten, okay, what is this piece of code going to do anyway? It's a very simple function, not a very, sorry, it's a very simple method. It's not going to be complicated to understand, but are you getting what ypred is going to do in this particular example? Is going to give me every specific value of ypred, okay, for values greater than 0.5 dot as type int and dot flatten. I'm sure you guys know what flatten does. Flatten as a function does. What do it do? If you take a nested, a multi-dimensional array, you can do something called flattening of the array, right? Like it will convert everything into one single dimension, be it 8D, 2D, 4D, 100D, 60D. Multiple different nested lists are converted into simple type. So first of all, every single value of probability is going to be converted into bool. I'm going to convert that into 1 and 0, and then I'm going to convert that into that particular value. Okay. Why don't we do argmax? The reason I don't want to do argmax is because argmax is going to return the maximum value from the entire list. My conversion doesn't work like that. My conversion works when I do something called greater or lesser, it returns something called as a bool value, right? It will return like this, no? True, false, true, true, false. I need to convert my true, false into 0 or 1, 0, 1, 1, 0. Understanding what I'm trying to say? I don't want to do argmax directly on it. I want to first take the bool values because this part of the code is going to give me what? A bool, no? That bool needs to be converted into numbers, zeros and ones, the binaries, and that binary needs to be converted into one single array so that I can extract values from it whenever I want. So that change I want in my code. I want that capacity and the capability to be run. So once that particular thing done, or once this model, versioning is done, what do we do next? Ypred is taken. What do we do next? We calculate something called as the test accuracy. Because I am passing what data here? I am passing X test data. Agree, disagree? So what will be my test accuracy? In your machine learning code, I'm sure you guys were taught a method called accuracy score. So if you remember from sklearn, you imported confusion matrix, classification report and stuff like that. If you remember from sklearn, right? From sklearn.metrics, right? In one of the, this does not autocomplete, is it? Okay. From sklearn.metrics, we import multiple items. If you are doing binary classification, one of this is a confusion matrix, if you remember. Confusion matrix is one of them. We also have something called classification report. If you have classification report, pretty much you're sorted. And there is also something called accuracy score. We have done this all the time we ran machine learning, right? Your support vector machines and your, logistic regression and your decision trees and your random forest, right? So test accuracy. I'm going to say that your test accuracy is nothing but the accuracy score of what? Don't we compare y test with y pred? Don't we test our value with y pred? So if you can see here, my y test and my y pred is printed. So if I just go ahead and print, my test accuracy is going to be what? I'm going to copy this, I'm going to paste it here, and I'm going to paste it here. What will be my, oh, okay, it's going to take some time because it's a larger data set. On test, I think it was something. On my test data, what is my accuracy? How many am I able to map back? At a 91%? If I print or plot its confusion matrix, will I be able to get a detailed analysis? True positive, true negative, false positive, false negative, all of that stuff. Okay. Let's take some sentences. Okay. Sentences is equal to. Okay. All right. Okay, cool. So now what we've done is we have taken multiple different test sentences. Can you see here? The packaging was nice, but the product tested was not to my liking. The customer service was excellent, but they were helpful and responsive to my questions. And now we have this third weird looking data where you have asked data like this. Now everyone tell me this. If I want to make a prediction, do I have to clean my data also? Because when I trained my deep learning model, I have cleaned the data and passed it to the data, correct? Like my model. I did data cleaning and I have passed it, correct? Correct? All right, good. Okay. So tell me, if I want to predict underscore sentiment from the model, okay? So sentiment from the model, how do I do it? Can I pass in something called text? Yeah. I'm going to be taking every single kind of text. I am going to be passing it to my model and I'm going to make sure that that text is going through a process. Now tell me, how do I clean my text or how do I make sure I have a cleaner text? If you go to the top variant of the version, okay, we have a small function written here called clean text. If I come over here, if you remember, we built it with all the hard work that we had to do. We scroll a little bit down, right? We scroll further down. Yeah. Do you have this method already written, some kind of a helper method called clean text? Yeah. Do we have a clean text part? So tell me, can I reuse this method called clean text? Come over here in the bottom. Here, what can I say? I can say my clean data is clean text and I will pass the text inside this. Once the text is converted, we need to convert it into sequence, right? We did that in our model also. So sequence is equal to, how do we do it? Whatever tokenizer you have loaded, the loaded tokenizer, you need to convert that into text to sequences. And inside this, pass in your data. But please make sure it needs to be in the format like this. Whenever you load any kind of tokenizer, my people, any kind of model loading also, no, please remember, you don't pass data directly in the argument directly straight. You have to pass it as a sort of like a sort of encapsulated in a open in a small bracket like a list. Now, once that is done, we also did something called padding if for data. So padded is equal to pad sequences. Okay, we are going to take something called pad sequences. We are going to pass the sequence of the data as it is. And we are going to take the max length of the data as the max length that we have taken in our model. So I think it was called max all capital, right? MAX underscore LEN, max length, right? And padding type is going to be of post. Now, if I do this, padding is done, sequence is done, cleaning is done. The next step would be to directly predict it. Now, what we do is just let me check whether the loaded model is passed here, right? So loaded model is gonna be, okay, so I'm gonna pass it directly. Okay, so I think this would be a nested array, right? So let's say probability, or give me 1 second, let me say probability is going to be equal to loaded underscore model, okay, dot predict. I'm gonna pass in the predict method for whatever padded sequence I have generated, padded padded. I am going to load method is usually nested. So let me see if this is correct. If not, I will remove one of the zeros. Okay. So the sentiment would be equal to, it would be positive. Okay. Let me say positive if the probability that I have generated is greater than, okay, you know what, actually I need to take thresh also, but let me take it here, 0.5, else it would be called as a negative sentiment for me to run on. And I am going to return both my sentiment, which is going to be generated, and I'm also going to return a probability, or prob, prob. So this is going to give me the sentiment and the probability for the model. So sentiment is passed, probability is passed. Okay, so this I am not sure. Not sure about. I think it is going to give me a nested array, but let me just check if this is correct. Okay. So what is the name of the test sentences? Test sentences. So for index, comma, sentence in enumerate, inside this I will pass the test sentences, okay, that I have taken. What do I do? So 0 is the packaging was nice, but the product was whatever it is, sentiment, comma, probability is equal to, I'm gonna pass something called predict sentiment, and inside this I'm gonna pass the sentence directly, and it's going to print for each individual sentence. So can I write it like this? For print f double quotes of the sentence that will start at I plus 1th index, because it starts at 0, my do I write it like a single quote? And let me write it like this. This is the name of the sentence. The one particular sentence is that sentence. And for that sentence, my prediction it will be, so prediction will be, I'm going to take that particular sentiment as it is. Then for that particular sentiment, I was able to generate a probability score of probability. So probability. Let me just copy the probability here and copy the probability here. Oh, yeah, this is loaded model. What was the name of the method? Loaded model, right? Give me 1 second. Not load model, right? Loaded model. This will go back to authentic, the original version of this. So let's run this once again. Let me just say tokenizer text to sequence is done, pad sequences are done, loaded model dot predict, positive if probability is greater than 0.5. So sentiment and probability is predict sentiment, sentence is passed, sentence I plus 1. Let me see if this is the answer. Wait, I understand what the problem was. See, here is the issue. We have taken test sentences, right? Let me write it down like this. Test sentences of index 0 is going to give me this particular value. See, the test sentences is an array that I have taken. If you can observe carefully, test sentences is an array that I have taken, correct or not? See here, if I just run this particular thing and come over to the bottom, I have taken this as an array. I'm going to write down test sentences as it is, right? If I print test sentences, it's an array part, right? Like if you can see here, if I print the type of it, it will be an array. Sorry, it will be a Python list. So if I just print type sentences here, it will be a Python list. Now, if I say the index 0, the packaging was nice, but the product test test was not to my liking. Now observe this, okay? I'm going to write 1, it's going to print. I'm going to write 2, it's going to print, okay? If I pass in the same exact thing here, if I write it down in the bottom like this, okay? What was the name of the method? Define predict sentiment, right? Let me copy this. Let me paste it here. And inside the predict sentiment, I'm going to pass the data as it is, right? So here the text is equal to test sentences of 2. Copy and paste here. Okay, I'm going to run this. See, did it still give me the answer? That's because what I did is I ran this particular function first before that. So it was not able to reference that first. So tell me, the last one is I expected my Bluetooth headphones to be great, but huge disappointment. No bass and a little high. It gives something called as negative. If I pass 1, can you call this sentiment as a usually positive sentiment? If I run this, what would this answer be? It's again giving negative. Why is everything negative? Because how many models did we run? 3. Every single version of this particular comment that you guys have given me, it is passing me all the values that is giving me is all wrong. It's giving me negative. If you say customer sentiment was negative, or sorry, the customer service was excellent, for at least this version 1, should it give me positive? If I removed a portion of the data, it is now giving me positive. If I give something like, say for example, the customer service was excellent, but not that great. So tell me, are you confusing the model, or maybe are you giving some kind of contradictory answers? If I run this once again and run this once again, what about now? Is it picking up not that great as a negative sentiment? Because at the end of the day, you predominantly focus more on the part that it is not that great. If I remove not that great or excellent, okay, or if I write something like the service, or the product, PRODUCT, was excellent, example, right? The product was excellent, or the item was excellent, or the product that you gave me was great. If I run this once again and run this once again it gives me positive. For a lesser epoch model, fine, it works. But for a variant where you have given something very, very large, so give me something which is somewhere in the line of positive but expanded in the form. Like, don't give me good, excellent, better yet. Give me something which is a little bit longer, but it means a positive sentiment. Can somebody give me a sentence like that? Like, for example, what if I pass it like this, right? Like I can say, I have observed that the products that I have received are to my preferences, are as per my preferences, and requirements, and I can not complain. Okay, I cannot complain. Okay, let's see if I can 0, 1, 2, 3, right? Did you understand? Like, I didn't want to mention anything good, great, excellent, best, perfect. I wanted to mention something which sounds very generic, but is a positive is a positive sentiment. So is it giving me a positive value here? We made sure, okay, you have loaded the data. This was the Amazon Fine Food Reviews data that we had. Okay. Once we loaded the data, we did some basic checks. We had to understand basic concepts like, okay, what does my data look like? We did some very basic EDA, like for example, making sure to get the answers in percentages with respect to 1-star review, 2-star review, 3-star review, 4-star review, 5-star review. We went ahead with that. We made sure all the sample reviews were done. We got the answers. We did some kind of data visualization. We kept the data ready because we wanted to print something like this. We wanted to print the rating distributions in the data to make sure we check for data imbalance. We also wanted to do the text length distribution because we wanted to see the actual value or the mean average for my text length distribution lies in which specific type of text length. We did that. We also did something called word count. Word count was done. We loaded that. We converted everything into a binary class because anything with multiple different classes, we have to go ahead with softmax and we have to do a couple of things differently. So in order to make it a little easy, because the goal was to make sure everybody understands what RNNs do and what LSTMs do. So Then after that, once we made sure that everything was converted into a binary class, we were checking for imbalance, we were handling imbalance, we were able to use some kind of a sampling technique. Specifically, we have downsampled our majority class and we made sure that we match it to minority so that they match, they are equal, right? And we were able to kind of take a sample out of it. We were able to clean the data. We were able to text a user text or a sentence. We were able to reduce the length of that sentence to a specific format, clean it basically, right? And once the clean data was available, we added it to the original data frame, not the original, a copy of the data frame called DF balanced, and we added it. Then we used tokenization, available already in TensorFlow. I made sure that I tokenized the input values for the training data, and anything which is out of vocabulary was given an OOV token or out of vocabulary token. We took the training data, the testing data, we sequenced it, we padded it. Once that sequence and padding was done, we were actually having a look at the data and the sequences, how they look like, what the padding does to our data, right? The main understanding of your recurrent neural network was this. Do not directly run your neural networks on a large data set. As mentioned, we imported every possible thing to create recurrent neural networks. Specifically, we have used something called the embedding layer, the simple RNN, the LSTM, the dropout, and the dense. We created the recurrent neural network. The logic was very simple. You have to first pass the data through some kind of an embedding layer that converts the data into an embedding of sorts. We then pass it to a simple RNN cell with 64 units. When I say 64 units, please don't think of it like your RNN unrolling into 64 unrolls, where basically your hidden length or your hidden state is of size 64. So all your knowledge and your representation of the language that you're trying to learn is imbibed or inculcated or is kind of added to this 64 sort of hidden state. So your knowledge and your learning are saved here. You can increase the size, decrease the size, whichever works in your favor. There is a false assumption in language modeling called context language modeling that larger the dense vector representation, better is the learning. That is actually not true. If that was true, then 8 billion parameter models and 3 billion distilled parameter models of LLMs would not have outperformed a 30 billion model, right? There are few differences. We have to understand them. Even though you kind of do quantization to the least amount of bit is, which is 1.58 bit. Llama.cpp does 1 bit, but truly it is not 1 bit. It has a lot of different variants to it. So remember, that doesn't necessarily mean that your token size, your representation has to be larger all the time. Sometimes they are enough depending on the problem you're trying to solve. Okay. You take a dropout layer, you take a dense activation, you make sure that you have like a fully connected layer, right? A sort of like a ANN towards the end of RNN, so that you're able to make sense of your data into categorization of binary class 1 or 0. We ran the RNN model, we gave it some kind of an optimizer. Of course, because it is going to be a classification problem, we are giving it a binary cross entropy, right? And once that is done, we were able to run the model. Once the model was run, we were able to kind of get like a the train accuracy on our data. We also plotted, we just wanted to get an understanding that validation versus test or validation versus this, how does the model perform, right? We printed that, we kind of got an understanding how the model's performance is over the period of, over multiple different epochs for both validation and training, both for losses and their accuracies. We have the plot. Of course, it is jumping weirdly between one place to other place because of the way we have trained the model. It's a very half-cooked work, but this was just to get an idea that, okay, is there a consistent improvement? Sometimes it happens that your data has a lot of noise. And when I say noise, please don't include that as an audio noise. Noise can also exist in the textual data, which may have not been caught by the data analyst or the data scientist in the beginning, which it could be Unicode characters, unnecessary characters, some slangs that are very, they are not frequent, but they definitely add certain uncertainty to my model. So there can also exist a certain kind of noise that can make my model's training behavior completely different. So remember, while working with a smaller data set, always make sure that the steps you have done before running the model are absolutely clear. You have not made any mistake. Once we did that, I made sure I also ran the LSTM model very similarly to how RNN models function. Pretty much this neural network is very easy to build in TensorFlow comparatively to building it in PyTorch. Uh, that's why actually one of the recommendations I give people is PyTorch is a brilliant framework to write your libraries, to write down your code, to write down any machine learning or deep learning code that you want to do. But predominantly people start with TensorFlow because it's easier to run, because what happens is the lowest form or lowest abstraction level where learning becomes very easy is Keras. Keras is a wrapper on top of TensorFlow. Then comes TensorFlow, because TensorFlow gives you different features or different types of modules to build on. And remember, of course, TensorFlow works completely differently and PyTorch works completely differently. There are two very completely different frameworks, the way they function and the way they operate, right? So in our case, of course, we have taken the help of Keras. We have built an LSTM model, the same exact thing. We have taken the embedding layer, the LSTM layer, the dropout layer, the same dense layer, and the dense layer 1, because we want the classification output to be 1 or 0. And we've written down the losses, and we've written down and we've printed the summary. Once we do that, of course, we train the LSTM also, sort of like run the LSTM model, we fit it, we try to see how it works. Of course, we also were able to see that how RNNs were able to perform on the training, validation, on training losses and validation accuracies and validation losses. We got the idea that the model is kind of showing an upward trend, which is great. Generally speaking, the model versus validation loss curve is supposed to be an inverse J curve. It is supposed to look like this. Remember, this is like the Bible, or how do I say this? The default. I wouldn't even call it default. The baseline to compare, right? The accuracy is supposed to improve over a period of epoch. The loss is supposed to decrease over a period of epoch. This is sort of like the ideal condition. That would be the right word, right? So we saw that it is improving, not a problem. We of course wanted to do hyperparameter tuning because we did not want to go ahead with grid search. We wanted to sort of create like a randomized version of it, which is not perfect. It has a lot of problems. Problem number one, random versions can also have duplicate values. Random numbers can also have a portion of it is which is also duplicate. So not just the entire value could be duplicate, but a portion of the random values could be RNN or dropout layer of the same, and the part of the variant could be different. So we've already done the processing. Why do we need to do it again, right? So this process or this problem will always exist. Worry not. Take the entire data as a data frame, deduplicate it on that, and run your random searches on the deduplicate data frames. It's very easy to convert a data frame into a NumPy array and then run the whole application faster. But anyways, we did not do this because that was not a necessity. We ran a param grid. These are all the parameters that I wanted to test for, that I wanted to check for, I wanted to run for. I ran the loop for the search space I'm going to look for. I'm going to print out all the combinations that I'm going to run. And I actually did not write my helper function first. I wrote down the values for printing out the random searches. So my search result told me that if you want to run 8 random trials, I will pick up random values from the param grid that you gave me for model type, embedding dim, units, dropout, and learning rate. And out of all the 40 plus combinations you have, I'm going to pick and choose the random 8 ones that I find convenient for me because it's completely random. I'm going to run all the random values, and it did run all the random values, where for every single trial, it gave me the validation accuracy, absolutely important, and the entire parameter type, that what did I run it on. We ran it on 10 epochs because this was sort of critical for us to decide what parameters are ideal for my data and for the type of model I want to run. So I ran all the 8 trials. Once all the 8 trials were run, I was able to kind of search for the best parameter by myself. I could have done a better job at writing this code because all I'm doing is mapping it again. But in TensorFlow, there is already a library or a module available that can save you a lot of time rather than writing this code. Okay, you can just directly use it. You don't need to run it code wise, but I wanted to give you guys a certain granularity that look, you do not have to heavily rely sometimes on the modules, because some processes are so simple that they can be implemented in Python very, very simply, right? We did that. We were able to import these two packages because it was helping me perform certain things. And those certain things are, I wanted to do early stopping. I wanted to do something called model checkpoints, where my model checkpoints for that specific model, whichever has run the best specific instance of that model, I want to save it. Number one. Number two, if my model is not performing or not improving over a period of time, since I've only taken epochs is equal to 3, this particular thing made no sense in the code. But let's say if you want to make the model's epoch say 500, right, then this piece of the code will give you the better clarity. Early stopping would then stop the model at maybe, I don't know, 50 epoch, maybe 60 epoch, I don't know, but it would not have let your time or your energy or your resources go waste, because it would stop my model after a certain instance, right? We of course fit the entire model. We get the final history of the model with all the parameters that we are passing. Basically the X train, the Y train, the batch size, the epoch, the validation split, and the callbacks that we want to use in the model. I of course save the tokenizer also, because while I save the model, it also becomes important to save the tokenizer, because that tokenizer has been trained on my specific instance of the data that I'm passed. Once that is done, I am also dumping that data in my particular instance. Now this runtime is gone, so I will not be able to run this code once again, but you get the idea. There was a folder here which was saving my pickle file. Once this pickle file was saved, I was able to kind of, have a, wait, is the runtime connected? Yeah, so we have it, that thank God. I think we saved the file someplace, right? We also were able to save the model, load the model. Once the model was loaded, the tokenizer was loaded, we wanted to make sure we get the answer of the probabilities to a certain limit, flatten the array because I want to compare the 5 pred later. We did that on X data set. We kind of calculated the test accuracy. This was very easy for us to calculate for the X particular text, because I wanted to compare my Y test with Y pred, and I wanted to give you an accuracy that, okay, how many zeros are matching with zeros, how many ones are matching with ones, how many zeros are misclassified as 1, and how many ones are misclassified as 0. I wanted these 4 instances to get me the test accuracy, which I got as 91%, right? I took a sample sentences called test sentences, and these test sentences were kind of able to give me some kind of a prediction or some kind of an answer that, hey, you know what? Your text needs to go through cleaning process. They need to be converted into sequence. They need to be padded. Very, very important. Please remember, when you did padding, I'm sure you guys know you did padding on your images also. To make sure your data representation comes in the middle, you also did padding towards the outer boundary. So everything became 0, 0, 0. So this is the model of RNN and LSTM that I ran. The next variant that I'm about to teach you right now, which is the seek to seek model, are a very important model for your generative AI application. Because tell me one thing, I'm sure you all use large language model daily in your life. Don't you give a one line text and your answer is like this big paragraph? You ask your chat GPT a small question, maybe in a 3-word graph, but it generates an answer in an entire paragraph. Tell me one thing, does this not represent some kind of a sequence to sequence mapping? Let me explain that. All of you have been very vocal about the fact that, sir, we did not understand any concept on encoder decoder model, correct? Sir, we had some trouble in understanding the encoder decoder model, and we want to get an understanding on how these encoder decoder model works. See, my people, your encoder decoder model's second name is what we call as a sec to sec model. Okay. We also call it sequence to sequence model. Okay. Now, I am going to introduce you to the concept of sequence to sequence. I'm going to teach you certain things that are a little bit advanced and complicated, but you kind of have to learn them. Okay. Like beam search, teacher forcing, reinforcement learning on human feedback. These are certain things that we are going to learn. DPO, PPO, LoRa, QLoRa, quantization, because these are going to be kind of important for your knowledge to be kind of mapped back into your generative AI skill. So we kind of learn about it one by one. Okay. So first of all, everyone, the information or understanding about, sir, what is an encoder decoder model do, and what do you mean by sec to sec or seek to seek model. So let's first actually learn about something called seek to seek model. Guys, when seek to seek model came, when I was, I think, only 2 years experienced as a data scientist, when I was working in a company, I think 2 3, I think comparatively that this was this was a phenomenal model that was making a big wave in the AI community, right? When the sequence to sequence models were actually implemented, right? So first of all, let's understand what is seek to seek model. Like, what is a sequence to sequence model? In sequence to sequence model, you will be able to understand how encoder decoder architecture works. Okay, first of all, I'm sure you guys know that there are basically data mappings available. Okay, there is something called data mapping. You need to understand how data mapping works. In every neural network, the goal itself is what you have called data mapping. Now, so what is data mapping? Tell me this. Do we have a neural network that looks like this? In your neural networks can be built to keep it very, very simple, that what we have in a neural network is what we call as a one-to-one mapping. In your recurrence or recurrent neural networks, apart from one-to-one mapping, how many different kind of mappings do we have in our data? One-to-one mapping, many-to-one mapping, right? Many-to-one mapping. We have something called many-to-many mapping. We have many-to-many mapping, right? One-to-many, many-to-one. We have multiple different kind of mapping. Tell me one thing. If you take one sequence or one text as a sequence, I love food, and your answer is also a sequence of food, like मुझे खाना बहुत पसंद है. Tell me one thing. You entered one sequence and your output was another sequence. So tell me one thing. The length of the sequence when you passed in was completely dynamic and variable, correct? But the output you got in the model was also dynamic and also was variable. I did not input three input as a sequence or a token, and did I get a 3 words or a 3 token as an output? No, right? My input sequence was completely different and my output sequence was completely different. So to build this specific kind of model, we had a model mapping created called sequence to sequence model. Okay. Now, sir, why do we use sequence to sequence mapping, and why is sequence to sequence mapping important for me? Remember, sequence to sequence mapping is important because if you want to do any kind of, let's say, if I give you an example, right? If you have a many to one sequence model, example, suppose if you have a many to one sequence model, right? It would look something like this. You have multiple different neurons, you have multiple different input, you have one output. Any kind of classification task you want to achieve, many to one sequence will be a great job. Super job for you, right? If you have one to many mapping, right? So if you have one to many mapper or one to many mapping, it would look something like this. You have one sequence and it maps to your multiple different output, right? Specific decoder models, okay, are using something called one to many mapping, right? When you had something called many to many mapping, so for example, if you had many to many mapping, it would look something like this: multiple neurons, multiple inputs, multiple outputs. See, if you did any kind of sequence labeling tasks, you would use something called many to many mapping. But many to one to many, and many to many, right? They are what we call as classical approaches to natural language processing. But when we started dealing with textual data, all the way from 1970s, when the first chatbot was built called Eliza, okay, from 1970s all the way to forward, researchers understood one thing, that somehow I need to figure out a way to do many to many mapping, where this many to many mapping is fixed. I pass in 3 input, I get 3 output, right? This is a fixed many to many mapper or many to many mapping algorithm or technique. But I want a many to many mapping where it is variable in nature, where it is dynamic in nature. If I give you set of 2 inputs, I not necessarily need 2 as an output also. It could be 3, it could be 4, it could be 5. The reason why this is important is because you need something called text summarization. Okay, I'm sure you guys know that your mails or your emails are nowadays summarized. You have an entire book summarized into one paragraph, one page, 5 page, 10 page, where you don't actually have to read the entire book, the entire email. It is summarized for convenience. You also have something called neural machine translation, or simply machine translation tasks, where you take one single language and you get an output into other language. Now, the problem with languages are many. I'm sure you guys know, I'm sure many people in this class know at least more than two languages. When you convert a language one into a language two, or one language into other language, do you see the context or the meaning of that language is lost in the conversion? In English, we have a sentence called lost in translation, right? We have a sentence that I want to convert. It gets lost in translation because the essence of the language is not transferred to the translated version. To solve this problem, we came up with an approach called NMT, okay, where you had something called sequence to sequence modeling. Now, if you want to do any kind of question answering, machine translation, if you want to do any kind of modeling like that, you needed a solid foundation to convert anything like that. Now, in order to do that, remember, sequence to sequence model does a very simple task. You know what it does? It has two single blocks. It has two blocks. One block is called encoder and the other block is called decoder. Okay, decoder. Now what I want you to understand is this. Sir, how does encoder decoder works? Encoder decoder is a very simple concept, my people, right? If you pass in your input data, the encoder of course encodes the data, but what it does while encoding is the representation of the data is very rich in context. Let me explain what I mean by that. So let me give you an idea. Imagine this is the front of the fast food restaurant that you are working on. Okay, the fast food restaurant. Suppose you are applying, or you want to eat in this fancy restaurant, and in this fancy restaurant you give your order, they will give you the order in the next 2 minutes. So see, you pass in your restaurant order like this. The order goes inside to the order taking team. Okay, let's call it OTT. The order taking team is not just responsible for taking your order, but they are responsible for taking multiple different order in sequences. They are also responsible for taking the order and passing the order to the chef or the team that actually makes the food. And based on the sequence you gave the order, the kitchen or the chef team is going to give the food and they will give the food back to the team again. So see, what happens is one part of the team is handling the data ingestion phase and other part of the team is handling the food, sort of like the creation of the food or giving of the food stage. Think of encoder decoder models just like that. But what happens in encoders and decoder models is, in your encoder models, you are going to have RNNs. What these RNNs do is, if I expand this for you, they will take a lot of sequences as an input. Okay, they will take all the sequences as an input, but they will block the output of all the RNN generation, meaning every cell or every context of the RNN's hidden state, for each individual unroll of a cell, the output is completely ignored and deleted. We don't take it at all. I do not include it, I do not reference it, I do not even keep it with me. I only take very rich input text, which is of course passed through some kind of an embedding layer. I take my input, pass it through an embedding layer, pass it directly to the new recurrent neural network. Now remember, you can take an RNN if you want. You can take an LSTM if you want. You can take a stacked RNN if you want. Stacked LSTM you want. Whatever you want to be your encoder, anything can be your encoder. Because the reasons why RNNs came into picture is because they can handle any data set size, correct? If you go back to the basics, In a multi-layer perceptron, can I say that my input is fixed? I cannot change my input. My input is definitely fixed. I cannot change it. You guys are aware of this. In convolutional neural networks, also I have some kind of a problem with dealing with that. But to deal with a data set size of multiple different sequences, RNNs are very good. So you can take any specific version of RNN, create that as an encoder. What is the output of the encoder? That is the most amazing thing. My people, what happens is your source value or your source text will be the input to my encoder. The encoder, which is a simple RNN, a stacked RNN, any kind of RNN you think of, that RNN input is gonna go inside my RNN cell. That RNN cell is going to give me an output, and that output is going to be very critical for me because that output is what we call as a context vector or a thought vector. Okay, so suppose if you give me a sequence like this, suppose if the sentence you have is my phone is dead, DEAD, dead. Now, of course, what will you do with my will be converted into some kind of an embedding model. So let me take this XXX, right? Let me make this a little bit more neat. Let me take the length of this slightly small. Okay. So my will be converted into some vector. Phone will be converted into some kind of a vector representation, sort of like an embedding, right? Think of it like this. Your dead is also considered into some kind of an embedding layer. Okay. My phone is dead will then be passed inside your encoder module, which is nothing but a simple RNN. So you will pass your phone, your is, and your dead. But the beauty is every single output value is gonna be discarded. Remember, in encoders, we do not include any kind of encoder outputs. Okay, so no outputs will be taken, discarded. But the most beautiful thing here is you have hidden state that is going to pass through multiple different layers, and finally you're going to have this very rich context rich vector value or embedding value generated outside. We call this particular embedding as a context vector. Okay, this context vector is also called as a thought vector, THOUGHT, thought vector. Please remember, your output from the encoder is this very rich, very this embedding value that is so rich in the context of the value. We call this particular thing as the encoding, right? This is going to be some random numbers, not random numbers, some numbers that will have the information of the data or the sequence that you have passed. Okay, this will be your encoding value, will be nothing but your final hidden state. Okay, your final hidden state. I'm sure every single person in the class knows that when an RNN is unrolled, it looks like this. You have an input to the RNN, you have an output to the RNN, but you also have a hidden state passed through an RNN. The same thing happens with your LSTM also. You have a long-term memory and a short-term memory and something called as the previous cell's hidden state. I'm sure you know that in RNNs also it applies, LSTM also it applies to GRU also. So what do? Your final hidden state from the encoder RNN can be given as your encoding value, your thought vector, or your context vector. This context vector or your thought vector or your thought embedding is gonna then be passed on to my decoder value. But my decoder works very, very differently. How my decoder works is, my people, you of course will have a decoder. This encoding, thought context vector passes through a decoder, and this decoder here is given a beginning, sort of like a token, and the name of the token is going to be called as a start token. Okay, so this start token is going to be given to your decoder model, and your decoder will generate some kind of probabilities using softmax function. Okay, using softmax, some kind of probabilities it will generate. Whichever term or token has the highest probability, that token will be generated. Example, give me 1 second, Google Translate. Okay, so if I translate English to Hindi, okay, let's take Hindi. What did I say? My phone is dead, right? So my phone is dead. मेरा फोन खराब है. Okay, let me copy this. Let me paste it here. Copy and paste it here. Okay, so what I'm gonna do is Control Z. Actually, let me Control Z. What's gonna happen is it's going to generate a token where the word mera, okay, is going to have the highest probability in the encoder because of the data training that has happened over a period of time. When you pass in a token like my phone is dead, the encoder is going to generate the first neuron, or the node of the encoder is going to generate a probability called mera. Okay, from the neuron or the cell of the first node, you are going to pass a hidden state to another node. Let's call it N1 and let's call it N2. But the input to my N1 or my input to the N2 is nothing but the same sentence called mera. So you take this mera and you pass it on as an input to your second sequence. Okay. What happens to the second sequence is, now because you have the start sequence, the context rich encoding or embedding vector called context vector and the newest token generated, you pass all three as a version to the next neuron or node 2. So node 2 is going to then generate another probability for the next token called phone. Now this phone variant is going to pop up here because phone had the highest probability among all the tokens that you have generated. The probability for the token phone was the highest. Again, you make this neuron go forward into node number 3 or node 3 of your layer, and by node, my people, I will explain very clearly how to decide these nodes. Okay, don't worry. You need to pass this particular variant again into the next part, and if you keep repeating this, you will get an output called mera phone kharab hai. But remember, the minute you have the word hai in the token, so suppose hai has been passed, one more node will give one more output called the end token. Understood? Okay, you will generate an end token that will tell the encoder, okay, stop, do not generate anymore, you have reached the final version of it. Okay, mera pass mera phone to N3 or just phone? No, it will pass phone. The reason it will pass phone only is because your embedding or your encoding context vector or your thought vector that you have generated is gonna first be passed to your encoder model to first generate a context rich first token, the FT, the first token. The first token model will then pass on the value of mera with the previous values also. In practically speaking, all your thought vector or your context embedding, right, they will be passed along with everything. In the architecture, it may not look like it, but we pass everything, because how else do I make a prediction that mera has the highest amount of probability to be predicted in the next sequence? Because it must have seen the data in the past do that. So remember, the encoder decoder model, just to get a basic level idea for now, understand this. Encoder could be any RNN, LSTM, GRU, anything. Your decoder also could be RNN, LSTM, GRU. It could be anything. The point is, your encoder is going to have a set of sequence that it's going to take as an input, and your decoder is going to have a certain set as an input. How is this encoder output HT any different than LSTM hidden state output, which also contains context rich vector? Let me explain LSTM models to you kind of importantly. LSTMs don't give you context rich vector as a, how do I say this, as a hidden state, right? Let me copy image and let me paste. I'm sure everybody knows this is the LSTM cell. Tell me, the long term memory, is it saved in the cell state? Yeah, I hope you guys know this. Your short-term memory, okay, your short-term memory is stored in your hidden state, right? Your cell state retains what? What is it your cell state does in LSTMs? Let's go back to the basics. What do we do in LSTMs? What does your long-term memory does and what does your short-term memory does, right? In your short-term memory, the one that you use to retain the small piece of the context of the conversation, do I have an output gate take reference from your short-term memory and update the newest state? Your hidden state is rich in context, but for a shorter version of memory, not for a longer context memory. I hope you are aware of this. Your hidden state does not define your larger context vector or your larger context memory. It is not built for that. LSTM does not solve that problem. LSTM solves that problem using two things. How does LSTM solve that problem, everybody? Tell me, in recurrent neural network, one of the biggest problem you have is your exploding gradient and vanishing gradient, correct? This is one of the biggest problem in using RNN. Does LSTM solve that problem by taking simple multiplication and addition, completely ignoring the fact that there is no weight multiplication and weight deletion happening at the cell state? There is no weight multiplication, no weight addition is happening at the longer state. It's only happening at these stages, right? Understood what I'm trying to say? While doing that, that's how my LSTM is able to retain a longer memory or a longer chain of memory. But your hidden state does not maintain a context rich embedding. That does not happen with your hidden state. Your hidden state is simply going to decide that, okay, based on the input that I have passed and the previous hidden state and the cell state, what should be my probable next context rich hidden state? But this hidden state is only going to have a window of a smaller memory, not the larger memory. Understanding? But tell me, in my encoder decoder, do I need to give rich or thought vector embedding with respect to the sequence? When you take an LSTM cell, when you pass it an input, are you only going to pass one text as an input, my people? Think beyond. Don't think only one sentence. Like, if I have passed my phone is dead. To train your sequence to sequence model, is this the only sequence you're going to pass? No, right? Your training data has maybe thousands of rows. So don't you need to build the context rich vector not with just one sequences over a period of time? My model learns how to create this representation with multiple training. This model that I have written here or this diagram that I have written here is only for one specific sentence I am telling you. But what will be the sequence to sequence learning will be to learn this context rich embedding to generate. How to generate that learning is how to generate this model. Understanding what I'm trying to say? Every single time you have been taught the concept of LSTM, RNN, GRU, whatever you have been taught, I am very sure, with one sequence of word as an output, correct or not? You have been taught with one sequence and you are taught how the one sequence is generated. But in reality, your LSTM needs to learn, no? Tell me, if you pass the input sequence, hidden sequence and cell state, will it automatically give you a context rich vector or a very rich vector in the long term memory and the short term memory directly with just one row of data? No, right? It needs to learn also, no, how much short term memory to retain, how much long to retain. Are you understanding what I'm trying to say? That training needs to be done. That learning is what LSTM does. It's not LSTM is able to directly with one row give you one short term memory, one long term memory. In the beginning stage, it will be the worst. I take the loss function, do back propagation and then become better. That is what learning means. So remember, when you take a sequence to sequence model or an encoder decoder model, it doesn't mean just I pass one sequence value and I'm automatically able to get the answer. It doesn't work like that. You need to give it multiple instances for it to know that, okay, the best way I can create a thought vector is like this. And that's when it knows how to create a thought vector. Understood what I'm trying to say? Not like you take every single input value, pass it to encoder, then pass it to decoder. It doesn't work like that. Okay, it will make a lot of mistakes and that mistakes needs to be rectified. Okay, have you been taught that when a recurrent neural network is built, We will do a forward propagation, then we need to backtrack, and then we do backward propagation, correct? Did you know that you can actually do something called teacher forcing? In RNNs, what is teacher forcing is, or when LSTMs also in any recurrent model, what teacher forcing is, every single output generated by my cell is measured against the output generated or ypred value. Meaning, I don't wait for my model to perform one forward pass and then compare the final result to the final prediction value. No. Each model's output is compared to the prediction. Second cell output is compared to the prediction. Third cell output is compared to the prediction. This is what we call as teacher forcing. Do you think language translation is not an easy task? My, does it map back to mera in Hindi? If I say my in English and mera in Hindi, are they mapping together? Are they aligning together with each other? Yes or no? It's correct. But do you think for every language this mapping exists? For every single language, my will be mapping back to mera. Will that be sort of possible every single time? No. That is why, remember one thing, my people, the training of sequence to sequence model is done not using just back propagation. It also uses something called teacher forcing. Okay. It doesn't just use your simple back propagation and my life is easy. No. You use a concept called teacher forcing in training your sec to sec model, your sequence to sequence model.
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.
Okay, all right. We were talking about a very important topic, which was called an encoder decoder model, right? We spoke that as a seek to seek model or a sequence to sequence model, right? Whenever you listen or hear about any encoder decoder model, remember it starts with something called seek to seek or a sequence to sequence model. Guys, when we talk about deep learning applications, right? Please remember deep learning applications are all about how the data flow occurs, okay? How the data is flowing from one direction or from one place to other place. This data flow, if you understand, you will be able to understand how the architecture works, what is the goal of the project, and what are we trying to solve. Every question that is that is difficult to understand will become very easy to understand. Okay. So let's try and understand what a seek to seek or a sequence to sequence model does. I'm sure everybody knows that we have something called as an encoder and a decoder model. Okay. Now what an encoder does is very simply, if you have a sentence like I am happy, okay, you have a sentence called I am happy. You convert I into an embedding of whatever dimension vector you want. You can take a 5-dimension vector, 100-dimension vector. Basically, the embedding dimension is up to you. You decide it. How much do you want? How large do you want? Do you want a dense vector representation of what dimension? You decide that. So first of all, because computers don't understand the natural language directly, we make sure we convert each individual words. Sentences are just one, words are three. So I am happy is one sentence, but inside this sentence I have three words, I am happy. Okay. What you do is you take each individual word, convert it into its respective embedding, okay, and you pass it inside either a recurrent neural network or you can pass it to a LSTM cell. The choice is up to you. So once you feed in your embedding layer inside this, okay, your embedding of the word itself inside the RNN or an LSTM, see, your model will have a hidden state passing through each individual cell. Okay. Your hidden state is also going to be a vector of some size. say 100-dimensional vector, okay? Meaning you are going to have your hidden state also decided how much will be the shape or the size of my hidden vector or my hidden state. This vector is going to create, or the RNN is going to generate something out of this encoder cell, okay? This encoder cell will have some output and it will have some embedding created where this embedding is very rich about the information about the text. I am happy. The I, the am, and the happy. All the contextual information, which is the semantic meaning of the text, including every other detail, is very much imbibed or embedded in this context vector, also called as a thought vector. Okay. Think of this one particular vector as having every information about the text. I am happy. What you do is you pass this context vector to a decoder, which is also an RNN. So by the way, just letting you know, if you take an RNN as an encoder, you take RNN as a decoder. If you take your LSTM cell as an encoder, you will have an LSTM cell as a decoder. Now, sir, why do we call it decoder and what is the reason behind it? The reason why the decoder part is called decoder is because here the previous hidden state of this particular node is nothing but the context vector that has been passed from the encoder itself. The encoder's context vector or the thought vector is going to be a part of your previous hidden state for the LSTM cell 1 of your decoder. Now, sir, the question arises in my head, why do we separate encoder decoder? Why can't I take 3 cell and 1 more cell? Anyways, the context vector has to pass to the decoder. Why am I splitting the encoder separately and splitting the decoder separately? The reason why we do this is because the encoder decoder model does not follow the same principle that it would have followed in a simple RNN or an LSTM cell. So listen to me very carefully. It will start making a little bit more sense in a second. Okay. So let's expand this, everybody, and let's try to go a little bit more deeper. Okay. My people, if you ever want to do any textual analysis using encoder decoder, remember you have to understand 3 different tokens. These are called special tokens. Okay. Sir, what are these tokens? The first token is called pad token. Okay, it's called padding token. The second token is called SOS token, and the third token is called EOS token. See, I will explain what is padding or what a pad token is a little bit later in the class. Okay, don't worry, you will understand this in a second. But let's understand what is SOS. SOS is called as start of sequence. Okay, start of sequence. EOS is called as end of sequence. Okay. Now remember, my people, these special tokens are going to be very important in the future for you to understand something. So I'm just going to keep this in the side, maybe somewhere at the top. We will talk about it a little bit later. Okay. So remember, while building a machine translation system using encoder decoder, you are going to be needing something called as special tokens like pad token, EOS token, and SOS token. Now, let me actually go back and tell you guys a little bit from the basics in the beginning. Okay. If I take this diagram, shorten it and keep it in the side, okay, only for your reference. When you talk about an RNN network or an RNN cell, okay, can I say an RNN neural network has multiple different cells like 1, 2, and 3, and it looks like this? There is a hidden state called h of t minus 1, where the input is called h of t or x of I, okay, x of 2 or x of 1, x of 2, and x of 3. Okay, let me write it down a little bit in detail. Give me 1 minute. Let me take it like this, right? Control Z. Let me erase this. Let me take it not directly but through embedding so that I can tell you exactly in detail. Okay, can I say in a neural network we have multiple different things? Example, you have an input, each individual input to your neural network like an RNN or an LSTM, right? We call this input as x of 1, x of 2, and x of 3. Suppose if you say I love ice cream, okay, or I say am, okay, am happy, HAPPY, okay, these are your inputs. You convert your input into embeddings, right? You already have a pre-trained embeddings, you convert them into embeddings, and these embeddings are gonna pass in my recurrent neural network. Every recurrent neural network is going to generate some output. Let's call it y hat of t, okay? Let's call it y hat of t1, another output called y hat of t2, and another output called y hat of t3. And because you're passing the hidden state between the RNNs, so there will be another hidden state from cell number 1. Let me call it recurrent cell 1, recurrent cell 2, and recurrent cell 3. Okay, and I pass it through the layer. So basically I am also going to generate a new hidden state called H of O. Is the recurrent neural network that I have written sounds familiar and is correct? I have taken my input, I have taken my previous hidden state, I have generated the output, and I have the hidden state generated from every recurrent cell. Correct, everybody? This is how a recurrent neural network works. Now listen to me carefully. Every single time, every cell generates an output. Can I close that? Can I ask the recurrent neural network that every single cell don't generate an output? I don't want it. I don't need your output. I only want the hidden state. I can do this, right? This is possible, right? This is very much possible. I can stop every recurrent neural net from generating output from each individual recurrence connection. I can stop that. This is possible. So what am I interested in? Am I interested in nothing but the hidden state generated? Okay. Now everybody, the hidden state that I have taken, I can decide the hidden state size of it, right? How many numbers will accommodate in my hidden state? If I say 100, am I creating a 100 dimensional vector at the output? Basically, my hidden state has 100 dimensional embeddings, correct or not, everyone? The word I am happy is represented with a very deeper contextual meaning with a vector generated by the hidden state where the vector is of size 100. I am not taking any output. Outputs are barred. I am only taking the hidden state of the vector. Now tell me, everyone, once we understand that the encoder is able to create this, what are we interested in? We will take exactly the same number of cells or recurrence that we have taken in the encoder. How many recurrence did we take in the encoder, everybody? How many recurrent connections do you see? 1, 2, or 3? How many recurrent connection is the data passing through? Is it passing through 1 recurrent connection, 2 recurrent connections, or 3 recurrent connections? Is it passing through 3 recurrence connection? What are you going to do at your decoder? 1, 2, and 3. You got the idea called 1, 2, and 3. Understood? Now what I want you to do is understand that whenever you take the encoder, encoder will also take, because this is also an RNN, this also requires a hidden state passing from the previous value. What hidden state value passed from the previous value? The same hidden state that you generated in your encoder, are you going to pass it in your decoder model in the beginning? The way this program is written, the way your data is written is when you pass the encoder state, okay, what's going to happen is it's going to take some input. Let's call it decoder 1 input. You are going to generate this time in the decoder. You allow the y hat of t to pop up. In encoder, you do not allow it, but in decoder, you do allow it. So what will happen in the beginning is, in any encoder decoder model, the decoder will first give you the output called SOS, meaning you are telling the decoder that, hey decoder, I am starting my machine translation. Can you please convert I am happy into something in Hindi, German, English, whatever it is, right? English into Hindi, for example. So what you do, my people, is the minute you generated SOS term, what happens is you pass in the SOS term inside the next input. But remember, your hidden state also is going to be passed to the next cell. This hidden state now has the information of the previous encoding of the encoder plus the current SOS token that you're passing. So you pass in the actual SOS token, the previous hidden state, and it generates the answer called ma, right? The same ma is going to be passed inside the next model with the previous encoded value, and you will generate an answer called मैं खुश, KHUSH, खुश. Now what will happen is the recurrent connections can expand and can decline depending on the size of your data. And because I have not completed my analysis, I will have one more recurrent connection here, okay? And in this recurrent connection, I'm going to pass khush back again. And you're going to say main khush hu, H-U-N hu, and that will be the answer. But your job is not done. Because right after you say main khush hu, there is one more sequence that needs to be generated. And when you pass in the data main khush hu and back again here with the hidden state, you will have to generate something called EOS. EOS is going to tell the decoder that I am going to stop my model, and this is what you call as an end of sequence. Your entire encoded value for the given data has now been decoded, which is validated by the start of sequence and the end of sequence token in the data. Okay. In case of English to Spanish or English to Hindi translation, the decoders will be different, right? Okay. Let me ask you a simple question. Translation of English into Hindi can always have different meanings if you don't maintain the word order. Am I making sense? Does this make sense? I'll give you an example. Okay, just a second. Google Translate. Okay, let's say English to Hindi. I am so beat. I am so beat. Can you see here? I am so beat. Translate to मैं बहुत हरा हूं. Okay, basically it should be हारा हूं. Also, that is not right. Okay, if you say my phone, okay, my phone, PHONE, phones battery is dead. Okay, मेरे फोन की बैटरी खत्म हो गई है. Okay, if I just take a screenshot for all of you and show you an example of one of the problems in machine translation. Okay, observe everyone. My is mera, right? So here my is directly aligning with the word mera. Phone is also directly aligning with phone, correct? Battery is not directly battery. We have something called key battery, because in English we use something called subject object verb. English is a subject object verb language, right? Hindi is not like that. To represent battery, you have to give it some kind of a verbal habit, some kind of a push. Key battery, khatam is dead, khatam ho gayi hai, right? The point is, not every single sentence will align with the translation. Sometimes you have to add new information, which is a supportive sentence, to make sense of this thing, to make the sense of the sentence. We call this problem as adequacy and alignment problem in natural language processing. Okay, what happens is, in some language your dead word will come first and your phone battery will come last. Sometimes what happens, you have adequacy problems and alignment problems when dealing with natural language processing. So remember, in terms of English to Spanish or English to Hindi, the decoders will have to have different set of sequences or recurrent connections, because your English was tokenized into only 4 words. My phone's battery is dead. 1, 2, 3, 4, 5. 5 tokens. But at the time of my output, if I split Hindi into tokens, मेरे phone की battery खत्म हो गई है. The amount of tokens that I input and the amount of tokens that I generate, they automatically don't follow the same sequence. It is always a good practice to start your connection of encoder and decoder with the same number of sequences. But as and when your data grows, or as and when your data has different kind of sentences within them, your sequences in encoder and decoder will differ. That is the most simplest of the reason. That's because my input sequences and my output sequences, they do not follow the same procedure. My input sequence and my output sequences are not going to match, and they will not match. Okay, sometimes if the sentence is a simple sentence, for sure, if I say khatam, okay, end will be ant. See, one mapped to month, end to end, ant se ant nahi bol sakte isko. In Hindi we can't say ant se ant. That is not right. Shuruaat se ant tak. Okay, how will the decoder decide and handle, provide us correct sequence and correct meaning? So tell me, sir, how should we decide what value of the decoder should be, right? How should a decoder decide what will be its length, right? Everybody, don't you handle this with something called padding? Do you handle this with something called padding? Let me explain. Suppose if you are building a model called I love India, okay? Let's say I love Bharat. I love to travel a lot. Suppose in your data set, you have these two sequences, okay? In your entire data set, you have these two sequences. Do you know which sequence is the largest sequence? Which sequence is the largest sequence among I love Bharat and I love to travel a lot? Which sequence is the largest? Can I say sentence number 2 is the largest sequence? And because in my training data, the sequence here is the largest sequence, can I say I can create my model for everyone to map to my largest sequence? If you take I, love, Bharat, everywhere else I will put 0. Basically, this is what we call padding. So when I make my decoder work according to the largest sequence in the model, it will always accommodate that. There is a better way to solve the problem. I will talk about it later. It's more dynamically handled. But in order to explain that, first I need to teach you something called encoder decoder model. But I hope you guys got the logic. In the most basics or the most basic of the way, take whichever is the largest sequence of the data and keep your decoder to that. Everything else you do something called post padding. Post padding meaning your zeros or your padding will come to the end of the text. Okay, there is something called pre padding, there is something called post padding. Okay, in the input and output sequence, don't map word by word, let's say English to Arabic during connection. How does the machine identifies the probability of word coming at a certain position? Your softmax and your data together help you solve that problem. Okay, so let's take an example. Let's say you're trying to solve something called Arabic. Okay, now Arabic doesn't work the way a sentence or a formation of a grammar works, because Arabic grammar is completely different, right? So see, what happens here is, if the input and output sequence does not map, okay, the input and the output sequence doesn't map. Point number one, we don't have to map them. Okay, it's not our responsibility to map them, it's the neural network's responsibility to map them. The connection or mapping is understood by the data you're going to pass. If your data is very well labeled for each individual word, meaning, semantic meaning, longer sentences, shorter sentences, over a period of time, my input and my output sequences will start matching. Because in my entire data set, whichever sequence has the highest longest sequence length, I am by default taking my decoder to that sequence length. So if I have a context vector or a mapping done at that part, that mapping can be done automatically when my neural network is going to be trained. So I don't have to worry about it too much. Okay. Let's say word by word mapping from English to Arabic. Okay. When you connect your encoder to decoder, right? In the beginning stages of your encoder decoder model, every single sentence will be wrongly mapped because your probability generated will not be correct. To solve this problem, we use a concept called teacher forcing. Okay, by the way, we call it as a strong teacher forcing. What strong teacher forcing done is, imagine you are in a situation where you want to understand, am I doing a good job or not, right? My probability of generations are right or not. If you compare your output, which is generated output, your answers will not be correct because you're trying to compare the probability with the input. We don't make that mistake. In encoder decoder model, we use something called as a teacher forcing method. Now in teacher forcing, what do? We compare the output generated with exactly the output or the actual data generated. So my context vector, what it does, it will try to understand whether my analysis, okay, is actually making sense, not with the probability generated, but with probability and the actual answer generated. So we use the actual tokens in the answer. This way we know, are we far away from the answer or close away from the answer? Okay, so the loss value that we get will be higher if the teacher forcing says that you're not even closer to the generated answer. And if the teacher forcing says that, look, the generated sequence was very close to the answer, the loss value will be lesser. You do not compare each individual probability with the actual generated answer. You have a, we compare the probability values. That's not the only comparison we do. Each individual probability generated is going to be using the actual sequences or the actual model that we got. Okay. So if you have some Arabic word that you have generated called SOS, right? Some word EOS, right? This is the generation that we got. We take this entire sequence generated by the model and we compare it with what was the original mapping done in the data. Okay, is the word to word mapping correct? How many word to word mapping is correct? Say 70% is correct. According to your mapping will be your loss generated. So first of all, point number one, your input to output sequence mapping is not something that you have to be concerned about, because what happens is the context vector that you're generating is going to be generated by a closed size of say 100 dimensions. Example, it will represent any data of any size. Your context vector will handle any data of any size. You write a paragraph, can be represented in 100. You write a one word, can be represented in 100. You write a sequence of an entire book, can be represented in 100. So first of all, your context vector manages that. And after your context vector passes it to the decoder, remember the mapping does not need to be worried separately. That is taken care by my neural network. That mapping, the dense rich mapping of the text will be taken care by my model. So I have nothing to worry about. Okay. And it is done iteration after iteration, data after data. The more data you have, the better my machine will be able to translate your text. The more layers you have in your encoder and decoder, the better also it will be able to understand. So remember, two things can solve your problem in this: context vectors plus teacher forcing. You do these two, you're not going to go wrong. Okay. Very simple. Think of teacher forcing like this. Okay. Teacher forcing like this. Have you ever been in a situation where you are writing an exam? Okay. Imagine, my people, you are writing an exam and you did not prepare very well for the exam. Okay. Everybody listen. You did not prepare very well for the exam and you are sitting here and your teacher is right behind you. The teacher is able to see that you are clearly writing a wrong answer. So can teacher sometimes give you a hint? Hey, did I not teach you this in the class? That 10 plus 10 is not 30, it is 20. Is the teacher not dropping hints to the student while the student is making a mistake? You prepared a little bit for the class, a little bit for the exam, but the teacher behind you is trying to give you guys a knowledge that, look, she's trying to guide you in the right path. Okay. This right here determines or somewhat similar concept to what we call as teacher forcing. Okay. She notices that you are making big mistakes. She's trying to put you in the right path. She's not guiding you with the exact answer, but she's putting you in the right path so that the actual answer that you're writing and the results, they map really, really well together. Okay. So this is how you're going to do that. TensorFlow does not decide the result is correct. You have to decide whether the result is correct, isn't it? So tell me, everybody, TensorFlow is only a framework designed to make you write easy Python programs for neural networks, correct? That is the only responsibility of TensorFlow. TensorFlow is not going to take the responsibility of whether your data correct is whether your results are correct or not. Make sense? The analysis of that has to be done by you. Parameters are perfect or not also you need to do. NumPy or TensorFlow or Pandas or all these libraries will help you program them to help you write the logic. Okay, everybody? Can we write our own machine learning translation program, everybody, like Google Translate, right? We will try to write like a simple Google Translate of our own, where we will convert a sequence of one word into another word. Okay. Decoders are not pre-trained. Okay. Decoders are not pre-trained. They are not, in terms of sequence to sequence, at least they are not pre-trained. Remember, there are other decoders that are pre-trained, but not these ones. For example, just to give you an idea, have you guys heard of something called as a transformers? The transformer architecture? Do you know what is a transformer architecture? A transformer architecture also has an encoder and also has a decoder, correct? Agree, disagree? Okay. All your chat GPT, your Claude, your Grok, or I don't know what nowadays people are using, they are decoder only models. What models, everyone? They are decoder only models. All your pre-trained models like BERT, Roberta, Dino, Elmo, all these models are encoder only models. Some models like Google T5 are both encoder decoder models. So remember, there are decoder models that are pre-trained, but in our situation, no. Decoders are not pre-trained. They learn alongside encoders. Decoders also learn how to map the current input in English to Hindi. Over a period of time, after a lot of iteration, after a lot of training, they learn how to make itself better. Understood? So you're not going to have them pre-trained. In some cases, they are pre-trained, but in some cases they are not. Specifically with sequence to sequence, they are not pre-trained. However, they are given a small help. A help that is given in sequence to sequence model is called as attention mechanism called Bhadnav attention. Okay. I wanted all of you to understand one thing. Sir, we are going to create our own, say, machine translation code, right? Say, for example, English into Hindi conversion. How do we do that? Okay, everybody, your theoretical encoder decoder model is different from your practical encoder decoder model, because in practical encoder decoder model, reality hits, right? Your real problems with the data will start hitting. So everyone, let's understand with how do we create an encoder decoder model and how will we program it. First of all, to do machine translation, I need data, because without data, all your fancy encoder decoder model is just a model. It's like a very expensive Ferrari car, no fuel, you can't drive it. Okay. So how do we take data? For example, I take multiple data like this. I am happy. Copy. The label for this in Hindi is, or the translation for this in Hindi is, मैं, okay, खुश हूँ. Okay. Now my Hindi is terrible. I know my teacher showed the same thing, but let's say you have multiple different type of data like this in English, in Hindi, in English, in Hindi, in English, in Hindi. Can I say it like this? This will be my data. I am taking a list of all tuples, and in the tuple I have English translation and I have Hindi translation. Can I say I can take a data like this, everybody? This is the raw sentence data. Can I call this data as my data pair? My data pair, English pair, Hindi pair. Of course, you know the first step would be to apply something called tokenization. Everybody knows this is a very important topic. Yes or no? What do I need to do? Do I need to convert my English values into English tokens, everybody? The English token will be I am happy. Did I tokenize my sentence? And if I apply Hindi tokens or Hindi tokenization, can I take मैं खुश हूँ? Now tell me one thing. Did I tokenize them on the basis of space? Whenever there is a space in the sentence, I space am space happy, मैं space खुश space हूँ. I did tokenization on the basis of space. Everyone agrees, right? I don't have a specialized tokenization for Hindi, okay? Don't assume I will use some specific Hindi tokenizer. No, I am just tokenizing them on the basis of space. So tell me, everybody, did I tokenize them? Did I tokenize my English into Hindi? Now, my people, what you need to do, you need to convert sentences to indices. Okay. You need to convert your sentences to indices. Sir, what do you mean by sentences to indices? First of all, you are going to add your special token to the data. Okay. Your special token to the data for my encoder decoder model to become better. So how do I add the special token? My English token TOK will be called now like this. What will be the first token? SOS, start of sequence. What will be the next token? I, then am, then happy. Then after this, you need to put something called end of sequence token. Did I do this? I am making my training data accommodating according to the encoder decoder sequence. And what will you do with the Hindi also? Because you need to tell the model also ki bhaiya, in मैं खुश हूं also, मैं is the start of the sequence. So can I say मैं, okay, खुश हूं, okay, हूं, and end of sequence. So did I add my end of special tokens to my actual tokenized data, end of sequence and start of sequence? Now everybody, what do I need to do from this data? After I have applied tokenization and after I have done added special token to the data, you need to create something called vocabulary. Sir, what do you mean by vocabulary? Vocabulary meaning how many sentences repeat according to how much of their frequency, correct or not? In your natural language processing, when I taught you RNN and LSTM, do you remember while teaching you, I taught you how to create your sequences? Do you remember here we have taken something called maximum feature is equal to 10,000? Can you see here? Maximum feature is equal to 10,000. What have I written around side? Did I say something called vocabulary? What do you mean by vocabulary? So tell me, for my English sentence, how many times has the word SOS repeated? SOS has repeated how many times? Only for English. 1. How many times is EOS repeated? 2. How many times is the word I repeated? 1. Remember, you can always calculate the maximum length from the data, but in recurrent neural networks or LSTMs or any natural language processing task, your model does not require all the training data. It does not require the actual overall length. Even if you pass the part of the paragraph, have you not seen a situation where you have not read the entire paragraph, only a part of the paragraph, and you understood the context? We are training our model to not look at the entire sentence, but only the sentence character up to 100 and identify whether that is positive or negative. You can definitely change the program here for max length to the length of the longest sequence. So you can write something like this: length of your longest sequence in the data. You can also pass that as maximum length. But if you want to make your algorithm run better, you can take it to a certain limit, correct? Now, so we have the end of sequence token padding 0, 1, 2, 3, 4, 5, right? So let me write it like this, right? Vocabulary, build it like this. SOS is by default given what index? It's given by default an index of 1 because it is repeating in the beginning, correct? Your padding sequence or your pad is automatically given 0. Understood, everybody? Whenever you're going to be creating your vocabulary, this is your vocabulary in indices. Okay, let me write it down like this. Give me a sentence to indices. I am taking them directly as per the indices value. Okay, so padding, remember everybody, in encoder decoder model, padding is always given 0. SOS will be given 1. Then what will be I? I will be repeated at what index value? Can I say 2? What will AM will repeat at? AM will be for what condition? 3. So padding, oh, I did not add end of sequence token, right? After SOS, we have EOS. Sorry, special tokens always come first. EOS will become 2. Okay, remember, first will come padding, then start of sequence, end of sequence. Now you will start I. I will be at the index 3. Am will be at the index 4. Happy will be at the index 5. So what did you create, everybody? Am I creating my sentence to indices vocabulary, where every single individual sentence based on the word order, I am adding this. The same thing will apply to Hindi also, everybody. Agree? Your padding, no, padding may be not many, padding will only be 1. Understood? Your padding will only be 1, not many. There can be many padding, but the answer is always going to be 1. The index of padding will all be 1. Okay. The 0, 1, 2, 3, 4, 5 are indices, your indexes. Okay. Your indexes. We will take frequency later. I'll tell you how to take frequency, but for now, focus on the index. Cool. So tell me, is this step clear? We took the original data, applied tokenization, tokenized the data, added the special tokens, and converted my tokens into indices, correct? This is how it became. So tell me, how will my English token look like? English underscore token, if I convert it into indices or numbers, how will they look like? English underscore sentence or tokens, will they look like this? 1 comma, what is the value of I? 3 comma 4 comma 5 comma 2. I am happy. SOS I am happy EOS token, is it now converted into indices like this? English token is equal to 1 comma 3 comma 4 comma 5 comma 2, and Hindi tokens to indices have become 1 comma 6 comma, this will be 7, right? 6 7, and this will be, last value will be 8, right? And this will be value 2. So how did we do that? What will be your PAT token, everybody? Your PAT token will be 0. Your SOS token will be 1. Your EOS token will be what? Will it be 2? So tell me, मैं is going to be what? 3. Your PAT token is 0. Your SOS is 1. Your EOS is 2. Now tell me one thing. Here, I'm not going to take 3. I'll tell you why. See here, everybody, 0, 1, 2, 3, 4 and 5. Did we take 0, 1, 2, 3, 4 and 5? When you took your actual data, I am happy. Which was the last number it ended? Which number did it end in the last? Did it end in the number last called 5? Did the I am happy ended at the last number called 5? So मैं will start at the index 6. You can't repeat 5 once again there. That will be duplication of data. That will not work out fine. So your मैं will be 6. Okay. Your khush. Okay. Your khush will be what? It will be 7 and your who will be 8. So does it map properly? See, 1, 6, 7, 8 and 2. This will be my English token and Hindi token. People, don't repeat the number here 5, 7, 8 or 5, 6, 7. The duplication in token values are not allowed. In the indices are not allowed. Understood what I'm trying to say? Your indices must be unique. Your keys can be same or could be same. See, pad, SOS and US is same, but indices can't be same. So tell me, was I able to convert? Look at it. I started with the sentence called I am happy, मैं खुश हूं. And do I have the indices mapping here done in the first step, everybody? All I did was just 1, 3, 4, 5, 2, 1, 6, 7, 8, 2. Correct or not? So this sequence is going to convert my sentences into indices. I'm taking my sentences and I'm converting my sentences into indices. Now tell me this, once my data is already done or my data is already passed, okay, inside my data, this is going to be step number 1. Indices are generated. Now what do I do next? Right? Sir, after I have generated the indices, I need to prepare the data. Step number 2, everybody. Okay. You need to prepare your data. Sir, I am already prepared. No, not the way you have prepared, but you have to prepare for your NLP application. So first of all, everybody, your input sequence to the model will look like this. 1, 3, 4, 5, 2. Okay. The entire step 1 is going to be one Python program I'm going to write. Tokenization se leke, from tokenization till the end of the part, all I am doing here is I am just going to write that as one part of the program. As in, I'm going to write one function that will be capable of dealing with the entire thing. See, your fit on text, what it does is, it will try to map your mapping. Of course, it does frequency calculations, but what it does is majorly fit on text is going to convert your I am happy, you are sad into indices value. So if you say the word I am happy, it will say I is 1, am is 2, happy is 3, you are 4, are 5, sad is 6. So what will happen is, of course, frequency is taken into consideration, but at the time of fits on text, we kind of indirectly calculate the frequency, but my major intention is to retain the word order. So that is why whichever order the word comes in, that is the indices of the word. But we of course rearrange the words based on frequency first. Okay. Let me open it up here. Okay. Tell me here, if you look at this program, what do you see? If you have a look at this program, what part of the model building I'm currently at? Like what is happening right now? I have taken a maximum feature size, right? I have taken a maximum feature size right now. Okay. I have taken the maximum length of my data. Okay. But what am I doing to my data right now? Like what is the major intention behind taking the maximum feature and maximum length? Because I want to create a vocabulary on my own or of my own. Okay. So after I have done this, what is my next process? What is my next piece of a process that I'm doing? After that, I have taken something called all the values from my data set and all the balanced value from my data set, right? After this, I take the tokenizer, number of words, and I'm also adding something called out of vocabulary terms. If I comment everything out and print out something called the tokenizer dot fit on text, according to you guys, what answers would it give? What your fit on text will do is, will it take individual value? For example, okay, let me show you an example. Let me go over here. Give me 1 second. Yeah. If I take a data like this movie is great. Okay, this movie is great example. Okay, and if you have another sentence like great movie but boring. Okay, but boring. And the third sentence is this is boring. Okay, boring, boring. The first thing it will do, the first process your fit on text does is it will split the text into each individual words. Okay, so your this movie is great will be this, then movie, then is, and then great. First of all, this will happen to each individual sentence. So sentence number 1, sentence number 2, sentence number 3. And what will happen is this appears how many times in my data? The this in the entire sequence appears how many times in my entire document? 2. Okay. Movie appears how many times? 2. Is appears how many times? 2. Great appears how many times? 2. But appears how many times? 1. And boring appears how many times? 2. So tell me, is the mapping done with something called as your as based on your frequency when I did something called fit on text? This movie is great but boring. Do I have their frequencies also? Okay. Now what happens is, have you added a piece of the program here in the fit of text, fit underscore text? Have you done something called text to sequences here? You have a method called text to sequences. But in order for you to generate sequences, don't you first need to know what your vocab is? This is my original vocab, which is going to be this, and the movie is this great. Now, I have a special token called out of vocabulary tag. So what am I going to do? Every special token will always come first. So out of vocabulary index mapping will be how much? This is going to be what? It's going to be 1. So tell me everybody, this movie is great but boring. Okay, this movie is great but boring, or great boring but whatever it is, however you want to take it. So tell me what will be the sequence. Can I say this appears multiple different times in the frequency, so the index of the this will be 2? What is the next sequence? Movie. Is the next sequence movie, so the index of the movie is 3? Are you understanding what I'm trying to say? All the heavy frequency word will be sorted, and based on the sorted index, I'm going to have the index number 1, index number 2, index number 3. Understood? Frequency was taken, no doubt. After frequency, based on the sorting of it, I will take the indexes. And when I convert two sequences, basically your word this will be the word 2. So the first sequence will be 2 comma. Okay. What is the next sequence? Movie. Movie is the third sequence. So 2 comma, 3 comma, 5 comma, 1 comma 2, whatever. Example, I'm just giving you a sequence example. This is how the entire sequence will be generated in the fit on text. Frequency considered, sorted. Based on that, I directly take the numbers. So if I take it directly into two sequences, I will have my numbers generated. Okay. So is my assumption correct that whatever model we have run so far until the sentence to indices part, everyone is happy, right? Everyone is gonna be clear with the answer of I am happy, this is happy, that is happy. So you're gonna be cool until this. Okay. So can I show you how I would write the program for the for this particular example? Until the indices, conversion of the indices, can we write the program only until that, so that we can know for a fact that we are sorted? This is gonna be my encoder decoder program. Encoder decoder, which is nothing but a sec to sec model, okay, or a seek to seek model. Okay, everybody listen to me. Before I even start my program, I need to start importing TensorFlow. Okay, so import TensorFlow as TF. I will also import NumPy as NP. I am also going to import, so I need to count, right? So let me do this. From collections, import counter. Okay, import. Let's take the use of PSL, Python standard libraries. We have a method called counter. It's a beautiful thing. And let's take something called as the random. Okay, I'll tell you why do we need this. Okay, first of all, the data that we are going to generate will look something like this. I'm going to take a tuple and I'm going to write it down here. Okay, oh, let me close this. Let me close this. Let me write down from here. Okay, also here. So the first thing I want to do is comma this. Google Translate. I am happy. Okay, I am happy. So let me copy I am happy and write it down in this particular code. I am Control Z. I am happy will be converted to मैं खुश हूं. Copy and paste. Okay, this is the translation of the word. Let's take one more word. Actually, let's take couple of words actually to make our model better. Otherwise, it will perform very, very bad. You are sad. Okay, not sad. Let me copy this. Let me paste it here. Let me write it down here and say you are sad. Copy this and write it down with आप दुखी हो. Right? Copy this and paste it here. आप दुखी है. Okay, ठीक है. I know हम दुखी हैं. She is tired. Okay. Example. She is tired. Tired. वो थक गया है. Isn't it वो थक गई है? Isn't like wow. Look at this. AI at its best. She is tired. Let's say वो थक गया है. Wow. This is not right. But anyways, I'm going to copy this and paste it as it is. Okay. I'm going to take another sentence and let's take we are hungry. Okay. We are HUNGRY hungry. हम भूखे हैं. Okay. Very nice. Copy this. Come over here. We are hungry. And hum bhuke hain. Let me copy this and paste it here. So how many did we take? Not enough for my seek to seek model. Let's say they are busy. Example, they are busy. वो व्यस्त है. Okay, copy and let's say paste here and I don't know. वो व्यस्त है. वे व्यस्त है. Okay, let me write it down. वे व्यस्त है. I am cold. Okay, will be मुझे ठंड लग रही है. Okay. So let me say I am cold, copy this and paste it here. Take another bracket, I am cold will be converted to मुझे ठंड लग रही है. Copy this, paste it here, paste it here. Let me take one more data here. Let's say you are late. Okay, you are late. तुम देरी से आए हो. Okay, ठीक है. This sounds good. Let me write it down. You are late with तुम देरी से आए हो. Copy this and we will paste this. Okay, and we will take one more thing. She is sad के बदले let's say she is happy, so that we have the same context. She is happy. वह खुश है. Okay, ठीक है. And paste here and let me take here. वह खुश है. Copy it here and paste it here. And let's take one last one because we will have a larger data. We are hungry. We will say we are ready. Okay, we are ready. R-E-A-D-Y, ready. So let me copy we are ready. Come over here. Let me write it down in English and let me write it down Hindi. Now, before I even start teaching you encoder decoder model, I'm gonna tell you this right now that this data is just nothing when it comes to training your encoder decoder model. Our encoder decoder model will perform worst because I don't have enough data. But remember, this is only for your understanding, okay? Because this data isn't even enough for it to start learning the differences between English and Hindi. But it's okay. We will just take this as an example. Okay. So everybody, this is the data using which I'm going to be training my encoder decoder model. Now, of course, this data is definitely not enough, but we are going to try our best. So first of all, everybody, the intention for us should be to build our vocabulary. Okay, build underscore vocabulary. So what are we going to do? Can I take sentences, okay, or whatever sentences that are going to be passed and the language of my choice or my preference? I'm going to take this in my this thing. Tokens is equal to counter. Okay, I'm going to take something called tokens is equal to counter. For sentence in sentences, for each individual sentences or sentence available in the sentence that I'm looping through, I will take tokens and inside the tokens, I will update the tokens with the sentence dot split. So I will take and I will make sure that each individual split value are added into my tokens, which is going to have a counter value inside it. Okay. Now what happens is for my tokens, I'm going to create a vocabulary where I need to mention the special tokens that I'm going to be creating. So the first token I want to add is going to be a token called pad token. So pad is always going to be mapped to 0. I want to tell my program that look, whenever you do mapping, you can do any mapping for any word frequencies, but please make sure padding SOS and EOS will remain at a certain sequence length. So I will say SPAD, SOS will always be at 1, and my EOS, okay, end of sequence tag will always map back to number 2. So 0, 1, 2, okay. So for 0, 1, 2, I will say for I, token, okay, for I, token, I'm going to take enumerate, okay, for all the token keys that I have, because that's how I'll know what to map on. So token dot keys, okay, for all the keys value from index 3, right, would be starting with vocab. Inside my vocab for that specific token will be mapped to 3. So it will first start at 3, and what I will do, I will return my vocab. So I will return the vocab that I have just created in my problem, right? So what I will do is token is taken, right? And so for sentence, in sentences, the counter value is already written. We have tokens dot update. For I comma token in enumerate token dot keys, map it starting at the third index, because 0, 1 and 2 is taken. So vocab of that particular token is going to map to index I. So it will start at 3 and I will return the vocab. Okay. Everybody, what's simply happening here is in the entire program, if you can see very clearly, what I'm doing here is I am taking a counter object. What a counter object does now is it will convert into word frequencies. So for example, if you take a specific sentence like I am happy, okay, or you are sad, for example, to show you, just to show you an example, okay, suppose your sentences are equal to I am happy, okay, and another sentence is equal to you are sad, okay, example, you are sad, okay. What you're going to do is your tokens is equal to counter, okay. When I call this counter, which is a Python standard library, it is going to generate my answer like this. I is going to map back to the sentence 1. Am is going to be frequency 1. Happy is going to be frequency 1. Sad is going to be frequency 1. So what happens is, see, inside the token counter where I have taken, I am passing something called as the tokens.update, and inside this I'm passing the sentence.split. So each individual sentences will be split. My padding sequences of 0, 1 and 2 will be taken, and for each individual vocabulary I am making sure that I am passing the data very obviously. So if I take build vocabulary, okay, and if I pass in your sentences, so basically if I take the data, right, for you, build vocab, let me just run it. See here, build vocab. Oh yeah, just a small thing, just give me 1 second. Mapping of I is done, special token is passed, okay. I will call sentence to indices where I will pass the vocab sentences. So if I take vocab and pass it to my sequence, so wait, will it be like this? SOS I am happy, map back to 111, index token 123, or 3, 2, 3, 4, 5, 6, 7, 8, EOS and padding done, right? So for example, I have a token counter is equal to this, tokens.update is equal to this. Okay, perfect. Give me a second. Let me tell you, give me a second, escape, and let me write it down like this. Okay, let me not show you like this. Let me show you like this. Okay, listen to me. First of all, you have a variable here called tokens is equal to counter, correct? So listen to me. What a counter does is, if you have a set of sentence, right? I am happy, you are sad, whatever it is. Your tokens value will be looking like this. Tokens is equal to I repeats how many times? 1. Am repeats how many times? 1. Happy repeats how many times? 1. You repeats how many times? 1. R repeats how many times? 1. And sad repeat how many times? 1. Your token is going to create a dictionary of all your key value mapping with respect to the frequency of the data. Okay. How many values repeat how many times? Okay. This is how your counter operation is gonna run. Once that is done, what I do, I take my token and I do something called update on it. What do you mean by update? Basically, I want to make sure that the tokens I have generated are on an individual split of the data. So sentence.split. If you take individual sentences, Will you get the entire sentence untokenized, the entire cent of sequence? I need to tokenize it with something called cent.split. Okay. After that, I take a variable called vocab. Inside the vocab, already my key value pair is starting at keypad index 0, key value SOS index 1, key value EOS and start 2. So tell me, to add the values in my data, will I start at index 3? Because 0, 1 and 2 are already taken, correct or not? Agree, disagree? For index value and the token value available in the token, okay, this token and I will be available in the token.keys. When you calculate something called token.keys, you know what keys are, right? We have both keys and values, right? Like we have key, items, values, right? In the dictionary. For all specific keys, I'm going to be taking its indices and I'm going to be taking the token. For the sentence available in the vocab, I'm going to make that available at I. So basically, for example, if your sentence is I am happy, so I will start at the index called 3. Am will end at index 4. Happy will be at index 5. And every single value in the vocab will be returned as it is. Understood? Dictionary will return your value where your final dictionary will look like this. Your padding is going to be how much? Your padding is going to be 0. Your SOS is going to be 1. Your EOS is going to be 2. But what will be I? I will be starting at index 3. Am will be starting at index 4. Happy will be starting at index 5. You at 6. And I think uske baad UR is going to be 7 and so on and so forth. This is going to be your final vocabulary that will be returned in this particular example. I am going to be using the language later. So I have written one more argument called lang. This I'm going to use later in the code, but this is only for your reference. Okay. Let me go to the bottom and start with step number 2. Anyways, okay. So guys, we were able to generate a sequence of numbers, okay, given the text, given the data, okay. In our data, if you take this as an example, okay, if I copy this data for you guys and paste it here, okay. So how many sentences do we have in the data? Look, 1, 2, 3, 4, 5, 6, 7, 8 and 9. How many sequences do we have? Sentences? We have 9 sentences, correct? For the training of our data, all the way from 1 all the way till 9. 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now everybody, the input that you got from the previous data for the word I am happy looks like this. 1 comma 3 comma 4 comma 5 comma 2. Agree, disagree? This is the sequence we received after we applied tokenization and tokens to indices or sentence to indices. When we converted, we got this answer. Okay. Everyone, in the entire sentence, which sentence is the largest? If you tokenize it, you will get higher tokens. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Can you see this sequence has the largest tokens if I extract? मुझे ठंड लग रही है, right? Okay. This being one of the largest sentences where the tokens value will be higher, every single sequence that we generate will not have 5 numbers, but how many numbers will it have? It will have 6 numbers, because we are accommodating my entire data to the largest value. We call this as concept called padding. Agree, disagree, everybody? This is what we mean by the reference padding. We are making sure that every sequence of numbers that we write, which is based on indices, is going to accommodate as per the largest data. So tell me, what is the size of the data? Is this data 1 cross 6? This sequence is 1 cross 6, right? 1 row, 6 columns. Can I say this is the size 1 cross 6, everybody? If I have 9 sentences, how many sentences do we have? 9 sentences. Does my overall data can be referenced as a 9 cross 6 array? Understanding what I'm trying to say? This is going to be the shape of the data that you are currently creating. Okay? It could be the shape of the data. Okay? It may be 7 instead of 6. Do you find in our data any other sequence more than that? So end of sequence, start of sequence, 1, 2, 3, 4, 5, 6, 7. That's correct. We forgot the end of sequence pad. Let's call it 7, right? One more 0 towards the end. because we have a special character. So we'll say 0. So do we have a shape called 9 cross 7 and not 9 cross 6? Yep, includes the EOS and SOS, correct. So EOS, SOS, 2, 3, 4, 5, 6, 7. Here is the last one, which is 7. So can we say that the output is going to be in the shape of 9 cross 7? And every other sequence will have a post padding. What do we mean by post padding? The zeros or the padding is added to the end, correct? Agree, disagree? This is going to be my padded sequence, right? We know for a fact that 0 is the key for the pad term called pad, correct? Your padding is named at what key number or what index number? Index number 0. Your pad is the key and the 0 is the value. That's why we are doing the padding with the number 0, everybody, correct? So in step number 2, what do you need to do? You need to be clear with the shape of your data. What kind of shape are you representing? Can I say my overall data is a 9 cross 7 shape? Right? If I take one more data, it could become 10. So we have something called 9 cross 7. Agree, disagree? This is how it's going to help me. Okay, very, very good. Now tell me, once I understand I have the entire sequence ready, in step number 3, do I have to do embedding? Because now my input data is already sorted in sequences. And now I have to take my embedding. Can I say before even taking your embedding, you have to decide what will be the size of your embedding layer or what is the size of each embedding? Let's say I say that the size of the embedding is 50. Am I taking each individual token and embedding it into a size of a 50-dimensional vector? Example, your SOS token, which is at index 1, your I token, which is at index number 3. Okay, your AM token, which is at index number 4. So can you say that each individual token, including special tokens and the data, is currently being embedded into each individual 50-dimensional ultra-rich context-heavy vector? Agree, disagree? Because the embedding size that I have taken is going to be 50. Now everybody listen to me carefully. Sir, how do I decide whether the embedding size should be 50, the embedding size should be 100, the embedding size should be 200, the embedding size should be 300? Listen to me very carefully. I have told you in the past that it has been observed in natural language processing that yes, in most of the cases, larger embedding size do capture more semantic meaning. But tell me one thing, if you take a glass and fill this much amount of water, will this much overspill? This amount of quantity of the water will spill? Agree? You're understanding what I'm trying to say? See, let me kind of make it a little bit more sensible to you. See, if this is your glass, okay, this is your glass. If you add water to it, the glass is 50 ml, example, and you add 80 ml of water inside the glass. How many data points will be spilled or how much water will be spilled? Can I say 30 ml of water will be spilled? Yeah. Okay, good. If I take a glass of 50 ml and I only add 40 ml, do I have more 10 ml remaining gap? Only 40 ml was filled. There is a gap of 10 ml left, correct? Finding out the right embedding size works something like that. If you take an embedding dimensional vector of size 250, can I say that the entire contextual information for me to gather, the size is enough to be maybe 150, not 250. So will my data or embedding data will have extra space for it to accommodate? Right? Meaning extra 100 dimensional vectors are capturing information. They may not necessarily be important for my feature extraction, or they are not necessarily great features for my data, right? Understand that extracting and writing down the embedding size also depends on the process you're doing. The best way to deal with it is first write down a 50. If you think it is not enough, right next neighbors, maybe 100 or 200 will be enough for you to represent that vector. If in case your results are not satisfactory. Okay. So tell me everyone, my start of sequence, I am dot 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 all the way till my end of sequence. Have I converted every particular value into a 50-dimensional embedding? So what is the output shape of my answer, or what is the output shape? Is it 9 cross 7 cross 50? It's a 9 cross 7 cross 50. This is the size of my value. Agree, disagree? The batch of data or the sentences in my data are 9. What is the sequence length of my data? Is it 7? And what is the embedding size of my data? Is it going to be 50? Is it making sense that currently I have converted my data into an output shape of 9, 7, 50? Agree, disagree? So this is the output I am going to be passing inside my encoder. Okay? Right? Makes sense? Everyone is clear. We were able to create an embedding layer of my specific size. Sir, what option do you want to choose as an encoder? See guys, I will teach you LSTM encoder, LSTM decoder. Okay. I actually wrote the program for you guys for by LSTM encoder and the answers were amazing. But the problem is, if I show you by LSTM, then I will have to tell you how by LSTM functions. I thought, okay, since we need to process with the topic, I'm going to show you LSTM. Okay, I'm going to try and process LSTM for you. So everybody listen to me carefully. Okay, the embedding tensor, the input to the LSTM that you're passing is going to be what shape? Is it going to be of the shape of 9, 7, 50? This is the shape that I'm passing to my embedding layer, which is going to be passed. Okay. The LSTM that I am taking, okay, the LSTM cell that I'm taking, can I take the LSTM cell with the units or unit is equal to 100? Do you know what units equal to 100 mean? Let me show you. Is this the program that we wrote for LSTM and RNN, everybody? Did I write down the LSTM here or an RNN here? Give me a second, right? Maybe I wrote down like a simple RNN for you guys, right? Ah, awesome. How many units did I write here? What is the representation of units? It's 64. Sir, what does that mean? If I take my units equals to 64 or my cell type is equal to 64, for example, if I take my hidden size, okay, hidden underscore size is equal to 100. What will it mean? Will it mean that my LSTM layer's hidden cell output will have a context vector of dimension 100? You're getting what I'm trying to say? Your units or your hidden state, your hidden size, you have taken that as 100. What does it mean? What does it represent, everybody? The shape that you are passing to the input is a 9 cross 7 50, but every input will process or generate an hidden state output with what is the size? It is a tensor, Roy. The input that I'm passing here is definitely a tensor element. This is a tensor. Anything that goes beyond 2D becomes 3D automatically, and anything greater than 3D is a tensor, right? So the number called 3D tensor is actually very confusing. It's a misnomer. Let me explain, okay? Matrix versus tensor. Okay, let me show you a diagram. With this, I think you should be able to understand it a little bit better. Okay, let me copy this and let me paste it here. See, in physics, chemistry, math, the definitions of tensors slightly differ and vary. Okay, if you do Green's calculus or Green's theorem, then the calculation or say vector algebra will be slightly different, but let's get an understanding. Okay, tell me this. Can I say a tensor is nothing but that has more than 2 dimensions? See, this is the matrix. I have rows and I have columns. Yes. If you have rows, columns, but multiple repetition of these vectors again and again, can I call this operation as a tensor operation? Is this a tensor? But isn't tensor automatically 3D? Roy, if you look at this definition, by default tensor is more than 3D. So if I say 3D tensor, does that mean it's a misnomer? Meaning, well, tensors are supposed to be highly complicated. Well, here is the answer. See, can you see tensor is nothing but multiple matrices within the matrices? You have a matrix. Inside this, you have another matrix. Inside this, you can have another matrix. Inside this, you can have another matrix. Are you understanding what I'm trying to say? Tensors by default, okay, are gonna be anything which is gonna be a higher dimensional value. Okay, when we say that the input sequence has a shape of 9 cross 7 cross 50, 7 is representative because 7 was the point of origin through the indexing that we stood, right? So for example, I am something 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 something, that contextual window was 7. This is where my entire data was able to frame its original embedding data from. But when we look at the actual data, which is the overall data, the significance of 7 reduces because now you're not looking at a contextual window, you're looking at referencing or getting the entire data. So if I want to forgive my 7 or forget my 7 and proceed forward with 9 and 50, that would be also okay. Okay. If I take a value of say hidden size equals to 100, which is going to be the cell structure, okay, the recurrent connection here, what I'm basically doing, okay, pre-process, I am going to pre-process, okay, my sequence, which is generated token by token, okay. For each individual token that I have taken, the LSTM layer is going to update its hidden state. Say your h of t is going to be your hidden state. In LSTM, we also have something called cell state. Because in my long short-term memory model, I have two things that are passed to the next cell, okay, in a recurrent connection. One will be your cell state, the other will be the hidden state, okay. Each will be 100 dimensional passing statement between one cell's recurrent connection to the other cell's recurrent connection, okay. For simplification, right, after I have passed my SOS token, my I token, my E token, whatever token you want to have, each individual token passing or having its recurrent network or connection to the other cell will generate its own hidden structure of some dimension and its own cell structure for other dimensions. So point being, you're going to generate a hidden and a cell state, okay, for every recurrent connection you're going to have. Finally, what's going to happen for your entire size of 9, you might generate a sequence of 100 every time you're going cross, as in you're generating for every recurrent connection. I just want to take this cell, have a recurrent connection with other cell, another recurrent connection with other cell. I want to have this connection as long as my contextual vector or my thought vector is generated to the output. The vector I am happy or the sentence I am happy will have a hidden state, will have a cell state. Okay, this hidden state and cell state are both going to be generated at 100 dimension because this is the value that I have put at the output of the encoder that I'm trying to define. The encoder LSTM has 100 recurrent connections, your cells processing the embedded sequence, the sequence that you're passing, finally giving me a context vector towards the end. And this is going to be the one that I want to pass inside my decoder. This is going to be the one that is going to be super critical for me to pass it forward to the next decoder value, because that decoder is then going to reference or use your context vector in the same part. Okay, we have taken an encoder or an LSTM cell. Each LSTM cell is going to have say 100 LSTM structure or a recurrent connection. We are going to process the sequence token by token. How many tokens did we have in this particular example, right? I am happy is converted to how many tokens? Can I say 5 tokens? My 5 tokens are start of sequence, I am happy, and end of sequence. So tell me, if my sequences are going to be 5, how many time steps there will be? There will not be 64 time steps, there will be 5 time steps. Because how many tokens are we passing? One by one? No, not 63. The number 63 has no reference, no? We pass the data sentence by sentence, not everything engulfed as one, not everything embedded as one, because I want to know how it performs data by data, not at once. So when we pass it one value at a time or one sequence at a time, time step by time or token by token, 5 time steps will be taken, 400 cells, generating my embedding dimensions of 100, meaning this 100 vector or embedding that we have created is gonna have a very deeper contextual meaning for all the 9 values that you have passed. Sequence by sequence, step by step, sentence by sentence I am passing. Got the logic? In order to accommodate that, my data or my program that is currently generating something called as a vocab for me is not enough. Because in the build vocab part, I haven't done anything respect to the padding of the problem. Okay. There is no post padding done. There is no pre padding done. In order for my padding to be done or for something to be converted at indices, okay, which is what I taught in the first part, I need to extract value separately. So if you see here, if I write down data of 0, okay, if I write down data of 0, I am going to get something called I am happy and मैं खुश हूं. If I want to extract all English words, I might have to loop into the data part and only extract English or English values at index number 0 or index 0. And if I want to extract Hindi, I might have to loop through all, but I will have to write the index 1 for me to generate the value called मैं खुश हूं, because this is a tuple value, right? In order for me to do that, my English sentences, right? All my English sentences, I'm going to say pair. From that pair, extract the index 0 for pair in data. Okay. So if I write down for this or this for all my English and Hindi sentences, I will say Hindi sentences will be equal to pair of 1 for pair in data. See, what is going to happen is if I write down English sentences, if I just run this and say English sentences pretty much, I am happy to all the way till we are ready, all English sentences are going to be segregated in one single variable, which I will reference later. So now what do I do is English underscore, okay, my English underscore vocabulary, okay, that I want to create only for my English sentences will have build vocab. I'm not going to use lang now. I'm going to use lang for referencing. So I'm just going to show it to you. Lang will be used as a developer pairing, meaning for the developer to understand that, look, this is going to be for English. So what do I do? Can I say build vocab? Okay. Inside the build vocab, I will pass in the English sentences. For your reference, I'm going to say that, hey, you know what? I ran this. The language preference, which was not given here, is for English values. The Hindi sentences or the Hindi vocabulary or Hindi vocab value would be for build vocabulary for my Hindi sentences, which is going to be passed here. And the English or the line statement which I will write here is going to be Hindi. So if I run this, okay, cannot access local variable token. Let me see, what did we do for I in, oh, sorry, tokens dot key, right? Because wait, I comma token in tokens. Yeah. So give me a second. Reference this right died. So if I say English vocabulary, run this. This is going to be my pad sequence, start of sequence, end of sequence. I am happy, you are sad, she is tired, we hungry, they busy, cold, you are late. Fine. And my Hindi vocabulary that I have built would be मैं खुश हूँ आप दुखी वह थक गया है हम भूखे वे व्यस्त मुझे wait where is मुझे here wait so मुझे ठंड लग रही है there is no other मुझे okay so fine लग रही है तुम देरी से आए हो तैयार okay so we have हम तैयार towards the last and मैं खुश will be at the beginning. Okay, so essentially what has happened here is, let me try to print it like this: English vocabulary comma end equals to a comma, so that everything is properly enabled. Okay, so see, for my English vocabulary that is generated right now, we have a special token called pad SOS, which is start of sequence, end of sequence, and all individual values that have been passed, and I have been able to create a vocabulary. This is going to be the large vocabulary or the overall vocabulary using which I will be taking or I will be taking a help of this vocabulary in the future. So just for my reference, let me just print what have we received so far for English and Hindi. So if I say, I don't know, English vocabulary, okay, vocabulary size is gonna be, let me take a bracket and say length of English vocabulary. So this is going to be the size of my English vocabulary size. Let me copy this. Let me print this in the bottom and let me say Hindi, H-I-N-D-I. Hindi vocabulary size is going to be H-I-N and vocab size. So if you can see here, we have generated two different vocabularies. English is lesser because it uses less. It's a subject-object work. So we have English 27. Now that we have taken English and Hindi separately, we are going to be converting, okay, our sentences that we have taken to all proper indices values, right? So these indices are going to help me create or prepare my data so that I can reference this data in my actual encoder, and my data after padding will be used directly. So if I want to do that, I'm going to write down the name of the function called sentence to sequence. Okay, sentence to sequence. SEQ, let me write it down like this, SEQUENCE, right? Or let me say not sequence, sentence to sequence, sequence to indices, right? First indices, we'll take indices. For every sentence and the type of vocab you are passing, for every individual value or for the analysis, I am going to take indices that I have in my data. If I want to take indices in my data, I will have to write like a list comprehension. So what I'm going to do from the vocabulary, I'm going to use a method in Python called get. Now what get does is, it references the value of any given key. It references it early stage on. So if nothing is returned, it returns none rather than giving me an error, right? So if I pass in something called token, okay, for my vocab.get, for that token, I'm going to get vocab.get, okay, vocab.get. First, I'm going to reference my UNK or my unknown token. So see guys, so let me write it down and let me explain what am I doing here. I'm going to write something called 0 here for token, okay, for TOKEN token, okay, for token in sentence that I'm passing, and I need to split the sentence. Okay. See, what I'm doing here is to create indices in my data. Okay. I have to basically write down something called vocab.get. So what am I doing here is, for example, if you have a token called I am happy, okay, of course, by default, so if you have a word like I am happy, okay, HAPPY, I am happy, my intentions are is to convert that into a indices value where I am able to map them back. Now, what happens with the indices is sometimes I need to pad them back into the original sentences the way that we did. So my sentence dot split, this written sentence dot split is going to split this into each individual value, like I, comma, am, comma, happy, right? HAPPY. It's going to split this into I am happy. Now to convert each word to index, right? Each specific word to index that I want to convert, the first step or the process flow, what I'm going to be calling is, I want the I to map back to the index 0, 1, 2, 3, whatever it is, right? So when I say I want to map it back to my index called 3. So for that is why I get something called vocab.get. Okay. In the vocab.get, if anything is not known, that would be the UNK or the unknown token. But everything else would rather turn out to be an index like this, 3, 4, 5, because I, then am, and then happy. So this is going to create, because the vocabulary is added like that, I'm going to make sure that for all specific values, I want extraction to be done like that. Now here, in indices, what happens, for every single value that I have, or the start of token or the end of token, right? What I want to do, once I extract all the indices, I want to make sure I add or put the SOS in the beginning and the EOS in the last. So the indices that I generated are not complete because there is no SOS added to the end or beginning or EOS. So the same array or list value which is giving me indices in the last value, for the same indices, I'm also going to take it as an array. Inside the vocab that I have already created, I want to access the SOS tag. Okay. The tag is then gonna be added to my indices, which is gonna be the previous indices that I have generated. Plus again, I want to take the same vocab file from which I'm going to be referencing something called my EOS tag. So what would I do? If I write my EOS, all I want to do is in the beginning of the indices, I want to make sure SOS is added, and towards the end of it, my EOS is added. So this program, what it's going to do, or this line is what's going to do is it's going to add the EOS and SOS to the part. And once we know we have referenced it properly, we come over here and we directly return the indices, because indices are going to be used by the program in the future. So basically, If I pass in any sentence here and the vocab part, I can pass it English sentences and English vocabulary, and it will try to put SOS and EOS with the mapping of all the 3, the 4, the 8, the 6, the 1, and I'm going to pass the value. Once the indices are passed, I still haven't done anything called padding. There is no padding done to my data. So because padding is the last step for my data pre-processing, what I'm going to be doing, I'm going to be taking all English sentences, I'm going to be taking all Hindi sentences, and I am going to convert them into padded values so that my source and my target padded values are padded and they are good to go. In order to do that, we will also call a helper function or a function that will help me achieve this, no matter what the size of the data will be, as long as the data is passed in the exact same format. Okay, you do not change the format to anything else, you retain the format. We do define prepare data. Inside the prepare data part, okay, we are going to pass the data itself, which is my original data, the English vocab that I have created and the Hindi vocab that I have created. Okay, these are not actually where the data is being passed. This is only a reference to tell you what the function will be taking. Okay, so the source data is going to be something like this, right? I already have something called sentence to indices. So I just need to loop through the data and call the sentence to indices, and the sentence to indices will be automatically created for my source and my target. My source is going to be the English language that I'm going to be using, and my target, so let's call it TGT underscore data, will be my Hindi. Okay, so this will have Hindi sequences and the source sequence will have a Hindi sequences. So I will take sentence to indices. Inside the sentence to indices, for all values of pair 0, okay, pair 0, for, okay, pair 0, sorry, for English vocabulary that I'm going to pass. So for each individual value, for sentences are going to be found in the pair of 0 in the data, and English vocabulary is going to be found in this, but this needs to loop. So we can say for pair in data, I am looping through the entire data, only taking up English sentences, passing it to the sentence to indices with the English vocabulary. I am gonna pass the same exact logic for my Hindi, but here the only thing that will change is it will become pair 1 for not English vocabulary, for Hindi vocabulary, for pair in data. So what's gonna happen is my source data and my target data indices are going to be ready, but again I have not padded them. So we will pad all the sequences that I have generated, including the end of sequence, the start of sequence, data in between, and end of sequence that you have generated. So for all of this, we already have a method in TensorFlow which we have learned in the past. It's called preprocessing.sequence. We have something called pad sequence, right? So to convert my source data into padded data, okay, PADDED, padded data, all I have to do is tf.keras, because Keras is my submodule, okay, it's a wrapper on top of my TensorFlow. So Keras dot pre-processing, I'm going to take pre-processing, and inside this we have a module called sequence. We have a method called pad sequence. Now inside the pad sequence, you can pass in multiple different fields depending on what you're trying to calculate. So the first thing I want to pass is the actual source data itself. Okay. I also want to tell my model that the padding I want to done, or the padding I want to achieve, is going to be a post padding depending on the sequence of the length you get. Okay. Remember, you also need to add the padding, which is everywhere. Whenever you find 0, you have already taken an own sort of token called as pad token. So for all the zeros you want to pass, the value it will reference will be nothing but the English vocab, and in the English vocab we already have a padding defined by ourselves by the name called pad. So basically we are telling the program that, hey, listen, what I want you to do is I want you to use your internal method or an API called pad sequences. I am passing in my source data. Please make sure that if you find any length in the source data, which is the largest, which is the maximum value, you please put the padding in the last, but don't give me zeros in the end, because I want the value to be having a sequence called pad. Okay, your 0 is gonna map to pad, because if you write your English vocab, okay, and write it down as a pad here, see the answer you're gonna get is 0. So either I could write my 0 or my padding key has a value map back itself to 0. So I'm gonna explain the program that this is how I want the padding to be done so that I can get the understanding from it later. The same exact thing for source padding or source padded data should also be applied to your target padded data, or your target also will be padded, because without this I'm not going to be able to proceed forward. So I'm going to take the same exact method, paste it here. I'm going to have tf.keras.preprocessing. Inside there is a module called sequence and we have a pad sequence. Here, rather than passing the source data, we will be passing the target data. We will be doing the padding equals to post. The value here rather will be for Hindi vocabulary HIN for the value pad. And once this method returns both, I will also return the program's output as a source padded data and the target padded data. So what is going to happen is my source and my target padding is done with just one function, which can be applied on the overall data. Let's say if tomorrow you want to add more sequences of Hindi versus English texts, what you need to do is these helper functions are then going to help me further in the program to make my processing become slightly easy to deal with, right? So far, we had the original data. We built the vocabulary because this vocabulary is going to help me build any vocabulary for the source sequence and the target sequence. I separate the Hindi and the English separately by calling them its separate vocabulary. We measured the length of what is the vocabulary size of Hindi, what is the vocabulary size of English. We converted the sentences into indices. Once the sentences were converted into indices, I am now preparing my data because then it is going to be padded and I'm ready to go. Now that I have this data prepared, I am also going to convert my actual data into source data, and target underscore data, DATA data is equal to, for my entire analysis called prepare data. And inside this, what is the data? My name of the data or the original file is also called data. The name of the English vocabulary is also English vocabulary, and the name of the Hindi vocabulary is also Hindi vocabulary, and I am going to run it. So now I have my source data ready with me. I have the target data ready with me. Before we print it or before we pass it to the encoder model, let's for simplicity reason print the shape. So the source of my data shape for the given source value is going to be src data, which is what I have printed, dot shape. Okay. I am also going to take the entire line sequence here and I'm going to paste it here. So source data shape, actually it's not source, this is target, right? This is target data shape is going to be TGT, which is going to be target data dot shape. So here you have the source data shape as a 9 cross 5 and a target data shape is going to be 9 cross 7, because so far there is no talks of embeddings yet because I haven't passed it to my encoder model yet. So there will only be with references to the entire data 9 and the value of indices that were mapped to. So 7 or 5 is going to be mapping indices for the Hindi target 7 and source target 5. 5 because the maximum tag that they were able to find in the entire English sentence were 5, and in Hindi sentences they were able to find 7 because EOS plus SOS plus the other value in between is going to give me the 7 value. So now that my data is prepared, now I'm going to let it pass through an encoder model where the embedding will be automatically a part of the encoder itself. So here what we are going to do is we are actually going to define our encoder. Okay. We are going to be writing down our encoder here so that everybody knows that encoder model starts here. Now what I'm going to do is, because encoder model in that encoder that we are going to write is going to be responsible for multiple different operations. So what we are going to do is we will take the encoder as a class which will encapsulate from one of the APIs available, okay, in the TensorFlow called tensorflow.keras.model, so that you can reference that thing internally and create as many layers as you want. So I hope we are aware that usually what happens now, I will tell you what happens is when we write a class, right? You can take a specific node value inside it. Suppose if you have a class called A, right? And then you have a class B which inherits from some other class, and this inherits class A. We have like a multi-level inheritance here. What we are going to do is we are going to reference something provided by TensorFlow. Rather than this, usually I prefer something called Pydantic, because Pydantic is beautiful at handling things like this. But only for a better understanding, what we are going to do is I'm going to take a class called Encoder, okay? And inside this encoder, I am going to reference something called tf.keras.model. Okay, now what happens is in my encoder, I basically want to create some kind of a model that is able to encode. It should be able to do or create an embedding layer. It should also be able to create an LSTM layer with the provided hidden state and all the XYZ values. So what do I do? For this to work, I'm going to take down a reference of encoder here with something called tf.keras.model. Okay. Now what I'm going to do here is inside this class, I'm referencing something called tf.keras.model. Now, because this is a class, I need to initialize things. So I'm going to call something called init, right? Now this none, this is called annotation. We don't need any annotation. We can remove this none. This none is basically to tell the program that you reference this this initializer or this init that you have taken, this constructor will return what, or what values have you taken. So first what I'm going to do is I'm going to take something called input underscore size. After I take input underscore size, I'm also going to take the embed size, and I'm also going to take something called hidden underscore size. Okay. These are the three things that I want the model to know. Okay. After I take this, I want to initialize them with a model called super, not a model. It's an actual value called super. Okay. So how do you use a super? You are going to call the class itself, which is going to be encoder. And for all values of self, I'm going to initialize it, right? This is going to make sure that the references of input, embedding, and hidden will be taken care by everything within the class. Meaning the data flow within the class will become easy. I don't have to go back and reference like my super class. Just take that, directly call the super, pass in the encoder, and reference it directly, right? So what do? I want to create a layer called embedding layer, correct? Which you have taken here, everyone. The self.embedding layer will be nothing but tf.keras.layers.embedding. Okay. So here I'm going to be using the TensorFlow's internal API called embedding, and inside the embedding, I'm going to pass something called as the input size, and I'm also going to pass something as the embed size. So what does that mean? The layer or the embedding layer will be created based on the input size that you pass inside the embedding, so that the embedding layer knows, and at the same time what is the embedding size you want to pass into the embedding layer, that also we are passing. At the same time, I am also going to call myself an LSTM layer. Now tf.keras.layers, with the use of or the method called layers, I'm also going to be calling something called LSTM. So LSTM can be called like this, right? Directly. Inside the LSTM, I'm going to be passing the structure of the hidden state, which is what hidden state do you want, okay? And return state for each individual LSTM cell will be returned as true. So return underscore state for all my model will be returned to true. This is going to be defining my LSTM cell, and this is going to be defining my embedding cell. So whenever a data is going to pass, it will first pass through an embedding state, then an LSTM state, and then I'm going to be returning both my hidden state and cell state, because I want, that is what I want. My output in the model, I prefer you give me the output of two values. I want the hidden cell state. I also want the cell state. Okay. I also want these two values for me to contextualize the answer, get a representation of the input sequence that you just added, so that I can pass it to my decoder with complete analysis. So in order to do that, I am going to separate the responsibility using another structure or another sort of nested function within the class, and I'm going to call it call. Okay. What this call method is going to do is going to take my input, okay? For all specific values of whatever you're passing in the data, embedded data that you just generated will be self.embedding for whatever value of X that you have passed, okay? This predominantly means, okay, here, this will return a sequence of what is the batch size, what is the number of people, or what is the number of sequence of data did you take, what is going to be your sequence length, and what is going to be your embedded size as per the data that we generated. So this is what I am interested in passing. Once this is done, I also want to get the hidden state, the cell state, and other values. Now what happens is when you pass an actual LSTM layer, it will give you an extra output towards the end, and I want to ignore it. In Python, if you want to ignore something, you write down underscore, comma, hidden, comma, cell. Sir, why are we writing underscore, comma, hidden, comma, cell? That's because whenever you pass the LSTM layer, it will give you two things in return. It will give you the hidden structure or the hidden vector and the cell vector, but it also passes the batch size in the beginning. And because I don't want to take batch as an input, I am writing underscore because I want my program to know that, look, I am not interested in taking anything related to batch size. I want to ignore. I am only interested in taking my hidden and my cell state. So here, after the embedding is done, you're going to pass in your LSTM cell, okay? Your LSTM cell, and inside the LSTM cell, you're going to pass your embedded data because LSTM cell time step by time step is going to be taking your embedding, okay? Now, from this entire part, I want to return my hidden and I want to return my cell state. So what's going to happen in this situation is it's a very simple encoder, right? I haven't even taken multiple different, how do I say that, stacking. I have not done any stacking of LSTMs. I have not done any by LSTM. It's a simple hidden LSTM with its hidden size that we will define later. We are also going to take a certain input size which we have extracted depending on the data and the embedding size. So remember, your encoder isn't very complicated and the intention is also not to build a complicated encoder. The point is to give an understanding that, look, the most important aspect about building an encoder is this. Point number one, you have an embedding layer through which you have already padded the data. That padding data is going to pass through your embedding layer. Your embedding layer will return three things for you. It will return the batch size, the sequence length, the embedding size for the given data. But I am more interested in just passing the embedding value and extracting the hidden and the cell structure, and which is what I'm going to return in the encoder part. So this is how it's going to consume your input. It's going to encode the input, and all the encoded input will be in a longer term memory and a shorter term memory, which is going to be your hidden and your cell structure. But after you are done with this, your decoder will be slightly complicated to build, because if I want to build a decoder, what is it that I have to do in terms of making my decoder work? If you want to consume your context vector, okay, let's say I have been given a context vector or a CV by my previous encoder value. So my encoder value ran, gave me a context vector. So now do I do what? I will also take a decoder with, let's say, similar shape of dimensionality of 100 vectors or like 100 cells, right? So hidden state pretty much is going to be 100, right? Now what do? I'm going to initialize the context vector, okay, for this particular sequence that also will be 100. Now what will happen is your initial hidden state will also be, say, h sub of 0, and your initial cell state also will be cell sub of 0 is going to give me some vector context value of 100 dimension, right? So the shape of the data will have, I will have a 9 ordered sequences with the sequence of 100. So 100, 100, 100, 100, 100. This is what I'm going to be passing eventually for both my hidden cell and my cell structure, okay? For whatever batch size. My batch size is basically, I have taken 9 sentences in my original data, right? The importance or the most important thing that a decoder does is it will start learning, or it will start predicting starting with the token called SOS token. Now this is where it becomes very critical for my decoder to first reference something called SOS token. Now why is it important that I reference something called input? Because what happens is I am going to be passing the embedding of a certain dimension, right? It might be 9, 1, say 50 example, right? This is the sentence sequence that I'm going to be passing. This passes through the LSTM. This is going to be my LSTM input and my LSTM output is for 100 different cells, right? So my new hidden state is created for H1C1, H1C1, H1C1 for every single time step that I run this model, okay? So my dense layer representation is going to be passing the entire Hindi vocabulary and the English vocabulary, whatever I have, I'm going to reference that. And for each individual references that I have passed in the model in the dense layer, I am just taking a probability of the SOS token. So after SOS token, after teacher forcing, what do you think out of the vocabulary, the entire vocabulary, which sentence has like the highest probability? 0.7 will have the highest probability of the word ma. If I have another probability, token probability called 0.2, I will have the word kush. So if I take all the probabilities, they match up to 1, but out of them, the maximum probability token or the token with the highest probability will be called 0.7 because I am passing all the source data and the target data. Okay. It will take both your source data and the target data. Okay. Tell me, if I pass in the SOS word or the token SOS word, is that the only thing that I pass in the model? Actually, that is not how it works. In teacher forcing, you have to split the data into step 1, step 2 and multiple steps. In step 1, the input that I have received, okay, will be starting with SOS. The input SOX was available at some index called index number 1. Now, because it is at index number 1, what will be the shape of this particular value? Maybe say 9, 1, right? You have a specific instance of SOS token that you are passing inside the LSTM layer. So if I want to pass an input to the LSTM cell itself, okay, for the decoder, you embed the SOS, which we have already done. When we write the embedding layer, we will be passing the SOS token directly there. If the embedding of the SOS token is taken, right, and the initial state, we will take the initial state, which is nothing but the context vector, plus we will be taking the embedding of the SOS. So the input to my LSTM cell of a decoder will not just be the SOS token, it will also going to be SOS plus the context vector together that passes inside my decoder. Will it not predict for May when SOS is received? So if I take my input value like this, right? Let me copy this. I am happy, मैं खुश हूं, right? Let me copy this and let me paste this. Copy the data here and pass the data here. So what will happen here? For only this specific instance, right? When I am happy is translated to some kind of a contextual vector. We call this as a thought vector. Once that thought vector passes to the LSTM cell of a decoder, my first decoder layer is supposed to actually generate or sort of produce the first initial token representation for the answer, which is going to be my SOS, which is going to be my start of sequence. So the input to my LSTM cell that I'm passing will start with the embedding of both the SOS token and the context vector itself. So the first reference material MA or the token probability MA will be generated when both the references are passed. So that will be happening. So both combined together only is going to give me the token probability of MA later. So LSTM cell is going to have both the references. References are passed, then the LSTM cell sequence by sequence, time step by time step is going to generate new hidden state, okay, new cell state, new hidden state, and the previous token value embedding are going to be passing on to my next model. Then the same sequence repeat until and unless the token probabilities are so low that we have something called the end of sequence token, because the low probability token count is actually happening at the time, because when my data is passed, After a lot of reiterating, the only vocabulary they have is a very small vocabulary. Even if it's a large vocabulary, I know I'm going to be generating an endo sequence because I know there is nothing other than मैं खुश हूं that can be a candidate token for my prediction. So we have something called end of sequence in the last. But the way we do this is we have to set something called teacher forcing ratio. And whatever ratio you put, right, this teacher forcing ratio is going to give it the chance of token probability, let's say 50%. If you do this, you use the actual versus the reference material to find out, okay, do I actually compare 50% of the previous values with my new value generated, and whatever ratio I am passing, I am able to map that exactly in my data. So the point is this, right? Very simple point. Let me write it down very simply. In your decoder, you are going to have multiple different LSTM structures. They are going to be passing each other some internal information about the sequence that you input plus the hidden state that you're passing. So these two things together are going to give me some value in the output, okay? Some sequences in the output that is going to determine my token probability, right? So basically what's going to happen is the decoder part, or at the decoder part, all I'm interested in is each individual cell's output. Hey, are you giving me some answer for the given input? Yes, I have given you the word main, then theek, then who. Okay, each individual structured output, which is going to be many to many mapping here, is going to be what I want or expect in the output. This is what I'm going to be referencing. Okay, this is what I want to reference, because at the time of step number 1, step number 2, and step number 3, what I'm more interested in is for each individual token, what token probabilities do I have? If I have a token probability which is going to be high, that will be my candidate token probability. If the token probability low, then that will be my lower token probability, and I am not going to reference it. Now in real life, okay, in real life, you are gonna find something very similar in your LLM predictions also, okay? So when you talk about the context of a sequence to sequence model or a generative AI model, no, you're going to be doing something called joint probabilities. Joint probabilities, because you have to entirely check your vocab, they do something called beam search, okay? We'll talk about that when I'm going to be talking about something with respect to how do you take a certain path of having like the conditional probabilities of sentences. If I say the word I love dash or I love ice cream and, so after I love ice cream and, what is the candidate token or candidate value for this? Let's say I will say ice cream and pizza. Pizza has the highest like probability to be matching up in this word. So does I love ice cream and I don't know, I can say ice cream and juice. Juice also have enough, what do you say? Looks like juice also is a good candidate for my prediction or generative text called this. So we use a better model than a greedy search called beam search, where you set up the number of beams that will help you calculate what candidate token is the best candidate token for that, right? So that importance is going to be very, very critical. In terms of our encoder decoder model also, if I want to decode something into English to Hindi, right? We are going to predominantly prefer not directly the sentence probabilities, but token level probabilities. But sometimes what happens in some large language models, that the way they are trained, sometimes sentence token probabilities and just individual token probabilities are considered to have like a candidate answer. We do this with using beam search when we are going to do large language models. Okay, of course, I mean, all of us will agree that training a large language model is not something we will be able to do in the class, because first of all, we do not have a label data. We have no reinforcement learning based technique like a DPO, PPO, right? Where we have nowhere the tagging done by a human label. Even if we get a data, the maximum we'll be able to do is going to be called as fine tuning. Apart from that, we are not going to be able to do anything. But at least what we can do is we can monitor something called log probabilities. Okay, so what I'm going to do is, we have in large language model, just like encoder decoder model, what we can do is, for the sequence of the token I'm inputting in the model, I can actually print all the tokens and their conditional probabilities in the given data. I can also do that. I can set up that, can you give me the top 5 candidate values which have the highest probabilities? So rather than getting the dump of every single token with even the 0.00019 probability, we will get only the top 5 values and we choose the value with the top end value. Now remember, it can happen and does happen in rarest of the rare cases that two candidate probabilities are very close to each other. Okay, meaning the top candidate token probability is say 0.6, or let's say a small value called 0.143, and the other token value is 0.14 say 29 or 296, right? Sometimes your candidate token probabilities, depending on the data, can also have problems like this. So there are ways to navigate this. There are ways to handle and control this. Remember, every token probability should combine to 1. Basically, everything should map up back to 100% of the overall value, right? We can have a candidate value that can give you a better probability in terms of an encoder decoder. All I'm looking for is a candidate value with the highest probability for me to know and steadily say that, you know what, after the start of sequence, I have found my first candidate token, which is going to be meh. After the SOS meh and the contextual vector that passes on to your next sequence, you're going to be finding out the next token probability, then the next token, then the next token, then the next token, and it goes on and on and on. And we finally get a good candidate value. This is good in theory, but in practical, what happens? Your neural network of your encoder and decoder, they need to map back to your loss function also. Okay, your loss functions are going to help you and you're going to analyze that. This is not what softmax do for you. Softmax is the reason why we use, if I have multi classes, suppose multiple different classes to predict, your softmax is going to give you the answer for all candidate tokens, for all candidate probabilities. Your softmax is going to have multi-class problems, right? So for your multi-class classification, if you use softmax, softmax will be able to give you a better idea. Now, I know everybody has heard of something called softmax, but let me tell you one of the most important understanding why softmax is actually preferred over sigmoid. I'm sure you guys have heard that sigmoid and softmax are both used for sort of analysis, right? Like if I want to do a binary classification, then of course I can use sigmoid. I want to do multi-class classification, we can use something called softmax. Softmax is going to be good at your output if you have multiple classes. Vanishing gradient is the bigger challenge when it comes to dealing with sigmoid. Your sigmoid activation function or your sigmoid as a probability calculator for your output class is gonna have a problem, and the problem is gonna be of vanishing gradient. Usually what happens in our analysis, if you ever do any kind of sigmoid calculation, right? Predominantly for large language models, there are two very important problems, okay? Softmax is going to give you what others call as, okay, so in terms of softmax, okay, at the time of classification, remember, your softmax calculation are going to give you something called as valid probabilities, okay? These valid probability distribution or valid probability which you get will all sum up to 1, meaning all over my tokens, whatever I'm calculated will map up to 1, making sure any proper sampling strategy that was required with respect to your cross entropy loss, whichever you have preferred, will always make sure any answer, okay, that you're going to give in logits, okay, will be properly summed up to ones, meaning there will be no leakage problem, there will be no vanishing gradient problems, and your mapping tokens are going to be mapped properly. So this is one of the reasons why people usually prefer softmax in large language models over binary class problems, okay? So you have issues that are solved directly by your softmax, okay? And softmax is actually very, very easy. It's not a very complicated part. You actually can implement it in pure Python code. It's not going to be very, very complicated. So I think to implement softmax is actually simple, right? And also having softmax as your token probability technique is also going to work out great for you. Okay. So on that note, sir, if I want to generate my decoder, what do I do? First of all, I'm going to make sure the encoder value is properly set. Now to write down my decoder, I have to take certain steps because I know I am referencing something in the past in the hidden cell. So I have to pass that hidden cell back to my decoder. In order to do that, I will take encoder exactly in the same way how I have taken encoder, right? So I'm going to copy the encoder class as it is and I'm going to write down here, okay? I'm just going to call this point as a decoder, okay? Decoder simply. I am going to remove this, you know what, let's not remove, let's do it like this, okay? Let me comment it out. Yeah, that would be better. So see what I've done right now is I've taken something called my decoder, okay? Now, of course, decoder also you need to have a constructor to pass in what are you going to be giving in the entire code. So I have a self, but rather than my input size, your decoder produces output. So you are going to call something called as an output size. The embedding size also will be the same, not same, but I'm going to be passing the embed size. I'm going to be passing the hidden size in my decoder also. And while I want to reference my model, which is the tf.keras.model, I will not call encoder. I will call something called decoder, which is the name of my class decoder itself. I'm going to be passing the self and I'm going to initialize it. I'm going to say init. I am also going to pass in the embedding layer. So tf.keras.layers.embedding, rather than having my input size here, I'm going to be having something called as an output size. Okay. I'm going to also have something called embedded size. Inside the self.lstm part, I'm going to pass something called tf.keras.layers.lstm. It will also have hidden size. It will have return state. But apart from return state, I am also going to pass something called return sequences. Because at the time of my value of decoder, for every time step, I want to return the sequences to the model back at it again, right? After this, I want to make a prediction at the output at a token probability level. So if I want to do that, I'm going to take like a fully connected layer like this. And I'm going to say tf.keras, okay, keras dot layers, and inside the layers, I'm going to make something called dense. The dense layer will exactly be equal to my output shape or my output size. The reason is for every cent or every sequence you have input in my model, I want an output which is as per the decoder's decoding, meaning whatever it decoded, I want that to be generated at the output. So I'm going to take like this one more layer, which is a dense layer, and it's going to give me this output size. Now, for my output cell or the cell state of my embedding layer or my decoding layer, I of course will take X, but apart from X, I am also taking the hidden from the previous, and I'm also taking the cell state from the previous value. So I am going to be referencing something from the past and I'm going to be passing it into here. So what will I do? I'm going to be taking myself, my X, my hidden and cell. This hidden and cell also becomes a reference internal to your cells also. Doesn't mean you're referencing only outside. So for example, if I take embedded is equal to self.embedding X, this is fine. This is okay. Because here I am also generating something internal to my LSTM cell, which is going to be the self.embedding of the input that I'm passing. But here in the hidden state, rather than calling it underscore, I'm going to say LSTM underscore output. The output you get from the hidden state or the output that you get from the LSTM, the hidden state and the cell state will be LSTM or self.lstm embedded, and my initial state, okay, initial initial state will be passed on as my hidden that is passed and the cell that is passed. If I take this and generate an output is equal to my output variable or the output here will be the self dot fully connected layer, and the LSTM output or the LSTM out is what I'm going to be passing in my cell structure here. So I'm going to copy this, pass this particular thing here, and whatever output I get, I will return two things. I will return the output that is generated by the model. So output comma, I am also going to take something called hidden. I am also going to take something called as a cell state. Now see, In very simple sequence, all I have done here is, in my entire analysis, I have taken a call to call the decoder itself. Now my decoder needs to reference something internally. What is that internal thing? In my decoder class, I want to return output at each time step, not just in the final. So here I made one big changes called return sequences equals to true, because I want my output for each individual time step, not at the once value that we get, right? We have also taken something called as a dense layer because I want to convert, okay, my LSTM output, which is gonna be in a different version or type of data, to vocabularies probabilities that I want to generate. So in case if I want to create output, okay, I will have to take this dense layer and I want to pass a dense layer through it. Now in the call state, what happens? I am taking the embedding size itself, which is going to embed my data. But this time I'm going to be passing something called as a one token at a time pass. So what would I do? My token will be passed one step at a time. So in my embedded layer here, I'm going to be passing the single tokens embedded 1, 1, 8, whatever, 1, 1, 50, 1, 1, something, right? In the LSTM shape output, I'm going to get the LSTM output for that particular time step. Okay. So for that sequence, for that particular time step, whatever is the LSTM output, I'm going to be getting that. And my updated states are going to be taken in my hidden and the cell state. Okay. I'm going to be passing down those into my self.fully connected layer, and then I'm going to be passing both the output of that particular cell, the hidden state, and the cell structure of that. But so far, I have only returned or written encoder and decoder. I haven't combined them yet. I haven't done anything called seek to seek model, okay, which is a sequence to sequence model. If I want to write, I haven't combined them together yet. But so far what we have done is we've taken the data, we've taken the class. Now what I'm going to do, deciding my batch size, deciding the encoder, deciding the decoder, deciding the teacher forcing ratio, the input to my model, initializing the output token, looping through the entire result, and then combining and concatenating those results. I will make sure I will do that in the sequence to sequence part, and then we will train the model. So the only thing we have to build so far is a model called seek to seek, where my encoder is going to be used, my decoder is going to be used, apart from some ornamentation and some new things I'm going to be doing in my seek to seek. Combine them together, we train the model, and we have the initial answers. Of course, since my training data is so small, the answers that I generate are not going to be that great, but at least the understanding internally, we will get a better understanding of that. Okay. What I want to do is basically combine my encoder decoder together, and I want to have capability of building it. Meaning I want to make sure I build up the encoder and decoder in one sequence to sequence model. Okay. Now, in order to understand how do you build a sequence to sequence model, okay, there are certain things that we need to remember and keep in our mind. For example, if you remember, okay, I'm going to take you through a step-by-step walkthrough, then we'll write down a Python program for it. Okay. My input setup was, I have an English sentence, and in the English sentence, I have a sentence like, I am happy. Okay. And I have a Hindi sentence from my entire data set, which is मैं खुश हूँ. Okay, this is like my Hindi sentence. Now, what we did, we applied data pre-processing, okay, some kind of pre-processing on my English and Hindi sentence, and I got my English vocabulary and my Hindi vocabulary. What does the vocabulary look like? Your padding data is going to be 0. Your start of sequence data is going to be 1. Your end of sequence data is going to be 2. Your I will be 3. So basically dot goes on and on. The same thing we got for Hindi. We got this logic as a Hindi vocabulary and English vocabulary. Now the thing is, after we converted this into vocabulary, we have a sequence of values. So for example, English is my source language. I want the computer or my model to understand that my source language will be English and my target language is going to be Hindi. So what was my source sequence? My source sequence for I am happy was something like this: 1, 3, 4, I don't know, 5, 2, 0 after padding. And my Hindi also had a sequence of numbers x, y, z, 1, 2, 3, 4, x, y, z, right? So these are my tensors or my tensor values that I'm going to be using it, okay, in the analysis of my encoder decoder model. Now my intentions are not to do anything crazy, but to just do the data pre-processing and have my data ready, because this is how the preparation of the model is going to go. Now what you have to do is, see, you have to define a class, okay? Because in Python, when I have to define a class, I will call every single thing, encoder, decoder, embedding, everything inside my class. So what I would start with in the beginning is I'm going to start with a class, okay? Let me write it down like this, okay? Let me say Python programs will be towards the left and my explanation will be towards the right and my program will be towards my left, okay? Now, why am I doing this? The reason I'm doing this is because sequence to sequence building is going to be a little bit complicated, because you have to do back propagation plus gradient calculation plus optimization and convergence. Now that program might be confusing because you must have not dealt with those methods and those APIs, okay? So the first thing I will do is I will build a class called seek to seek model. Okay. I'm going to call my class as a seek to seek, and I will inherit the tf.keras dot, I think it's model, right? MODEL model. Yeah. So I'm going to inherit the keras tf.keras.seek to seek. This is going to be my class. Now, of course, I need to initialize the model. This is my parameterized constructor, right? I'm going to have init, right? So I'm going to call this init. So underscore underscore init underscore underscore. And I might call my encoder here because my encoder is written, and I'm going to call my decoder here. Let me take my here. Let me reduce the size of this. Yeah. So what I'm going to do, I'm going to take a class, I'm going to initialize it, okay? And once this thing is done, the constructor is written, I'm going to call the super inside the init, right? So once you write the init, I'm going to call the super, right? This is my parent constructor. So I'm going to call the same model that I've written here, seek to seek, right? So seek to seek, I'm going to call. And of course, I'm going to call self because I want to make sure that the values pass dot underscore underscore init underscore underscore, right? This is what you call as a dunder method, right? Now I want to initialize, okay, my encoder decoder as my class attribute because I want to pass it inside my model. So I'm going to take self dot encoder, okay? Encoder is going to be my encoder, okay? My self dot decoder is going to be my decoder. Now this is what you call as a very basic class, strategizing. Basically what you're doing here is I am just taking a simple class and I am making sure that that class is accommodated, right? I want to make sure that the process of the class continues forward. Now what happens is, once this particular code is written, I have written down my seek to seek, I've written down my methods, I have parameterized it, I have initialized it. Now what I want to do is I want to basically combine everything together. I want to combine my methods, I want to combine everything together so I'm able to start analyzing the data instantly. So we had written encoder decoder initialization, or maybe if I can just show you an example, right? Here, if you can see here, I had written something called self.embedding and self.lstm. I was able to call a variable embedded is equal to self.embedding and pass some value inside it, right? So whatever you take as a self, you can basically call them at any method or function that you have. Now what happens is, right, when I go back to my program, okay, what I want to do is I want to write down a method, okay? The method would look something like this, okay? If you observe carefully, I'm going to be calling my function, or I'm going to be writing a function called call, okay? Whenever you call the call, it's going to do something for you. What is that something? So first of all, I'm going to address everything with self. I'm going to pass inputs inside this, comma, I'm going to pass my training parameter by automatically it's going to be false. I'll tell you why I'm doing this. And I'm going to be writing something called teacher, okay? Teacher forcing ratio is equal to 0.5, okay? I'm going to write down my teacher forcing ratio at 50%. Now, what do you mean by teacher forcing ratio? We'll talk about that. But before I do that, let me write down something called as a source comma target is going to be equal to my inputs. Okay, whatever inputs I'm passing to the model. From the source and the target, I'm going to be taking something called as a batch size. Okay, my batch size will be nothing but TensorFlow dot shape. Whatever is going to be my source is here. I'm going to be taking the same source and I will extract the 0th index out of it. Okay, and I'm also going to take something called as the target length. Okay, target length will be nothing but tf dot shape of target, and this time I'm going to be accessing something called index number 1, and my target underscore vocabulary underscore size will be equal to length of Hindi vocabulary. So sir, why have we written source is equal to and target, source comma target is equal to something like this? That's because, my people, if you understand, what happens is your inputs in the data, okay, I want you to understand that this particular value that you're passing inputs in the data, what will be the format of the data? It will be a tuple value. Okay, inside this you will have the array of inputs and you will have a target value also. Now this will be two dimensional, please understand, that's because of the shape we took past. So here all the sequences that you've taken, your source, okay, in the array format will come and sit in the first part. So your source target will come here and your target array will come here. So you know for a fact that if you take source, it would be at the 0th index, and if you take target, it would be available at the first index, right? Now what happens is your tf.shape.source, okay, when you take shape of something, it will return something like 1,6, meaning there are 6 tokens for the first value of source. Okay, and your target will return basically 1,6 will return one sentence. Each individual sentence has 6 tokens inside it. Okay, if you want to extract the dimension that which sentence am I dealing with, so you have to address that with an index 0, that look, in the tf.shape, because my value is 1,6, I want to know that my batch size is going to be 1. I'm addressing the first batch, and in that batch, what is going to be my say target length? Of course, the same tf.shape, if you take target, you're going to get the value called 6. So basically, your token length or your target length will be 6 and your batch size is going to be 1 because you're currently addressing the first value. Okay, now to get the overall vocabulary of your entire sentence, you know you have 6 in the value, right? So if you take the length of the Hindi vocabulary for that target, okay, for specifically target, you're going to get some number called 6, whatever, depending on the vocab length you have, you're going to get that. So basically you have taken something called as the batch size, you have taken something called as the target length, okay, and you have done something called as the target vocab size. So this will give you numbers like 1,6,6 example, right? Now what you do is, right after you have taken your call, you actually have to process those calls or you have to pass those data. So in order to continue forward into my program, I will write something called HIDDEN, hidden comma, cell state would be equal to self.encode, okay, or encoder, your encoder. You are going to pass the source to your encoder. Now what you're doing, my people, is you are passing your training data to the encoder. Why are you passing the training data to the encoder? Because I want to generate like that final hidden cell and the final cell state. Okay, the hidden state and the cell state. Okay, now what I'm going to do is I'm going to take another variable called outputs. Okay, every single output is I'm going to assign like an empty array. Okay, and I'm going to write this weird looking answer. Okay, I'm going to write this weird looking thing called your input token. Okay, your input token will look something like this. Your target, I will split it, or I will sort of divide or separate all my batch sizes with the source target length like this. Okay, then once I get the input token, I'm actually going to use or utilize something called as the decoder step. How will that look like? For t in range of 1 comma target length, I want to do decoding for every single number or value as long as your target length is, say, suppose 6 sequences. Basically, I want to implement 6 time steps in my neural network. Okay. What I'm going to do is I'm going to take that my output OUT, PUT output comma hidden comma cell state will be equal to self dot decoder. Okay, I'm going to pass my decoder, and inside my decoder, remember my people, you have to pass the token, the hidden state and the cell state. We've already spoken about this. So if you take the input token that you just generated, you're going to pass the hidden cell inside this, and you're also going to pass the cell state inside this. Whatever output you get, you are going to take your empty array which you've defined here, outputs, dot append, and for every individual loop, loop number 1, loop number 2, loop number 3, loop number 4, for every single individual loop through your time step, you are going to append your output into the variable or an empty array declared called outputs. Okay. Now, sir, what is this particular thing that you've taught us so far? Very simple. See, I want you only to look at these 4 lines of code, okay? Hidden, output, input, and for. See, everybody, what I want you to understand is when you pass something called self.encoder src, all you are doing is, if you remember, you have already written something called encoder here. See, this is your class. When you call this, what you're essentially doing is, let's say your input data, okay? Let's say, let me put it down in white color so that it is easily visible. See, what you're essentially doing, my people, is, suppose your input shape is like this. 1 comma, what was the number? 134520. 134520. See, this is your input source or input sequence, okay? The shape of the sequence is a 1 comma 6. Okay, this is going to be your shape and this is going to be your input. What you're doing is, when you convert this into an embedding, each individual token 1 will be converted into a 50-dimensional vector. Your token 3 also is going to be converted into a 50-dimensional vector. Okay, your token 4 is going to be also converted. So basically, you are converting 6 tokens together, totally 6 tokens, and each token is converted into your 50 dim vector or whatever dim vector you want. I am only taking an example called 50. Your embedding or your self.encoder is doing just that, where you're saying that I have one sequence, 6 tokens and 50 embeddings. This becomes like your shape. Okay. This is only for your understanding. You're not supposed to inference it in reality. Okay. Your number 6 isn't going to make sense in your real data or original data. This is only for your reference. Okay. Now, once you convert your data like this, what you're doing, my people, is you are going to take all and each individual values. Okay. When you pass in this individual value to your LSTM, for each individual value here, you are going to generate a hidden state H1 and cell state H1, hidden state H2, cell state H2, okay, C2, hidden state H3, cell state C3. Go on and on. Finally, you're going to generate something called H6, C6. This H6, C6 is going to be my final state, everybody. Okay. This is what I want to pass it to my encoder. Now, who is taking care of all of this? The entire taking the sequence, converting it into embedding, passing down to this particular thing is entirely taken care by just this one single function called hidden cell is equal to self.encoder, because this is the responsibility of an encoder. So what happens is, finally, the output that you're going to get from the encoder is hidden state H6 and the final cell state C6, and each individual value in the hidden state and cell state will be a 100-dimension vector, because guess what? Your input embedding for the tokens was taken as 50, but your output for the hidden state and the cell state after the encoder runs was a 100-dimensional compressed vector. So now, my people, you have this compressed sentenced in a 100-dimensional vector for hidden state and a 100-dimensional vector for cell state. So only after writing one sequence of line, you were able to convert your sequences into hidden state and cell state. And remember, my people, This is what we call as a context vector or a thought vector. This is what the encoder is supposed to output from the answer. Okay. Now everybody, once I do that, sir, why have I written something called outputs equals to empty and input token is equal to some weird number or the weird looking thing called colon? But in Python, what happens is, let's say, if you have a value like this, your target is equal to, okay, 1 comma, what was it? 134520. 13452 and 0. Everybody, if this is your target, okay, can I say my input token, okay, my input token, if I say target, okay, TGT target of, if I write down colon and bracket here, okay, and print the input token, okay, INPUT input token as it is, okay, input underscore INPUT underscore token as it is, okay. If I write this, see, this will give me the entire data 123450. But you know what? If I write down something called 0:1 and run this between this particular data, okay, wait, did I take this as a value 1 comma 3 comma 4 comma 0 and 0? Oh, yeah, right. I should have started with this. Okay. See, let me start with this. Let's say if you have a target column, okay, and this is like a nested list, okay, 1 2 3 4 5 2 0, okay. If I want to extract like the first value of it, okay, don't consider 0 comma 1 at all. For now, just say there is no value inside this. I'm going to write my output token as it is. If I take the 0th index, I get the 1 2 3 4 5 2 0, and inside the 0th index I want 1, okay. If I write both 0 comma 0, am I going to get a number called 1? This 1. And 1 we already know is always going to be a start of sequence. We already know that start of sequence is going to be 1, okay, end of sequence is going to be 2, and padding is going to be 0, okay. We already are aware from our understanding that whenever we take a specific value of, say, a target, right, the output that we are going to get, or the output that we are expecting, is going to give me the first column of an answer, okay. To extract the first column of an answer directly, I'm going to take this particular target list, okay. Inside this target list, if I want a specific value between a set sequence, right, so what I do is, if I take the target and if I say 0, from 0 I want everything, so see, I'm getting all the answer, okay. But what if I say for 0, I want everything from some value beginning to last value 3? See, what I'm essentially doing here is, for my initial sequence 0, I want everything from the beginning to the last 3 value. The reason I'm doing this is because I want 2 things from my data, okay? I want the batch size from my data, and I also want the shape of my data, okay? If I write down, because originally your target token isn't going to be a list, it's going to be a tuple imbibed inside a list, okay? To extract it, I'm saying take everything in the beginning of the list, give me everything, but in that, I only want the source sequence to start at 0 and end at 1. Basically, I'm looking for something called SOS token, okay, in my input token. I am telling my decoder that, hey decoder, you know for a fact that you're supposed to start your analysis or start decoding with looking forward to an SOS token. So easily, if I could just take my input token and remove this target and directly write is equal to double string, okay, equal to string, and if I also mention something like SOS, this also would be a valid program, okay. So what do I do is, rather than passing it like this, I am passing it dynamically for my program to extract just the SOS token. Start decoding with the SOS token. That's what I want, okay. Now the problem here is, your decoding isn't going to start automatically just because you've written the program. What will happen is, you need to start iterating, meaning for t in range of 1 to target length, we know the program is gonna run for starting with iteration t is equal to 1 all the way till whatever is your target length. What is the target length that I have taken in the program? See here, your target length is taken here. You are telling the program that, hey, look, you know what? I have 6 digits or values inside my data, Okay, my sequence that was generated after pre-processing has 6 tokens inside them. Okay, I want to run my code starting from 1 all the way till target length. Okay, when you run and start the iteration, your program will start at the iteration number 1. Okay, your iteration number 1, or maybe let me start it here. Okay, in the bottom, you will start with something called as the iteration 1. Okay, your input token is already going to be 1. Okay, your hidden state or your hidden vector I already know. Your cell state vector I already know. Your input token 1 means I am starting with the SOS token. That's what it means. What happens is you are going to call something called as the output comma hidden comma cell. Observe this piece of code, everybody. Output comma hidden comma cell is equal to self.decoder. See, you're calling this method called decoder. Okay. Now what will happen when you call the decoder is you are going to be calling this function. Okay. The call function. So in the first iteration, your decoder function call is going to be called. Now you guys are aware, we wrote down the call function. What is going to happen? Multiple things are going to happen. First of all, you are going to do something called embedding. Okay, so your input sequence, which is going to be my token, okay, with the SOS token that I'm passing, okay, is going to be converted into a dimensional vector, okay, a 50 dimensional vector, because when you start decoding in the decoder, the first set of decoded statement is going to be your SOS. Okay, what you're doing is you are embedding your SOS and you're passing it to a decoder because you want your decoder to be aware of this. Okay, what will happen is after you pass your SOS token into a decoder, now you want to get the output of your LSTM. So your LSTM's output will be your hidden state, your output of the hidden cell, your output of the LSTM. Whatever your hidden cell, your cell state, your metadata of your LSTM, all these values are going to be generated in the first iteration in this particular part. Once you do that, you are going to pass it to a linear layer called output dot fully connected layer LSTM out. See, the reason you have written a linear layer is because you want to convert those dense vectors or your embeddings into probabilities. Okay, that is why you have a fully connected layer. So what am I doing? I am converting my linear layer, all your LSTM output that you generated, I am going to pass my LSTM output to my fully connected layer, and now I have probabilities for each individual token value. Okay, you're going to be passing for each individual basically you're going to have your token probabilities for all individual words. This is what you're going to be passing. The main differentiator between your decoder model is your decoder model first of all relies on some kind of a context vector to even start decoding. Okay, so one of the major differentiating factor, okay, for a decoder to work is both your encoder are also going to encode. If you see here, you're going to be doing embedding in both encoder also, you're going to be doing both embedding of the decoder also. But the major difference between your encoder and decoder, okay, to translate a set of sequence would be one major factor. Whatever language is your source language and whatever language is your target language, okay, depending on the source sequence and the target sequence, if you take a context vector and the context vector genuinely is able to understand and after a lot of iterations understand the deeper meaning and alignment between your data, well, you will not have any issues. Okay, so you're not going to have any issues directly as it is as going to be a problem. Okay, I said that what I did in my program when I called it, I'm basically generating sort of like probabilities. Okay, now let's say your output of the decoder is going to be like this. Okay, your output from the decoder is going to be all probabilities. So probabilities for the first sequence will be, I don't know, 0.3 or 0.1, comma 0.05, 0.02, 0.7, 0.1, 0.03. See, what you did here is your output here of your decoder just helped me generate probabilities for each individual token. See, 0th index, 1st index, 2nd index, 3rd index, 4th index, 5th index, or the number that you have generated here is this one. What is the number? 134520. So 1, 3, 4, 5, 2 and 0. For each individual sequence, I now have some kind of an output probability. Okay. You have gotten the updated hidden state also. See here in the program, the only reason we are doing decoding here is because LSTM for that time step is going to generate my answer, but I also need to take the updated hidden state and the cell state for the same embedding. See, I'm passing the same embedded value here. So basically what you're doing is at the time of your SOS token generation, you are going to be updating the SOS in the hidden state also. Your context vector plus this state, including hidden state, you're going to pass it to the next particular vector. Okay. Then whatever is generated here, you're going to generate the combined hidden state of that. Again, the token is going to be passed into the next decoder. So to follow the sequence, all I have to do is just make sure I loop through the entire code like this. Okay. But the only difference in the code is what I want to achieve. I want to make sure that every single time I generate an output, okay, every single time I get an output, I don't want my output to be compared against the actual prediction. I want to compare it against an actual reality of the data. In order for you to compare it against the actual reality, you have something called teacher forcing. Okay. And if you observe carefully, usually if you take a teacher forcing value of a certain level, okay, say if you take a teacher forcing value of say 50% or a teacher forcing ratio of something, what you're essentially doing here is you are asking the program that, hey, look, I am generating the answer, okay, for every single input sequence that you have passed, and for each individual time step, I'm generating the answer. Can I take 50% of the time? I don't rely on probabilities. I rely on the actual data that exists in the data set. Okay. Meaning I'm going to compare my real actual data with the prediction and not with the probabilities that I have generated. I want to compare them. So 50% of the time I'm going to be using teacher forcing for my data for inferencing. Other time I'm okay comparing the probabilities. Okay. Either from teacher forcing or either from prediction. So what happens here is in this program, you need to mention a piece of line of code. What will happen in that is, so let me just write it down. First of all, let me write it down until whatever I wrote here. See, first of all, I'm going to generate my seek to seek model with a simple class, right? So what do? I take a class. I'm going to take a seek, okay, SEQ, seek to seek. Okay, this is going to be my model. I'm going to inherit this with tf.keras dot model, okay, dot model model. I'm going to inherit this. Once this is done, I write down the underscore init. I don't want annotation, so I'm going to remove this. Okay, I'm going to remove the annotation here. I'm going to take self. I'm going to take encoder. I'm going to take a decoder. Okay, what I'm going to do is I'm going to take super here. Okay, and inside this super, I will run my seek to seek parent constructor, call it as it is. So seq seek to seek, I'm going to pass, I'm going to call it self, okay, self self, and here dot underscore init, okay, I'm going to call this, parameterize it, done, okay, it's callable now. Self dot encoder, okay, encoder is going to be my encoder, apologies, encoder, and my self dot decoder is going to be my decoder. Okay, this is very much simple. Now I'm going to write something called call, and inside this I'm going to pass self. I'm going to pass something called inputs as it is. I'm going to pass something called training is equal to false. I want this flag to be used later. Okay, I'm going to use something called teacher underscore forcing underscore ratio. Okay, I'm going to add it to something called 0.5. This is also something that I use. My source data, comma, my target data is going to be all the inputs that I'm passing in the model. So I'm going to say something called as inputs. Okay, INPUTS inputs. My batch size is going to be defined by my tf.shape, and inside the shape I take source and I only want the first value, which is going to be my batch size. My target length is going to be divided by tf.shape. I'm going to take the same value called target, and inside this I'm going to take something called 1. This is going to give me the target length. I'm also going to take the overall target vocabulary length. So I'm going to say vocab underscore size is going to be length of Hindi vocabulary. Okay, I'm going to pass this data. So this is going to help me process the data in the future. Now what I want to do is I want to do encoding. Okay, just my encoding will be done with one single call. Say hidden state and cell state is going to be equal to self.encode. Okay, self.encode, and what I'm going to do is I'm going to encode inside my self.encoder function. I'm going to call my encoder function and I'm going to pass the source because I want to encode. Okay, now I will take an empty output array called out underscore puts is equal to outputs outputs equals to an empty array. This is fine. Now I'm going to start with my SOS token because that's what I want, right? The SOS token is what I want to start with. So if I want to start with this, I want to take my input token to my model will be whatever target you give, TGT, okay? In that, give me all on a specific sequence from 0 to 1, okay? So let's say 0 to 1, this is what it's going to give me as a batch size versus the start token key as 1. Now what I do is I actually start something called decode. Now in the decode part, you have to be very, very careful, okay? TGT target. In the decode part, I'm going to say for I or say T in a range of, I'm going to start with something called 1 comma target length. I'm going to loop through the entire thing until the target length of it. So TGT underscore length. Now for each individual value, I'm going to generate something called output comma, hidden comma, cell is equal to self dot decoder. Okay, I'm going to call something called self dot decoder. I'm going to pass my input token, which is going to be one of the things that I pass to my decoder, but I'm also going to pass the updated hidden state. Okay, and I'm also going to pass something called cell state. Okay, so this is going to give me an understanding of the previous hidden state updated, right? So for every single empty array outputs, for every single loop, I'm going to append for each time step whatever output I have received. So I'm going to update it or append it to my empty dictionary, empty list called outputs. Now this is where the actual logic comes into picture. Okay, this will be slightly complicated to understand, but don't worry, I will explain. See, if the training is happening, okay, your actual value here is training equals to false. Okay, by default you have passed in a flag called training equals to false. As long as you have passed in the false is equal to false, okay, I'm going to pass it and make it go to else statement. Okay, I'm also going to write something called pass. So if your flag is false, okay, as long as your flag is going to be true, it's going to enter into this condition. As long as it's going to be false, or if it is false, it's going to go inside FALSE, okay, it's going to enter into the else condition. So what if I have passed the training equals to true? Then I am preferring using something called teacher forcing. Okay, so I will take teacher underscore force is equal to random dot random. Okay, random dot random, I'm going to take like this random dot random part. If this is lesser than my teacher forcing ratio, okay, I'm going to write something called teacher forcing ratio. If that is the case, then my input token, okay, is going to look like this. Your target value, give me everything from the beginning, but for the target token T, start with T plus 1. Okay, I'll explain this. Don't worry, everything will become kind of clear. Okay, if teacher force, okay, let me write down if teacher, TEACHER, if teacher force, okay, if teacher force, else tf.argmax, okay, inside the tf.argmax, what I want you to do is take all the values of your output, which is going to be this. Okay, I'm going to say that my axis is going to be -1. Okay, there is a reason why we do that in axis also. And the data type of my output would be output underscore type will be TensorFlow in 32-bit size. Okay. Now, sir, why do I need to give all of this? Don't worry. Everything will become clear in about a second. Okay. Otherwise, if there is no teacher forcing that I'm including or the value matches, I'm going to take my input token as it is and I'm going to say tf dot argmax. Okay. And inside the argmax, I'm directly going to pass something called as my output. I'm going to take my axis same, and I'm going to take my data type as it is that I have passed. So I'm going to take my axis here, output here, and this here. Now, sir, what have we written here? What is the logic behind this? It's slightly tricky to understand. Well, don't worry. Let's actually understand it one by one, okay? See, in order to understand this piece of code that you've written here in the cell state or in the call state, you also need to understand how are you going to be generating the output, okay? What I've essentially done here is I have written a class called seek to seek, okay? Inside the seek to seek, I want to combine all the answers because I have clearly done something called decoding of the value. So what am I going to do is, to make it make sense, I'm going to go and teach you this. In the indentation of for, I'm going to write one more logic, okay? If outputs exist or is a true condition, I'm going to return two things, okay? I'm going to return tf.concat, okay? tf.concat. I'm going to return all the outputs, okay, as one, and the axis will be equal to 1. Will be equal to 1. Otherwise, okay, otherwise in the else condition, what do? We return return return. I will return all the tf dot zeros, okay, available in the data, and I'm going to pass it like this. Your batch size, I'm going to also pass in the 1, and what was the value? Target vocabulary size, right? TGT underscore vocabulary and underscore size. Okay, good. So allow me to copy this entire code one by one, and let me pass it to you, and let me give you an idea, okay? See, let me start line by line, iteration by iteration, so that you guys are able to understand what exactly are we doing, okay? Line by line, iteration by iteration. See, first of all, I am starting with iteration number 1. Okay. When you start with iteration number 1, you encounter this particular code, output equals to, or output comma hidden comma cell is equal to self.decoder input token hidden and cell. Sir, what are these values and how do we work with it? Tell me one thing. Your input to decoder are how many things? Your input to your decoder will be two things. What are those two things? Number one will be your SOS token, not directly passing it as string, but converting it into a vector of sorts, or some sort of an embedded value, right? You also have the hidden cell as some kind of a 100-dimensional vector. You also have a cell state as a 100-dimensional vector, okay? This hidden cell of 100-dimension vector and 100-dimension vector, this comes from the encoder part. This hidden cell and your updated cell state and hidden state is also your H6, C6, meaning the encoder's last value was H6 and the last value was C6. So my thought product or my thought vector was H6 and C6, which is my hidden state and my cell state, and this is going to be my input to the decoder, okay? Now the problem is, for my decoder to work, what you did is you called another method in the decoder like this. What you did is, to use the decoder while calling self.decoder, you actually ended up calling the decoder module itself, right? So when you called something called self.decoder right here, you basically gave a callback to your friend saying that, hey decoder friend, can you help me? Now in the decoder, what you do is your output here, the output it generates here, okay? I already gave you guys an idea here a while ago that this is going to generate some kind of probabilities for you, okay? So what happens is, for every single decoder output, you are going to get some, how do I say this? You're going to get a value of all the token probabilities, right? So your output will look something like this: 0.1, 0.6, 0.7, 0.9, some kind of probabilities you're going to generate in the output part, okay? The shape of this will be 1, 1, 6, okay? 6 probabilities, one individual token length for entire sequence or entire sentence 1, okay? Now what happens is, because among all of this, let's say 0.7 has the highest probability. Sir, how were you able to map 0.7? SOS, मैं, or it would be say padding, SOS and मैं. may has the highest probability of 0.7. So that means my decoder says that the probability that the next sequence may should be higher. So we got the highest probability of may in this variable in the output. Sir, what about my hidden cell and cell state? This hidden cell and cell state, or this cell and hidden, is going to give me the updated vector that passed both the context vector in the past and the SOS token. So you're going to update this, and your updated cell state and hidden state will be generated here. So your new hidden state and cell state that I want to pass to the next sequence is ready to go. So this output comma hidden comma cell is handling that. Okay, very, very good. Every single token probabilities that I have generated, I am going to add it or append it to my empty list that I have taken called outputs equals to this empty array. And inside this empty array, every single iteration, iteration number 1, iteration number 2, iteration number 3, iteration number 4, no matter how many iterations I'm doing, I'm going to take for each individual iteration, your output 1 is going to give you the prediction called may. So currently you're going to have a value of may in your outputs. So that is done. Very, very good. Now I am deciding to run something called teacher forcing. Now, by default in my program, I have not given teacher forcing true. I have not done any teacher forcing. So by default, it will go inside my else block because this condition does not become true. Okay. In Python, if a condition has to exist, that condition needs to be non-empty. Suppose 3. And if I say if A, return or print true. Okay. If I can write like this, print true. Okay. Otherwise, I'm going to say else. Okay, I'm going to say print false. Okay, as long as the values are non-empty and your flags are very clearly defined, everything will be true. If you say A is equal to false, of course the false will be printed. And if you say A is equal to true, of course your true is going to be printed. So the point is, whenever I've taken a flag, I want the option for you guys to do teacher forcing. Now, let's say, sir, my teacher forcing value flag is true. If it is true, you're gonna come inside this condition. Now listen to me, guys. Sir, why do you take random.random? Because this random.random will generate a random number like this, 0.3. Okay, for example, if I show you an example, okay, random, okay, random.random, okay, random. If I write it like this, see, you're gonna get an answer called 0.7. If I run it again, 0.6. 0.7, 0.7, 0.2, 0. If I run it again, 0.8, 0.7. Point is, random.random is going to generate some random number between 0 to 1, and I'm going to call that thing as 0.3. Example, I got a random number generated called 0.3. Of course, 0.3 is lesser than the teacher forcing ratio I passed, something called 0.5. So what's going to happen here is, we will come to this part of the code, input token. Okay. Now, see guys, input token in the end of iteration 1, when you passed it, what you're essentially doing here, no, is you are going to have a target token of all the values. See, your input token here is going to be something called as target. Where did we take last target? My target was here, right? TGT. Can you see here? This was my target. And do you remember how target looks like? My target looks like this, right? In Hindi, 1, 4, 3, 2, 6, 0, right? My target looked like that. In that particular target, okay, I want to get every single value in that target, okay? But what am I doing here is, I am using a variable, okay, called t colon t plus 1. If you guys know Python well, if you started with the original index to index plus 1, it is always going to be 0 colon 1, 1 colon 2, 2 colon 3, 3 colon 4, 4 colon 5, 5 colon 6, 6 colon 7. The sequence itself starting with it and its number 1 or 1 plus 1. Here, my t value is nothing but the iteration you are currently looping at. So whatever iteration you are at, that iteration plus some number is what you're going to be getting. For that sequence, I'm going to check whether teacher forcing equation or the teacher for equation is a true condition or whether it is a false condition. Basically, what I'm trying to do here, guys, is a very simple concept. Okay. All I'm trying to tell my program is this. Hey, when you take the input token, okay, or when you're generating the input token for me, okay, are you going to have something like this? My input token, my prediction word my next token input, the next token actual thing, right? So for example, if you take a teacher forcing value of some value, right? A teacher forcing value of 5, there are 50% chances, because I have my teacher forcing ratios 50%. It means use actual targets for prediction. Okay. And if it is less than 50%, what you're going to be doing is you're going to gradually move to something called tf.argmax. Sir, what do you mean by tf.argmax? In your entire token, okay, of all the probabilities that you have, okay, you are going to find out which is the maximum value for that particular sequence given the output. And you guys already know that here also I am passing output, here also I am passing output. And what does output have? Output have all your token probabilities, right? What I'm essentially asking the teacher forcing to do is, if and when my model has a lesser value than the teacher force method, use the actual prediction against the data to compare and give it to me as an input token. Otherwise, if you don't match that, you go inside and you calculate whichever is the maximum token generated, for example, 0.1, 0.7, 0.3. Among all three, the maximum token that had the maximum probability was 0.7. So my token is going to be mapped to my output token, or my token that is going to be passed to my input. All I am doing in the program is a very simple thing. I am telling my computer program one thing. Hey, can I please take all your values, okay, all the values that you have given me so far, and can I just concatenate it together to my output? Okay. If my outputs exist, if they don't exist, return everything as a 0. Make sure everything as a 0, but don't give me an error. Return everything as a portion of 0, because I don't want my next sequence to go with an error or have error. Okay. Usually your else condition is only a plan B, or what if something goes wrong. But otherwise, if nothing goes wrong, you retain your seek to seek model as it is. So if I run my seek to seek model, what I have currently from my seek to seek model is I have a flow diagram, or a flow where every single instance of my data is now going to be encoded, passed it to a decoder. My input token here is going to tell me which token among my output has the highest probability for the print, or which token is my actual token for the answer. If I passed in I am happy, you passed it to the decoder, decoder returned SOS, and after SOS, what is the next sequence in the iteration? The next sequence on the iteration will be may. SOS and may, if I pass it with the context vector, and what will be the next sequence? The next sequence would be something called as push. SOS, may and kush, if I pass it again to the decoder, what will be the next sequence? Who. SOS, may, push, who. If I pass it to the sequence again, I will get the answer called as end of sequence. But yeah, I have found out my answer and my answer is good to go. But you cannot run this model directly if you have not trained the model, or if you are not passing to train the model. So sir, how do we train the model? Training the model is going to be very, very easy, because what you need to do is you just need to pass what will be your source data, what will be your target data, what will be your optimizer, and all of that stuff. So if I say define train, okay, of my model, what will I pass in the model? I'm going to pass something called model directly. I'm going to pass in the source data, because this is what I have in my source. I have a target data, so I'm going to call it as a target data. And the epochs I want to run my model, it will be, say, for example, for 100 epochs. I want a lot of forward propagation and backward propagation. Now, Before training the model, you need to define your loss function and you need to define your optimizer. So my optimizer will be equal to tf dot Keras dot optimizer, okay, optimizers, and inside the optimizers, I'm going to take an Adam optimizer, okay. Inside this, I'm going to pass in a learning rate of, I don't know, 0.01, right? Because this particular answer is going to be multiple classes or logits, I'm going to have a loss function, but the choice of loss function I will choose is going to be different. I'm going to take something called tf.Keras.losses. You have a model called losses. Inside the losses, you have something called sparse categorical cross entropy. Inside this, I'm going to pass something called from logits is going to be equal to true. And I'm going to pass something called reduction will be equal to none. Sir, why am I passing something called loss function is equal to tf dot losses dot sparse categorical cross entropy? What is the reason behind it? And is there an intention of calling something called sparse categorical cross entropy, right? Yes, there is a reason behind it. And the reason is also very, very simple. See, what usually happens at the time of your prediction or at the time of your data is, of course, you know that if you take a sparse categorical cross entropy function, what's going to happen? Whenever you use a multi-class classification, okay, whenever you're going to do any multi-class classification, because you want to choose words among multiple different types of vocabulary, for multi-class, we usually go with something called categorical cross entropy, okay? Sir, the reason why we are using something called sparse is because, okay, your labels or your train labels are actually not your data itself, but they are sequences 1, 3, 5, 4, 0. Now, I don't know that these are just values. These are just integer values directly. These are not one hot encoded values. These are not unique. These are some kind of label encoded values of sorts. Don't say it label encoded, but these are integer values with labels as a number. Because these are numbers and target labels and not one hot encoded values, and the classes I want to predict are going to be multiple classes, I don't have any other option but to use sparse categorical entropy, cross entropy. Because cross entropy, okay, in machine learning, you must have learned this. Cross entropy will measure the delta, the difference between the predicted distribution and the true probability distribution. Okay, so your predicted distribution versus your true probability distribution, if I want to compare the differences between them, cross entropy is like the best thing that can help me do that. So for my example, for the problem statement I'm solving, you always have to prefer something called as sparse categorical cross entropy. But the reason is the sparsity exists while while sort of working with padding values, at the same time not having true labels like one hot encoding. So that would be sparse categorical entropy. Sir, why did you take from logits equals to true? See, my input is going to be having a raw model output. I'm not going to have softmax probabilities at the output. So what I want my model to do is give me logits, is give me probabilities, right? And reduction equals to none means I want to return the loss for each individual token calculated. Okay, meaning I don't want you to give me or calculate something called as a mean Huber or an average loss. I want for each individual token, I don't want you to do any kind of reduction. I don't want you to collectively calculate something and give me the average for losses. No, I want none of that. I want each individual token to return me the loss so that I can take that loss and use it in my function. So remember, the way you define your loss function will make or break your encoder decoder model. Okay, if you don't know what loss function you're going to be using, pretty much you're going to be screwed. Okay, so remember, usually while working with sparse or working with an encoder decoder model in a textual analytics, right, you preferably go with a sparse categorical cross entropy. There are conditions where you can just go with a binary cross entropy depending on what you're trying to predict, but then it beats the purpose of your model of encoder decoder. You could just have a direct RNN or a bi LSTM or a stacked LSTM that can give you a binary output, right? You can take a simple RNN and get the answer. Now, everyone, since we've defined our training model and we've defined the optimizer, sorry, the loss function and the optimizer, what you need to do is you need to define something called the train step. Okay. Now, guys, I want to show you how to calculate gradients and to calculate the new updated weight values while doing backward propagation. Okay. So what will happen here is, if you want to do that from the beginning, what you need to do, you need to take your source, you need to take your target. Now, this piece of code might get a little confusing. I am not going to deny, because this is going to expect you to have a certain understanding of TensorFlow. But what I'm going to do is I'm going to write down something called with tf.gradient tape. Okay. Now I'm sure you guys may or may not have heard this in the past, but let me explain what gradient tape is. Okay. I'm going to first write down my entire function. Okay. I'm going to say tf.gradient tape as tape outputs is going to be equal to my model, and inside this model I'm going to be passing my source and I'm going to be passing my target. Okay, and after this I'm going to passing my training flag is going to be equal to true. I want the teacher forcing to happen, and for that my teacher forcing ratio, okay, is going to be kept at 0.5. okay, I'm going to pass it. I could have passed the default 0.5, but yeah, let's actually pass it at 100%, right? Let's do all the teacher forcing method. Let's say target underscore labels will be equal to the target. I'm going to pass it all the way from here. I'm going to pass it from 1, and my sequence underscore length will be tf dot shape, and inside the tf dot shape target labels, and inside the target labels I'm going to take the first part of it, index 1. Outputs is going to be equal to your outputs value, and inside this I'm going to take this, but this time I'm careful that I'm only taking from sequence length and then allow everything else to pass through. Okay, and if I will take a mask, how much of the data to allow and padding to remove, I'm going to say tf.cast. Inside this I will take target labels. Okay, if the target labels are not equals to in the Hindi vocabulary, which is going to be my target, I will take something called as a pad. Everything wherever you see a pad, okay, make sure that it is taken as a tf.float of 32. Let's take a larger size. So tf.casting is done as long as my target labels do not match to Hindi vocabulary parts wherever the padding is done. So loss is going to be my loss function, okay, for each individual value of my loss function for the target labels, okay, that I want to predict for the given outputs that I have generated. So for this, I am going to calculate my overall loss as a loss function multiplied by the mask I have generated in 0 and 1. So my mask will be 0 if the padding exists. My mask will be 1 if the value has an actual number of probabilities. So total loss, TOTAL, total loss is equal to, I think I can use something called reduce sum, right? Give me a second, right? So wait. Do we have, so input tensor, okay. So tf dot reduce sum, I have it passed in my array. So okay, so 1 plus 1 plus 1 3, 1 plus 1 plus 1 3. So x is taken, so this is what, 3 of 3, right? So if that is the case, then can we take all the gradients that we have calculated? Okay, so tape dot gradient, if I take in like the okay, so can I do it like this? My total loss before going to the gradient calculation, let's reduce the sum. So reduce sum for my values in loss, right? So this will be 1 plus 1 plus 1, so 2 2 2. So for each individual value, say loss, my total tokens that I have passed will be tf also gonna be reduce sum, and whatever is going to be the mask, I'm going to pass that. So my mean loss, now that I have the value of it, I will take total loss and divide it by my total tokens. So that would be this. Just so that I don't divide by 0, I take 1e to 8. So basically I'm going to make sure that there is always a small error in the program so that I don't divide by 0. And my gradients, okay, will be, so gradients will be equal to, for all the value that I have found in the gradient, okay, so gradient gri dot gradient, I'm going to pass in the mean loss for my code, and for every individual trainable value, which is going to be my weight value. So trainable underscore variable, if I'm not wrong, I have forgotten how it is it called trainable underscore variable? Is that how it's called? Okay, so it's going to be called as a trainable variable. So we are going to pass v1 dot trainable variable. No, but this is, wait, is it trainable variables, right? So trainable variables, I'm going to take this, I'm going to copy this here, and I'm going to pass in the model dot trainable variables, right? So wait, I have passed in the gradients, done. Okay. The optimizer that I have taken. So optimizer dot apply gradients to whatever I have taken. That gradient I'm gonna be applying. So gradient or dot gradients, I have forgotten this also. Apply gradient or gradients, I am assuming gradients. Apply gradient TensorFlow for optimizer, let's do this. So tf.optimizer.apply gradients, right? So this is dot apply gradients. I'm going to come over here, I'm going to apply something called gradients. Now for my gradients part, I know for a fact that the values are together, so I'm going to zip them. I'm going to pass in the gradients as it is. So let me just take the gradients, pass them as it is inside this. And my gradients are, so does that mean that my gradients are zip of grade? Okay, wait. So wait, apply gradients. I applied gradients. Inside this, I will take a zip of something. So inside this, I have passed my gradients. And once I am passing my gradients, I will take all the weight, all the values that are assigned. So trainable values are also going to be this. So let me take all my trainable values here. Let me paste them here. Okay, now that I have passed in the weights, I will return their mean loss, right? I will take the mean loss and I will run it. So in that case, if this is going to train my model, can I have a source sequence, right? So suppose if I want to input underscore size of the model is going to be length of my English vocabulary. Let's see if this actually runs or not. I might have an error because I have not seen the syntax of it, but let's see if this works. Output underscore put underscore size will be equal to a length of, I'm going to pass in the Hindi vocabulary also as it is. So Hindi underscore vocab is right here. So my input size and my output size is sorted. My embed size is going to be 50 because I want each individual sequence to be a 50, and my hidden underscore size will be equal to 100. So I have defined the sequences done. And now if I initialize the model, so in case if you want to see it carefully, so let's actually do this, right? Initializing model with colon, I'm going to come over here. I'm going to print F double quotes for your understanding. I'm going to write things like my input vocabulary size that I've taken in the model is going to be colon input size. So I'm going to take input size is going to be my input vocab size. I'm going to copy this. I'm going to paste it here. And I'm going to say that my output vocab size, your output vocabulary size is actually going to remove everything. Control G, I'm going to remove everything. I'm going to call this as a output vocab size or my output size, right? This is also done. Once I have taken my output vocab size, I am also going to print my embedding, right? So embedding size is going to be my embed size. So whatever is my embed size, I have taken that. And again, I'm going to take print f double quotes of same exact thing. I'm going to take my hidden size for the LSTM cell is going to be looking something like a hidden size. So here, so what, 20, 27 embed size, let's make this M smaller, embed size is gonna be 100, correct? Now, if I initialize my encoder, so encoder is equal to encoder model, okay? Inside the encoder model, I'm gonna pass something called as the input size, okay? Embed size, I'm gonna also pass in something called as the hidden size. So if I have taken this as my encoder part and my decoder, okay, is going to be, let's say, decoder. Let's just test it once if this works. If it works, we can run it entirely together. So decoder would be what, say output size, because that's what you're going to run. You're going to pass in something called embed size, and we are also going to pass something called hidden state or hidden size. So once that is done, I'm going to create my model, and the model here will be seek to seek, and I'm going to pass my entire seek to seek model with the encoder that I just passed and with the decoder that I just created. So encoder, decoder are now passed inside my seek to seek model. I'm going to run this. Okay, done. Encoder, seek, decoder are part. So if I call it once, so let's just call it as a dummy source of my entire data. TF dot, let me run it for zeros, and inside this 1:5, okay, D type that I'm going to be passing inside this, comma, D underscore type is going to be TensorFlow dot int 32. I think this is enough. And let me also take a dummy target. Wait a second. TGT target is equal to TF dot zeros 1,5. D type is equal to this. So just run the instance of my model, right? Underscore equals to model. And inside this, I pass in my dummy source. So this is going to be this one of the output. I'm going to pass in my dummy target. This is passed my training. What was the name that I took? Did I take training equals to true, right? Let me just copy this. For now, just to run it faster, let me just call it false for now. Okay. So if my model is run, how many parameters do I have? That the total trainable parameters. Wait, if my value runs for the trainable parameters will be what? How many values do I run it with? So do I give trainable parameters as an instance? Maybe not. Maybe not. So if I just train the model directly here, if I say train, and if I pass in my model here directly, and if I pass in the source underscore data, comma, and if I pass in the target underscore data as it is, and I'm going to be passing my epochs, let's reduce the epochs to 50 for now. Okay. So this is gonna initialize. Yes, I knew it. So there will be a problem with the tensor shape. Expected initial state, but gotten keyword argument initial state. Oh, wait, where did I make this mistake? FV. Let's calculate this. Initial state. Wait. So initial state is gonna be in this particular thing. Where have I passed it? So my initial state, right, is going to be the value. So let me run the encoder decoder class module, and let's say training. If there is any tensor operation issue, we are not having tensor operation issue. Awesome, cool. Okay, let's understand line by line, process by process, and actually with some examples to understand, okay, how do the process flow actually happens, right? What happens is you have a function called train step, okay? What this training step does is it takes two inputs called source and my target. I already told you in the beginning that this is going to be my source and this is going to be my target. Okay, I'm going to have a sequence of these numbers that will be mapping to its original vocab, but I have currently the source and my target. Now remember, these are numbers. These are not values. These are not string values. What do? I use a method. Actually, this is a standalone, very deeper method. Now, what gradient tape is used for is if you want to do forward propagation plus backward propagation in the neural network, and for forward propagation you want the answers and backward propagation you want the answers. So basically all the weight updation, all the values of your weights, all the initial training parameters, if you want to get an access to all those numbers, you have gradient tape as a method. It will record all your back propagation all the way through your forward propagation. Okay. What I'm doing here is I in a neural network will allow something called as a forward propagation. All of you know this. My output from the forward propagation is going to be very simple. I already have written a method here called output equals to, if you can see here, output equals to model of SRC target training is equal to 2 and teacher forcing equals to 1, right? For my forward pass, what's going to happen? I'm going to have this piece of code going to give me some outputs. Now, what are those outputs going to look like and how does it work? Well, it is very simple. See what happens. You have a source word and you have a target word. Okay. Now, when I say word, please understand I'm talking about an array. Okay. Suppose if the array was 1, 3, 4, 1, 3, 4 and 5, 2, 0, if I'm not wrong, 5, 2, 0, right? This is your target sentence. This basically means your start of sequence, I am happy, end of sequence. Okay. And in the end, if you observe very carefully, everybody, in the end here, you have a sentence or you have a number called 0 because we did something called post padding. Okay. It means your letter would look like this. S start of sequence, I am happy, 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 end of sequence, and your padding token pad will come to the last because you have done padding in the end. The same exact thing will happen in your Hindi also. So if your target word is say some number like, I don't know, 1, 12, 14, 2, 19, example, some word, you're also going to have a Hindi word that looks like this. Start of sequence, मैं, push, who, end of sequence and padding. Okay. Because we've done post padding, everything is going to go towards the end. This is how my model will look like. When I take my source and my target and I run this piece of line, which is output is equal to model, source of target, training is equal to 2 and teacher forcing is equal to 1.0, you know for a fact that you're going to be running your outputs is equal to model. You have created a sense of model here. If you can see here, you have taken a model and the model is nothing but your sequence to sequence model, meaning you're calling your encoder decoder also, right? So that's why I have taken something called model here. What's going to happen is you are going to run this model for a size like this. So your output shape size will be 1, 5, vocab size. Okay. Assuming you have vocabulary of 25 such words in your Hindi. Okay. In the first iteration, you will get the probability for the first position, meaning you get a prediction called the word main. In the second iteration, you're gonna get a probability for the second iteration. You're gonna get the second position value called khush. Okay, main khush. In the third sequence, you're going to get a probability of the third sequence called main. In the fourth one, you're gonna get end of sequence. In the fifth one, you're gonna get something called padding. What my outputs or my output is going to give is for each individual iteration, it is going to give me a probability of all the tokens 0.1, 0.2, 0.7 because my word Hindi main comes at the third index, which is also for the third value main. The same thing will happen for the second probability, third probability sequence, fourth probability sequence, and fifth probability sequence. So basically, your value outputs is going to give you all probabilities for your source in target sequence, and all of these are going to be saved in your outputs. So every single probability value as a large array, like a two-dimensional large array, is going to be saved in my output position. Now the problem is I already have gotten the output, but I want to map my maximum target or my maximum probability with some kind of a target label. In order for you to get your target table, you have this thing called TGT target. Give me everything starting at index position 1. Why do you start at index position 1? Because 0, 1, you know 0 is going to start at padding and 1 will start at SOS, which is start of this. Okay. What I want to do is I want to make sure for each individual sequence, I am mapping this properly. So if my example variable of my target was something like this, right? My target was, if I take a copy of this, if I paste it, copy and paste it towards the bottom, you have a target of 1, 3, 4, 5, 2, 0. Okay. And your target label also will be some number, let's say 5, 6, 7, 8, 9, 10, whatever it is, right? At each individual time step, okay, you want your model to predict the next word, which will be encapsulated or given to you by your target label. Now the problem is, in order to get that, I need to do some kind of alignment, okay? Some kind of data alignment I need to perform. Sir, how can I do alignment? Alignment can be done by these two things. Sir, what do you mean by alignment? See, what will happen is, to make sure your output and your target will have the same sequence length, okay? You want to make sure that the sequence length of your input, which is going to be your variable here that you're passing, your source, and the target, you want to keep it same. You need to take some kind of a sequence length. So sir, if I take 1 comma or tf dot shape of target labels, where is target labels defined? Target labels is defined right here, okay? And you are choosing to take index number 1. What will basically happen here is, it will give you some number like say 1 comma 6. Your sequence length will be set at 6. Now what you do is, you write down something called outputs equal to outputs of slicing at the first level, at the second level, and the third level. Sir, what am I doing? Basically keeping only the first 5 or the first 6 predictions. Okay. Basically, if you say that my word is output, say it is 0, right? My first prediction, my first probability was this probability value. This probability's value's maximum number is 0.7, and I want to map it back to my target label, and the label of the target was 12, and 12 directly maps to the word man. Okay. So for each individual probability value, I want to maintain that the sequence is going to be same. I want to have my target label, and I want my output to give me the number itself, 12. Look, for the first iteration, your first prediction is going to be the word man. But this is not enough, because you also have one problem. You are doing padding, and padding is a problem at the time of prediction, because padding is a number called 0. I don't want to deal with 0. I don't want any of my loss functions to deal with 0. If I'm doing back propagation, and if my back propagation prediction target is 0, I don't want 0 to be dealt with at all. I don't want it to manage. What we do, my people, we create, and there is a concept in machine learning called padding masking, okay, or padding mask. Sir, what do you mean by padding mask? You take the same exact thing, and I'm going to paste it in the bottom, okay? Sir, what do you mean by padding mask? See guys, what I'm doing here is, TensorFlow has a method called mask, okay? Essentially what I'm doing here is, I am going to take every single training value, okay, or my target variable here, or a target value here, or a label, wherever I find the Hindi vocabulary key, and inside that I have a padding, I know I am referencing a number called number 0. I am referencing a value called 0. So what I'm doing is, I am creating a mask of a Boolean value. How many sequences of values do we have? 6. So true, comma true, comma true, comma true, comma true. 1, 2, 3, 4, 5 and 6. Basically what I'm doing is, I'm creating a Boolean value and I'm doing something called tf.cast. tf.cast is going to give you an understanding or give you all the mask values to true. And all those true values, eventually I want to convert them into float 32. So all your trues will now become 1.0, 1.0, 1.0, 1.0, 1.0 and 1.0. Remember, do not confuse these 1.0 as a sequence 1 for SOS token. That is different. This is different. This is just an array inside an array. It's a 2D array where for the sequence length that I have, I am taking all individual values as true, 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 true. By default, I'm considering everything to be 0. But if you observe, there is a small issue. The issue is if you take all your actual source value and paste it here, in all my sequence, did everything was true? Was every single value true, or was every single value filled with a number? Actually, no. I had 1 as a true value, 3 was also filled, 4 was also filled, 5 was also filled, 2 was also filled, but 0 was not filled. 0 was 0. So when I cast it as a mask, my mask value will be 1 converted to 1.0, 3 converted to 1.0, 4 converted to 1.0, 5 converted to 1.0, 2 converted to 1.0, but my 0 will be 0.0 because when I actually implemented my tf.cast on the output, okay, so here on my target label, I know for a fact that this is going to be false because there was nothing there, it was padded. So here you're going to get a mask for your first sequence going to be 1 1 1 1 1 0. What you're essentially doing is for the sequence 1 3 4 5 2 0 in the future, when you're going to calculate your forward propagation and backward propagation, you will get some loss values for each sequence. Loss value will be 0.1, loss value will be 0.9, 4 value will be some number, some number, some number. But for 0, there is no loss. Okay, I don't need to calculate the loss. Okay, so predominantly what you're doing is you are making sure that your mask values for each individual training label or your target label, depending on the data, you're creating some kind of ones and you're some kind of zeros. So for example, sir, if I get multiple different targets, for example, 12 comma 13 comma 14 comma 2 comma 0, this is going to be one more value. I have one more sequence called 15 comma 16 comma 2 comma 0 comma 0. I have another sentence and it is 17 comma 18 comma 19 comma 20 comma 2. So see, basically in my target sentences, I have 3 sentences. What will happen to these masks, or the mask will be created very simple. It will be 1 comma 1 comma 1 comma 1 comma 0. The second sentence will be 1 comma 1 comma 1 comma 0 comma 0. Okay, it will be 1 comma 1 comma 1 comma 1 comma 1. So basically for your sequence of or sentences in the data, I now have a mask created that will help me control the flow of the data. So for multiple data types, I now have created a mask, and that is why we create another variable and we call that variable as mask. This is what's going to be important. So tell me, so far I have gotten the understanding until the mask. Okay, I'm going to go and understand it until the mask. Now my people, because you are using something called gradient tape, which is going to give you the value of the gradients at the time of back propagation, sir, can I also calculate the loss inside this? Yes, because guess what you did? You used a function called loss function. You are going to pass the function for the target label and the output, and all your losses will be now saved in the variable called loss. The problem is, my people, when I'm going to calculate the actual loss, I don't want even the 0.0001th gradient for the mask value. So what do? For the sequence 12, 13, 14, 2, 0, I have a mask value called 1, 1, 1 and 1. Okay, so suppose I have a masking value, let me write it like this: 12, 13, 14, 2 and 0. Okay, this is the sequence of the data. For this 12, 13, 14, 2, I have calculated the gradient for each individual token step. Okay. For each individual time step, I had calculated their losses. This loss value will be multiplied with the mask. Because you multiply the same number with 1, you will get the same loss back. You multiply the loss with 1, you get the same value back. But when you have a mask value called 0 and you multiply, or the gradient value, 0, loss value 0, and you multiply it with 0, you're gonna get a 0. Meaning I am telling my program that, hey, can you ignore any loss calculation, be it your backward propagation's gradient calculation, from anything which is a pad sequence? I do not want padding in my data, so don't give me any losses or any loss value from my data. So what's going to happen is, when you calculate the log probabilities in the future, your mask will handle that no loss was encountered. So point being, your loss multiplied by mask is just a way of making sure that no loss is calculated for the sequence pad or for the padding sequence. Absolutely simple. Now the thing is, my people, you cannot calculate loss directly and just run through it. No, you need to take 3 individual types of losses. You need to take the total loss, so the overall loss in the entire time step, which is going to be given to me by something called as total loss. You're going to calculate that. Your total tokens, or whatever mask value were passed to it, you're also going to calculate how many tokens were involved. Overall, you're going to calculate something called as the average loss. Now, why do you want to calculate average loss? Because you want to know, on an average, what is the loss scenario for sentence number 1, sentence number 2, sentence number 3, and sentence number 4. Because in the total loss, I have taken all the time step for all the loss. In the total tokens, I have also taken reduce sum for all of them. In the mean loss, I want like this one averaged value for everything. But the problem is, padding is so notorious and so bad that sometimes the total tokens can also have a mask value where everything appears 0. Meaning, what if you have a sentence, all of them are padded because there is some edge case in the data, and when you divide A divided by B, you cannot divide by 0 and you're going to get an error. So that you don't get an error and your loss is as less as possible, can you see I have taken 1e to the minus 8, meaning 10 to the power of minus 8. Rather than dividing something by 0, can I divide by 0.000000008? The answer approximately won't be 0, but I will not get an error division of 0. So what do we do now is, sometimes when you want to calculate after padding a total loss or a mean loss, we don't divide it directly with the total tokens. We don't divide it by the actual number, the actual over number. We add a small error of 10 to the power of minus 8 in the last, so that when A is divided by B and every single value that I got were 0 in padding, say some edge case in my data, some out of vocabulary term, something that my model did not understand, and everything was written as padded, then at least I'm not going to get the error at the end. Once we have calculated the overall loss, I'm sure you guys know this, but even for your understanding, I'm going to tell you what I'm going to do. Okay. See, what happens, my people, is you calculated something called as a loss, and for each time step you got a loss like 0.1, 0.7, 0.6, 0.2. So your total loss will be 0.1 plus 0.7 plus 0.6 plus 0.2 divided by 4. Okay, you're gonna get a total loss. The problem here is, okay, you have a mask value of 0 comma, or sorry, 1 comma 1 comma 1 comma 1 comma 0. So your total tokens will be 1 plus 1 plus 1 plus 1 plus 0. If you average it, not average it, calculate it, you get 4. So your total token values that you get here, according to the sequence passed, will be 4. and the total loss for the overall sequence for that sentence is going to be say 1.36. What you do, you calculated the mean loss, total loss divided by total token plus some error value. Now what you do is, after you apply this sequence or the step of this particular Python code, you are going to get like the overall mean loss in the data. But your job is not done here. Because if you calculate the overall mean token for your loss, you're going to get some value, but you still have the gradients or updated weight values you need to solve for. Sir, how do you do that? See, my people, this is not going to be very easy to understand, but I'm going to give you an idea. I'm sure you guys know that there is an optimizer called Adam. Adam optimizer is one of the most generic optimizers. Okay. See, adaptive learning rates is one of the key factors. It's very adaptive. Okay. Adaptive means it's very dynamic. Adam calculates momentum and velocity, okay, of your gradient. Momentum will be nothing but your hyperparameter beta 1 times momentum plus 1 minus beta 1 times gradient, okay, your gradient that you calculated through the loss, okay. Your velocity is going to be other hyperparameter b2 times velocity plus 1 minus beta 1 times your gradient, okay. Now the problem here is kind of difficult to explain, okay. See, your weight update or your weight update value is going to be the learning rate multiplied by momentum times velocity plus another term called epsilon or upsilon, okay. Your new weight will be equal to your old weight minus your weight update. So this weight update WU is going to be giving you the new weight. Now what happens, my people, is when you implement something called optimizers, okay, optimizers, here you have written something called optimizers, okay, and inside this at the very top, if you can see here, I have applied something called optimizer dot, give me a second. Yeah, right here. Optimizer dot apply gradients, okay. In the optimizer dot apply gradients, what you're doing is you're taking all your mean loss, comparing it with the actual trainable weights. So basically whatever weight values was assigned by the neural network, you're going to take your weight values, you're going to compare it with your loss value. And I'm sure I don't need to teach you that you have to apply chain rule to go completely backward all the way from your decoder all the way to your encoder, right? You go backward in each time step and your each time step value is calculated per token, right? You get like this average losses or losses overall in each time step. So what you're basically doing is you're telling the program that, hey, look, for each individual gradient that I applied as per the Adam, I want you to take as per the loss function, sorry, I have taken all my mean loss value. I have the model parameter, model trainable values. These are nothing but your weights in the model. Okay. I want you to take all those weights and apply the optimizer where your gradients and your weights will become now zipped. Zipped meaning in Python, if you take an array like this, array is equal to 1, 2, 3. Okay. And if I have another array called array2 is equal to say 4, 5, 6, right? What you're doing here is 4, 5, 6. When you convert it into list of zip of array, array2, you are going to be creating a tuple where every single value r_2 is equal to, is going to give you a tuple of 1, 4, 2, 5 and 3, 6. Basically gradient with the weight, gradient with the weight, gradient with the weight, which you can then later on apply. So what you do is in the TF function that is automatically happening, like it happens automatically. What you do is in the optimizer.apply, if you just convert it into a tuple format, zip it, don't even have to do conversion into list, pass it and just return the overall mean loss. Optimizer is going to give you the optimized convergence or whichever optimization is good for. It will tell you that, look, you know what? I am going to calculate the optimizer and the gradients, the best gradient possible for my data. Okay. So now if you do that, right, after you do that, you need to train your model. You need to make sure that your model works, right? So I did not write the training part because I wanted you guys to understand the train step. Okay. All the sequences well. Now, if you want to actually train your model, you got to move forward. Okay. See, so far what you have done here is for the value of width, right? If you see in the indentation of width, you have taken your gradients, you have taken your optimizer, right? This is how the entire code works. I have taken the train weights. Inside the train weights, I have taken one more function called train step. Okay. Can you see here? There is an indentation in the def, right? In the define statement, I have taken one more internal function called def, right? Now, what do I want to do is, if I want to train my model, okay, I will have to go out with the train part, which is the indentation of define here. And here, I'm going to write down a sequence of my model. Like, for example, print. I'm going to say print starting the training, okay? Print starting the training of my model. Now, how do you start the training of the model? You're going to write something like dot, dot, dot. I'm going to start my training. For epoch, E-P-O-C-H, epoch, in epochs, or for epoch, actually, let me not take epochs because I've not defined it. In range of epochs, okay, E-P-O-C-H, let me get the indexes also. What I'm going to do is, for number of epochs you want me to run the model, I'm going to calculate the loss, and that will be calculated by something called train step. Inside the train step, I'm going to take the source data because I need it. I'm going to take the target data because I need it, right? Once this is done, if for every 10 epoch, okay, if epoch 10 equal to 0, what I want you to do is, I want you to print and give me the analysis or understanding how am I doing. So print f of, if I take epoch here, I will take loss. What is the overall loss in my model? So I'm also going to be printing something called loss. So loss is going to be loss dot LOSS, okay, loss dot NP, or just gonna write down something called as a numpy, and I'm gonna keep it empty. For every value that I receive here, I'm gonna take it only up to the 2 nearest digit, okay? For my loss, I'm gonna calculate it, the percentage, let's take it to 4F, let's be more granular. But this is what I'm gonna do. And I'm gonna come out to the for indentation and I'm gonna say training completed, okay? So I'm gonna say training completed, okay, completed. The reason I have written this program, okay, inside my function is because from now on, whenever I'm going to call train step, in any other method I will use in the bottom, I want the training also to be taken care by the model. So if I run this, the training also will be taken care by the model. So can you see here, my model training has started. For 0th epoch, loss is this. For 10th epoch, loss is this. For 20th epoch, loss is this. For 30th epoch, loss is this. For 40, loss is this. I'm going to say after the 50 epoch, my model has run. My model is now kind of ready to go and good to go, right? After my model has kind of run, I have also taken my encoder value, my dummy data, and my train model, okay? The most important thing I need in my data is the capacity to translate something, okay? So basically, I want the capacity that somebody will ask me any question they want, and I should, based on my data, translate the English sentence into English Hindi sentence. So I already have a model that I trained. I want to pass in some kind of a sentence. So sentence will be passed. I will also take the English vocabulary because I need it. I will also take the Hindi vocabulary I needed, and the maximum length I'm going to allow for the data to be passed is going to be 15. Okay. Because I want to restrict my data analysis or my data to be translated for a shorter sentences. Okay. So give input to the user that, hey, translating, okay, translating your sentence, and which this sentence is going to be bracket, write down the name of the sentence that you want to pass. Okay, this is the sentence you are asking me to translate, and I'm doing exactly that. What you need to do is, because you have not trained your data on string values directly, you need to convert your data into tokens, tokens into indices, indices into tensors, and pass it to the data. Otherwise, you will not be able to translate, because when you did your training, you did not pass your data directly. Okay. So what did you do? You actually did tokenization first. So if I say tokens is equal to, I'm going to take my sentence. Okay. I'm going to take the sentence and I'm going to split it. Okay. Based on the spaces. Indices. Okay. Indices are going to be very simple to do. If you remember, I have created indices at the top. At the very top, I had written down a logic for indices. If you can write here, see, at the time of building the model, I had to write it down that indices will be vocab.get for each individual token. But now that we know we had paired the EOS token, SOS token later, we want to make sure that our model stays prepared for anything we change. So what do? We start the model with the SOS token. So we say English vocabulary, okay? And we are going to pass it the token SOS. We know that the sequence of the number is 1, okay? Plus, we are going to take another array and we are going to pass something called English vocab here. Dot get, same exact logic, the token for the index 0, okay, for token in tokens, okay? So all other values in the tokens will be appended here or added in the list. Then to make sure that every single individual value in my token ends with the end of sequence token, I copy this and I pass it down to the end, and instead of this SOS, we take EOS. So what I'm doing here is I am making sure that my model, the model that I'm writing, is going to have a SOS token in the beginning, the indices in between, and the end of sequence in the last. Once this is done, it is always better to confirm visually whether you are able to do that or not. So input tokens or the tokens that you're passing in the model, okay, are going to be written down like this. I'm going to pass something called tokens. Print F double quotes of my input indices, okay, indices are going to be my indices. Whatever indices I have taken, I'm going to take the indices, I'm going to copy this and I'm going to paste it here. Now padding is not what we do right now. Padding can be taken and will be taken care by my helper functions, Subarao, okay? We are not going to be adding padding right now. That's not the intentions for now, okay? We are going to have a helper function do that for us, okay? Once my tokens are converted and indices are converted, I will convert to tensors, the tensors that I initially used, okay? The tensor values that I was using in that value, initially, I'm going to convert everything into a tensor operation. So my tensor source is going to be tf dot convert to tensor. Okay, you already have a method like that. On the basis of the values of indices and each individual data type I want inside my module will be TensorFlow dot integer 32. So this will be a TensorFlow integer data type. And inside the TensorFlow integer data type, it would be a 32-bit representation for each individual tensor. After everything is done, my first step is to encode. I have taken my tokens, converted them to indices. I am printing the token and the indices, not a very complicated thing. And after the tokens are converted to indices, I had taken an output tensor of sorts. We had converted our data or indices into tensor representation, right? Now, my people, what's going to happen is the next step for me to perform is to perform something called encode. So can I say hidden comma cell state will be equal to model.encoder. I'm going to call something called encoder, and inside this my source tensor, I'm going to encode this. My encoding is done. Okay. If you want to print it, which is always a great habit, let me also print what the result will look like. It will look like encoded to a context vector, okay, encoded to a context vector of shape. What is the shape? The shape is the hidden dot shape. To give you better idea that look, I encoded every single thing that you passed into this specific shape that you wanted me to have. Now, once the encoding is done, I want to decode the output, okay? Decode the output. Now, in order to decode it, you're going to take your input token because of course you're going to decode it on the basis of what you are passed, okay? So decode is equal to tf dot, again you're going to take convert to tensor. In the decode step, you're going to take every single part of the Hindi vocabulary because this is going to be important, starting with the SOS token because this is where my token is going to be starting with, and every other type we are going to maintain a common data type, and the data type is going to be tf.int32. Okay, I'm going to pass it to tf.int32. So once I retain my input token for the decoding part, I'm going to take output underscore tokens is equal to an empty array because now when the encode decode will actually happen, For decoding, I'm actually going to show you how the output tokens were added. Okay, so let's write for the user that, hey, I'm going to starting the decoding. So decoding steps, all the decoding steps we are going to print. So sir, how are we going to do? For step in the range of maximum length, for the data that you have passed here, for whatever max length you have, I'm going to take the same exact thing. I'm going to take max underscore length, okay, underscore length, okay, for whatever range you want to pass your data for, I'm going to take it all, okay. For this, I'm going to generate your output comma, okay, output comma, hidden comma, cell state for the given value. So model.decode, I'm going to take a decoder. Inside this, I'm going to pass in your input token, which is passed here directly, okay. My input tokens that have been taken here, I'm going to take my input tokens. For those input tokens, okay, I also will get like the updated hidden value, and I will get the updated cell structure or the cell state for it. The predicted underscore token, I already know that I get output predicted probabilities, and from that I want to get like the maximum argmax of the probability. So whatever is your output, I want that. Axis is going to be -1 dot numpy. I'm going to convert this into a numpy representation, and here my people, I'm going to write something called 0, 0. Sir, why do we have to do that? The reason why we have to do that is because in my entire code of prediction, right, at the time of predicting the answer, there is a small problem, okay, not a problem, but at the time of translation, the data that you have, okay, the data that you are dealing with is gonna be in a different data structure altogether, right? In order to make sure you retain the data structure completely, you have to kind of make some changes in the data, okay? To do that, you have to actually understand how the flow works, how the data transfer or how the data flow happened. So first of all, what did we do? We took a translate method, we converted them into tokens, we converted them into indices. We also had something called source tensor. If you guys remember, a source tensor was created at the end. Once my word index mapping, my source to my source is converted into a tensor operation, right? What will happen here is, after everything is done, I am going to be calling the encoder value, okay, to encode the values for me, okay. Keep it ready because I'm going to be passing it to the decode. I'm going to keep the tokens ready also, but here is where it's going to have a problem. And the problem is, when I'm going to convert something called df or the tf dot convert to tensor, which I've called it here, okay, my tensor is going to be like this two-dimensional array, okay. So my input token is done, my output token is done. Now, the complicated part here is, when I take this variable here in the decoder call, what's going to happen is, you are going to have an input token, okay? Your input token that you want to pass to the decoder, the hidden state and the cell state, okay? These are going to be like the 50-dimensional vector embeddings, okay? Now, when you pass in something called your tf.argmax, okay, inside the model, you know for a fact that in your decoder, you had a fully connected layer, which is going to give me the probabilities, the output token probabilities here, right? So what would happen here is, I will have all the answer here in the output part of the code, okay? I'm going to take the output and I am going to convert them, okay, into the maximum probability or the probability which has the highest value, okay? Now, sir, the problem here is, why do we take an axis equals to -1 and why are we taking it as a 0, 0? There are two reasons behind it. And this reason is actually very, very simple. At the time of translation, I'm sure you guys have heard that TensorFlow or in your Python lists, you have a way of taking certain axes at the time of detecting things or at the time of extracting things. What usually happens is, when your output value that you're trying to calculate, okay, is going to run through the entire input token, hidden cell and all of that, your output token did give you the answer, right? But the problem here is, in tensors, okay, last value for that vocabulary is represented by axis equals to -1, meaning when you take a tensor operation, okay, so for example, right, suppose if you have a value like this, let me take a 3D array, okay, let me take a 3D array. Let's say you have a value called 2.1, 0.3, negative 0.5, I don't know, 7, 0.7, 0.6, something like that, right? See, each individual value will have an axis called 0, 1, 2, 3, and 4, right? These are all the indexes that you have, right? Your argmax, tf.argmax is going to give you the maximum value among the array, okay? If you say along the axis of -1, you are actually finding out the value of some number. Say for example, if you had a number called 0.4, you are going to find out the maximum number 0.4 at the index called 3. Okay, and for the index number 3, I want to extract them out from this multi-dimensional tensor or this value that I have. Okay, so what you do along the axis, if you traverse, okay, it will give you the argmax or the maximum value reference at a specific index, and that index representation will be given to you. So that representation, if I want, and I want to convert it into a numpy value, to deal with the multi-dimensional data, we pass in the value called 0, 0. This 0, 0 towards the end tells you that, hey, I am getting a shape along 0th index, which is the first dimension. And within the first dimension, I want you to pick up the second dimension. In Python, you must have implemented it like this. For the 0th dimension, I want the first value. So within that particular shape, I want the 0th comma 0, meaning I want the first of the batch dimension, and inside that batch dimension, I want the first. So whatever is the batch, in that batch, I want the first sequence to be that particular value. That's why we write this as a 0, 0, right? Now the problem here is, once you have a predicted token or the word value or the probability for that predicted token or the token itself, right? You want to be able to convert that back. To convert that back, I need to inverse my Hindi vocabulary. Okay, the vocabulary that I have created for Hindi had tokens and then the value, but I will reverse them right now. So I will take value comma key. For key comma value, see, here is where I reversed in Hindi vocabulary, okay, dot items. What I did, I just reversed my entire dictionary where the value becomes key and the key becomes value, because I want to map it back. Okay, so for value colon key, for key comma value in Hindi vocabulary dot items. Now what is going to happen here? Oh, sorry, this is not colon, this is equal to, right? So what's going to happen here is the predicted word, okay, not the token. I don't want the token. I want the word to be printed to the user or to my model. So I will take that inverse Hindi vocabulary thing that I have converted, dot get, and now I can directly reference my predicted token and it will directly give me the word. Okay, until and unless I do not have any UNK or unknown word. Okay, if that happens, I don't want this to return, or I want this to return something called UNK, unknown. I don't know what you're trying to ask. Nothing of that sort exists in my dictionary. So print to the user, I'm going to say that, hey, in a tab value, the step was the index step plus 1, because I want to start it with 1. For that particular step, your predicted word that I was able to extract is this, and the token that I was able to extract looked like this, predicted token. So I'm going to be telling the user that, hey, I did run the step, I did run the model, and when I ran the model, I got this answer. So if you say that the predicted token that you have just extracted is equal to of Hindi vocabulary, in the Hindi vocabulary, are you now looking at end of sequence? Did you arrive at an end of sequence? If your tokens and time steps after multiple iterations have arrived it, you need to print for the user that, hey, tab, reached, REACHD, reached end of sequence token, stopping the model. Okay, token stopping, STOPPING, stopping the process. Okay, stopping the process. Let me say that this is the sequence, and once it is done, I want to break out of the loop. I don't want to continue because I have arrived my end of sequence. Now the problem here is, in the same indentation of this, my output tokens will be appended with all the encoder decoders that I have taken collectively. So all my predicted tokens will be added to my output token, and my input token that I have extracted from the conversion will be converted into a tensor once again. So TF dot I convert into tensor. I will convert this to tensor, and inside the tensor I'm gonna pass two things. One is my predicted token because that's how I'll be able to get the answer, and for every single thing I'm going to maintain the same d type. So TF dot integer 32. I am done, almost done, processing is done. The problem here is every single thing that has been passed in my value is either a token of some sorts, and input token have also been passed as a token and converted into values. What I want to do is I want a way to convert everything back into words. So basically convert my indices, which is after the final encoder decoder process, I want to convert them back into words. So if I created the inverse Hindi vocabulary that I created here, I'm going to take the exact same copy. I'm going to paste it here. Okay. Value comma key for key comma value in Hindi vocabs dot items. Now the translated words, okay, translated words underscore words will be equal to, I know for a fact that I already have the help of something called inverse underscore Hindi underscore vocabulary. So I'm going to take Hindi vocabulary. For this, I'm going to do get. What am I going to get? For that specific index, if that index is not given, pass it something called unknown. I'm going to loop through the entire sequence for IDX or index and output tokens. For all output tokens generated by my module, I'm just going to take all output tokens, loop through it, get all the indexes, and get my translated word back. Once the translated words are back, I need to combine everything together because these are going to be not your sentences but word, right? So translation is going to be joining the word. So can I say dot join on the basis of the space, join every word, and I will pass something called translated words. So every single translated words that I have generated, I'm going to pass it inside this. And finally, I'm going to get the translation back of my original model. Once you get the translation, I'm going to print F double quotes of my final translation of the model is going to be translation. I'm going to call something called translation here as it is. Okay. Translation as it is. And I am also going to return translation because I will use it in the function later. So I'm going to say return. I'm going to pass in something called translation. What this function does is if you want to translate 100 other sequences in the past, say for example, if you have 500 such words and I want to test it, say for example, you guys want to test something, right? So for example, let's say, cancel this. Let's say I want to start test underscore sentences is equal to, I don't know, I am happy. Okay. Happy, HAPPY. This is what I want to translate. I want to translate you are sad because that's what I had taken in the last, right? I am happy, you are sad. And what did we take? We are ready. Suppose I will also write something called we are ready, right? Let me take one more sequence and let's say we are ready. So what you've done here essentially is every single test sentence, I will loop through it. I will apply the translation model and I will get an answer, but I will get a detailed answer for sentence in test underscore sentences. Okay. For test underscore sentences inside this expected graph or expected is going to be equal to none. Okay. I'm going to take a false or a flag, sorry, and I'm going to be passing it something called expected is equal to none, meaning in the result, my people, I want to show you actual and expected as an answer. Okay. So I'm going to take a flag by default none for English. Okay. For for English comma ENG comma Hindi in data. Okay. I'm going to be referencing my actual data that I have. If English or ENG is equal to the sentence. Okay. the sentence that I'm passing here, if that same sentence matches in the data, if the exact same data matches, then I'm going to say expected, okay, expected is going to be equal to Hindi, and we come out of the whole thing. We break out of the sentence because this is going to be matched, right? I'm going to take that indentation and I'm going to be passing it. Now, this is not for, this is for, okay? Yeah. For English, comma, Hindi in data, I'm going to be taking if English indentation, again a problem, expectation, again an indentation, break in the indentation, okay? For English, comma, Hindi in data, if English is equal to the actual sentence, expected will be Hindi, I'm going to come out of it. This is going to give me the expected that you were expecting in the Hindi, right? Translation is going to be equal to the model that is going to be translate. I'm going to copy that. I'm going to paste it here in the bottom. Okay, translate. Inside the translate part, I have taken multiple different things: model, sentence, English vocabulary, Hindi vocabulary. By default, max length is 15. So I am not going to change that. I'm going to take the model as it is. I'm going to take the sentence as it is. I'm going to take my Hindi vocabulary and English vocabulary as it is. So English vocabulary is English vocabulary and Hindi vocabulary is going to be Hindi vocabulary. I'm going to take it as it is. To print the answer as expected, so I will say expected, okay? Expected answer was nothing but the same answer that you got, okay? So expected answer, I'm going to take it in the bracket and I'm going to put something called expected here, okay? For the same answer print, I got, what did I get? What is the prediction that I got? I got, let's take space and let's also map it properly. Let's take indentation here. Actually, let me go one step back and say translation, okay? Translation that I have in the data. And to make sure that the translation is done nice, I'm just gonna rerun it once again, right? So, if I say test run it on the data, so referencing would not be, I think, okay, so do I map it for you? Okay, I don't think mapping would be needed now. So let me just take it as it is that I have taken and maybe we will run this. So just to get a better representation, let's just go ahead and say print, okay, inside this double string, double here or an equal to sign, or let's take this multiplied by 40, okay? Let's see, one second, let me run this translate method and wait, where did I make a mistake? It is showing that we made a mistake somewhere at the type of SOS and EOS, right? Wait, where is the SOS part? English vocab indices is equal to SOS. Give me a second. Let's check where did we go wrong here. Indices is equal to SOS. So wait, indices are going to be English vocabulary for SOS, which is fine. Can I not get it directly? Give me one second. If I take English vocabulary and inside this, I am taking something called SOS. If I run this, why do I have a, oh, yes, I made a mistake. The token was not just SOS, it was EOS, right? Also here, my people, because it was not a string, it was not just an empty string, right? It was like this. It was SOS here and an SOS here. Now we will get the index value 1, correct? Makes sense. Run this, run this, run this. Do I need to start it from the beginning? Let me see if I can start it from here. And let me see if I have the sequence ready. So I am happy, you are sad, we are ready. A predicted word is inverse of this. So, okay, I'm going to get the error here also because there is no EOS token here, right? You have not taken SOS here also. This is also a problem. We did it. Did we make a mistake somewhere else? We did EOS, UNK. Let me also add it properly, right? Did we make the changes somewhere else? No, right? So let me rerun this once again from the beginning. Let's create the token variable and everything from the beginning. Let's see if we get any error. In case if there is any function that I may have made any mistakes, because there might be chances that I may have missed out the data structure or maybe it returning in some other dimension. So I might have to check the shape later, but let's see if I get the answer. Okay, all right. See, I'm going to make you understand the output one by one, okay? See, I am happy is my input token. Okay. Input indices was 10452. This was encoded into a context vector of size 1, 100. Okay. This is going to be the context vector size. When I did decoding, I ignored the SOF token. Okay. I don't need the SOS token. See, at the time of training of the model, okay. At the time of the training of the model, okay. Here, when I'm taking the tf.cast at the time of gradient calculation, and no, not here, sorry, at the time of my hidden and cell, yeah, at the time of my call function here, at the time of the training model or seek to seek here, once I am applying for each individual value for decode, I am making sure that every single time I pass in the value, right, I don't include SOS token as a part of it, as a part of the process for it. So as a process of it, what happens is, once it runs, it will start with the token 3, Khush equals to token 4, who is token 5, ending at EOS token, and the minute EOS token is reached, we say EOS token reached, stopping the process. So the final translation was main khush hu, expected equals to none, we got main. Okay, so I think I have made some mistake at the part of none. Oh, we did not change the flag, right? I maintained the flag as it is. So if I change the flag, wait, if English sentence will become, I have said expected will become Hindi, right? So if for English comma Hindi in data, wait, let me fix this for you once again, wait. If English comma Hindi in sentence, let me actually loop through this and say print English, okay, let me print both ENG and HIN, okay, not this, print ENG and HIN. So I am happy, main khush hu, which is fine. So my Hindi and this is printed. If I remove this, if English is equal to the sentence that is passed in my model, then I am changing the flag expected to Hindi, but why is it passing none? Okay, all right, I will have to see, wait, okay. If this is going to break, can I print expected expected print? Okay, so it's passing none and none. Okay, I now understand what is the problem. Give me a minute. There is no lower that I did, and I am so dumb for not doing dot lower. See, the reason why it is returning none is because the way I passed I am happy, it is not able to do an exact hardcore mapping. Okay, see here, you are sad is U capital S small. So I will take you are sad, copy this and paste it as it is. Of course it will return none because the sentences that I've passed are not as it is, right? I'm going to paste this, and we are ready is going to be how we are ready. So all small, nothing capital. So copy this. I'm going to pass something called we are ready. So now it won't be none because the flag will be updated at the time it will match. Okay. So let me do the translation here. Rerun it once again. So see, expected will be main khush hu. Got the answer main khush hu. Translating the sentence you are sad. I have an input token sentence called you are sad, and I am also having the input indices. I am passing it to an end of sequence because everything is done. So my expected result was also aap dukhi ho, and got also is aap dukhi hai. So basically, even though my training data was able to do lesser training, I am able to make a getter answer, right? If I write down another sentence that the model has never seen, okay, for example, let's try that. See, we said, I am happy, you are sad, she is tired, we are hungry. Can I say tired and hungry? There is no and, no. Tired, how can, what sentence can we form from this? We are hungry. Hungry, late is sad. Okay, late is sad. We can say something like this. Late is sad. Okay, tired is hungry. Yeah, that's a good one. That's a better one. That's a better one. So let me take one more thing called tired is hungry. Okay, HUNGRY. Okay, tired is hungry. Okay, so tired Tired, tired. Tired is hungry. 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 Okay, fine. Let's try this. I know the results are not going to be great, but let's see how what answers does it get. Okay. Tired is hungry. The answer we got is wo thak gaya hai. So basically, it did not understand the word hungry. It understood tired and is, and it gave you the answer same exactly available in the data. See, wo thak gaya hai. Can you see here? Tired, वो थक गया है. You're getting what I'm trying to say. It was not able to map the answers exactly properly, but it was able to understand that you're talking something about tired. See, it was able to understand that you're talking something about being tired, right? So it was able to map back to वो थक गया है, basically. See, the point is that look, the data set that we got is so bad and so terrible that of course we do not have how do I say this? I do not have enough representation for me to know very clearly what is tired, what is hungry, and you did not give me multiple instances of hungry also. Correct or not, my people? See, here I have only passed the instance of hungry once. Is there any other data talking about hungry? We have given something called tired. Do we have anything related to tired? No. So point is that whenever you write a data for your simple machine translation, okay, essentially what we've done is we've taken a model with a lesser sequence set of data and I've run it.
Just a quick info guys, Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.